You are about to embark on a study of the branch of computer science theory known as automata theory or language theory. We're going to follow fairly closely a one-quarter course I gave at Stanford a few years ago. Its traditional number is CS 154. This theory plays an important role in computer science. I am aware that many students don't see the importance of a mathematical approach to CS. The feeling is, just let me near a keyboard and let me code. It's quite common. In this introductory video, I'll try to give you some reasons why you should learn the material contained in the course. A number of years ago, Stanford took a survey of its graduates 5 years after they got their undergraduate degrees. What they wanted to find out was whether Stanford was teaching stuff that they actually used in their jobs. So computer science graduates naturally cited our introductory programming courses as the one they used most. No surprise here. Next came our sophomore level courses covering basic data structures and algorithms and systems software. Again, no surprise. But after the required courses, we found the CS 154, the automata course on which this set of videos is based, was second after the database course. It was cited by 3 times as many as cited the introductory AI course, for example. So I want in the next few minutes to try to explain what it was about automata theory that impacted what our former students were doing in their professional lives. So let's see some of the ideas we're going to learn about in the course and how they appear in practice. One very commonly used idea is the regular expression, a simple notation for describing many of the patterns that arise naturally in practice. Many pieces of software that you might find yourself working on in the future need a simple input language to describe patterns. So you might well find yourself implementing some form of regular expressions. For example, many Unix text processing commands use a variety of regular expressions. This expression describes a line of text that has a letter A followed by any number of characters followed by the letter B. For a more modern example, the XML document markup language invites us to describe the structure of documents by a DTD, or document type definition. The DTD language consists of descriptions of elements such as the example given here. A person element consists of a name element, followed by an address element, followed by any number of child elements. Finite automata are another topic we'll see early on. They are, in fact, the way regular expression-based languages are implemented. They also have been used for decades to model electronic circuits, and in particular to help design good circuits. They have also been used to model protocols, and we'll give some examples later in this course. Especially, finite automata underlie the body of techniques known as model checking, which has been used to verify the correctness of both communication protocols and large electronic circuits. Another important aspect of the course is the context-free grammar. These are used to put a tree structure on strings, typically text strings, according to some recursive rules. They are an essential for describing the syntax of programming languages and are a part of every compiler. They also play an important role in describing the syntax of natural languages and are used in software that does machine translation and other natural language processing. And the DTDs we mentioned in connection with regular expressions are really context-free grammars. It is the single rules of a DTD that look like regular expressions. The topics we just mentioned are essentially tools for doing simple but important things, but there is a second broad theme in this course. There are fundamental limitations on our ability to compute. A computer scientist should be aware of these limitations, because only then can you avoid spending time attempting something that is impossible. One limitation is undecidability. There are problems that cannot be solved by computation. For example, you might imagine you could write a compiler that would refuse to compile programs that printed out dirty words. Even assuming you had a precise definition of what words were dirty, you can't do this. We're going to prove that there is no way to tell whether a program will ever print a particular word, or even whether it will ever print anything at all. And we also need to know about the class of problems called intractable. These are colloquially problems that we can solve but whose solution takes time that is exponential in the input size. These problems generally need to be finessed in some way, such as by approximating the solution. The reality of the theory of intractability is quite a bit different from the colloquial version, but while the undecidable problems have been proved not to have any solution, for the intractable problems we have very strong evidence that they require exponential time but no proof. We'll explain all this when we get to the theory of NP completeness as the culmination of this course. So another thing you'll take away from this course is the ability to navigate the space of problems that you might encounter in a life of creative software construction. You will learn how to determine that a problem is undecidable and how to determine that it is intractable. That lets you avoid the problem altogether in the first case and to modify your approach in the second case. There are several less concrete benefits to this course. First, you will improve your skills at proving facts, especially inductive proofs, of which we'll do several in great detail. Now, I'm not one of the people who thinks that formal proofs of programs will ever be a serious software methodology. But as you construct code, you should have a sense of why what you're doing works the way it is supposed to. Often the trickiest parts of a program deal with trees, graphs, or other recursive structures. Understanding inductive proofs lets you at least formulate a reason why you think your method works, even if you don't try to dot the I's in a formal proof. We're also going to learn about a number of important abstractions: finite automata, regular expressions, context-free grammars, and varieties of pushdown automata and Turing machines. Some of the essential parts of this course are proving equivalences among the models. That is, any example of one model can be simulated by some instance of another model. The process of simulation across models is essentially the same as the modern approach to programming in layered abstractions, where you write programs at one layer using the primitives of the layer below. At Stanford, I found that a number of people taking the Automata course were not computer scientists at all, but were mathematicians by inclination. That's cool. Welcome to those of you out there. I probably won't do things quite as formally as you would like, but more formally than the typical computer scientist likes. However, be warned that some of the past have found the subject sufficiently interesting that they saw the light and made major contributions to computer software. A case in point is Ken Thompson, the fellow who gave us Unix. Before doing Unix, Ken developed an interest in regular expressions and saw that they were an important part of a text editor. He worked out efficient ways to compile regular expressions into programs that could process text, and his algorithms are an important part of what we teach about the subject today. It should be no surprise that regular expressions form an integral part of so many Unix commands, and that these commands give more flexibility and power to Unix users than did those of earlier operating systems. Another interesting case is Jim Gray. Jim, before his mysterious disappearance, gave us many important ideas in the database field, including two-phase locking for concurrency control, for which he won the Turing Award. But I knew Jim when he was a student at Berkeley, and I was on leave there for a brief period. He did a thesis on two-way pushdown automata. We're not going to talk about them. They turn out to have been a backwater of the theory, and I'm sure Jim would agree. But they are related to ordinary pushdown automata, which we will talk about in connection with context-free grammars. What is interesting is that Gray told me quite a bit later that he decided to become a computer scientist because automata theory intrigued him. Only later did he switch into database systems, and I believe that the experience he got dealing formally with automata made him more capable as a designer of several very innovative systems. So here's a summary of what will be covered in the course. We'll start off with what are called regular languages. A language is just a set of strings, for example, the set of character strings that are valid Java programs. The regular languages are exactly those sets of strings that can be described by finite automata or regular expressions. This discussion will also introduce the important concept of non-determinism, machines that can magically turn into many machines that each do something independently but with a coordinated effect. This model of computation is fanciful, to say the least, but we'll see it plays a really important role in several places, including design of algorithms and in understanding the theory of intractable problems. We're then going to turn to properties of the regular languages. These properties include the ability to answer certain questions about finite automata and regular expressions that we cannot decide about programs in general. An example would be to tell whether a device makes an output in response to even one input. You can't tell for programs in general, but you can for finite automata. It is this tractability, our ability to understand what simple formalisms like finite automata or regular expressions do, that make them so very valuable when they can be used. We're also going to talk about closure properties of regular languages. For example, the union or intersection of two regular languages is also a regular language. The next big topic will be context-free languages. This is a somewhat larger class of languages than the regular languages, and they enable us to do things that you can't do with regular languages, such as match balanced parentheses or XML tags. We'll talk about two ways to describe such languages. First, by context-free grammars, a recursive system for generating strings, and then by pushdown automata, which are a generalization of the finite automata that we'll use for regular expressions. We'll then repeat our examination of decision properties and closure properties for this larger class of languages. Many of the things we can tell about regular languages that we cannot tell in general, we can also tell about context-free languages. But there are unfortunately some exceptions. Similarly, many of the operations under which regular languages are closed also yield a context-free language when applied to context-free languages. But again, we lose some operations. For example, context-free languages are closed under union but not intersection. Next, we take up the largest class of languages that we can reasonably say can be dealt with by a computer, the recursively enumerable languages. We also look at the smaller but important subset of the recursively enumerable languages called the recursive languages. These are the languages for which there is an algorithm to tell whether or not a string is in the language. We introduce the Turing machine, an automaton in the spirit of the first kinds of automata we meet, finite and pushdown automata. The Turing machine is, however, much more powerful than either of these. In fact, it is as powerful as any model that has ever been thought of to answer the question, what can we compute? The payoff for the study of Turing machines is that we can answer the question of what can be decided by computation, or what can be computed by any means at all. We shall develop tools for showing that certain problems cannot be decided, that is, answered by a computer. The example we already mentioned, does a program print a dirty word, should give you an idea of what we can achieve. Finally, we're going to cover the theory of NP-completeness. The critical question is, what can we do with an algorithm that runs in time that is some polynomial in the length of the input? It would be lovely if we could distinguish between problems whose best algorithm took, say, n cubed time from those that could be solved in, say, n squared time. But no theory has ever been devised to be that precise for general problems, although the best running time for some problems is known. Fortunately, we can learn a lot by dividing problems into those that can be solved in some polynomial amount of time from those that apparently require exponential time. We'll give you the tools to do this, and Turing machines are the tool you need to build this theory, as well as the theory of what can be computed at all. This course follows the third edition of the textbook I wrote with John Hopcroft and Rajiv Motwani. You do not need to buy this book. The homeworks and exams will all be based on what you can learn by observing the slides and listening to my commentary on the slides. Okay, the following is optional and depends on what we decide to do about the page references in the homeworks. You will, incidentally, find as you do the homeworks that there are explanations when you make a mistake. These explanations refer to pages or sections in this book, but you do not need the book since the explanations, like the course material itself, are designed to be self-contained without your having to read the book. I ask one thing, however. Please do not download a free copy from a file sharing site or delete it if you have already done so. This book was published by Addison Wesley under a contract that dates back to 1967. At that time, there was no internet and it wasn't all that easy to produce books. Addison Wesley invested a good deal in the production of this book and its predecessors, and they deserve to recover their costs. It is stealing to download a copyrighted work without paying. There's no two ways to look at it. Admittedly, the world has changed, and recently I have started to put books on the web for free, download from my own Stanford web pages. You are welcome to what is freely given, but please do not take what is not offered gratis. Today we begin with an informal introduction to finite automata. I'll offer some brief remarks about their uses and then move to an extended example of an automaton that describes how a game of tennis is scored. The finite automaton is a mathematical model, but fortunately it is a model that should be quite familiar. You can think of it either as a graph or as a table. The finite automaton is simple because it stores only a finite amount of information. That can be bad, because in many applications there is no limit on the amount of information we need to remember about what has happened in the past. When that is the case, the finite automaton is not a useful model. But the finiteness of memory is great when the model can be used, because we can do a number of things with finite automata that we cannot do with programs in general. For example, given a program, you cannot really tell anything about it, what it does, or whether there is a shorter program that does the same thing. However, you can tell whether two automata do the same thing, or whether there is a smaller automaton that does the same as a given automaton. You can also tell whether an automaton does anything at all. That ability lets us tell, for example, whether there are input sequences that cause an automaton to get to an error state, which in turn lets us check whether protocols or other simple systems have flaws. A finite automaton is built around a finite collection of states. Each state has a name, and that name represents what is remembered about its history. States change in response to inputs. Inputs are either characters if we're doing something like processing text, or events if we are modeling something like a communication protocol. The rules that give the new state for each current state an input are called the transitions. The finite automaton is useful in a number of computing applications. We mentioned the design and verification of communication protocols and digital circuits. And together with the related formalism called regular expressions, they are important in text searching algorithms. They are essential for the portion of a compiler that breaks the input into tokens, identifiers, keywords like if, and so on. You find automata and regular expressions in many other applications as well, typically where simple language is needed to describe patterns that are sequences of symbols or events of some sort. To see the power and also the limitations of a finite automaton, we shall take up an example, scoring a game of tennis. If you don't play tennis, it's almost like ping pong, except you are really tiny and you stand on the table. Depending on which page comes first in response to your search query, you'll find it was invented in the 12th century or in 1879 by people who evidently had too much time on their hands. The scoring system is arcane, with matches consisting of sets, which consists of games. Games consist of points where one player or the other wins by causing the other player to hit the ball off court or into the net. We'll talk about scoring a game. One player is server throughout the game. To win the game, you must have at least 4 points, but you also must win by at least 2 points. The states we are going to use for the scoring automaton represent the numbers of points won by each player, and they have strange names, which we'll see as we go. The inputs are events in which one player wins a point, S for the server wins, and O for the opponent wins. It is common to represent a finite automaton by a graph, with nodes for states and arrows labeled by the input for transitions. Here's the first state of the automaton that scores tennis games. The name of the state is love. You may ask, what's love got to do with it? But that's what 0 is called in tennis. The state love represents the history in which nothing has happened, and we indicate that history begins with this state by an arrow labeled start. The first point will be won by one of the two players, so there are 2 transitions out of love, one labeled S, the other O. You might think the names of the states would be 1-0 and 0-1, because the server's score always goes first. But they're not. In tennis, there is the fiction that you score 15 for winning a point, and 0 isn't 0, it's love. The next point can lead to 3 states, 2 where one player has won both points, and 1 where they're tied at 1 each. Here are the states with their names. There is something interesting about the 15-all state. It has forgotten how we got there. We know the sequence of inputs was either SO or OS, but we don't know which. It doesn't matter, of course. That's a good thing about finite automata. They only remember what must be remembered. In state 15 all, the question of who won the first of the 2 points can't have any effect on the outcome. After another point, there are 4 new states the game could be in. They have the expected names, except people are too lazy to say 45, so they just say 40. Now let's look at the transitions from the state 40 love. The server is well ahead and can win on the next point. If the server wins, we'll go to a state indicating that win. The game is over and the automaton has no further moves. We indicate this output of the automaton by calling the state a final state, and we indicate it as final by a double circle. There is another state reachable from the state love 40 if the next input indicates the opponent won the 4th point. There are 3 other new states as well, called 40-15, 30 all, and 15-40. Each indicates that 4 points have been played, with 3, 2, or 1 of these points won by the server. From the 40-15 state, if the server wins the point, we go to the server 1 state. But if the opponent wins the point, we go to a new state called 40-30. A similar thing happens from 15-40, and from 30 all, we can go to either the 40-30 or the 30-40 state. Now let's look at the state 40-30. If the server wins the next point, they've won the game. But if the opponent wins, then the game is tied. The name for this state is deuce. The deuce state is quite interesting. It remembers that the game is tied, but it remembers neither the sequence of wins and losses of points, nor even how many points have been played. And the 30-40 state is handled similarly. Next, consider what happens in deuce. You have to win by 2 points, so it is impossible for either player to win immediately. If the server wins the next point, they are ahead by 1 point, although we don't know how many points in total have been played. The strange name for this state is add in, or advantage in. In refers to the server. Symmetrically, if the opponent wins in state deuce, we go to state add out. The out refers to the opponent. Then in state add in, if the server wins the next point, they win the game. But if the opponent wins, you're back to deuce. Likewise, from add out, a server win puts you back in deuce, but an opponent win gives the opponent the game. We can now look at the entire transition diagram for the finite automaton. While most of it just allows flow away from the start state, the loops involving deuce, add in, and add out, that is, these, they allow for cycles and for an infinite number of possible strings of S's and O's to lead to one of the final states. The job of an automaton is to process strings of input symbols, or input strings. We always begin at the start state and we read each input symbol in order. For each input symbol, we follow the transition from the state we are in to discover what the new state is. We accept the string if we wind up in a final state after processing the entire input. Here is an example. Here is our input string. It represents a game in which the server and opponent alternate winning points until the very end, when the server wins 2 in a row. We'll mark the current state by the star, and initially the current state is the start state. That's where all finite automata start out. The arrow indicates which input we are about to process. So here we are about to process the first event where the server wins the first point. We're going to follow the transition out of the state love, labeled S. Here we've made the first transition. The next input is O, and we're in state 15 love. The transition from that state on O is to state 15 all. In state 15 all, we see another S on the input, so we go to state 30-15. And O takes us to state 30 all. Then on S, we go to state 40-30. From there, we go on O to deuce. And from deuce on S to add in. From there on O back to deuce. And another cycle on S and O between add in and deuce. Now come the first of the 2 S's. This S takes us to add in again, but the second S takes us to the server win state. Good going, server. Now let's get a bit more formal. The job of a finite automaton is to process strings of inputs and accept or reject them. It accepts the string if it leads from the start state to a final state. Accepting state is a synonym for final state. A language is simply a set of strings in the formalism used for automata. The language accepted by an automaton A is denoted L of A. In our tennis example, we called the two states where one of the players wins the final states. In that case, the language of the finite automaton is the set of strings of S's and O's that end the game, no matter who wins. We could change the set of final states, say by making only the server win state be final. Then the automaton would have a different language, the set of strings of S's and O's that lead to a win by the server. Or we could make only opponent wins be final and have the language of ways the opponents can win. We are now going to express the ideas behind finite automata more formally. We'll see how to represent finite automata either as graphs or tables. They are two representations of the same idea. And we're going to do a few proofs in considerable detail and learn some useful proof techniques, especially inductive proofs. An alphabet is simply a finite set of symbols. There are many examples. Two standard alphabets we see frequently are the ASCII and Unicode alphabets. An alphabet we'll use frequently is the binary alphabet, consisting of only the symbols 0 and 1. We'll also sometimes use alphabets of letters like ABC, and in the tennis example we use the alphabet of outcomes consisting of the letters S and O. Each protocol has a set of signals, and the set of all signals used by a protocol is also an alphabet. Strings are the usual data type you've seen in languages like C or Java. That is, a string is a sequence of symbols chosen from some alphabet sigma. The strings over sigma are those strings whose symbols are each members of sigma. For example, 011 is a string over alphabet 01. It is also a string over alphabet 0, 1, and 2. It just happens not to have any 2's. Unlike programming languages, which typically put quotes around strings, we're not going to do that. And even though strings are lists of symbols, we're not going to separate the symbols by commas or other separators. We'll just write down the strings like this. We use the expression sigma star for the set of all strings over the alphabet sigma. The length of a string is the number of positions in that string, and a special string is the empty string, which has length 0. We represent it by epsilon. For example, the language 01 star consists of all strings that can be made from the symbols 0 and 1. For example, epsilon, the empty string, is in this language. There are two strings of length 1, the strings 0 and 1, and there are four strings of length 2, and so on. Notice that we do not make a distinction between a symbol like 0 and the string of length 1 that consists of a single instance of that symbol, the string 0. We trust that context will make clear which we mean. Programming languages do make this distinction. So in C, for example, we'd put single quotes around the 0 if we meant the symbol or character 0, and would put double quotes around it if we intended the string consisting of only the 0. Languages are sets of strings, and they can be finite sets or infinite sets. The only limitation we place on languages is that there is some alphabet that is a finite set of symbols from which all the strings in one language are composed. Here's an example of a language L we're going to meet several times. Its alphabet is 01, and it contains all strings of 0s and 1s that do not have two consecutive 1s. So the empty string is there, and both strings of length 1. Of the strings of length 2, all are there except 1, 1, because that obviously has two consecutive 1s. 5 of the 8 possible strings of length 3 are there, as are 8 of the 16 strings of length 4. Here's a little puzzle for you to think about. For length 0 through 4, we see there are 1, 2, 3, 5, and 8 strings. Do you recognize the sequence? And can you extend it to strings of length 5, 6, and so on? And in particular, can you prove that your prediction is correct? Now we'll give the formal notation for deterministic finite automata. There is a finite set of states, and we usually use Q as the set of states. Don't ask me why it's Q, it just is. And there is a finite input alphabet. The traditional name for the input alphabet is sigma, again for no known reason. There is a transition function, which we'll discuss on the next slide. It is the guts of the automaton, since it tells us how the automaton moves from state to state in response to inputs. The traditional symbol for the transition function is delta. One of the states in Q is the start state, and we designate it Q sub 0 typically. And some of the states are designated final states, or synonymously accepting states. The final states are typically denoted F. The thing that makes the automaton work is the transition function. This function, usually denoted by delta, takes 2 arguments, a state Q and an input symbol A. It gives you back the state that the automaton goes to when it is in state Q, and the next input symbol to arrive is A. The function delta is total. That is, it has a value for every state and symbol. There are examples of automata where we really don't want to continue in certain situations. For example, our tennis automaton did not have transitions out of the 2 states where one player or the other has won the game. To fix up such situations, we have to introduce a dead state. A dead state is a state that is not accepting and that has a transition to itself on every input symbol. Once you get to a dead state, you cannot leave it, and you can never accept. So dead is a pretty good description of what is going on. We're going to use the abbreviation DFA for deterministic finite automaton. The deterministic means that there is a unique transition for every state and input symbol. We're going to meet non-deterministic automata soon, and there it is possible to transition to many states from one state on one input. Now, back to the matter of a dead state. Here's our tennis example, and you can notice that the 2 accepting states do not actually have any transitions out. So we add a dead state, and all the missing transitions go to that state. The transitions from the dead state are to itself on all possible input symbols. Like the tennis automaton, we can represent any finite automaton by a graph. The nodes of the graph are the states of the automaton. The arcs are the transitions. There is an arc from state or node P to state or node Q labeled by all the input symbols A, such that delta of P and A is Q. For example, this arc would be present if delta of P and A and delta of P and B were both Q. We represent the start state by adding an arrow labeled start into that state, and we indicate final states by double circles. This is an interesting example of an automaton that processes text. The goal is to recognize that the string read so far ends in ing. The start state represents the condition where we have made no progress towards seeing ing. If in that state we next see I, we've made some progress, so we go to the state that says I was the last symbol seen. Otherwise, we stay in the start state because what we've seen so far is no help in seeing ing. Now, from the saw I state, if we next see an n, then we have made more progress. We go to state saw in. If we see another I in state saw I, then we've not made progress, but neither have we lost ground. We may be reading a word like skiing with a double I. Thus, the transition from state saw I on I is to itself. On any symbol other than I or n, we go back from saw I to the start state. In state saw in, if we next see a G, then we win. We've just seen ing as the last three symbols, so we go to the accepting state saw ing. On the other hand, if from state saw in we next see an I, then the pattern in is broken, but a new pattern beginning with I has started, so we go into the saw I state. On any input other than I or G, including N, we have no progress at all, so we go back to the start state. And finally, from state saw ing, we can only go to state saw I if the next input is I, and otherwise we must go back to the start state. Here is an automaton that represents the simplest possible protocol for sending data. The program is in one of two states, ready and sending. It starts in the ready state. Eventually, it gets a signal that some data has been loaded into its buffer, and at that point it enters the sending state, where it does what is necessary to transmit the contents of the buffer. The receiver will send back an ACT signal when the contents are received, in which case we are ready to return to the ready state. However, if the receiver is down, we may instead get a local timeout signal that warns us something is wrong and the buffer must be retransmitted. This automaton is not complete. There are no final states because the automaton is designed to run forever without rendering a decision. Also, there are missing transitions. It is okay to ignore ACK or timeout signals if you're in the ready state, staying in the ready state. However, a data signal in the sending state is an indication of an error, so we might want to go to an error state. And the error state is a dead state, so we need transitions to itself on any of the three inputs. A typical question that is asked about protocols is whether you can get to an error state. We could, for example, make the error state be final, and then ask if the language of the automaton is empty. As we shall see, there is an algorithm to tell whether the language of a finite automaton is empty, a question we could not ask about programs in general. In this example, however, it is really easy to see that there is a path in the graph from the start state to the final state, so its language is not empty and errors are possible. For a running example, we're going to use this automaton. Its language is the set of binary strings that do not contain two consecutive ones. State A is where the automaton will be whenever the input string seen so far is good. That is, it contains no consecutive ones. And also, in state A, it does not end in a 1. Surely the state should be the start state, since when no input has been received, there are not two consecutive ones, and moreover, the input so far does not end in a 1. We get to state B when the input is good, that is, no two consecutive ones, but the last symbol seen is a 1. Notice the only way to get to B is to be in A and then to get input 1. C is actually a dead state. We are there whenever two consecutive ones have been received. We arrive at C for the first time from B, which you recall means the previous input was 1, and in state B we receive a second 1. Once in state C, we stay there because once a string has 1, 1, you can never undo that fact, no matter how many zeros you see. We can also represent automata by tables. Here's our example automaton for strings without consecutive ones, shown as a transition graph in the corner. And we also see a representation of the same automaton as a table. The rows each correspond to one of the states, and the columns correspond to the input symbols. We indicate the final states by putting a star next to their name, and the start state is indicated by an arrow. The entries of the table are the values of the transition function applied to the state that is the row and the symbol that is the column. For example, this entry is C because it is in the row for the state B and the column for input symbol 1, and we know that delta of B and 1 is C. There are two important conventions we're going to use. They let us know the types of things without declaring types. In particular, we can distinguish between strings and characters. We use lowercase letters at the end of the alphabet, W, X, Y, and Z, and sometimes U or V to represent strings. When you see one of these letters, you need to think, aha, that's a string. And lowercase letters near the beginning of the alphabet will represent single symbols. Again, we'll try to remind you at first, but you have to think single symbol when you see one of these letters. The extended transition function delta is a function that takes a state q and a string w of any length, including 0, and tells us where the automaton gets to if it follows a path in the transition diagram from q, where the arcs are labeled by each of the symbols of w in order. That is, we look for the unique path from q whose labels form w. In some materials you will see a hat over the delta to remind you that it is the extended version. However, as we shall see, the extended delta agrees with the given delta when the string w is of length 1, that is, it is a single symbol. Thus there is not really a need to distinguish the extended and original deltas. The definition of the extended transition function delta is an induction on the length of the string to which this function is applied. For the basis, delta of q and epsilon is q. That is, if you are in state q and no input symbols arrive, then you stay in state q. For the induction, suppose the input string is wa. By our convention, w is a string of some length, possibly 0, and a is a single symbol. The inductive rule says that we first see where you get to from state q on string of inputs w. That would be delta of q and w. And then you see where you get from that state, whatever it is, on the last input a. In this example, 0, 0, 1 is split into w, which is 0, 1, and a, which is 1. Then we have to compute delta of b and 0, 1 and see where it goes to on input 1. Now 0, 1 is broken into a string w that is just a 0, and then an a, which is 1. So we need to compute delta of b0 and then see where we get to on input 1. Okay. But delta of b and 0 is a, see, right here. Thus, we can replace delta of b and 0 by the a, and now we have to say, what is the value of delta of a and 1? Well, that's b. Okay, so that's a b, and we replace that by the b there. And then finally, delta of b and 1, that's c. So that's our answer. Delta of b and 0, 1, 1 is the state c. As I mentioned, the extended delta sometimes is given a hat. However, we really don't need to distinguish the two deltas because they agree on single symbols. That is, if we want the extended delta for a state q and a string consisting of one symbol a, formally we treat that string as the empty string followed by the symbol a. Then we have to compute delta hat of q and epsilon, but we know by the basis rule that this is q itself. Thus, delta hat of q and a is the same state as delta of q and a. In fact, I really cheated on the previous slide. I needed delta hat of b and 0. I just went to the table and looked it up as if it were delta of b and 0. Now we see they are in fact the same, so it was no harm, no foul. There are many different kinds of automata. We've seen only the deterministic finite automaton so far, but there are many others. But no matter what kind of automaton, its job is to define some language. We'll use L of A to denote the language defined by automaton A. For a deterministic finite automaton, the language it defines is the set of strings that may take the start state to a final state. Formally, the language of a DFA is the set of strings W such that the extended delta applied to the start state, and this W, is a final state. For example, consider our running example of the automaton that accepts strings without consecutive ones, and consider the input 1, 0, 1. It should accept this string because it obviously does not have consecutive ones. The start state is A, and if we follow the path labeled 1, 0, 1, we first go to B. Then from B we follow the arc with a 0. That leads us back to A. The third input is another 1, so that gets us back to B again. Since the path from A labeled 101 gets us to a final state, 101 is indeed accepted by the automaton. Now this expression is called a set former. It describes sets, and in particular we'll use it to describe languages. In this example, it's describing the language of the automaton that has served as our running example. The set former starts with a curly brace, and then an expression representing the things we want to put in the set. In this case, the expression simply says that the set consists of some strings W. We know they're strings because of our convention. The vertical bar can be read such that, and then there follows a description of what must be true for something to be a member of the set. In our example, we say that the string consists of zeros and ones and does not have two consecutive ones. Many important facts about automata that we might want to prove are of the form that two sets, typically languages or sets of strings, are really the same. We're going to prove that the DFA we've been playing with accepts the language I claimed it does, the set of binary strings without consecutive ones. So one set is the language of the DFA from our example, and the second set is the language consisting of all strings of zeros and ones without two consecutive ones. I'm going to spend a good deal of time proving this simple result because it will give you all the details of how one proves things about languages. In the future, I'm not going to be so focused on proofs, but I think it is important that everyone go through one of these proofs in all its gory detail. To prove two sets S and T are equal, we generally need to prove two things, that each is contained in the other. That is, we start by assuming W is a member of one, say S, and we use that fact to prove W is in the other, T. Then we start over, and we assume W is in T, and we use that to prove W is also in S. In what follows, we take S to be the language of the DFA we have been playing with, and T to be the set of binary strings without consecutive ones. First, we're going to prove that if W is accepted by this automaton, the one shown in the slide, then W has no 1-1s. Okay, and the proof is an induction on the length of W. It turns out that if we simply try to prove this statement on the slide, we fail, and I'll point out in a few slides what goes wrong. A common trick for inductive proofs is to make a more detailed statement here than you really want because it makes the inductive proof work. Here we need to distinguish whether an accepted string gets you to state A or state B because we need to know whether or not the string ends in 1, even though the conclusion no 1-1s is true in both states A and B. The inductive hypothesis will be in two parts. Part 1 says that if W gets you to state A, then not only is W good in the sense that it doesn't have consecutive ones, but it doesn't even end in 1. Part 2 says that if W gets you to state B, then W is still good, but it must end in 1. Remember, the induction is on the length of W, so the basis case is when W is the empty string, the only string of length 0. We're going to use bars around a string to denote its length. And now, let's prove part 1 of the basis. Delta of A in the empty string is indeed equal to A, but the conclusion is true since the empty string does not have consecutive ones. For item 2, things are a little trickier. It is false that delta of A and the empty string is B, but it is also false that the empty string ends in 1. However, an important principle of logic is that the statement false implies false is true. That is, whenever the if portion of the statement is false, then it doesn't matter whether the then portion is true or not. The statement as a whole is true. Thus, a statement like, if I am Superman, then I wear red undershorts, is a true statement simply because I am not Superman. You don't have to concern yourself with the color of my undershorts. The mathematical term for an if-then statement that is true because the if part is false is that the statement holds vacuously. Now let's address the inductive step. We assume that W is a string of length at least 1, and we assume that the inductive hypothesis, the statements 1 and 2 from the previous slide, about strings that get the automaton to states A or B, is true for strings shorter than W. Let's let W be XA, where by our convention A is the last symbol of W and X is all the symbols, possibly none, up to but not including the last symbol of W. Since X is shorter than W, we assume the inductive hypothesis for X. We're going to prove both statements 1 and 2 for W, which remember we broke up as a shorter string X followed by the last symbol A. Let's start with condition 1. That is, if delta of A and W equals A, then W is good. It has no consecutive ones, and it does not end in 1. How can you get to A by reading string X followed by symbol A? Well, look at the diagram. The only transitions into A are on input 0. That's this and that. So symbol A must be 0. That immediately lets us conclude that W does not end in 1. And furthermore, these transitions to A are only from A and B. Thus X must get us to A or B. Now, regardless of whether X gets us to A or B, we can conclude, using the inductive hypothesis, that X is good. It has no consecutive ones. Thus W, which is X followed by 0, also has no consecutive ones, and it surely does not end in 1. Now for part 2. If delta of A and W equals B, then W is good and ends in 1. There's only one way to get to B. You have to be in state A, and the input has to be 1. Thus, if W equals X followed by A, then X gets us to state A, and the symbol A is a 1. We can therefore conclude that W ends in 1. We apply the inductive hypothesis to X, and we conclude that X not only has no consecutive ones, but doesn't end in 1. Any occurrence of 1, 1 in W would either have to be at the end or lie completely within X. We know it doesn't lie within X by the inductive hypothesis. We know 1, 1 cannot be at the end because X does not end in 1, and A is only a single 1. We conclude that W does not have consecutive ones. Notice that if we don't use this more complicated inductive hypothesis, where we distinguish between A and B according to whether the string X ends in 1, then we cannot make the inductive proof. If we know only that X gets us to A or B, then we might think that X gets us to state A yet ends in 1, in which case W, which would be XA, would have 2 consecutive ones. But we're not done. We still have to prove that T is contained in S. That is, if S is a good string with no consecutive ones, then it is accepted by the automaton. It is helpful to restate what we need to prove in its contrapositive form, which is logically equivalent to the original. The contrapositive of an if-then statement, say if X then Y, is if not Y then not X. We can see why this is an equivalent statement, since if Y is false, it couldn't be that X is true, because whenever X is true, Y is true. In this case, X is the statement that W is a good string with no 1, 1s, and Y is the statement that W is accepted by the automaton. The contrapositive is that W is not accepted by the automaton, then W is not a good string. That is, it contains 1, 1 as a substring. A deterministic automaton has exactly one transition from each state on each input symbol. Thus, any string W gets the automaton from the start state to exactly one state. So the only way W could not be accepted is if it gets this automaton to state C. Notice that the only way to get the automaton to C is for some string X to get it to B, and then for an input 1 to follow. Once in C, you stay in C, so anything can follow the X in 1. We'll call that Y. That is, any string W that gets the automaton to state C must be of the form x1y, where X gets to B. We already observed that the only way to get to B is by a string that ends in 1, since the only transition into B is on 1. Thus X must be of the form z1 for some z. Thus W is really z11y, and we can conclude that if delta of A and W is C, then W is bad. That is, it contains 2 consecutive ones. Now we introduce a class of languages called the regular languages. These are the languages that have a deterministic finite automaton accepting them. That means that the language is exactly the set of strings accepted by this automaton. Soon we shall see that there are several other ways to describe the regular languages, including by regular expressions and non-deterministic automata. While many common languages are regular, there are also many that are not. Intuitively, finite automata cannot count beyond a fixed number. Thus, they cannot do things like check whether they have seen the same number of zeros as ones on their input, or check that parentheses are balanced in an arithmetic expression. For those tasks, we need more powerful mechanisms such as context-free grammars, which we will meet soon enough. Here is an example of a language that is simple to understand but is not a regular language. To understand what this notation is saying, we first need to know that an exponent I on a symbol is shorthand for the string consisting of I copies of that symbol. Thus, 0 to the 4th means the string 0, 0, 0, 0. Thus, we read this set former as 0 to the n, 1 to the n, such that n is equal to or greater than 1, or more verbosely, the set of strings consisting of n zeros followed by n ones for some n equal to or greater than 1. The strings of the language L1 are thus 0, 1, 0, 0, 1, 1, and so on. Here's another example of a non-regular language, the set of strings that are balanced parentheses. The strings of balanced parentheses are those that can appear in an arithmetic expression. For example, the string 0 of left paren, right paren, can appear in an expression like a plus b times c. Or this string can appear in an expression like a plus b times c plus d. Examples of strings that are not balanced are the right paren followed by a left paren. This is not balanced because no prefix of a balanced string can have more left parens than right parens. Obviously, there is no arithmetic expression that has this sequence of parentheses as its sole set of parentheses. Also, 3 lefts followed by 2 rights. It's not balanced because it has more left parens than right. However, regular languages are common. For example, in each language there is a format for floating point numbers, and this format can be quite complicated with optional e's or decimal points and strings of digits that could be empty. But in all programming languages I know about, the set of strings that represent some floating point number is a regular language. This is a very interesting case illustrating what finite memory means. We want to know if a binary number is divisible by 23. We're going to read the bits high order first. But if we have only finite memory, how can we remember exactly what sequence of bits has been read, since the sequence can grow very long? But there is a trick. We don't really need to remember everything about the bits read. It is sufficient to remember what the remainder is when divided by 23. Thus, we'll have 23 states, 0 through 22. These correspond to the 23 possible remainders when an integer is divided by 23. The start state is 0 because we interpret the empty string as representing the number 0. That may be a bit of an assumption, but nothing else makes sense, and treating it as 0 makes everything work out right. State 0 is also the only final state, since we want inputs that leave a remainder of 0 when divided by 23. We're going to assume that things are working right after reading a binary string w. That is, w takes state 0 to the state that is the correct remainder when w is divided by 23. I'm using the C-style percent operator to denote the remainder. You can read the percent as modulo or mod, which is just another way of saying the remainder when divided by. The transition from each state I on input 0 is to the state that is the remainder of 2i divided by 23. To see why this works, we know that I equals 23a plus b. For some integer a and for some integer b in the range 0 to 22. That is, b equals I mod 23. Then 2i is 46a plus 2b. Since 46 is divisible by 23, 2i mod 23 is just 2b mod 23. That is, when we divide by 23, we can just get rid of the 46a. We know it will leave a remainder of 0. Thus, we can take the state b, which is the remainder, double it, subtract 23 if it is 23 or more, and that gives us the new remainder and therefore the new state. We never need to know what a is, and we never need to know I exactly. For the same reason, when a 1 arrives at the input, we can go from state I to the state that is the remainder of 2i plus 1 when divided by 23. For example, twice 15 is 30. So from state 15, we go to the state that is the remainder of 30 divided by 23, or state 7, when the input is 0. From state 11, on input 1, we go to the state that is the remainder of twice 11 plus 1 divided by 23. That's state 0. So whenever a string gets you to state 11, that is, the string leaves a remainder of 11 when divided by 23, that string followed by a 1 must be divisible by 23 and therefore must be accepted. Interestingly, another regular language is the set of all the binary strings that if we read the strings in backwards, that is, low order bit first, they form a binary integer that is divisible by 23. And there's nothing special about 23. It could be any number in both this example and the previous one. So for example, 0110100 is in this language because when we reverse it, we get 001011110, which has the value 46 in decimal, and 46 is, of course, divisible by 23. It is really tricky to design a DFA to accept this reverse language. However, there is a theorem, which we shall see soon, that says if a language is regular, then its reversal, what you get by reversing each of its strings, is also a regular language. The proof of this theorem will let us construct the DFA for the reverse language from the DFA we just saw. Today we introduce the non-deterministic finite automaton. We're going to use the subset construction to show that every language that can be recognized by any non-deterministic finite automaton is still a regular language, in that it can be also recognized by a deterministic finite automaton. We're then going to add something to the non-deterministic automaton called epsilon transitions that allow sort of spontaneous jumps from state to state, and we will in fact show that these automata, even though they look more powerful, also can recognize only the regular languages. A non-deterministic automaton has the ability to be in several states at once. A transition in a non-deterministic automaton is from some state, say Q, on an input, say A, it can go to several different states. So we can have several transitions all labeled A. And this is the thing that allows the automaton to, in a sense, guess, to be non-deterministic. It can go from state Q to really any of these states, and therefore it actually goes to all of those states at once. Okay, like the DFA, a non-deterministic finite automaton, or NFA as we will call it, has one start state where a computation begins. The NFA can have any number of final states, and an input is accepted if any sequence of choices leads from the start state to some final state. The intuition is that the NFA is allowed to guess which way to go, but it is able always to guess right, since all the guesses are followed in parallel, and the NFA gets credit for the right guesses, no matter how many wrong guesses it also makes. In our example of a non-deterministic finite automaton, the states are squares of a chessboard. In general, you can occupy several different squares at a time. In a red move, which we represent by the input symbol R, you get to move to any adjacent red square. So in effect, you replicate yourself and move to all of them. Similarly, if the input is B, you can move to any adjacent black square, So in effect, you move to all the black squares. The question we ask is whether the given sequence of R and B inputs can get you from the start state, which will be the upper left corner, to the one final state, which is the lower right corner. The answer is yes, if any sequence of choices we get with each input leads us from the upper left to the lower right. It is not necessary that all such choices do, and in general there will always be some choices that lead us astray. Okay, so here's our example. The chessboard will be rather tiny. It's only 3 by 3 instead of 8 by 8, but the ideas are all the same. Okay. Now, using the moves which I have summarized in a transition table, but which follow the intuition that I gave you, we're going to examine the sequence of inputs RBB. That is one red move followed by two black moves. We'll start in the start state, state 1 only. So we're going to show state 1 there. Okay. Now, we get an R input, so we can move to any of the red squares adjacent to square 1. Or in terms of the transition table, here's the row for state 1. We look under R, and we find states 2 and 4 are the possible moves. Okay, and notice that adjacent really means one king move, so that from state 1, let's say you can go to 2, 4, or 5. Obviously, only 2 and 4 on a red move, and only 5 on a black move. Okay, so after reading the R, we go from state 1 to states 2 and 4. Okay, so now we're in states 2 and 4, and B comes in. So what do we do? Well, from state 2, we can go to 1, 3, or 5. You can figure that out either by noticing that 1, 3, and 5 are the adjacent black squares, or you can just look it up on the table here in row 2. The black moves are 1, 3, and 5. Now, how about state 4? Well, from 4, you can go to 1, 5, or 7 on a black move. Some of those states were already listed, but the point is that between 2 and 4, the states you can get to are 1, 3, 5, and 7. Now, that's all for the first B. Now the second B comes in, and from 1, you can only go to 5. From 3, same thing, you can only go to 5 on a black move. Now from 5, you can go to a lot of states. You can go to 1, 3, 7, and 9. And from 7, again, you only go to 5. So after reading RBB, you are in fact, all the odd-numbered states, or all the black, the black squares. Since 9 is the accepting state, we say that RBB is accepted by this automaton. The fact that it's also in states 5, 1, 3, and 7 are not relevant to the question of whether it's accepted or not. Here are the components of an NFA. They look exactly the same as for the DFA, and we'll typically use the same letters to represent them. The big difference is in the type of the transition function, and we'll see that on the next slide. For the NFA, delta of state Q and input A is now a set of states, possibly empty, rather than a single state as it was for the DFA. The extension of delta to strings is a bit more complex. The basis is still easy. Delta of Q and the empty string is just the set containing Q, since the only state you can reach on no input is the state you are in. For the induction, suppose we start in state Q and we read string W followed by symbol A. We first compute delta of Q and W, the set of states you get from Q by following W. So from Q, let's say following paths labeled W, we might get to states P1, P2, and so on. Okay, then for each of these states, say P1, P2, and so on, we're going to use the given delta function to find the set of states they each get to on A. So let's say P1 might go to these two states, I don't know their names. P2 might also go to that one, and several others, and so on. You find all the states you can get to, but always on transition labeled A. And the resulting union, this set, is delta of Q and WA. Okay, the language of a non-deterministic automaton is simply the set of strings that it accepts, that is, the set of strings W such that when you compute delta of Q, Q naught and W, that's Q naught is of course the start state, when you compute delta of Q naught and W, you have a set that contains at least one final state. Okay, the language of the non-deterministic automaton that we designed to represent moves on a chessboard is actually quite tricky to describe. For strings consisting only of B's, it's easy. You start in only in the state 1, and on the next move with B, you only go to state 5, so you're only in the set containing 5. Another B, if you'll notice, will take you from 5 to 1, 3, 7, and 9. So now, after the second B, you're in 1, 3, 7, and 9 only. The next B, well, each of 1, 3, 7, and 9 only have B as an adjacent black square. Their other adjacent squares are red. So after 1, 3, 7, 9, you are now in just the set 5. And from 5, you go to 1, 3, 7, 9, and so on. As a result, you accept all the even length non-empty strings. That is BB, BBBB, 6 Bs, 8 Bs, and so on. And you don't accept strings B or BBB, and so on, the odd length strings. Okay. It's less clear what happens when there are R's in the input. Obviously, an accepted string must end in B because only state 9 is accepting, and you only get there on a B move. But I'll leave it to you to figure out exactly what strings with one or more R's are accepted. Okay. In a sense, a DFA is an NFA that just doesn't have any non-determinism. Formally, given a DFA with a transition function, which we'll call delta sub D, you can create an NFA with the same states and inputs as the DFA and the same start and final states. The only thing different about the NFA is that the form of its transition function is what it has to be for an NFA. It gives you a set of states rather than a single state. But that set of states in delta N will be exactly the one state that delta D gives you for a given Q and input A. As a result, the NFA, after reading some sequence of inputs, is in the set of states that's always a singleton. It always contains only the one state that the DFA is in. Okay, so that says any language accepted by a DFA can be accepted by some NFA, and in fact the NFA really looks the same as the DFA, and it almost is the DFA. Okay. Surprisingly, for any NFA, there's a DFA that accepts exactly the same language. And the proof is called the subset construction, and this construction was the thing that, as a graduate student, convinced me that there was something to computer science theory. It had only been discovered 5 years before, and it boggled my mind to see a construction that, while it could be described easily, resulted in something that could not be grasped. Okay. The problem is that the number of states of the DFA that you get from an NFA can be the number can be exponential in the number of NFA states. Now, if the NFA has 3 states, the DFA can have 8 states. That's not a big deal. I can visualize an 8-state automaton. But if the NFA has 10 states, The DFA could have 1,000 states, and that's already becoming quite hard to imagine. And if the NFA has 20 states, which is still something we can visualize, the DFA can have 1,000,000 states, and we're completely lost, even though we know the DFA exists. Oh, and by the way, the situation is not nearly as bad in practice as it looks in theory. Many of the non-deterministic automata that you construct in things like compiler design, when you convert them to a DFA, the number of states doesn't really grow much at all, if at all. In fact, the chess NFA that we just introduced actually has an equivalent DFA with fewer states, as we shall soon see. So let's start with a typical NFA. It has the conventional names for the components, although we'll use delta n for its transition function to distinguish it from delta d, which will be the transition function for the equivalent DFA that we're going to construct. Now, in the DFA, states are represented by 2 to the q, which is 2 to the q is a mathematical notation for the power set of q, that is the set of all subsets of q. Okay. Notice that if a set q has n elements, then its power set has 2 to the n elements, so the notation sort of makes sense. Okay. So the important point to remember is that the DFA states are actually sets of states of the NFA, and there can be an exponential number of them compared with the number of states in the NA. The inputs of the DFA are the same as the inputs of the NFA. That's the set sigma. The start state of the DFA is the set containing the start state of the NFA. Okay. Remember that the states of the deterministic automaton are sets of states of the non-deterministic automaton. Okay, thus the start state, which is a single state of the DFA, is written as a set of states of the NFA. Of course, this set contains only the start state of the NFA. Okay, then the final states of the DFA are all those states that, they're thought of as sets of states of the NFA, contain a member of F. Remember, F is the set of final states for the NFA. Just to make sure we understand what's going on, the DFA states have names that look like sets of states. However, they are single objects. Okay. An analogy that might be useful to make is with a class of objects in a language like Java or C++, whose values happen to be sets of objects from some other class. Okay. The transition function delta d is defined by delta d applied to, now again, this is not a set of, this is a set of NFA states, but this is a single state of the DFA, and input A is the union over all all the states Q1 through Qk of what you get when you take the delta n, or there's the transition function of the non-deterministic automaton, and apply it to that Qi and A. So you have Q, here's Q1, here's Q2, and you see where you get to on A, and like that, that's A, and so on. And this set of NFA states is the name of the DFA state that you get to when you go from this state of the DFA on input A to the next state of the DFA. Okay, we're going to, as an example of the subset construction, do a lazy construction of DFA states. That's generally much better than assuming we need all the subsets of NFA states. Okay, we're going to start. Of course, we know we need the set containing the initial state, so we surely need, as one of the DFA states, the set containing 1, because that's the initial state of the NFA. But we're only going to create rows for states when we are sure that we need them. Okay, so obviously we need the start state of the DFA, which is the set containing 1. So we'll begin the construction with a row for the set containing 1. Now, from the NFA table, which I've outlined here in red, we know that on R, 1 goes to 2, 4, and on B it goes to 5. And since this set is a singleton, that's all we need to know. So we know immediately that in the DFA, the set containing 1 goes to the set containing 2, 4 on R, and the set containing 5 on B. Now, I've put these two sets, I've made rows for them in the table. I haven't filled out the rows yet, but we know that we're going to have to because they obviously are states that you can reach from the start state of the DFA. Okay, here we've filled out the row for the DFA state whose name is set containing 2, 4. Okay. Well, on input R, we look at this is the NFA table. We look at the things marked in red, that is, on 2, so from 2 on input R, you go to 4 and 6, and from state 4 on input R, you go to 2 and 8. So from the set containing 2, 4 on R, you go to 2, 4, 6, 8. Again, this is a single state of the DFA. And since I haven't encountered the state before, I now create a row for it, reminding me that I'm going to have to figure out what its transitions are sometime in the future. Let's see, again, from state 2, 4 on input B, you just look at where the NFA goes on those two states, and you take the union of 135 and 157. That's 1357, and that's in there. And I also put it here because I'm going to have to figure out its row in a minute. Now we fill out the row for 5. Again, that's fairly easy. You just look at the row for 5 on the NFA table, and you enter the states right there. 2, 4, 6, 8 we've seen already, so we don't have to create a row for it. 1, 3, 7, 9 has not been created, so we will create it now. And I've also started because notice that is a final state of the DFA. It has the final state of the NFA, state 9. Okay, now for 2, 4, 6, 8, again, I've in the NFA table, I've put in red the relevant rows. For R, I just take the union. I've got 4, 6, 2, 8, 2, 8, 4, 6, so the union is 2, 4, 6, 8. That's a state I've seen already, not interesting. On B, I've got 1, 3, 5, I've got 1, 5, 7, I've got 3, 5, 9, 5, 7, 9. The union of that is 1, 3, 5, 7, 9. That's a new state, so I add it to the list of rows I need to construct. And by the way, it's also a final state because it contains 9. Okay, here's the row for 1, 3, 5, 7. Again, same process. You again get 2, 4, 6, 8 on R, and now you get 1, 35, 7, 9 on B, and these are both states you've seen, so we add no new rows. For 1, 3, 7, 9, we just compute its entries. Perhaps the only interesting thing is that on a B, all of 1, 3, 7, and 9 go to only B, so only 5 on B. So what you get is a set containing only 5. That is a state that we've seen before, as of course is 2, 4, 6, 8. So we don't have to add any new states. And finally, 1, 3, 5, 7, 9 also yield no new states. And so we now have completed the entire transition table for the DFA. Notice it only has 7 states, while the NFA had 9. So it actually shrunk the number of states. Again, you have to be rather lucky to do that, but it does happen. We're going to prove that the NFA and the DFA we construct by the subset construction are equivalent. That is, they define the same language. We must thus show that if one accepts a string W, if and only if the other does. That is, the two languages are each contained in the other, and therefore they are the same. Now, notice that delta n is a set of NFA states. Delta d, on the other hand, is a single state, but its name is a set of NFA states. So it is quite reasonable, at least it's an interesting pun, to argue that this as a single state is the same as that as a set of states. For the basis, let W be the empty string. Then delta n of Q0 and the empty string is the set containing Q0 by the basis rule for extending the delta for non-deterministic automata. And delta D of the set containing Q0 and the empty string is the set containing Q0, again, by the extended delta rule for deterministic automata. For the inductive step, we'll assume the inductive hypothesis that the states of the DFA, that the DFA and the NFA get to on string W are the same sets for all strings shorter than W, and we'll prove the statement for W itself. Okay. W is of length at least 1, so we can write it as string X followed by symbol A. And we can assume the inductive hypothesis holds for X, because it is clearly shorter than W. That is, we're going to assume that delta n of Q0 and X is delta D of the set containing Q0 and X, and we'll call that set S. Let T be the set of states the NFA can get to by starting in state S and following a transition on A. So that is, we have, let us say, here's set S of states, and coming out of various of these states are transitions on A. Okay, by the rule for the extended delta for NFAs, the set T of all the states that you get to is delta n of Q0 and W. By the subset construction, we also know that delta D of S and A is T. Thus, delta n of Q0 and W and delta D of Q0 and W are both T. The latter, of course, is by the extension rule for deterministic automata. That is how you compute the extended delta. So we have therefore proved the inductive step. Okay. We are now going to add an additional capability to NFAs, the ability to make a spontaneous transition on epsilon, that is, without using any input. We just saw that the NFA, while it can be a convenience in designing automata, still accepts only regular languages. The same is true for the new model, which we'll call epsilon NFAs, but they can be a real convenience in constructing automata, and yet they still accept only the regular languages. Here's an example of an epsilon NFA. The transition diagram has some arcs labeled epsilon, and we can follow any such arc without adding to the sequence of inputs that the automaton has processed. That is, epsilon is invisible as far as input strings are concerned. Okay. We also see the transition table for this automaton. Notice it has a separate column for epsilon, but epsilon is not an input symbol. It's not a member of the input alphabet. For example, from the start state A, let's look at A, there is only one transition on 0 to E, and that's why you have set containing E over here. There's only one transition, that's to B, on input 1, so that's why you have set containing B there. And there are no transitions out on the empty string. So we have the empty set symbol represents the transitions from A on epsilon. It's not an input. It represents spontaneous transitions. Let's look at E now. On 0, there's a transition to F, and only to F, so you get set containing F there. There are no transitions at all from E on a 1, so you get the empty set. Okay. And on epsilon, you have transitions to both B and C, so that you have a set containing BC at that entry. Okay. Notice that if we are in state E and the input is 1, then we can spontaneously go to B on epsilon, and then on the 1 wind up in C. Okay. We can also go spontaneously from E to C on epsilon and wind up in D on input 1. Okay, now to do the conversion of epsilon NFAs to regular or ordinary NFAs, we need to have the notion of the closure. The closure of a state Q, which we're going to write as CL of Q, is the set of states we can get to starting in Q and following only epsilon transitions. So, for example, from A, you can get nowhere else on epsilon, right? If you're here, there are no epsilon transitions out. As a result, the closure of A is just the set containing A. Of course, you're in A to begin with, so you can stay in A. So closure of a state always contains at least itself. The closure of E is trickier. Okay, we start in E. Surely we can reach E. Then there are epsilon transitions from E to B and C, so we can surely get to B and C. But now we have to see where can we get to from B and C. Well, C doesn't have any epsilon transitions out, so we can't get anywhere else, but B also has D, a transition on epsilon to D. D has nowhere else to go on epsilon. So the conclusion is that the closure of E on is all of B, C, D, and E. And that's what we've written here. Then we also are going to need to apply the closure operator to sets of states, and the definition is quite simple. The closure of a set of states is just the union of the closures of each of those states. Now, we need to describe the operation of an epsilon NFA by defining the extended delta. And again, it's intended to tell us about where we can get from a given state following a path labeled by a certain string W. However, epsilon, the empty string, is invisible along paths, so W only involves the real input symbols of the automaton. As a result, we follow paths that are labeled by real symbols of W, but with arcs labeled epsilon interspersed as much as we like. Okay, so for the epsilon NFA, delta hat of QA is not the same as delta of Q and A, because delta of Q and A does not include any epsilon transitions. So we're going to keep the hats on the extended delta when we need them. Okay. So for the basis, delta hat of Q and epsilon is the closure of the state Q. So it's not just Q. If you can reach anywhere from Q on epsilon, then that's included in the closure and therefore in the delta hat. For the induction, suppose the input is string X followed by symbol A. Start by figuring out what delta hat of Q0 and X is. Say it is a set of states S. Okay. For example, let's suppose that X is BC. Then we might start from Q0 and we'll follow paths labeled epsilon and then a B, and then maybe more epsilons, possibly none, to a state where we follow a C, and maybe even then more epsilons. Now, suppose this takes us to a set of states S. To compute delta hat of Q and X followed by A, we look at all the states in S, we find all the A transitions, no epsilons now. We then have to take the closure of these states, that is, we follow all the epsilon paths. And finally get to the state that is this set of states is delta hat of Q and XA. Here is an example. This is the automaton that we've been playing with. I say delta hat of A and epsilon is the closure of A. That's the basis rule. And that's just set containing A, because A doesn't get you anywhere on epsilon. Now, I'd say the delta hat of A and 0 is the closure of E, which is B, C, D, and E, as we discussed earlier. Why closure of E? Because when we already determined that the closure of A is A, and on 0, the only place you can get to from A on a 0 is E. So we have to close E. Now, delta hat of A and the string 0, 1, I claim is closure of C and D, which actually is just C and D. Why is it closure of C, D? Well, look, we already know that delta hat of A and 0 is the set containing B, C, D, and E. Okay, so we're sort of here, 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 and here. Now, on a 1, where can I go from any of those states? Well, from E, no place. From D, no place. From B to C, and from C to D. So the only places you can get to from B, C, D, and E on a 1 are C and D. So that's why we start with C and D. We take the closure. Now, neither C nor D have any epsilon transitions out, so we conclude that delta hat of A and 0, 1 is set containing CD. What that means is, if you look at, starting in A, all the paths labeled 0, 1, with as many epsilons as you wish thrown in the middle, those paths lead you only to C and D. That is, there's this. There's this, and there is this. Okay, and that's it. Okay. Finally, the language of an epsilon NFA is defined in the expected way. For any string W, you compute the extended delta of the start state and that string W, and if you see if any of the resulting set of states is a final state, you accept W if so, and if not, then not. Okay, we now want to show that the NFA and epsilon NFA models yield the same languages, the regular languages, of course. One direction is easy, since an ordinary NFA is an epsilon NFA that happens to have no transitions on epsilon. But proving that for every epsilon NFA there is an ordinary NFA that accepts the same language, we're going to have to get rid of the epsilon transitions. We do that by combining them with the next transition on a real input. Okay. If you're following the text, you should notice that this construction is somewhat different from the one in the text, but both constructions work. Here, we'll have to change the set of final states, while the one in the book doesn't, but this construction is, I believe, a bit simpler. Okay. This is a picture of how we iron out the epsilon transitions. We start from a state, okay, here, and we follow all the epsilons we can using the closure operator, and I'm sort of imagining that the yellow area represents paths that are labeled only by epsilons. We then follow all the transitions from any of the states we reach on a real input symbol A. The ordinary NFA is able to get to, on input A, any of the states that can be reached using these transitions of the epsilon NFA on input A. That is, the ordinary NFA will have a transition from here to each of these states on input A. Now, since we don't close the states after transition on A, we have to make additional final states, those that can reach a final state on epsilons only. So, for example, if this state might not be final, but it might be able to reach by epsilons some final state. If so, this is a final state of the epsilon NFA, but in the ordinary NFA we're constructing, we're going to make this state be final. Because in effect, it has the power of a final state in the epsilon NFA. Whenever you get there, epsilons will take you to a final state. So you know that whatever got you here will be accepted by the epsilon NFA. So you want the ordinary NFA to accept it as well. We're going to start with an epsilon NFA that has the usual components, Q for states, sigma for inputs, and so on. But we'll use delta E for its transition function. Okay, and we're going to construct an ordinary NFA with the same set of states, same input symbols, same start state, a different set of final states, perhaps F prime, and its transition function will be called delta N. Okay, now, the way we compute delta N of Q and A is as follows. We're going to start in state Q. We're going to close Q, that is by following epsilon paths, to get to some set of states S. Okay. Delta N of Q and A is take all the states in S, we find all their transitions on A, and this is the set of states that is delta sub N of Q and A. Okay. That is, in the ordinary automaton, Q gets you on A anywhere that the epsilon NFA can get you by following 0 or more epsilons and then an A. Okay. Now, prime, the set of final states of the ordinary NFA, is the set of states Q such that the closure of Q contains a state of F. That's the thing that, again, allows you, if there's an epsilon path to a final state, then this state gets the same accepting power that wasn't needed in the epsilon NFA. Okay, we're not going to prove this, but the idea is that the NFA on any input W enters the set of states the epsilon NFA enters on the same input using epsilon transitions anywhere it likes except at the end after reading all the real inputs of W. However, state P in delta N of Q0 and W is a final state if in the epsilon NFA P can get to a final state following only epsilons. Okay. Thus, the fact that the equation holds, that is this equation here, is enough to say that W is accepted by either both or neither of the automata. That is, if delta E contains an accepting state, then delta N of Q0 and W will contain a state which has also been made accepting because it can reach on epsilons an accepting state of the epsilon NFA. Here's the epsilon NFA we used before as an example, and the NFA, ordinary NFA, that we construct. The interesting changes are marked in red. So first of all, here are all the non-trivial closures. That is, the closure of B, because B goes to D on epsilon, the closure of B is B and D. And the closure of E, which we've worked out before, is, E goes to B and C, B goes to D, so E can go to B, C, D, and E. Okay. In the NFA without epsilon transitions, we need to change the transition from E on input 1. And the reason is that we first take the closure of E, which of course is B, C, D, and E, and then we ask, where can I get to from those states on a 1? And if you look at the epsilon NFA from B, C, D, and E, all you can get to are C and D. Okay. So we put C and D. It becomes the entry there, whereas in the epsilon NFA it was the empty set. You can see that. Okay, the transition from E on 0 actually doesn't change. The reason is that B, C, and D have no transitions on 0. So the fact that we can get to them on epsilon doesn't help us when the input is a 0. Okay, finally, since the closures of B and E include the final state D, they become final states as well as D in the ordinary NFA. And that's the entire construction. So, we now have 3 different formalisms for describing languages: the DFA, the NFA, and the epsilon NFA. They look progressively more powerful, and in fact they are more powerful in the sense of the things they can do. But in fact they give us exactly the same class of regular languages. Very soon we'll see a 4th formalism called regular expressions that look quite different from these, but in fact also give us exactly the regular languages. So we might be getting the idea that the regular languages are quite a natural class of languages, and indeed they are. We should notice that the added power of NFAs and epsilon NFAs are quite useful. For example, we shall talk about designing automata to recognize sets of keywords, say the reserved words in C or some other programming language. That is an important task for building a compiler for the language. We could design a DFA for the task, but it's much easier to start with simple DFAs for each keyword. It's just a chain of states. Say for else, it's just an E, an L, an S, and an E, and of course that's a final state. Okay, so that's how you recognize your keyword else. Then we'll connect them all with epsilon transitions from a single start state. So you put an epsilon here. This becomes the start state. And you'll have epsilon transitions to a lot of these chains for all the keywords. And they, of course, all end in a final state. And that's all there is to it. You've got an epsilon NFA. And then we're going to convert them to a deterministic automaton, because the deterministic automaton is necessary for if you want to actually execute an automaton. That is, only a DFA can be implemented. No one has yet invented a non-deterministic computer, although I've heard that Intel is working on it. Today we're going to introduce the idea of regular expressions. This is a simple algebraic notation that describes exactly the regular languages. In practice, it's very common to have a regular expression-like notation to describe patterns, such as patterns in text, and to have behind the scenes a compiler from regular expressions into finite automata, in particular deterministic finite automata, because these are the things that actually can be executed. So after introducing the notion of a regular expression, we're going to show you that you can convert any regular expression into an automaton, and also any automaton into a regular expression. That's the proof that the languages accepted by regular expressions and the various kinds of finite automata that we've met are exactly the same. Okay. The algebra you are most familiar with is probably arithmetic, using operators plus and times and operating on numbers. The regular expression algebra operates on languages, and it has 3 specialized operators. Regular expressions, like algebraic expressions, are built up by applying these operators to operand. So, regular expressions then describe languages by an algebra, and they, as I said, describe exactly the regular languages. we'll use L of E as the notation for the language described by the regular expression E. And we will describe regular expressions in the languages recursively. Regular expressions use three operations, the union, concatenation, and the Kleene star. Okay. The union of languages is the usual thing, since languages are sets. And here's a very simple example. Here are two sets, they're languages, each with with three strings and with two strings. 0, 1 happens to be in both, so it will be once in the union. 1, 1, 1 is there, 1, 0 is there, and 0, 0 is there. So that's the common notion of the union on sets or languages. Okay. Concatenation is also a fairly simple operation. We'll denote the concatenation of two languages, say L and M, by juxtaposition, that is, L, M with no punctuation in between them. The language LM contains every string that is W concatenated with X, such that W is in L and X is in M. So here's an example. We are, in effect, multiplying the two languages. That is, we'll take 0, 1 from the first language, and we can concatenate it with 0, 0. That gives us 0, 1, 0, 0. We could also take 0, 1 again, concatenate it with 0, 1, and that gives us that. Then 1, 1, 1 concatenated with the two strings here gives us these two strings in the result. And 1, 0 concatenated with 0, 0 and 0, 1 gives us the final two strings in the result. Okay. Kleene star is probably something that you're least familiar with. If L is a language, then L star, which is called the Kleene star or just the star operator, is the set of strings that you can form by concatenating 0 or more strings from L in any order. That is, you can take one string from L, you take no strings from L, that would give you the empty string. You take one string from L. You take two strings from L, that can be any two strings, they don't have to be the same. You can concatenate them. You can take three strings from L, concatenate them, and so on. Incidentally, Stephen Kleene was the fellow who invented regular expressions and showed that they describe the same languages that finite automata describe. Okay. If L is a language, then L star, the Kleene star, or just star operator, is the set of strings formed by concatenating 0 or more strings from L in any order. Thus, L star would consist of the set containing the empty string. The empty string is always in the star of any language because that represents no choices of string from L. Then we'll union with L itself. And then we can take two strings from L, so we take L concatenated with L. We can take three strings, and so on. Any numbers from L. Anything you can form by concatenating any number of strings from L will be in the language L star. So here's an example. Language L just has two strings, 0 and 1, 0. The star of that language, well, we can take no choices, that would give us the empty string. We could take one or the other string, that will give us these two. We can take two choices from the language L. So if both choices are 0, we get 0, 0. If we take 0 for the first choice and 1, 0 for the second, we get this 0, 1, 0. Or we could take 1, 0 for the first choice and 0 for the second choice. That will give us 1, 0, 0. Or we can make both choices be 1, 0, and that gives us the string 1, 0, 1, 0. There are three parts to the basis in the regular expression definition. The first part is for single symbols. Okay. If A is a symbol, then A also denotes a regular expression. The language that this regular expression denotes is the language with one string. That string has length 1, and the one position of that string has A in it. Okay. By the way, in order to distinguish A as a symbol or string from A as a regular expression, we usually make the regular expression boldface, but a context should help you to distinguish strings, symbols, and regular expressions anyway. Okay. The second part of the basis is the symbol epsilon. Okay. This is a regular expression, and its language is the language that has one string. That string is the empty string. And the third part of the basis is the empty set symbol. This is a regular expression, and its language is the empty language. Okay. The inductive part of the definition also happens to have three parts. Okay. For the first part, we can connect any two regular expressions by a plus sign, and this plus sign represents set union. That is, the language of E1 plus E2 is the union of the languages that E1 and E2 denote. The second part involves the concatenation operator. We can write one regular expression next to another to denote the concatenation of their languages. That is, E1 followed by E2 denotes the concatenation of the languages that E1 and E2 denote. As we shall discuss in a minute, we sometimes need parentheses to group expressions properly. So in some circumstances, we need to put parentheses around E1 and or E2. So we might, for example, see something like that. Okay. The third part is the star operator. If we follow a regular expression E by a star, then the language we denote is the Kleene closure of the language that E denotes. Again, it is in some circumstances necessary to put parentheses around the E to make sure the operators inside the expression E group properly, like that. As with other algebras, we can and must use parentheses to force the intended order for operations. For regular expressions, the order is star, then concatenation, then plus. You can think of plus, the lowest precedence operator, as analogous to addition in arithmetic, concatenation is analogous to multiplication, and star as analogous to exponentiation, although in the case of star, there is no power to which its argument is raised. In a sense, star means raised to all powers. Okay. For example, the regular expression 0,1 represents the concatenation of the language consisting of one string, which is 0, and the language consisting of one string 1. The result is the language containing the one string 0,1. In general, any string of symbols as a regular expression represents the language that contains only that one string. The language of expression 0,1 plus 0, that's this, is the union of the language containing only the strings 0,1 and the language containing only the string 0. The language of 0 concatenated with 1 plus 0, that's this expression, is the two strings 0,1 and 0,0. Notice that we need parentheses to force the plus to group first. Without them, since concatenation takes precedence over plus, we get the interpretation of the second example, that is, this one, and obviously you'd get somewhat different languages. The language of 0 star is the star of the language containing only the string 0. This is all strings of zeros, including the empty string. Here's a little more complicated example. It denotes the language that we've been playing with when we talked about automata, that is, all strings of zeros and ones without two consecutive ones. To see why this works, in every such string, that is any string in the language, each one is either followed immediately by a 0, or it comes at the end of the string. Now, this part of the expression, 0 plus 1 0 star, denotes all strings in which every one is followed by a 0. Okay. These strings are surely in the language that we want, but we also want those strings that are followed by a final 1. Thus, we concatenate the language of 0 plus 1, 0 star with the union of two languages. One is epsilon, and concatenating with epsilon just gives us the same strings, that is those that don't have a final 1. And we can also concatenate with the language containing the string 1. That gives us any string in which every 1 is followed by a 0, and then it also has a final 1. Okay. We're going to show that regular expressions define exactly the regular languages. We already have 3 equivalent representations for the regular languages: DFAs, NFAs, and epsilon NFAs. We need to show that for every regular expression there is some automaton that defines the same language, and for this job we may as well pick the most powerful of the 3 varieties of automaton, the epsilon NFA. For the other direction, we need to show that every regular language is defined by some regular expression. Here we may as well start with the most restrictive variety of automaton, the DFA. We'll begin with the process of how you convert a regular expression to an epsilon NFA. The proof is an induction on the number of operators, the operators of course being the plus, concatenation, and the star that appear in the regular expression. And we're always going to construct an automaton that has a special form, which I'll show you on the next slide. The special form of epsilon NFA we construct is suggested by this sketch. There can be any number of states in the middle, but only one start state, as is true for any automaton, and only one final state, which is a restriction. More importantly, as we build larger automata from smaller ones, we never allow an arc into the middle or into the final state. The only outside arcs must come into the start state. That is, we might add arcs like that, but you can't add an arc that goes to a state that's inside. Okay, likewise, you can't add an arc that goes to the final state. Similarly, we never have an arc from any of these states except the final state to someplace on the outside. So you can't install some arc leaving like that. And notice that we put quotes around the term final in final state, because although this state is final if this is the entire automaton that we construct, if it's a piece of a larger automaton, then the final state will no longer be final in the larger automaton. Okay. The induction is on the number of operators in the regular expression. And here are the basis cases, the expressions with 0 operators. Okay. A regular expression without operators has to be one of the basis cases from the definition of regular expressions. If the expression is a symbol A, then the epsilon NFA we need consists of only a start and a final state with an arc labeled A from start to final. Obviously, this automaton accepts the language of the regular expression A, that being only the one string A. If the expression is epsilon, then it is sort of the same, except the arc is labeled epsilon. And if the expression is the empty set symbol, then we just have the start and the final state and no way to get from one to the other. Okay. Now we begin the induction. There are 3 cases depending on whether the outermost operator is union, concatenation, or star. Here's the construction for union. Suppose our expression is E1 plus E2. Both E1 and E2 have fewer operators than the entire expression, so the inductive hypothesis applies to these sub-expressions. We may thus assume that there is an epsilon NFA of the desired form for E1, and likewise for E2. We form the epsilon NFA for E1 plus E2 by introducing a new start state and a new final state. The old final states are no longer final. There are epsilon transitions from the new start state to each of the 2 old start states, and there are epsilon transitions from the old states to the new final state. If there's a path from the new start state to the new final state, it must consist of epsilon transitions at the beginning and end with a path that is either wholly within E1 are wholly within E2. So, for example, the path might look like this. Go here, and then wiggle around, could go through the same state many times, finally comes to the old final state of E1, and then out to the new final state. Notice the fact that there's no way to get into the green thing labeled for E1 and no way to get out of it except, as I've shown, guarantees that the path must, from here to here, must either go through E1 or through E2. There are no other options. Okay. Here's the construction for concatenation of E1 and E2. Again, we assume by the inductive hypothesis that there's an epsilon NFA of the right form for E1 and ditto for E2. We add an epsilon arc from the final state of the automaton for E1, and that state, of course, then is no longer final, to the start state of the automaton for E2. The start state of the bigger automaton is the start state of the automaton for E1, and the final state is the final state of the automaton for E2. The new automaton is the concatenation of the languages of E1 and E2. Any path from the start to final state must first pass through E1. That is, it will do something like this. Then it will take this epsilon arc, and then it will do something E2. There's no other option because you can't get into or out of the green areas except as shown. Finally, here's the construction for star. Suppose we have an automaton for some expression E and we want to construct the automaton for E star. We add new start and final states, and the old final state is no longer final. There's an epsilon arc from the new start state to the new final state, so epsilon is always in the language of this new automaton. There are three other epsilon arcs as shown. The first of these epsilon arcs brings us to the start state for the automaton for E. We must traverse the automaton for E following a path whose label is any string in the language of E. Now, when we reach the old final state of this automaton, we have a choice. Okay, if we follow the epsilon arc to the new final state, then we're done. We've found a path that has a label that is one string from the language of E. Or we have another option. We can go from the old final state back to the old start state, maybe take another path to there. Now we have a path that has a label that is the concatenation of two strings from the language of E. And we can go back again, take another path, make a label of that path would have now concatenation of three strings from E, and so on. We can do this as many times as we like, but then finally we go off to the final state, the new final state, and we are done with that. So this automaton really does have a language that's E star. You can go through the automaton for E 0 times by just going around it, or you can go through it once, twice, 3 times, as many times as you like. Now we're going to do the construction the other way. We'll start with a DFA and construct a regular expression defining the same language. The proof is inductive, and to make the induction work, we need to assume the states are named 1 through n. There's no harm in making this assumption since the names of the states do not influence the language an automaton accepts. The induction is on the maximum number of a state that is allowed to be in the middle of a path, an idea that is explained on the next slide. We're going to talk about k-paths, which are paths that can go from any state to any state, but in the middle, that is excluding the endpoints, only states numbered k or less can be found. The inductive construction is on k, and it states that there is a regular expression whose language is the set of labels of all k paths from state I to state j. We start with 0 paths as a basis, and by the time we get to n paths, there's no restriction on paths at all, so we have a regular expression describing the language of the automaton itself. Notice that an n path represents no restriction on paths at all, since there are no states whose names are higher than n. To get a regular expression for the language of the DFA, we take the union of the expressions for the n paths that describe how you get from the start state to each of the final states. For example, here's a little automaton. Okay. The 0 paths from state 2 to state 3 are the language of the regular expression 0. The reason is that we can only follow an arc from 2 to 3, and there's only one, the one that has label 0. That's the 0 describes the only path that gets us from state 2 to 3 without going through any other state. The 1 paths from 2 to 3 can go through state 1, but not through 2 or 3. Thus, we can still follow the arc from 2 to 3 labeled 0, but we also can follow the arc labeled 1 from state 2 to state 1, that's this, and from there the arc labeled 1 from state 1 to state 3. Notice that once we get to state 1, we cannot go back to 2 in a 1 path, and if we go to 3, we're finished. The path must end. The 2 paths from state 2 to state 3 are more varied. The only thing we cannot do is pass through state 3. Thus, from state 2, we can go to state 1 and back to 2 0 or more times. The labels along each such path is 1 0, so 1 0 star describes the labels we traverse by following this path any number of times, including 0 times. After oscillating as many times as we wish and winding up in state 2, we can then follow the 0 arc to 3. That's that part of the regular expression. These paths from state 2 to state 3 are described by the regular expression 1 0 star 0. That's this whole part. An alternative plan is to oscillate between states 2 and 1, winding up in 1. The labels of all these paths are described by 1. That is, you can go to state 1 for the first time, and then you can go 0 1 0 1 as many times as you like, including 0 times. Finally, though, you have to follow the path from 1 to 3, the arc from 1 to 3, in fact. And so 1 followed by 1 followed by 0 1 star followed by another 1 describes all those paths that start in 2, go from 1 to 2 several times, wind up in 1, and then go to 3. Okay. The regular expression for the labels of all 2 paths from state 2 to state 3 is the union of these 2 expressions that we have just described. The 3 paths from state 2 to state 3 also have a regular expression, but it is sufficiently complicated that we're going to save that example until we have seen the complete construction. Okay. Now here's the induction of how you go from a DFA to a regular expression. Okay, the basis is k equals 0. Notice that a 0 path can have no intermediate states at all. Thus, the set of 0 paths from a state I to state j can only consist of a single arc, plus, in the special case that I equals j, no arcs at all. We can construct a regular expression for this language, connect with pluses each of the labels, and in addition, if I equals j, then add an epsilon. So, for example, here's state I, here's state j, and suppose it has an arc labeled A, B, and C, then its regular expression is A plus B plus C. And if there's also an arc, let's say, from I to I, in addition, let's say that there is a loop with labels D and E on the state I, then the regular expression for the paths from I to I would be D plus E plus epsilon. We now need to introduce some notation. Let Rij super k be the regular expression for the set of labels of the k paths from state I to state j. we've really seen the basis case k equals 0. That is, Rij super 0 is the sum of the labels on the arc from state I to state j. If there's no such arc, then use the empty set symbol as the regular expression, but we add epsilon if I equals j. Okay, here's our example DFA again. Okay. R12 super 0 equals 0, since that is the label of the arc from the state 1 to state 2, and of course state 1 is not equal to state 2. Now consider R11 super 0. There's no arc from state 1 to itself, so we start out with the empty set. However, since the beginning and end states are the same, we add epsilon. Okay, and incidentally, notice that there's an algebraic law. That is, the empty set union anything is that other thing. So whenever you see an empty set symbol plus something else, you can just get rid of the empty set and the plus and just take what's left there. Now we shall do the inductive step, where we assume we've written all the regular expressions with super k minus 1, and we need to write the expressions for the k paths. A k path either never goes through state k at all, or it does so one or more times. That lets us write the expression for Rij super k in terms of expressions for k minus 1 paths. The first term covers the case that the k path doesn't even go through the state k once. That is, every k minus 1 path is a k path. All other k paths get to state k at least once. Thus we start out with Rik super k minus 1, which generates us the labels of all the paths that get us from state I to state k for the first time. Then comes Rkk super k minus 1 all starred. It generates the labels of all paths that go from state k to state k 0 or more times, with those paths not passing through any state k or higher. Finally, we concatenate with the language of the expression Rkj super k minus 1. That generates the labels of all paths from state k to state j that do not pass through state k or higher. Here's a picture of what a k-path looks like with the vertical axis representing the state number. We've shown I and j above k, although they could be at any height. That is, for example, I could be down here, so could j, could be down there, or they could be higher. Doesn't matter. Okay. So one possibility is that the k-path never goes through state k, or it could go through state k for the first time, but only through lower states. And from k to k, you could go, again, through lower states 0 or more times. And finally, you go from k to j through lower number of states, states numbered lower than k. And that represents all the paths that go from I to j through k and lower numbered states. Finally, as we have hinted, the regular expression with the same language as the given DFA is formed by taking the union over all final states j of Rij super n, where I is the start state. Okay. So here are our example DFA again. Now we have to install a start state and some final states. So let's assume that state 2 is the start state and 3 is the only final state. So the regular expression that we want is just R23 super 3. Okay, here's the expression for R23 super 3 in terms of the super 2 expressions. This expression is special because state 3 appears in two places as both k and j, and as a result we can simplify it as shown to R23 super 2 concatenated with R33 super 2 star. The reason is that if E is any regular expression, such as R33 super 2, then E star E is the concatenation of one or more e's. Okay. Now we have another expression, R23 super 2, that you can think of as itself concatenated with none of the e's. Remember, e is actually R33 super 2. So this is R23 super 2 concatenated with no e's. This is R323 super 2 concatenated with E star E, that's one or more e's. So together you have R23 super 2 concatenated with 0 or more e's. And that's what this expression is saying. Again, remember E is R33 super 2. Okay, so we figured out what R23 super 2 is. We did that earlier, so let's just use it here. Okay. And here's an expression for R33 super 2. I won't give the details, but remember that this expression has to represent paths from 3 to 3 that never go through 3, so it could only jump from 1 to 2 and back again until it returns to 3. And here is the simplified expression composed of R23 super 2 and R33 super 2, that last being starred. So what you have at the end is a regular expression whose language is the same as the regular expression of this automaton in the corner. Each of the three types of automata, the DFA, the NFA, and the epsilon NFA that we discussed, and regular expressions as well, define exactly the same set of languages, the regular languages. That is, if you remember, we started with the DFA, and we showed that any NFA could be converted to a DFA, that's the subset construction. We then showed that any epsilon NFA could be converted to an ordinary NFA, that was sort of the closure construction. And earlier in this lecture, we showed that any regular expression can be converted to an epsilon NFA. And now we just showed that every DFA can be converted to a regular expression. That says any language defined by any one of these four notations is defined by all the others. Okay, we're going to finish up with a little discussion of the algebraic laws for regular expressions. We have several times argued that two different regular expressions represent the same language, and therefore one can be substituted for the other. Now, these are examples of the sort of algebraic laws that we find in the algebra of regular expressions, of arithmetic, Boolean algebra, and other algebras. The laws for regular expressions are not too different from those for arithmetic, but we have to be very careful to observe the differences. First, plus and concatenation behave almost like plus and times for arithmetic. The plus operator, which remember is set union, is associative and commutative just like addition. Remember also that the commutative law says that x plus y equals y plus x. That is, the order of the arguments doesn't matter. Okay. The associative law says that you can group the operator in any order, or formally x plus y grouped plus z equals x plus the grouping of y plus z. That is, you can apply plus to the first two arguments first, or apply it to the last two arguments first. It doesn't matter. The result is the same. Concatenation, like multiplication, is associative. Moreover, concatenation distributes over union, just like multiplication distributes over addition. That is, x concatenated with y plus z equals xy plus xz. That is, x, y plus z equals xy plus xz. That's the distributive law. Okay, the big difference between regular expressions and arithmetic is that concatenation is not commutative, although multiplication obviously is. That is, the regular expressions AB and BA don't denote the same languages. That is, the first, AB, just denotes the language that contains the string AB, while the second, BA, denotes the language that contains only the string BA. Okay. Arithmetic also has certain constants that serve as identities for addition and multiplication. Obviously, 0 is the identity for addition, and that adding 0 to any number gives you that number back. Likewise, 1 is the identity for multiplication, because multiplying any number by 1 gives you that number. Finally, 0 is also the annihilator for multiplication, because multiplying any number by 0 gives you 0. Union and concatenation have analogous identities. As we shall see, the identity for union is the annihilator for concatenation, just like the identity for addition is the annihilator for multiplication. Now, the identity for union, as we actually have mentioned, is the empty set. Obviously, taking the union of the empty set with any set yields that set. The language containing only the empty string is the identity for concatenation. Concatenating any string S with the empty string yields S, so concatenating the language represented by the regular expression epsilon with any other language, say the language represented by regular expression R, will result in the same language, the one represented by R. Finally, the empty set is the annihilator for concatenation. That is, if we take any language, say the language represented by regular expression R, and concatenate it with the empty language, we get the empty language. Why? The result of the concatenation requires that we take strings from both languages and concatenate them in all possible ways. But you can't find any strings in the empty language to use in the concatenation of strings. Today we're going to give some hints about how regular expressions are used in practice. I'm going to mention some of the extensions that are found in various Unix commands. I'll also talk about some specifics of text processing algorithms and concentrate on the important task of lexical analysis, that part of a compiler that looks at the entire program being compiled and breaking it up into tokens, which are sequences of characters that logically belong together. Many systems use regular expressions of some sort to describe patterns. Often these are embedded in the proprietary code of a company, but there are also some quite visible ones, such as a number of Unix commands. I'm going to tell you one particular story involving proprietary software before moving on to generalities regarding text processing. Jungli was a startup founded by 3 of my PhD students and 2 others in 1994. At the time, the web was really new, and they had the idea of building systems to integrate web pages into more useful products. They were doing that for about 2 years when they got a contract from Yahoo to build a facility that would let Yahoo visitors search for books and get a table giving the price, delivery charge, and delivery delay at different booksellers. Immediately upon deployment of that product, Amazon bought Jungli in order to shut down the comparison shopping capability. Interestingly, Amazon did not understand that I bought from them not because they were the cheapest, but because I was confident that they would deliver what I asked for and deliver it on time. And apparently I was not alone in that thinking, but the world of online commerce was new, and Amazon could not be sure of the impact of automated comparison shopping. An interesting sidelight, Amazon actually got good value for Jungli because one of its founders, Anand Rajaraman, while at Amazon, was the inventor of Mechanical Turk. But the first paid work that Jungli got was a contract from the Washington Post to produce an online table of the employment opportunities offered by companies that were placing print classified ads at the Post. This job was not trivial. Jungli had to go to several hundred websites and extract the information about each job automatically. If you look at one site, you can probably figure out how to do it, which links to follow from the home page to get to the employment pages, and once there, how to navigate in the HTML source text to find the critical information about the job, such as the title and salary. But you need to do this for each site, and to make matters worse, the Jungli guys discovered that these sites were evolving. That is, not only the jobs changed, but the structure of the pages or even the whole website changed. The result was that approximately once a week, the reader for any given site would break and have to be redesigned. So the Jungli guys developed a regular expression language for describing how to navigate a website to extract the information they needed. The input symbols were the usual characters such as letters, so they could look for important words like salary. They also treated HTML tags like OL, that is this, as input symbols because they gave important hints about the page structure. For instance, a page might say, send salary requirements to, but that doesn't indicate the salary for a particular job. But when you get to a list of jobs, and that is indicated by the ordered list tag, that's the OL, and only after that does salary mean that the number following is a salary for a job. Another important kind of input element is a link, which indicates that it's necessary to move to another page. Once this regular expression language was implemented, it was easier to write regular expressions to find key information like title and salary than to write the code to process web pages directly. Thus, there was an increase in productivity as they added sites to their database. Moreover, when the site changed, it was relatively easy to modify the regular expressions to track the changes in the site. The architecture of the system developed at Jungli appears in many places. The input language is regular expressions plus actions, which are arbitrary code that is executed when the regular expression is recognized. In this case, the actions would be things like return this integer as a salary. The regular expression is compiled into a DFA or sometimes into an NFA that is simulated, effectively by executing the lazy version of the subset construction as needed. The simulation of the DFA or NFA goes on exactly as we have described it theoretically. Each input symbol causes a state change and nothing more. The magic happens when an accepting state is reached. Then the associated action is executed, and this action allows the regular expression processor to interact with the rest of the world in some useful way. We're now going to talk about the Unix extensions to regular expressions. There are many commands in Unix that have some sort of regular expression notation for input. An important example is the grep command, which stands for Global Regular Expression and Print. Most of the regular expression-based languages, even though they have extensions to the notation we've covered so far, define only regular language. There are also some commands that have additional extensions that allow non-regular languages to be recognized, but we're not going to go into these features. Incidentally, it is no coincidence that regular expressions figure heavily into the original Unix commands. Before he did Unix, Ken Thompson had worked on a system for processing regular expressions by converting them only as far as an NFA and simulating the NFA in code. We're now going to meet some of the Unix extensions to regular expressions. You can put brackets around any list of characters as a shorthand for the same characters connected by plus signs in the notation we have used until now. You can also describe a sequence of symbols that are consecutive in the ASCII order of characters by giving the first character a dash and then the last character. For example, A-Z, that's this, stands for any lowercase letter because the lowercase letters have consecutive codes in ASCII. You can represent any letter by putting dashes between lowercase a and z, and the same for uppercase. That's this. Okay, notice that the upper and lowercase letters are not consecutive in ASCII, so you cannot represent these 52 characters with a single range. Incidentally, as we see, characters like brackets and dash have special meanings in Unix regular expressions. So if you want to use one of these characters as itself, you need to precede it by a backslash. So for example, slash left bracket is a real left bracket. It's not the left bracket that you find in range expressions. And the character dot or period is shorthand for any character. Here are some more Unix changes to the regular expression notation we learned. Okay. The union operator is actually represented by a vertical bar instead of the plus. But the plus symbol is another operator used like star and meaning one or more. That is, in the Unix notation, E plus, that's that, is shorthand for E concatenated with E star. So for example, A-Z all plussed means one or more lowercase letters. The question mark operator is also used like star, but means 0 or 1 of. That is, E question mark is shorthand for E plus epsilon. So, for example, AB in brackets question mark means an optional A or B. We would write it in our original notation as A plus B plus epsilon. You may remember our DFA example for recognizing strings that end in ing. It involved a lot of explanation as we considered where to go from each of the states that represented some progress toward finding ing. However, there is an easy regular expression for the same language using the Unix dot. It's just dot star ing, like that. Okay. Or even if we didn't have the dot in our notation, we could simply replace it by all the legal input symbols connected by pluses. In fact, it's even much easier to design an NFA for this language than it is to design a DFA. Okay, here is an NFA. Essentially, it guesses when it has seen the I that begins the final ing. Thus, even on an input like the first I in skiing, it can remain in the start state. That is, it can go from the start state to itself on an I if it likes. And in fact, it always does like, because the NFA always does everything. Okay, it can remain in the start state on the first I and then only travel to the right, that is here, on the second I. There's no need to worry about what to do in a state like one that represents the discovery of I and N. Where do you go if the next input is not G? It doesn't matter, because you'll still be here, and another sequence of states will get you where you actually need to go. Now let's talk a little bit about lexical analysis, the breaking of an input program into its basic units called tokens. For example, every identifier in a program is a token. Likewise, the reserved words like if or while are tokens. Many single characters are tokens by themselves. In typical programming languages, semicolon is a token used for separating statements. Plus is a token indicating addition. Less than is a token by itself indicating the less than comparison operator. There are also multi-character operators such as the less than or equal sign, which together indicate the less than or equal comparison. There are tools like Lex, or its open source version Flex, that let you write a regular expression for each token. You can also provide a piece of code as an action to be executed when an instance of that regular expression is recognized. For example, the code for when an integer is found might simply return that integer. As an example, the expression for identifiers might be the one shown here. That's this. Using the Unix notation, this expression describes identifiers as any letter, that's this, followed by 0 or more, the star, letters or digits. In many languages, identifiers allow some more options. For example, underscore might be included as if it were another digit, so it would just appear in this list here as an underscore. In Lex, you write an action, which is an arbitrary code to be executed when the regular expression for a token is matched. In the simplest cases, all this code does is return an integer code representing the token found, but the action might be much more complicated. For example, if an identifier is found, the action might involve installing that identifier in a symbol table where all identifiers used by the program are stored. When building a lexical analyzer using regular expressions for the tokens, there is some resolution of ambiguities that need to be faced. Two examples are illustrated here. For one, reserved words like if also match the expression for identifiers, but if is not a legal identifier, so we have to make sure the lexical analyzer does the right thing on if. Okay. For another, when we see less than, we don't immediately know if it's a token by itself or part of a larger token, which would be less than or equal in this case. We need to make sure we don't prematurely declare victory and return the less than when less than or equal is intended by the programmer. Okay. A good architecture for building a lexical analysis code from regular expressions is to start by converting each regular expression to an epsilon NFA. Each of these epsilon NFAs has its own final state with which the action for that regular expression is associated. We combine all these epsilon NFAs by introducing a new start state. The start state has epsilon transitions to the start states for each of the NFAs. Okay. It looks something like this. Here's the new start state. Here are all the old start states and their automata, and we just put transitions on epsilon to each one of them. Okay. All the final states of the NFAs remain final, and they each have their associated actions. So, for example, these are all final states. An NFA can have several final states, in fact. After that combination, we convert to a DFA, or perhaps an NFA without epsilon transitions, which we will then simulate. Okay. We need to give the regular expressions an ordering, and this ordering determines the priority among actions. A typical ordering puts all the reserved words ahead of identifier, so that way, if the DFA discovers that the next token is if, it in principle does not know whether to execute the action for the reserved word if, or for identifiers, or both. But the fact that if takes priority over identifiers says that this token should be treated as a reserved word and not as an identifier. However, to make all this work right, the DFA actions need a special ability. The ability to take an input symbol it has read and put it back at the front of the input stream. That input will then be read again, typically the next time the lexical analyzer is told to look for the next token. Here's an example of why the ability to restore an input symbol just read back to the front of the input is important. Suppose the lexical analyzer is told to find the next token, and the first character it reads on the input is the less than symbol. It has to read the next input, and if that input is an equal sign, then we can be sure the token is less than or equal. Okay. But if the input is anything else, for example a blank, a letter, or a digit, then that character must be put back on the input and less than by itself declared to be the token. For another example, if the lexical analyzer has read the characters I and F in its quest for a token, it might have seen the reserved word if. But we won't know until it reads the next character. If that character is a letter or a digit, anything that can extend that identifier, then we do not have the reserved word if, we have a longer identifier. However, if the next character is not one that can extend an identifier, such as a blank or a left parentheses, then we really do have the reserved word if. In that case, the next character must be pushed back onto the front of the input. Today we're going to discuss algorithms for answering questions about regular languages, or really about the representations for the languages, such as finite automata. The questions we can resolve for finite automata include many we cannot resolve for programs in general. Examples include whether a given string is accepted by a given automaton, that's the membership problem, or whether a given automaton accepts any string at all, the emptiness problem. As part of our discussion, we're going to prove an important theorem called the pumping lemma that lets us show certain languages not to be regular. Automata theory talks about many different classes of languages, including context-free languages, recursive and recursively enumerable languages. We're going to meet each of these classes, but for the moment we know only one class, the regular languages. When we investigate a class of languages, there are two important issues. The first is decision properties. We shall see that there are many questions we might like to ask about a language, or rather its representation, such as whether it is empty, finite, or infinite. It is good to know there are algorithms to answer such questions, at least for the regular languages. Unfortunately, as we meet larger classes of languages, we find that in general, the larger the class of languages, the less likely there is to be an algorithm to answer a question about languages in that class. The second important issue is closure properties of the class. These involve applying operations such as union to languages in the class. We're going to defer the discussion of closure properties to another lecture, although I'll give you an example on the next slide. Closure properties are statements that when we apply certain operations to languages in the class, the result is also in the class. For example, we say that a class of languages is closed under union if given two languages in the class, the union of those languages is also in the class. So if I have two regular languages, I can represent them by regular expressions and connect those expressions by a plus with the appropriate parentheses to get a regular expression for their union. Similar constructions work for their concatenation and closure. Now let us address the main topic of this lecture, decision properties of regular languages. We've used both formal and informal ways of describing languages. The formal ways include finite automata and regular expressions, each of which defines a language by a precise mathematical definition. But we have also described languages informally by prose statements and set formers, such as this, or even more informal statements like this. However, you can't answer questions about a language unless you have a formal description. For instance, we will talk shortly about testing whether a regular language is infinite, given one of its formal representations. It looks like the last of the informal descriptions describes an infinite set, but does the word some mean any, or some one particular number like 10, for example, that I have in mind? Thus, we're only going to use formal descriptions of languages when we talk about algorithms for deciding things about those languages. Thus, a decision property for a class of languages is an algorithm that takes a formal representative of the language. The algorithm answers some particular question about the language, such as whether or not the language described by the representation is empty. Here are a few examples of why we might be interested in decision properties of regular languages. Both involve protocols represented by automata. If we ask whether the language of such an automaton is finite, we are in effect asking whether the protocol it represents is guaranteed to terminate. Or if we make the final states of the automaton be error states, then asking if its language is empty is tantamount to asking whether the protocol can fail. And remember, we couldn't answer either of these questions about programs in general, so we couldn't get the answers to these questions about protocols by looking at the code that implements them. Another use for decision properties of regular languages involves minimizing their representations. For instance, DFAs are a good representation for certain kinds of digital circuits, those that have memory. We usually want the smallest circuit to accomplish a task, and a good first step is to find a DFA that does what we want and has the smallest number of states of any DFA for the same language. It turns out that we can tell whether two DFAs are equivalent, that is, whether they define the same language. That lets us find a minimum state DFA equivalent to any given DFA. Again, we could do none of this for programs in general. We can't tell whether two programs do the same thing, and we can't find a smallest equivalent for a given program, even though we know in principle that one must exist. The membership question for regular languages is answered by an algorithm that takes a DFA and a string and tells whether or not the string is accepted by the DFA. The algorithm is the obvious one. Simulate the DFA on the input. Here's an example. It's something we've seen several times before. Each time I show it to you, I use a different style of presentation, but the idea is always the same. Here is the DFA for strings without consecutive ones, something which I know we've seen before. And the input string is 0, 1, 0, 1, 1. That obviously has consecutive ones, so it shouldn't be accepted. Well, let's see what happens when we simulate it. We read a 0, we stay in A. When we read a 1, we go to B. Read a 0, we go back to A. Read a 1, we go to B. Read another 1, we go to C. When we simulate this DFA on the input, we see that indeed the string gets the automaton to state C, and it is not accepted. Now you might wonder, what if the regular language were represented by an NFA or a regular expression, for example? Then you first need to convert the representation to a DFA and then simulate the DFA. It is possible to convert from any of the 4 representations we know about to any of the others using this circle of conversions. So doing might exponentiate the size of the description, but there is still an algorithm to do the conversion, and that's all we need to show there is, for example, an algorithm to tell, given a regular expression and a string, whether the string is in the language of the regular expression. Generally, proofs of closure or decision properties require either a DFA or a regular expression, by the way. The emptiness problem is, given a representation for a regular language, does its language contain any string at all? Okay, we're going to assume the language is represented by a DFA. Obviously, if by some other representation, then convert it to a DFA. Finding reachable states requires a breadth-first or depth-first search from the start state. I'm not going to assume you are familiar with these search techniques, but it is fairly easy to think of some way of searching a graph from a single node by following all arcs out of the node and marking those nodes you have visited. Then, follow arcs out of the nodes you visited and mark any other nodes you visit. Keep doing that until you cannot mark any other nodes. The marked nodes are those that are reached from the start state on some input. If at least one final state is marked, then the DFA accepts at least one input. If no final state is marked, then it is impossible for the DFA to accept anything and its language empty. Here is an example. Here's your start state. We might mark these guys, maybe mark these guys as we go. But if all your final states are out here and never get marked, then obviously, no matter how complex this automaton is, you can't reach a final state and you can't accept anything. Now, if you have an automaton with 3 states, it's pretty easy to tell what's reachable and what isn't. But if you have 1,000,000 states represented by some table, then it is hardly easy to tell. But fortunately, we have a straightforward search algorithm regardless how large the automaton or graph is. Now let us take up a more difficult problem, but one that we can still solve. We'd like to know whether or not the language defined by a DFA is finite or infinite. The first fact we're going to prove is that if the language of the DFA contains any string of length n or more, where n is the number of states of the DFA, then the DFA contains an infinite number of strings. Surely, if the DFA doesn't accept any string of length equal to or greater than n, then it accepts only a finite number of strings. However, it doesn't seem feasible to test membership for all input strings of length n or more, since there are an infinite number of them. Can we ever finish? If not, then we really don't have an algorithm for testing infiniteness. But as we shall see, it is possible to limit the length of strings we have to test to twice the number of states, so we have a really large and ugly but finite task, and we really do have an algorithm. So let's try to prove the point we need, that if the DFA accepts any string whose length is at least the number of states n, then it accepts an infinite number of strings. First, observe that a string of length n or more has at least n plus 1 states along its path. For example, a string of length 2 has 3 states on its path. Here is a typical picture we might have. String AB looks like that. Notice, no matter how many, well, the number of symbols in the string is the number of arcs, and there's always one more node than there are arcs in the path. That's why there will be n plus 1 states for a string of length n. Okay. Now, if there are only n different states, and there are n plus 1 states along the path, then 2 states along the path must be the same. That's called the pigeonhole principle, you might remember. Here's a picture of the path for string w, which we're breaking up as x, y, z. X is the prefix of w that gets the DFA to the first state that repeats on the path, which we call state q. It's right here, of course. Then y is the part of w that gets the DFA back to q for the first time. That is, the end of y is the second occurrence of q. Notice that therefore y cannot be the empty string, although x or z might be. Finally, z is the rest of w, and we know it gets the DFA to a final state because w is accepted by the DFA. Notice that the path labeled z may have states that also appear earlier, but it doesn't matter. The important thing is that we identified the first repeating state q. We claim that x, followed by I repetitions of y, followed by z, is also accepted by the DFA for any integer I. To see y, x takes us to state q, so we could, for example, go like this. Okay. And then we could skip y altogether, just follow z, and we get to a final state. That tells us that xz is in the language. Or we could follow x to state q. We could go around loops many, many times, and then finally go off following z, and again get to the final state. Or after I uses of input y for any I, however large, we follow input z and we accept. This proves that x, y to the I, z is accepted for any I. Remember that y cannot be empty, so all these accepted strings are different. Thus the DFA accepts an infinite number of strings, one for each I. Remember, we still do not have an algorithm because we can't test the infinite number of strings of length equal to or greater than n. However, we don't have to, because it is sufficient to test strings of length between n and 2n minus 1, and there are a finite number of such strings. When we prove this statement, we shall at least have an algorithm, although it is a rather time-consuming one. Now, we picked y to be the first cycle on the path, so the length of xy cannot be greater than n. That is, some state within the first n plus 1 states on the path surely repeats. We also know that if the length of y is at least 1, so y lies between 1 and n, then if w is the shortest accepted string of length at least n, then we claim that w cannot be as long as 2n. For suppose it were. Now xz, as we know, is another accepted string, and the length of xz is the length of w minus the length of y, and the length of y is at most n. So the length of xz is at least n. That means that xz is a string shorter than w, yet at least n in length, and it's also accepted. But we assume that there was no string accepted that was shorter than w and also of length at least n. As a result, given any really long string w that's accepted, we can keep taking out pieces of length between 1 and n, that's the y in each of these diagrams, and we just keep throwing them away, and eventually what's left of w will be between n and 2n minus 1. So the algorithm to decide whether a regular language is infinite is to construct a DFA for it and let the DFA have n states. Test all the strings of length between n and 2n minus 1 and say infinite if any of them are accepted. Otherwise, say finite. This is a terrible algorithm. If there are k input symbols and n states, then the number of strings we have to simulate is about k to the power 2n. That is a lot of work, and there is a much more efficient algorithm, one that takes time proportional to the number of transitions, that is k times n, if implemented right. I wanted to give you the argument about the lengths of strings because it's important when we take up the pumping lemma, a technique for showing languages not to be regular. However, let's sketch how the efficient algorithm would work. We already discussed searching forward from a node in a graph to find all the nodes you can reach. So we can eliminate the states that are not reachable from the start state. We then want to eliminate states that don't reach a final state. This algorithm is the same, except start by marking the final states and follow the arcs backwards. Now there's an elegant algorithm for finding cycles using depth-first search that takes time proportional to the number of edges or transitions. I'm going to trust that you will meet this algorithm in a course on algorithms and data structures if you haven't already done so. However, here is a simple way to test for a cycle in a graph. It takes time proportional to the number of nodes or states times the number of arcs or transitions. We're going to do the same thing for each node n. Starting at n, search forward until you either can reach no more nodes or you discover that you can reach n. That is, here's node n, we explore forward from it, and if we're lucky, at some point we reach a node that has an arc back to n. Okay. If you can reach n, then you have a cycle and we can conclude the language of the DFA is infinite. If not, try the same process from another node. If you exhaust all the nodes as starting points and you still haven't found a cycle, then there are none and you conclude the language is finite. This is a good time to introduce the pumping lemma for regular languages because we have essentially proved it during our analysis of the infiniteness problem. Here's the statement of the pumping lemma. For every regular language L, there is an integer n, which happens to be the number of states of some DFA for L, such that for every string W in L whose length is at least n, we can break W into W equals x, y, z, where y is the label of the first substring of W that goes from a state to the same state, as we saw in the previous slides, such that three things are true. First, the prefix xy of W is short. It is of length at most n. We assure that by making y be the label of the first cycle we encounter. Second, y is not the empty string. We assure this because y connects two different occurrences of the same state along the path of W. And lastly, x, y to the I, z is in L for all integers I. This statement is particularly complex because it is of the form for all there exists for all there exists. But here's how we use it. Think of a game played between you and an adversary. You pick the language L that you want to show is not regular, and suppose the adversary claims it is regular. Then the adversary has to provide the there exist parts while you play the for all parts. You've already picked L. Now the adversary has to pick n. He can pick a number as large as he likes, but once picked, it is finalized and the game proceeds. Now you get to pick the string W, subject only to the constraint that it is at least as long as n, the number the adversary picked. Next, the adversary has to break your W up into x, y, z, subject to the constraints that the length of x, y is at most n and the length of y is at least 1. You win the game by picking an I such that x, y to the I, z is not in L. However, in a proof, we don't know what moves the adversary will make. Thus, to win, we need to cover all possible moves. That is, we know the picked n, but we don't know n's actual value, so we must pick W in terms of n. Similarly, we know W equals x, y, z, but we don't know exactly where y is, except that it is not empty and it is among the first n positions of W. Thus, our argument that x, y to the I, z is not an L must work for any of these possible y's. Now, let's see an example. Let us pick this language as L. It is the set of strings consisting of some number of zeros followed by the same number of ones, and we have claimed before that it is an example of a non-regular language. Now we're going to prove it. Now the adversary picks n. We don't know what n is, but we know it has some fixed value. Now we get to choose W in terms of n. And we pick W equals 0 to the n, 1 to the n. That is n zeros followed by n ones. But then the adversary gets to break W into x, y, z, and we don't know exactly how it is broken. But we know enough about x, y, z to show that there is some string, in particular the case I equals 2, that the pumping lemma says has to be in the language L. But obviously it isn't because it has more zeros than ones. That is, we know that y, being part of the first n positions of W, can have only zeros. Okay, so two y's have more zeros than one y, and the number of ones, which are all contained within z, doesn't change. We next take up the question of testing whether two regular languages are the same. We suppose we're given representations for two languages, L and M. Whatever representation we're given, we convert to DFAs, and then we have to combine those DFAs into a single DFA that in a sense runs both DFAs in parallel. We call it the product DFA. Suppose these two DFAs have states Q and R. In the product DFA, the states are pairs, one state from Q, the other from R. The start state of the product DFA is the pair consisting of the start state from each DFA. For the transitions of the product DFA, suppose we have a state that is the pair QR, and suppose A is the input symbol for which we want to figure out the transition. We look at the transition function for the first DFA, say delta L, and we see where Q goes on input A. So here's Q, and on input A it goes to some state like that. Then we look at the transition function for the second DFA, say delta M, and we see where R goes on input A. So here's R, on input A it goes somewhere here. Okay. Then in the product DFA, the transition from the state QR on input A is to the state pair that is whose first component is delta L of QA and whose second component is delta M of RA. That is, we simulate the two transitions in parallel. Here's a little example. Here are the two given DFAs. We'll call this the orange DFA and that the purple DFA. And here's the product DFA. It's obviously here. For example, let's figure out the transition from AC on 0. So here's state AC, and I look in the orange automaton, A on a 0 goes to A itself, and in the purple automaton, C on a 0 goes to D. So the combination AC goes to AD, and you see that transition here. For another example, where does AD go on input 1? Well, the orange automaton says A goes to B on 1, and the purple automaton says D goes to C on 1. So on 1, AD goes to BC. That's this transition there. The algorithm for testing whether two DFAs are equivalent, that is, whether they accept the same language, begins by constructing the product DFA. Make the final states of the product DFA be all those pairs such that one is a final state and the other isn't. If string W reaches one of these final states in the product, then W is accepted by one of the original DFAs and not the other. Thus, the two languages are not the same. Only if the product DFA with this selection of final states has an empty language are the two DFAs equivalent. Here's an example. AC is made a final state because in the original automata, C is final and A is not. Likewise, BD is final because B is final, but D is not. We now see that the two original DFAs are not equivalent. It happens that the final state BD is not reachable from the start state, so there are no strings that the orange automaton accepts, but the purple one does not. However, AC is also a final state, and it is obviously reachable from the start state because it is the start state. That is, the empty string distinguishes between the two automata. The empty string is accepted by the orange automaton but not the purple one. A related question to ask about regular languages is whether one is contained in the other. The test is in a sense one half of the equivalence test we just saw. Start by building the product automaton. But we have to define the final states differently. How would you do that? That is, L is not contained in M if and only if some string W that is in L is not in M. Such a string would get the DFA for L to a final state, but would not get the DFA for M to a final state. So the question of containment is the same as the question of whether there is any string W that gets the product automaton to a state QR where Q is final and R is not. Here, B is the only final state of the first automaton, and D is the only non-final state of the second automaton, so only BD is final. As we observed before, BD is not reachable from the start state. It has arcs out, but no arcs in. Thus, the language of the product automaton is empty, and we conclude that the language of the orange automaton is a subset of the language of the purple automaton. Next, we're going to attack the problem of, given a DFA, find the equivalent DFA with the fewest states. There is an obvious dumb algorithm. Just consider all the DFAs with the same input alphabet, but a smaller number of states. There's a huge by finite number of such automata, so in principle we can solve this problem. This time we're not going to dwell on the bad algorithm. We'll talk you through the good algorithm immediately. The key idea is to build a table of pairs of states and figure out which pairs are distinguishable, in the sense that there is some input string that leads one of the pair to a final state and the other to a non-final state. Otherwise, states are indistinguishable and they can be merged into a single state. Here's the tennis automaton we saw way back at the beginning of the course. Now, let's look at the states 40, 30 here and add in. Input S takes them both to an accepting state, that is, server wins, and input O takes them both to deuce, right, here and here. Thus, no further inputs could ever distinguish 40, 30 from add in. Similarly, 30, 40 and add out are indistinguishable. Now we can deduce that 30 all, that's here, and deuce are also indistinguishable. On input S, they go to 40, 30 and add in, respectively. That is here, 30 all goes to 40, 30 on S, and deuce goes to add in on S. But we know that those two states are indistinguishable, so we'll never be able to distinguish 30 all from deuce by a sequence beginning with S. And further, on input O, well, 30 all goes to 30, 40, and deuce goes to add out, and we said we can't distinguish these two states. So there's no string whatsoever that can distinguish 30 all from deuce. Okay, we're now going to talk about how we find the distinguishable states. The basis is pairs that are distinguishable by the empty string. These are the pairs that have one final and one non-final state. For the inductive step, we can mark a pair QR if these states go at some input A to distinguishable states. That is, say here is Q, and on A goes to some state. I don't know what it is, but it's certainly delta of Q and A. And here's R, and it goes on A to, again, some other state. I don't know what it is, but it's delta of R and A. And then these two states on input W, we'll say that this one goes to a non-final state, and that goes to a final state on input W. Okay. Then I claim AW distinguishes Q from R, because obviously Q goes on AW to a non-final state and R goes on the same AW to a final state. After no more marks are possible, the unmarked pairs are equivalent and can be merged into one state. This point may be obvious, but we're going to need it in what follows. If there's no string W that distinguishes states P and Q, and there's no string that distinguishes Q from R, then how could some string W distinguish P from R? That would mean that there's some string W leads one of P and R to a final state and the other to a non-final state. Let's say R leads to a final state. So here's W leading P to a non-final state, and here's R, and on the same W gets to a final state. But then W also distinguishes Q from either P or R. So here's Q, and W leads it to some state. Okay, so let's say that W leads Q to a final state. then W distinguishes Q from P, because here P on W goes to a non-final state, Q on W goes to a final state. Okay. If Q goes to a non-final state, then it doesn't distinguish P from Q, but it does distinguish R from Q, because Q would then go to a non-final state while R goes to a final state. Incidentally, distinguishable is not transitive. It is quite possible that W distinguishes P from Q and also Q from R, but does not distinguish P from R. For example, W could lead both P and R to final states and Q to a non-final state. We're not going to use the table of indistinguishability to merge states that are indistinguishable. That gives us the minimum state DFA, although we must be careful to remove at some stage all the states that are not reachable from the start state. Okay. Suppose we have a set of indistinguishable states, say Q1 through Qk. We're going to replace them all by a single state that behaves as they all do. Call the representative Q. It can be one of the Qi's or some new name we create for this purpose. On any symbol A, all the indistinguishable states, the Qi's, go to states that are also indistinguishable from one another. For if not, then we could use a distinction between, say, the states delta Q1 of A and delta Q2 of A to distinguish between Q1 and Q2. But we already know that Q1 and Q2 are indistinguishable, so that can't happen. Thus, make the transition for state Q on input A be the representative for the indistinguishable states delta Q1A and so on. Let's work with the DFA that we constructed from the NFA that represented moves on a chessboard. We're going to make it easier to work with by renaming the states to be single letters. For example, A is the set containing only 1, and G is the set containing 1, 3, 5, 7, and 9. Here's a little trick for arranging pairs in a triangle so each pair appears exactly once. Notice that the rows are the states in order except for the last state G, which doesn't appear there. Then the columns are labeled by the states in backwards order except for the first state A. We begin the table of indistinguishabilities by marking each pair that consists of a final state and a non-final state. Here the final states are F and G, so pairs that have one of these and one of the other states, A through E, are marked. Let's look at the transitions on input R. Notice that the column for R has only states B and D. Since we have not yet distinguished B from D, there is no way input R can help distinguish other pairs of states at this point. However, we have more luck with input B. Some states go to final states on input B, namely C, D, E, and G, and the others, A, B, and F, go to non-final states. Thus, we can distinguish any of C, D, E, or G from any of A, B, or F. Some of these pairs are already distinguished, but we get 7 new pairs marked in red here. At the next step, we discovered 2 more distinguishable pairs, CD and CE. For example, C and D lead to F and G respectively on input B. So we know that whatever string W distinguishes F from G, B followed by W will distinguish C from D. Now we can mark the pair AB. These states transition on input R to B and D respectively, and we already know we can distinguish B from D. Unfortunately, D and E can never be marked because on both inputs they go to the same state. Okay, we are now done. We have distinguished every pair of states except for D and E. Moreover, we can never distinguish these states since they both go to D on input R and to G on input B. Thus, D and E form an indistinguishable group of states, and we can replace them by a representative. We choose the new state H as the representative, and all transitions from other states to D or E are replaced by transitions to H. The rows for D and E are replaced by a row for H. As D and E transition to D on input R, H transitions to itself on R. The transition on input B for H is to G, which is the same as it was for both D and E. As we mentioned, collapsing indistinguishable states to a single state goes a long way to finding the minimum state equivalent to a given DFA. But there is one other issue that indistinguishability doesn't address: the possible existence of unreachable states that are cluttering up the transition diagram or table. But it is easy to find such states, and we can either eliminate them from the original DFA, or we can eliminate them after merging indistinguishable states. It doesn't matter. Now we've done our best to combine states that we know how to combine. But it is in principle possible that there is some other smaller DFA that we can't get by combining states of our DFA. And fortunately, that can't happen, as we shall now see. Here's the proof that there is nothing smaller than the DFA we get by merging states and eliminating unreachable states. Suppose A is our DFA and B is a hypothetical equivalent with fewer states. Okay. Imagine we combine the states of A and B to form a larger DFA. It doesn't matter what the start state of the combined automaton is, but the final states are those of A and B. We need to use distinguishable in its contrapositive form. That is, if W distinguishes delta of QA from delta of PA, then surely AW distinguishes Q from P. So if Q and P are indistinguishable, then so are their successors on any input A. Here's an informal illustration of the proof technique. We start off with the fact that the start states of automata A and B are surely indistinguishable because the automata accept the same language. Now suppose the start states go to some states P and Q on input A. P and Q must be indistinguishable because if they were distinguishable, then we could distinguish the start states, and we know we cannot do that. Now suppose Q and P go on input B to two other states, R and S. Then R and S must be indistinguishable for the same reason. Formally, we shall prove that every state Q of A is indistinguishable from some state of B. The proof is an induction on the length of the shortest string that gets you to Q from A's start state. Notice that because we eliminated unreachable states, we know there is such a shortest string. For the basis, the state of A that is reachable from the start state by a string of length 0, which is of course the start state itself. We know that this state of A is indistinguishable from the start state of B because the languages are the same. For the induction, assume the inductive hypothesis for strings shorter than W, and suppose W is a shortest string getting A to state Q. Let W equal XA, that is, A is the last symbol of W and X is all the rest of W. We can apply the inductive hypothesis to X because it is shorter than W. We know X gets A to some state R that is indistinguishable from some state P of B. But then A takes state R on input A to state Q, and we know B takes state P on input A to some state, say, S. Then Q must be indistinguishable from S using the argument that we saw 2 slides ago. Okay. Now, we use the transitivity of indistinguishable to argue that no two states of A are indistinguishable from the same state of B, for if they were, they would be indistinguishable from each other. But A cannot have indistinguishable states because we merge them all constructing A. Thus, B has at least as many states of A, even though we started off assuming that there was no relationship between the automata A and B, except that they each accepted the same language. So that concludes the entire argument. It says that by throwing away unreachable states and then merging indistinguishable states, you get an automaton that is as small, that is, has as few states, as any other automaton for the same language. Today's topic is closure properties for the regular languages. We should recall that a closure property is a statement about a certain operation on languages that says when the arguments are languages in the class, then so is the result. You can see on the title slide the list of closure properties for the regular languages that we are going to discuss. Our first closure property will be union. That is, if L and M are regular languages, so is L union M. To prove this fact, we use the regular expression, say R and S, whose languages are L and M respectively. We know L and M have regular expressions because they are assumed to be regular languages. Then R plus S is also a regular expression, and we know its language is the union of L and M. The same idea works for concatenation and closure. Remember to draw parentheses around R and S if they are needed, like this. For example, if R is 0 plus 1 and S is 0, then you need to write the expression with parentheses around the 0 plus 1. Otherwise you'll get the wrong language. You don't need the parentheses around the 0. Regular languages are also closed under intersection. For intersection, we can't use regular expressions very easily, but the DFA is perfect for proving closure under intersection. So we take DFAs A and B for the two languages whose intersection we want, and we construct the product automaton. The final states in the product are those states that are final in both of the given automata. Thus the product accepts an input string if and only if both of the original automata do, and that's exactly what we want for intersecting the languages. Here's an example based on the same product automaton we used last time. The only final state in the product is BC. That's this, of course, because B and C are the only final states of their automata. B and C are there. Here's an example of how closure properties prove useful. Okay, remember we proved using the pumping lemma that L1, the set of strings of zeros followed by an equal number of ones, is not a regular language. L2, the set of all strings with an equal number of zeros and ones, isn't regular either. However, suppose L2 were in fact regular. Then since regular languages are closed under intersection, the intersection of L2 with the language of the regular expression 0 star 1 star would also be regular. Now the language of 0 star 1 star is all strings with any number of zeros followed by any number of ones. But what is the intersection of L2 with this language? It is L1, because L2 forces the number of zeros and ones to be equal, while the language of 0 star 1 star forces all the zeros to precede all the ones. Set difference is another operation under which regular languages are closed. The difference of languages L and M, written L minus M, is the set of strings in L that are not in M. For the proof of closure under difference, start with DFAs A and B for languages L and M respectively. Construct C, the product automaton for A and B. Make the final states of C be the pairs where the state from A is final and the state from B is not. Then C accepts an input string W if and only if A accepts W but B does not. That is, W is in the difference of their languages. Here's our favorite product automaton again. This time, BD is the only final state. Because B is the only final state of the orange automaton, and D is the only non-final state of the purple automaton. Notice that the final state BD is not reachable from the start state, so this version of the product automaton accepts the empty language. That's exactly as it should be, because the first automaton, the orange one, accepts a subset of what the second automaton, the purple one, accepts. That is, the first automaton accepts all strings that end in an odd number of ones, while the second accepts all strings that end in at least one one, plus the empty string. The complement of a language is defined with respect to some alphabet sigma. Sigma has to include all the symbols from the alphabet of the language L, but may include other symbols that don't appear in L. Then the complement of L is all strings in sigma star that are not in L. Since sigma star is surely a regular language, and we know that regular languages are closed under difference, we immediately know that the complement of any regular language is also regular. Now we shall look at the operation of reversal. Recall one of our earliest examples of a regular language was the language of binary strings that, when interpreted as integers in binary, were divisible by 23. We commented then that the language of such strings that, when reversed, were divisible by 23 was also a regular language. We also said that constructing a DFA for that language is tricky. So here's the tricky construction, which really isn't so tricky now that we have mechanisms like regular expressions to work with. First, the notation we use for reversal is superscript r. That is, L super r means the reversal of language L. This language consists of the reversals of all the strings in L. Here is a simple example. L has three strings, 0, 0, 1, and 1, 0. Then L reversed is the reversal of each of these strings. 0 reversed is still 0, while 0, 1 reversed is 1, 0, and 1, 0, 0 reversed is 0, 0, 1. So L reversed consists of 0, 1, 0, and 0, 0, 1. To begin the proof that regular languages are closed under reversal, we start with a regular expression for a regular language L. We'll show by an induction on the number of operators in the regular expression that there is a regular expression for the reverse of L. The basis is expressions that are either single symbols, the empty string, or the empty set. These are the only expressions with zero occurrences of operators. In all these cases, the expression doesn't change. That is, the reversal of a string of length 1 is the same string. The reversal of the empty string is still the empty string, and if you reverse all strings in the empty set, the set is still empty. The induction consists of the three operators for regular expressions. For union, it is easy. You just reverse the expressions for the two parts of the union. Concatenation is a little trickier. To reverse a string wx, where w comes from f, say, and x comes from g, you need to reverse w and reverse x, but then you need to flip the order of the reverse strings. That is, x reversed comes before w reversed. For example, if w is 0, 1, 1, it's w, and x is 0, 1, then the w reversed is 1, 1, 0, and x reversed is 1, 0, but the x has to come first, so the reverse of 0, 1, 1, 0, 1 is in fact 1, 0, 1, 1, 0. And for the star, we reverse the expression f that is starred. That's this guy here. So it now produces the reverses of all the strings that f produces. We then star the reversed expression to get concatenations of any number of the reverse strings in any order. Let's reverse this regular expression. Its language is all strings of zeros and ones such that the first bit never again appears. That is, the strings are either a 0 followed by any number of ones, that's this part, or a 1 followed by any number of zeros, that's that. The outermost operator of this expression is the plus, and the way we reverse a sum of two expressions is to reverse each expression separately. That is, the reverse of this whole expression is the reverse of the two parts separately. Now let's look at one of the expressions 0, 1 star. We have to, let's look at this. We have to reverse it. So the way we reverse a concatenation is to reverse each of the component expressions and put them in reverse order. So 0, 1 star, its reverse is 1 star reversed followed by 0 reversed. The other expression, 1, 0 star, which must be reversed, is handled the same way. It's 0 star, and we have to reverse that, followed by 1, which we must reverse. Okay. The basis rule tells us the reversal of 0 is 0, and the reversal of 1 is 1. That is, the reversal of this 0 is just that 0, and the reversal of 1, again, is just that 1. Also, the reversal of 1 star is the star of the reversal of 1. That's that. And similarly, the reversal of 0 star is the star of 0 reversed. Finally, the reversal of 1 again, that's this, is just 1. So we get 1 star 0. And the reversal of 0 again is just 0, and we get that. Now we have no reversals left, and we are done. The resulting expression is what you would expect. Its language is the binary strings where the last symbol does not appear elsewhere. Homomorphisms are transformations on symbols that replace each symbol by a string, which may be empty, another symbol, or a long string. When a given homomorphism is applied to all the strings of a regular language, the result is a regular language, as we shall see. Here's an example of a homomorphism, one that we shall use repeatedly in the discussion. This homomorphism H replaces every 0 by the string AB and replaces every 1 by the empty string. We apply any homomorphism to a string by applying the homomorphism to every symbol of the string in order and concatenating the results. For example, if we apply our homomorphism H to the string 0, 1, 0, 1, 0, each of the zeros gets replaced by AB, and the 1s effectively disappear because they are replaced by the empty string. That is, this 0 becomes that AB, this 0 becomes that AB, that 0 becomes that AB, and the 1s are replaced by epsilons that sort of go in the middle there, but you don't see them, of course, because they're empty. Thus, H of 0, 1, 0, 1, 0 is AB, AB, AB. We claim that if you take a regular language L and apply a homomorphism H, then the result is also a regular language. Note that the result of applying H to the language L is the set of strings you get by applying H to all strings in L. I'm not going to give you a formal proof, but the big idea is that you start with a regular expression for L, and you apply H to every symbol in that regular expression. The result will be a regular expression for L. Here's a simple example. H is the homomorphism we have been using as an example right along, and L is also a language whose regular expression E we saw before in connection with reversal. We compute an expression for H of L by replacing each occurrence of 0 in E by AB and each occurrence of 1 by the empty string. The resulting expression is this one. Okay. That is, this 0 got replaced by AB, this 1 got replaced by the empty string, that 1 got replaced by the empty string, and this 0 got replaced by AB. By the way, here is a good example where you have to introduce parentheses, since 0 star needs no parentheses, but AB star, that is, if I wrote just this, would be wrongly interpreted as an A followed by any number of B's. Rather, what we mean is any number of unit ABs. We can simplify this expression considerably. First, epsilon star is any number of empty strings, so we can replace AB epsilon star, that's this, by just AB epsilon. Remember that the empty string is the identity under concatenation. So we can remove the epsilons to give us just AB plus AB star. That is, these guys go away, leaving us just that. Okay. But the language of AB is just one occurrence of AB, while the language of AB star is any number of occurrences of AB, including exactly one occurrence. Thus, we can just drop the term AB here, and we are left with just AB star. That's the simplified expression. We can also define the inverse homomorphism of a language or a string. We denote inverse homomorphisms by a superscript -1. That's this notation here. The result of applying the inverse of a homomorphism H to a language L is the set of strings W such that when you apply H in the forward direction to W, you get a string in L. So here is the language L. These are all the strings in the language L. Okay. And H will be represented by downward motion. So any string that goes anywhere in L, when you apply H, these are all in H inverse of L. And any string that misses L when you apply H, that's not in H inverse of L. Here's an example. Let H be the homomorphism of our running example. L is the language with two strings, A, B, A, B, and B, A, B, A. Okay. That's that right there. Then H inverse of L is the language of strings that have two zeros and any number of ones interspersed. Here's a regular expression for this language. To see why, let's look at the two strings in L. Okay, A, B, and B, A, B, A. A string like 1, 1, 0, 1, 1, 0, 1 maps to A, B, A, B. The ones disappear as they go to empty string, and the first zero goes to that AB, the second zero goes to that AB. But nothing can go to BA, BA because a zero has to cover that AB in the middle. That's the only way you can map a zero. Now you've got to be able to map something to the B, but the only way you can do that is if you have a zero, but that would then map to AB. And similarly, this A, there's no way to map to that A without mapping to another B which doesn't exist. While for forward homomorphism, the regular expression representation was dandy, to show that the inverse homomorphism of a regular language is regular is best done with DFAs. Okay. Start with a DFA A for L and construct a DFA B for H inverse of L. B has almost everything the same as A, the same states, the same start state, the same final state. But the input alphabet for B is the appropriate input alphabet, that is, the set of symbols to which the homomorphism H applies. We then fix up the transition function for B to reflect both the new set of input symbols and the effect on those symbols of the homomorphism. Suppose B is in state Q and the input symbol is A. We apply H to A and we see where the automaton capital A would go on that sequence of inputs H of A. That is, delta B of Q and A is delta A, that is the transition function for the automaton A, starting in state Q, but reading sequence H of A. Note that H of A could be the empty string or some long string of symbols. So this is really the extended delta, but that's okay, we know what that is. Here's an example automaton, and we'll use the same homomorphism we've been playing with all along. Since H of 1 is the empty string, each state of the automaton for the inverse homomorphism will transition to itself on 1. That's what these transitions, for example, are suggesting. For transitions on 0, we need to figure out where the original automaton goes on AB. For example, starting in state A and following the path labeled AB, you wind up in state C. That explains why the transition from A on 0 goes to C. Similarly, starting at B and following the path labeled AB, it's that, you also get to C. And the same thing is true if you start from C. You get A and then B. We're not going to do the complete proof that regular languages are closed under inverse homomorphism. The heart of the proof is an induction on the length of W that says that W takes automaton B from the start state to state P, if and only if the string H of W takes automaton A from the start state to the same state P. That's this equation. Now B accepts W and A accepts H of W if and only if P is a final state. That is, W is in the language of B if and only if H of W is in the language of A, which is the same thing as saying B accepts the H inverse of the language of A. Good morning, good afternoon, good evening, or good whatever, or whenever you are actually listening to this. Today we're going to start a completely new tack where we learn about a second important class of languages other than the regular languages. This class is the context-free languages. They include all the regular languages and more. The most common description for these languages is a context-free grammar. We'll see the definition of these grammars and the way these grammars define languages, which is through derivations. We're also going to introduce a related notation called Backus-Naur form. The two most important applications of context-free grammars are probably in processing natural languages and computer languages. I'm going to focus on computer languages, where almost every language today has its syntax defined by a context-free grammar in the Backus-Naur notation. Grammars are also essential when designing a parser for the language, that part of the compiler that puts together the tokens of the language into the proper structure. For example, the parser discovers the order in which arithmetic operators are applied in an arithmetic expression and groups statements properly so their execution sequence is as intended by the programmer. A context-free grammar defines a language by a mechanism we will soon learn. Every regular language has a context-free grammar describing it, but there are also languages that can be described by a grammar, but that are not regular. On the other hand, the context-free grammar is still a relatively weak formalism. There are some languages that are simple to describe yet have no context-free grammar. Many of the languages in the context-free class that are outside the regular languages are languages that involve nested structures, such as the patterns of left and right parentheses that we call balanced. Okay. The central elements of a grammar are variables. These are symbols that generate particular sets of strings. One of these symbols, called the start symbol, will generate the entire language, but we can have many others to help us in that definition. The variables, or rather the sets of strings they generate, are defined recursively in terms of one another. The rules that define the languages of the variables are called productions. Each production has a variable on the left, say A, an arrow, and 0 or more symbols on the right. We'll draw, say, X and Y on the right that serve as the definition. A rule like this says that the concatenation of the languages represented by X and Y is a subset of the language represented by A. A variable may have several productions, and its language is thus defined to be the union of the languages described by the right sides of each of its productions. But remember, all of this may be recursive, so grammars are in fact far more powerful than the regular expressions we can build from unions and concatenations. For our first example, let's consider the language that we showed not to be a regular language, the set of strings with a form of n zeros followed by the same number of ones. Here is a grammar for this language. There are two productions or rules and only one variable s. The first production, this one, is a basis rule. It says that the string 0, 1 is in the language of S. The second, this, is an inductive rule. It says that if W is a string in the language of S, then 0W1 is also in the language. That rule lets us build longer and longer strings, at each step adding 1 0 to the beginning and 1 1 to the end, so we always have the same numbers of zeros and ones, with the zeros preceding the ones. Now let's make precise our informal introduction to what context-free grammars look like. Okay. The terminals of the grammar are analogous to the input symbols of an automaton. They form the alphabet for the language being defined. The variables, or non-terminals, are something like states of an automaton, but they are more powerful. One variable is called the start symbol. It is the language of this variable that the grammar defines. Any other variables are used as auxiliaries, but we can think of them as internal to the grammar, and their languages are not visible outside. The productions of the grammar, which are akin to the transition function of an automaton, have the form of a variable on the left, sometimes called the head, an arrow, and a string of 0 or more symbols which can be terminals or variables. These are sometimes called the body of the production. We have a convention about the letters used for certain symbols and strings. These conventions are more complex than the convention we use to distinguish input symbols, little a, little b, and so on, from strings, w, x, and so on. But they're really important as a reminder of the roles different components play, and it is something worth committing to memory early on. First, we use capital letters at the beginning of the alphabet as variables. However, S is also normally a variable. In fact, it will be the start symbol in many grammars. On the other hand, lowercase letters at the beginning of the alphabet are terminals. This convention agrees with our earlier convention that made these letters stand for input symbols, since there is a good analogy between the input symbols of an automaton and the terminals of a grammar. Capital letters near the end of the alphabet are used for symbols that could be either terminals or variables. We typically don't know which. Lowercase letters at the end of the alphabet stand for strings of terminals only. Again, this matches our earlier convention. And we use Greek letters at the beginning of the Greek alphabet for strings that may consist of both terminals and variables mixed. We'll design a grammar for the language of strings with the form 0 to the n, 1 to the n. The terminal alphabet is 0 and 1, of course. We need only one variable in this case. We'll call it S. S will be the start symbol. There's no other option since it is the only variable. And here are the productions which we explained earlier in our informal discussion. The first production generates only the string 0, 1, and the second production puts a 0 and 1 at the beginning and end, respectively, of a shorter string in the language. A derivation consists of a sequence of strings that typically have both terminals and variables, although they could have only one kind of symbol or even be empty. We start with the string consisting of just the start symbol. At each step, we find a variable to replace, say A. The productions for A, or the A productions, are those that have A on the left side, that is, the head of the production. We replace this A by the right side, or body, of the production. We can then repeat the process as many times as we like until we are left with only terminals, at which point no replacement is possible, and we have in fact generated a string that is in the language of the grammar. Here's what the replacement looks like. You take any string that has an occurrence of some variable A, and anything to the left and right, terminals and or variables, which is what the alpha and beta we have here suggest. You take an A production whose body is gamma, and you replace the A by gamma. Here is an example derivation. We always start with a string that has just the start symbol S. We choose the second production, so S is replaced by 0S1. Now we replace the S again using the second production, and again we replace the S, but this time we use the first production whose body is just 0 or 1. We are now left with a string that has only terminals, and this string cannot be subjected to further replacements. You should be aware that in more complicated grammars, variables can be replaced by strings that contain 2 or more variables, and when that happens we have lots of choices of what variable to replace at each step, and derivations can be much more complicated. The double arrow symbol represents single steps of a derivation, and just as we extended delta to many steps for automata, we need to have a notation that means any number of steps for a derivation. This is the arrow star symbol, and we define it inductively. Okay. The basis is that in 0 steps the string can't change, so any string goes to star itself. The inductive step lets us get from alpha to beta using any number of steps, including 0 steps. That's that. And then, with one more step, get from beta to gamma. Okay. The conclusion is then that alpha goes on some number of steps to gamma. Here's an example using the same grammar as before and the same derivation sequence we just discussed. We can conclude that S goes to itself in 0 steps. That is, we just start here, don't go anywhere. So we can conclude that S goes to star itself. Then inductively, S goes to 0S1, rather, 0S1 and 00011. Notice also that we don't have to start with the start symbol. It is also true, for example, that 0S1 goes to star 000111. Okay, that is, anything along the derivation sequence goes to goes to itself and any later position along the sequence. A sentential form for a grammar is any string derivable from the start symbol. That is S arrow star the sentential form. The sentential form can consist of any mix of terminals and non-terminals. The language of a grammar G is the set of terminal strings W such that the start symbol of G derives W. Here's an example grammar that is just a little different from the previous one. Here the basis rule is that S goes to epsilon rather than S goes to 0, 1. Note that epsilon is a perfectly legitimate body for production, and its effect is to make the variable on the left disappear. As a result, this grammar can derive the empty string along with all the other strings that have some number of zeros followed by the same number of ones. That is, the language of this grammar is the set of 0 to the n, 1 to the n, such that n is at least 0, while the previous grammar had at least 1 as the condition on n. The class of languages called context-free languages consists of all those languages that are defined by some context-free grammar. We now see that there are context-free languages that are not regular languages, such as the 0 to the n, 1 to the n example just given. However, there are languages that are not context-free, and the intuition is that context-free grammars can count 2 things, but not 3. Thus, an example of a language that is not context-free is 0 to the n, 1 to the n, 2 to the n, say, such that n is equal to or greater than 1. That is, you cannot match both the zeros against the ones and the ones against the 2 at the same time. I want to introduce a notation called BNF, or Backus-Naur form, which you may have seen in manuals for programming languages, and which is closely related to context-free grammars. BNF has a number of extensions to the grammar notation we use, and these extensions are useful in manuals but don't add any power. BNF-style notations were used for 2 of the original programming languages. John Backus used it in the original description of Fortran, and Peter Naur used it in the original description of Algol. In BNF, you usually use a word to describe a variable, for example, statement, if the intent is that this variable will generate all the strings that are valid statements of the programming language. Conventionally, these words are put in triangular brackets to tell us they are variables rather than terminals. Some terminals for a programming language are single characters, just like in our formal context-free grammars. For example, the plus sign or semicolon are commonly terminals in the grammar for a programming language. However, other terminals are really reserved words like if or while, and we see these shown either in bold or underlined depending on the style used to remind us that they are single symbols. In BNF, we often find : equals used in productions rather than the arrow. We also find a vertical bar used to list several production bodies that have the same head. That is a useful convention that we shall use in formal grammars as well. For example, our original grammar can be written with S once on the left side and the bodies of the two S productions listed with the bar connecting them. Another extension of BNF is similar to the Kleene star, but it means one or more rather than zero or more. We follow a symbol or a bracketed expression by ... to mean one or more occurrences of the symbol or the symbols within the brackets. So here is an example. We have one variable, digit, with the obvious 10 productions, all grouped together with the bars. Then we have one production for the variable unsigned integer with right side digit ... that is one or more digits. In general, we can replace alpha ... by two productions. Let A be a new variable that generates all sequences of one or more alphas. A has two productions with bodies A alpha and just alpha. You should be able to see how A can be replaced by any sequence of n alphas. Just use the first production n-1 times and the second production once. For example, here is a grammar for unsigned integers where the BNF d ... has been replaced by these two productions. These generate any sequence of one or more d's. Then d generates each of the 10 strings consisting of a single digit. That's, of course, that. We can make part of a production body be optional if we surround it by square brackets. For example, many programming languages have both an if-then and an if-then-else construct for statements. We can see this as an if-then statement with an optional else clause. In BNF, we put brackets around the else clause to make it optional. That's essentially this stuff there. We can replace an optional alpha by a new variable A. This variable has two productions, one with a body alpha and the other with the empty string for a body. Thus, the alpha can be either there or not when we expand the new variable A. Here we're using I for if, T for then, and E for else, and the semicolon is another terminal standing for itself. S is the start symbol standing for statement, and C is another variable representing conditions. We really need to add productions for conditions, but I haven't done so in this fragment of a real grammar. Notice that A is a variable standing for an optional else clause. It can be replaced by a semicolon, an else, and another statement if we want to have the else clause there, or by epsilon if we just want an if-then statement with no else clause. Curly braces are used in BNF for grouping several different elements. You need this, for example, if you want to have a repeating group of elements in a ... or one or more construct. For example, it is common in programming languages to allow a statement list to be one or more statements. The statements are separated by semicolons, so there is one fewer semicolon than statements. That is, a statement list consists of one statement, that's this, followed optionally by one or more groups consisting of a semicolon and a statement. There. Brackets form a group, and then finally the ... applying to the group says one or more of these groups. Finally, you have the braces, and those braces say that the whole thing is optional. To translate groups to our original notation, just create a new variable A for the group. A has one production whose body is the group. Here's an example of a production that uses all three BNF features, one or more, optional, and grouping. It says a list of statements L is a single statement S, optionally followed by one or more groups, each group consisting of a semicolon and a statement. The first thing we'll do is replace the group semicolon S by a new variable A. A has one production in which it is replaced by the thing it stands for. That's this guy right here. And next, we'll introduce a new variable B, which stands for the optional A dot dot dot. B has two productions. It is replaced either by the A dot dot dot, that would be this choice, or it is replaced by the empty string. Finally, we replace the A dot 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 and the B productions by the new variable C. The productions for C, which are here, allows C to be replaced by any sequence of one or more A's. When a sentential form has a number of variables, we can replace any one of them at any step. But what string of terminals a variable ultimately gets replaced by is independent of what else is in the sentential form. That's actually where the term context-free comes from. As a result, we have many different derivations of the same string of terminals. We can restore some order to the world by requiring that a particular variable be replaced at each step, although we cannot demand that any particular production be used for the replacement. One reasonable rule is to require that the leftmost variable be the one replaced at each step. This rule restricts us to what are called leftmost derivations. Similarly, we could require that the rightmost variable be replaced at each step, and that gives us the rightmost derivations. The double arrow with an LM subscript, that's this, represents one step of a leftmost derivation. That is, on the left of the arrow LM, we must have a string of the form WA alpha. Here you see one. That is, since W by our convention has terminals only, A must be the leftmost variable in the string. On the right is the same string with the body, say beta, that, of some A production replacing A. The symbol consisting of the double arrow with a subscript LM and a star, that's this, means becomes by a sequence of 0 or more leftmost derivation steps. Let's introduce another very simple grammar that generates a language that is not a regular language. This grammar has only one variable, but unlike the 0 to the n, 1 to the n grammar, there are productions with more than one variable in the body. This grammar generates strings of balanced parentheses, those strings that are legal in arithmetic expressions. The last production, here's its body, says that a pair of matching parentheses is balanced. Of course, the left parenthesis must come first. The middle production, this, says that if we put matching parentheses around a balanced string, it is still balanced. And the first production, this, says that the concatenation of two balanced strings is balanced. We need to prove that every string of balanced parentheses can be generated by this grammar. The proof is not too hard, but we're not going to do it here. Here's an example of a leftmost derivation. We start with just S, so that is the leftmost variable. Okay. We replace it by two S's at the first step. There we go. Next, the first of these S's must be replaced in a leftmost derivation. We choose the second production for the replacement. There we are. At the third step, the first of the S's must be replaced, and here we choose the last production in the replacement. That's giving us that. Okay. At the last step, we have only one S, and that naturally is the one we replace. We have chosen to replace it using the last of the three productions, so now we have a terminal string and are done. The arrow star leftmost notation can be used to express 0 or more leftmost derivation steps. So for example, S is related to the terminal string by this relationship. It is also related to itself and all the other steps in the derivation by the same relationship. And in fact, each step is related to itself and all the following steps. Here is an example of a derivation that is not leftmost. The problem is that at the second step, the second S, rather than the first, was replaced. Rightmost derivations are defined quite analogously to leftmost derivations. The arrow with an RM subscript, this, means that the rightmost variable was replaced at the step. Notice that the string on the left, which is this, has W, which must be a string of only terminals following the variable A that gets replaced. Thus A is surely the rightmost variable. And the arrow with an RM and a star means 0 or more steps of a rightmost derivation. Okay. Here's our balanced parenthesis grammar again. Now we have a rightmost derivation of the same string as before. Notice that at the second step, the second S got replaced rather than the first. S is related to the terminal string by the arrow star rightmost operator, and as for leftmost derivations, each step in the rightmost derivation is related by this operator to itself and all the steps that follow. Here's an example of a derivation that is neither leftmost nor rightmost. See how at the third step, the middle S is replaced. Also, notice that the second step is correct, but ambiguous in a concerning way. One of the S's here, one of these two, got replaced by two S's, but we don't know which. The parse tree is a graph that shows how a particular string was derived using some context-free grammar. These trees have a direct connection to leftmost and rightmost derivations, which we shall explain now. One important use of the tree representation of derivations is that it lets us express the important concept of ambiguity in grammars. That is, unambiguity, or the ability of a grammar to provide a unique tree structure for every string in its language, is vital. For example, if a programming language has ambiguity, then there are programs with two or more distinct meanings. The same is true of a grammar for a natural language. It would be insufficient to provide an intended meaning for all valid sentences of the language. Parse trees for a grammar G are trees whose nodes are each associated with a symbol of G. I'm going to draw you a little tree here. Leaves are always labeled by either a terminal or by epsilon. So we might draw, for example, an A on that one, a terminal B on that one, and perhaps epsilon on that. Interior nodes are labeled by a variable. Here are some examples. The important property that makes a tree a parse tree is that there is a production of the grammar with the label of the node in question as its head and the labels of its children read left to right as its body. Okay. For example, if you look at this parse tree, we would infer that A goes to BC is a production. Also, B goes to little a, little b is a production, and C goes to epsilon is a production. The root must be labeled by the start symbol. In our example tree here, I'm going to have to guess that if this is the root, then A is in fact the start symbol. Here's a parse tree using the grammar for balanced parentheses that we discussed earlier. Notice how each interior node is labeled by a variable. It's here, 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 and here. It must be S because that's the only variable we have. Okay, each leaf is labeled by a terminal, either a left or right parentheses. These are here, 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 and here. Okay, the production at the root is S goes to SS. You can sort of see that by looking at the root and its two children. Okay, here's another interior node. And the labels of its children are left paren, S, right paren, and you know that left paren, S, right paren is another production of the grammar. That's right here. And here we have an example of an interior node labeled S, and its children are labeled left paren, right paren. That corresponds to this production body right here. You have the same exact use of that production here. Okay. The yield of a parse tree is the string of labels of the leaves from the left. This order of leaves is the order you visit them in during a pre-order traversal. The path would look something like this. That's sort of a pre-order traversal path, goes around the tree counterclockwise. The order in which you visit the leaves is the order in which their labels appear in the yield. So here the yield is left paren, right paren, right paren, left paren, right paren. That's what we said here. In what follows, we're also going to talk about parse trees with a root A that might not be the start symbol. These trees follow all the other requirements of a parse tree. The leaves are labeled by terminals or epsilon, and an interior node with its children form a production of the grammar. We're going to show how to convert parse trees to leftmost or rightmost derivations and vice versa. As is often the case, our road is made easier by proving something more general than what we really need. In this case, we'll talk about generalized parse trees that can have any root label, say A, and we'll talk about leftmost and rightmost derivations from any variable A. We'll prove two statements. One is that if there's a parse tree with root A and the yield W, then there's a leftmost derivation of W from A. The second statement is the converse, that for every leftmost derivation of W from A, there is a generalized parse tree with root A and yield W. The matter of rightmost derivations is completely analogous. We'll start with point 1 by showing how to convert parse trees to leftmost derivations. The proof is an induction on the height of the tree. The basis is height 1. That is, a tree consisting of a root labeled by some variable A and one or more leaves. There must be a production with head A and body being the labels of the leaves from left to right. That's A1 through AN in this picture. Okay. Then A derives the yield of the tree by the one-step leftmost derivation in which this production is used. For the induction, we'll assume statement 1 for height less than h and prove it for h. That is, we assume for every parse tree with root A and height of up to h minus 1, there's a leftmost derivation of its yield from its root. Now let's look at a parse tree of height h. The case h equals 1 is the basis, so h is at least 2. Thus, the production used at the root has at least one variable on its right side. Say this tree has root A and the children of the root labeled x1 through xn. If xi is a variable, then it is the root of some subtree of height at most h minus 1 and some yield, say wi. If xi is a terminal or epsilon, then we imagine xi is the root of a trivial tree, not a parse tree, that consists only of the node labeled xi. Okay. The yield of this tree is just xi itself, but for consistency we shall refer to xi as the string of terminals wi. The yield of the entire tree is w, which is w1 through wn. We can put together a leftmost derivation of w from A as follows. Start by applying the production at the root. So the second step is x1, x2 up to xn. That's this. Okay. Now we need a leftmost derivation of W1 from X1. If X1 is a terminal, then it equals W1, so we're already there. And this step is then really 0 steps. On the other hand, if X1 is a variable, then we apply the inductive hypothesis. The subtree with root X1 and yield W1 has height at most h minus 1, so there is a leftmost derivation of W1 from X1. In that case, this X1 has been replaced in a leftmost derivation by W1, and this goes to star, represents all the steps that were necessary to replace X1 by W1. Either way, we can conclude that there's a leftmost derivation of W1 X2 through Xn. That's this. We can continue arguing this way for each xi in turn. Either it is a terminal, in which case nothing needs to be done, or it's a variable, in which case we can perform a leftmost derivation of wi from xi. The needed sequence of leftmost derivations is a leftmost derivation of the entire yield w, that's w1 through wn, from A. Now we need to prove the other direction, that leftmost derivations can be turned into parse trees. The proof is an induction on the number of steps of the derivation. The basis is a one-step derivation. In this derivation, a variable A is replaced by a string of terminals, perhaps the empty string, using some production for A. If the string is not empty, then there's a parse tree of height 1 with A at the root and the sequence of terminals in the body as the labels of the children. It's this, and there are the children. Okay, if the body is epsilon, then there's again a parse tree. It has A at the root and one leaf labeled epsilon, so it just sort of looks like this. Now let's do the inductive step. We assume that leftmost derivations of fewer than k steps can be turned into parse trees with the proper yield, and we'll consider a k-step derivation from string w from variable A. The first step of this derivation uses a production with head A and body x1 through xn for some n. Thus, the second sentential form in this derivation of w is x1 through xn. That's that. Remember the important properties of derivations, that production bodies replace production heads at the position where the head is. Thus, we can divide w into the concatenation of n strings, w1 through wn, in that order, where for all I, wi either is xi if xi is a terminal, or xi derives wi by a leftmost derivation of fewer than k steps. Since the whole derivation is leftmost, the derivation of w1 from x1 must happen first, then the derivation of w2 from x2, and so on. So we know that each xi either is wi or derives wi in fewer than k steps of a leftmost derivation. For the second case, where xi is a variable and the leftmost derivation takes one or more steps, the inductive hypothesis tells us that there is a parse tree with root xi and yield wi. Thus, we can build the parse tree shown, that is this. The root uses the first production of the derivation, that is A goes to x1 through xn, and the ith child either is wi if xi is a terminal, or it is the root of a parse tree from xi deriving wi. The yield of this tree is w1 through wn, which is w. Okay, that is, this string w is w1 through wn. All these strings are derived left to right in that order. This proves the inductive step, and we conclude that there is a leftmost derivation of w from A. Then there is a parse tree with root A and a yield w. It is also true that if there is a rightmost derivation of w from A, then there's a parse tree with root A and yield w, and conversely. But we're not going to prove that part. The proofs are essentially the same as what we have seen. And in fact, any derivation, even one that isn't leftmost or rightmost, of a terminal string w from variable A implies that there is a parse tree with root A and yield w. The first step of any derivation from A must use a production and replace A by some string of terminals and variables, say x1 through xn. If W is the terminal string ultimately derived, then we can still break W into W1 through Wn, where each Wi either is xi or is derived from xi by fewer steps than the whole derivation. The only tricky part is that now the steps of the derivations from xi and xj may be intermingled, and we have to sort the derivation steps according to which xi's descendant is being replaced at that step. We'll leave you to think through the details of this construction of parse trees. As we mentioned at the beginning, it is important in many applications, including parsing of programming languages in a compiler and parsing of natural language sentences, that we use a context-free grammar that assigns a unique parse tree to each string of the language. We say a grammar is ambiguous if there is at least one string in its language that has two different parse trees. Otherwise, it is unambiguous. The grammar for balanced parentheses that we have been using is ambiguous, alas. I'll show you two parse trees for this balanced string, that is left, right, left, right, left, right, on the next slide. Notice that each of these trees has the same yield, that is, 3 pairs of left and right parentheses. However, they are evidently not the same tree. The first replaces the first child of the root by SS, and the second does the same but with the second child. Notice that the two constructions we just gave, leftmost derivations from trees and trees from leftmost derivations, have the property that two different parse trees produce different leftmost derivations, and conversely. The same is true for the analogous transformations between rightmost derivations in trees. Thus, we could also define a grammar to be ambiguous if it has a string with two different leftmost derivations or two different rightmost derivations. Fortunately, just because one grammar for a language is ambiguous does not mean that we can't find another grammar for the same language that is unambiguous. But as an aside, which we'll get to later, the opposite is not true either. That is, there are some ambiguous grammars for which no unambiguous equivalent exists. Anyway, here is a grammar for balanced parentheses that is unambiguous. Variable b, which is the start symbol, generates all balanced strings. But r, another variable, generates all strings that are balanced except for having one more right parenthesis than left. By balance in this context, I mean that no prefix of the string has more right parentheses than left. And examples would include, well, a single right paren, left, right, right, that would be generated by r, and also something like this. Left, left, right, 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 right. Here's the unambiguous grammar for balanced parentheses again. Suppose we're given a string of parentheses which we'll call the input, and we want to find its leftmost derivation or derivations. We claim that for every input symbol, and for either variable b or r, there is only one choice of production that could possibly lead to a leftmost derivation of the input. That is, no string of parentheses has two distinct leftmost derivations, and therefore the grammar is unambiguous. Imagine we are constructing the left sentential form as we scan the input. As we go, the terminals to the left of the leftmost variable must match the input, or we'll never derive that input string of terminals. So we can check off input symbols as we match them. Notice that the only place b can ever appear in a left sentential form is at the right end. That is because the only production with b in the body has that b at the right end, and it also has head b. That is, this b can only go to a string that has a b in it, and the only way a b can appear is if it was either the start symbol or it was the result of replacing this b at the end by the paren rb in that production. Thus, an easy induction on the number of times this production is applied shows that the b is still at the right end. Now suppose b is the leftmost variable of a left sentential form. If there's a left parenthesis as the next unmatched input, then we have to expand the b using this production, the paren rb. Because if we use epsilon, then the left sentential form has no more variables, and we can never generate the unmatched left paren. The only time we can use epsilon to replace b, that's this production, is when we have matched the entire input and we have found the unique leftmost derivation. If r is the leftmost variable, then the next input symbol forces us to use one of the two r productions. That is, if the next input symbol is right paren, you must use r goes to right paren. That's here. And if the next input is a left paren, you must use r goes to left paren followed by two rights. There's never an option, or the left sentential form we are deriving can never match the input string. Here's an example. Suppose we want to find the unique leftmost derivation for this string of parentheses. That's this string right here. We set the string up as an input with a pointer to the next symbol that must be matched in the leftmost derivation. Okay. We start off with the left sentential form, that is the start symbol b alone. Okay. The next input to match is a left paren, and we must therefore expand this b to left paren rb, that is, using that production. Here we've made the expansion. The first left paren is removed from the input, since it has been matched. That is, it appears to the left of the leftmost variable in the current left sentential form. In essence, this left paren is what used to be on the input there. Our next input symbol is another left paren, and we have to expand in r, the leftmost variable. That's this guy. Our only choice is to use the body r goes to left paren r. Okay. That's what happened here. The r was replaced by paren r, and the second left paren has been matched. It appears to the left of the leftmost variable, as here. Now the next input is a right paren, and we must expand the leftmost r. The only choice is the first production that will enable us to match. Now the third input has been matched. We have r to expand, and the right paren as the next input. So we again use r goes to the right paren. That is, we expand that r, replacing it by a right paren. That's what's going to happen on the next slide. Here the left paren is the next input, and we must expand b. The choice is the first production for b. That. Now r is the leftmost variable. We're up here now. And the next input is the right paren, so we replace the r by right paren using the first production for r. That's that, and let's see. Now there's no more input to match, and b must be expanded. That's b, the leftmost variable. The only choice is to use the second b production, which is that, and we effectively make the b disappear. And we're done. We have a leftmost derivation of the original input, which of course appears as the final step of the derivation. Had we deviated from the choices we made at any step, the result of the leftmost derivation would not have been this input string of terminals. There is a name for grammars such as our example, where it is always possible to choose a unique production to use in a leftmost derivation of any string in the language, in the simple manner that we illustrated. At each step, we looked only at the first unmatched symbol of the input, and we were able to make the unique choice correctly. Such a grammar is called LL of 1, standing for leftmost derivation, that's the first L, left to right scan, that's the second L, and one symbol of look ahead. It is normal for a programming language to have an LL of 1 grammar. Probably, as this theory became widely understood by designers of programming languages, they saw the advantages of keeping the language parsable in this simple way and made choices to preserve this ability. And the same argument we gave for our example grammar tells us all LL of 1 grammars are unambiguous. And remember, unambiguity is vital for a programming language, as we must assign a unique meaning to any legal program of the language. For balanced parens, we found the first, simplest grammar that we wrote down was ambiguous, but we were able to redesign the grammar to make it unambiguous. One might hope for an algorithm that would do that for any ambiguous grammar. But alas, there cannot be such an algorithm. There are certain context-free languages for which every grammar is ambiguous. Such languages are called inherently ambiguous. We're not going to get into the proofs of what I just said, but I'll give you an example of an inherently ambiguous language. The set of strings with the form some number of zeros followed by some number of ones followed by some number of twos, such that either the numbers of zeros and ones are the same, that would be this condition, I equals j, or the numbers of ones and twos are the same, that would be j equals k, or both, of course. The problem is that any grammar for this language must generate at least some of the strings with equal numbers of all 3 symbols in 2 different ways. In the first derivation, or parse tree, the grammar forces the numbers of zeros and ones to be the same, using the same trick we used to generate a set of strings with the form 0 to the n, 1 to the n. The grammar can generate any number of 2's to go along, but it may happen to generate the same number of 2's as zeros and ones. The second derivation of parse tree makes sure the numbers of ones and twos are the same, but it may accidentally generate the same number of zeros as well. Here's an example grammar. It is ambiguous, but that doesn't prove the language is inherently ambiguous. As I said, we're not going to give that proof. It's very complicated. However, you might wish to play around with grammars for the same language and see how you are forced to do something like this grammar in order to generate exactly the language we want. It should be easy and familiar to observe that A will generate all strings with 1 or more zeros followed by exactly the same number of ones. We've seen essentially this pair of productions here as a complete grammar before. And it should also be obvious that B generates any string of 1 or more 2's and nothing else. Likewise, C generates the strings of 1 or more zeros, and D generates 1 or more 1's followed by exactly the same number of 2's. Now, all derivations start with S, and the first production replaces it by either AB or CD. If we go with AB, then we get strings where the zeros and ones match, while if we go with CD, then the ones and twos match. As a result, strings like 0, 1, 2 with the same number of each symbol will have 2 leftmost derivations, one starting with S goes to AB, that's this, and the other starting with S goes to CD. Here are the 2 derivations for 0, 1, 2. Context-free grammars can be badly designed. For example, they can have variables that play no role in the derivation of any terminal string and therefore shouldn't be there. That is analogous to states of a finite automaton that aren't reachable from the start state. There are also certain productions that, while they are necessary, cause derivations to take many steps that can obviously be combined. These include productions whose bodies are the empty string, or unit productions where the body is a single variable. We can get rid of these, and the way to do so is similar to the way we removed epsilon transitions from an NFA. Finally, we're going to introduce Chomsky normal form, where all the production bodies are either a single terminal or 2 variables. Incidentally, the Chomsky referred to is Noam Chomsky. Back in 1956, he wrote the paper that introduced the idea of context-free grammars. Then he was a linguist trying to provide some mathematics for the structure of the language. Since then, he has unfortunately become somewhat notorious for his political views. Oh well, back to context-free grammars. Here is an example of a really bad grammar. A is okay. It derives all strings of 1 or more A's using its 2 productions. However, B has only 1 production, and that production has B in its body. Thus, once a sentential form has a b in it, you can never get rid of that b, and as a result, b derives no terminal strings. To make matters worse, S has only one production, so that must be the first used in any derivation, but that production introduces a b into the sentential form, so it is impossible to derive any terminal string from S, and therefore the language of this grammar is empty. Almost all the algorithms we need to simplify grammars are based on the same principle, which I call discovery algorithms. These discover facts by an induction process. The basis is always certain facts that are obvious. Then, based on what is already known, we discover more facts in repeated rounds. Finally, at some round, they can discover no more facts. There's no point in going on, since without new facts at the current round, we cannot discover more on the next round. We generally have to prove only that any true fact of the type we are trying to discover will be found this way. Here's the image of discovery algorithms we should keep in mind. Okay, we start with some facts that you get from the basis. We expand the set of facts you know by using the basis facts. This is the first round. For the second round, we expand the set of known facts further by using both the basis facts and the facts you discovered at round 1. You keep going until at some round you have no more facts that can be discovered. So one of the first things we need to do when dealing with grammars is to detect and get rid of variables that can't derive any terminal string. We shall give a discovery algorithm to find inductively all variables that do derive at least one terminal string. Any variable not discovered by this algorithm derives no terminal strings and can be eliminated. For the basis, if a variable A has a production whose body has no variables, then A certainly derives a terminal string in one step. Note that this body could be the empty string. Technically, the empty string is a string of terminals. Now, suppose A has a production with a body alpha, and alpha consists only of terminals and variables that we have previously discovered to derive some terminal string. Then we can also conclude that A derives a terminal string. Since the number of variables is finite, eventually this algorithm terminates where it can find no more variables that derive terminal strings. It is easy to prove that whenever the algorithm says a variable derives a terminal string, that it really does derive a terminal string. We're not going to prove that. The harder part is showing that the algorithm doesn't miss anything. That is, if variable A derives some terminal string, then the algorithm will eventually discover A. We'll do that on the next slide. The proof is an induction on the minimum height of a parse tree with root A and a yield of terminals. The basis is a tree of height 1, which consists of root A and one or more leaves labeled by terminals, or perhaps epsilon. Then the basis step of the algorithm discovers A, so we're okay there. For the induction, assume the statement is true for height up to h-1. That is, all variables that are the roots of parse trees with height up to h-1 and a yield of terminals are discovered by the algorithm. The parse tree for A of height h, which must be, of course, equal to or greater than 2, has children of the root labeled x1 through xn. That's this. Any one of these xi's that is a variable is the root of a subtree of height at most h-1, and therefore it is discovered. Moreover, one of these variables is discovered last. At the round where the last of the variable ai's is discovered, we must surely do another round since the set of discovered variables just changed. On the next round, A will be discovered because it has a production, that is, A goes to x1 through xn, whose body consists only of terminals and discovered variables. The algorithm to eliminate variables that derive no terminal string is now simple. Use the algorithm we just described to find the variables that do derive terminal strings. Call the other variables useless. Then remove from the grammar all productions in which at least one useless variable appears. It doesn't matter whether the variable appears in the head, the body, or both. Here's an example grammar to which we first apply the algorithm to discover variables that derive terminal strings. For the basis step, we immediately discover A and C because they have productions with bodies that are terminals only. Here they are. For the first round of the induction, S is discovered because there is an S production with body C, and C was previously discovered. However, at the next round we can discover no more variables, The only variable we have not yet found to derive a terminal string is b, and b has only one production body, which is little b followed by big B. But this body does not consist only of terminals and discovered variables, so we can never add b to the set of discovered variables. Thus b is useless and we eliminate all traces of it. That includes not only the production b goes to bb, but the production s goes to ab, leaving us, of course, fortunately, s goes to c, still remains, as well as the two A productions and the C production. In addition to eliminating variables that don't derive anything, we need to eliminate variables that derive some terminal strings but cannot be derived from the start symbol. The algorithm to find symbols, both terminals and variables, that appear in derivations from the start symbol is another example of a discovery algorithm. For the basis, obviously the start symbol can be derived in 0 steps from itself. For the induction, suppose that we have discovered that we can reach variable A. Then for every production with body alpha and head A, we can also reach all the symbols appearing in alpha, the terminals and variables that appear there. It is an easy pair of inductions to show, first, that if we discover a symbol by this algorithm, then it appears in a sentential form derivable from the start symbol. Second, that if we do not discover a symbol, then there is no derivation from the start symbol in which it appears. We're not going to give the proofs here. But remember, our goal is to get rid of symbols that do not appear in the derivations from S. So after discovering all the symbols that do appear in a derivation, delete from the grammar all the productions that contain a symbol in either the head or body or both that does not appear in a derivation. Say a symbol is useful if it appears in a derivation of a terminal string from the start symbol, and call it useless otherwise. There are two reasons a symbol could be useless. Either it derives no terminal string, or it appears in no derivation from the start symbol, or both. We have algorithms to eliminate symbols that are useless for each of these reasons, but we must apply them in the right order. First, eliminate the symbols that fail to derive a terminal string. And then eliminate symbols that do not appear in any derivation from the start symbol. In this example grammar, if, as we should, we first eliminate variables that do not derive a terminal string, we eliminate only b. However, eliminating productions with b gets rid of the only s production. We then use the algorithm to find symbols unreachable from the start symbol, and we find everything is unreachable. That is, all the productions are deleted. However, if we do things in the wrong order and first eliminate unreachable symbols, we find everything is reachable from S, so nothing is eliminated here. Then, when we look for the symbols that do not derive terminal strings, we eliminate only B. That leaves the productions A goes to C and C goes to little c, these guys, which should not be there because A, C, and little c are useless. Here's why first eliminating variables that don't derive terminal strings is the right thing to do. After eliminating those variables, every remaining symbol is either a terminal or it is a variable that derives a terminal string. After removing symbols not reachable from the start symbol, all remaining symbols appear in some derivation from the start symbol of some sentential form. But the variables that appear in sentential form still derive a terminal string because such a derivation can only involve symbols that are also reachable from the start symbol. Epsilon productions are those that have body epsilon. They can be eliminated from a context-free grammar, and the only thing that we lose is that we can no longer derive the empty string. If the empty string was not in the language to begin with, then we can eliminate epsilon productions and still have a grammar that derives the same language. However, if epsilon was in the language, then we lose it. The two cases can be summarized by the theorem on the slide. If L has a grammar, then L minus the set containing the empty string has a grammar with no epsilon productions. Notice that if epsilon was not an L, then L minus epsilon is just L anyway. To eliminate epsilon productions, we need yet another discovery algorithm, this one to find the variables that derive the empty string by one or more steps. We call them nullable symbols. The basis of the discovery algorithm is that if A has a production with an empty body, then it is surely nullable. And the induction is that if A has a production with body alpha, and alpha consists only of variables that are nullable, then A is also nullable. Here's an example grammar for which we will discover the nullable symbols. For the basis, we know A is nullable because of the production with epsilon body. It's that. In the first round of the induction, we find B is nullable because of the production B goes to A. That is, all symbols in the body, namely the A, are already known to be nullable. In the second round of the basis, we discover S is nullable because of its body AB, both symbols of which are already known to be nullable. This algorithm finds all and only the nullable symbols. We're not going to give the proof, which consists of two simple inductions. To eliminate epsilon productions from our grammar, we need to turn each production, say A goes to x1 through xn, into a possibly large number of productions. The idea is to guess which of the nullable symbols in the body of a production will derive epsilon in a particular derivation. Since we make all possible guesses by creating many different productions, we always manage to guess right. More precisely, for each set of nullable xi's, we delete these from the body of the production and make a new A production. Note that if two of the xi's are the same nullable symbol, then we have to consider the possibility that one position derives epsilon and the other does not. That is, we form one production for each set of positions that hold nullable symbols, not just for each set of nullable symbols. However, in the special case that all the xi's are nullable symbols, we do not consider the set of all positions, and we do not create a new production with the epsilon body. Here's an example grammar. Each of A, B, and C are nullable because they have epsilon productions. Okay. Thus, S is also nullable because of its production S goes to A, B, C. Let's construct the new grammar. For the S production, there are 7 subsets of nullable positions that we must use. The set of all 3 positions is also nullable, of course, but eliminating all of A, B, and C would leave an empty body which we don't allow. However, if we use the empty set of positions, we get body A, B, C. If we use the set of only the third position, we get A, B, and so on. Now let's look at the A productions. We do not use A goes to epsilon, of course, but for production A goes to little a, big A, that's that. Only the second position is nullable, so we get 2 productions, one with the variable A present and the other not. That's what we have here. The situation for B is the same. However, for C we cannot use the C goes to epsilon production. So in the new grammar, C has no production. That means that in the new grammar, although not in the old grammar, C is useless and must be eliminated. That forces us to eliminate all productions with C in the body, and we are done. The proof that the new grammar we construct generates the same strings except for epsilon as the old grammar generates is a little tricky, so we're going to give the details in one direction. As is often the case, we need to prove something more general than we really need. In this case, we need 2 statements about every variable A. First, if W is a non-empty string that is derived from A in the old grammar, then A also derives W in the newly constructed grammar. Second, if A derives W in the new grammar, then first of all W is not empty, and second, A derives W in the old grammar. Once we have that for all A, we can apply the statement to the start symbol and thus prove that the language of the new grammar is the language of the old grammar with epsilon removed if it was in that language. We're going to prove the first direction, and it is an induction on the number of steps by which A derives W in the old grammar. For the basis, if there's a one-step derivation of W from A, then A goes to W must be a production. We assume in part 1 that W is not empty, so A goes to W is a production of the new grammar. We make the desired conclusion that A derives W in the new grammar. Now let's do the induction. Assume the inductive hypothesis for derivations of fewer than k steps, and suppose W is derived from A in k steps of the old grammar. The first step of this derivation must be A replaced by the body of some A production. Assume this body consists of symbols x1 through xn. Then we can break W into W1 through Wn, where each Wi is the portion of W that either is xi, if xi is a terminal, or is derived by xi, if xi is a variable. All these derivations from variables are in fewer than k steps. If xi is a variable and the piece wi is not empty, then the inductive hypothesis tells us that xi derives wi in the new grammar. When we constructed the new grammar, we replaced the A production A goes to x1 through xn by a family of productions, and one of these eliminates from the body exactly those xi's such that wi is epsilon. We know that is the case because if wi is epsilon, then surely xi is nullable. We also know that not all wi's are epsilon because w is not epsilon. That is, at least one xi is either a terminal or it is a variable that we do not need to remove from the body. Thus, in the new grammar, the first step can replace A by a body consisting of all those xi's such that wi is not epsilon. We can continue the derivation in the new grammar by a derivation from each xi that remains of the non-empty string wi. We know this derivation in the new grammar exists by the inductive hypothesis. We also need to show part 2. If W is derived from A in the new grammar, then it is non-empty and also derived in the old. We're going to skip this part. So we're now ready for a new simplification of grammars, the elimination of unit productions. A unit production is one whose body is a single variable. We can eliminate all such productions. The idea is to discover, using a discovery-type algorithm, all pairs of variables A, B, such that A derives B by a sequence of unit productions. Eventually, a sequence of unit productions must end with the use of some other kind of production. So we can collapse the steps that use unit productions into the next one that does not use a unit production. That is, if B goes to alpha is a non-unit production and A derives alpha by unit productions, then we'll add A goes to alpha. Finally, we drop all unit productions. At this point, we do not need the unit productions and can drop them from the grammar. Here's the algorithm to discover the pairs of variables A, B, such that A derives B by unit productions. For the basis, surely A derives A by unit productions only. This is a sequence of 0 steps. For the induction, suppose we already discovered that A derives B by unit productions. Then if B goes to C as a unit production, we may add the pair AC. There are 2 proofs that we need, but we're not going to do them here. First, an induction on the number of rounds of the discovery process lets us show that the pairs we find are valid. That is, they really are pairs AB such that A derives B by unit productions. And conversely, we can show by an induction on the number of steps of a derivation from A to B, using unit productions, that we will in fact discover the pair AB. Another proof that we're going to skip is the proof that a new grammar has the same language as the old. Again, we have to prove something more general, that A derives W in the new grammar if and only if it does so in the old grammar. Each production of the new grammar simulates one or more steps of a derivation of the old grammar. That is, some number of unit productions, perhaps 0, followed by a non-unit production. Conversely, every use of a production in the new grammar can be replaced by 0 or more unit productions followed by a non-unit production in the old grammar. We can now combine the three simplifications to make a strong statement about grammars. If L is a context-free language, then L minus epsilon has a grammar with no useless symbols, no epsilon productions, and no unit productions. Another way to put it is that L minus epsilon has a grammar in which every production body is either a single terminal or has length at least 2. We apply the constructions just learned, but we have to be careful about the order. We must start by eliminating epsilon productions. We have to do this step first because eliminating epsilon productions can produce unit productions that weren't there before, and as we saw in an example, it can create useless symbols that were not useless before. That could only occur if the production was only used to derive the empty string, however. Second, eliminate the unit productions. Third, eliminate variables that derive no terminal strings. We explained earlier why this step must precede the next step in our quest to eliminate all useless symbols. So finally, we do the fourth step of eliminating all the unreachable symbols. We've almost got our grammars into Chomsky normal form, or CNF. Such a grammar has only two kinds of production bodies, single terminals or two variables. We're now going to give the construction of a CNF grammar for L minus epsilon, where L is any context-free grammar. Incidentally, one important use of putting grammars in CNF is that it gives us a relatively efficient algorithm for testing membership of a string in a context-free language. One might imagine that it was easy to make such a test by looking at all derivations of a certain limited length, but with epsilon productions and unit productions in the grammar, it is not obvious how long the derivation of even a short string of terminals has to be. Moreover, even if we could bound the length of the derivation, as we can, we'd still be faced with an algorithm that took an amount of time that is exponential in the length of the terminal string. Rather, by putting the grammar in CNF, we can make this test in at most the cube of the length of the string. Our first step is to do the cleaning we just described. The result is the grammar no longer generates the empty string, even if the old one did, but otherwise the languages are the same. But all production bodies are either a single terminal or have length at least 2. Our second step is to turn those bodies that are not a single terminal into bodies of all variables. The trick is simple. For each terminal little a, create a new variable that we'll call a sub a. It's that. The job of this variable is just to generate the terminal little a, so replace a in all bodies of length 2 or more by a sub a, and add the production a sub a goes to a. That is, of course, that. Here's an example involving the production a goes to b little c, b little e. C and e are terminals, so we must have created variables a sub c and a sub e with their productions. A sub c goes to c and a sub e goes to e. Then we can replace a goes to b, c, d, e by a goes to b, a sub c, d, a sub e. Now all production bodies that are not a single terminal are strings of 2 or more variables. If exactly 2, that's great because that's what CNF requires. But if a body consists of 3 or more terminals, we have to break the body into pieces by using new variables that appear nowhere else. An example should make the idea clear. If we have a production a goes to b, c, d, e, then we need 2 new variables, say f and g, and they are used only for this production. They may not appear in the new grammar except as we describe here. In general, if the body consists of n variables, we need n minus 2 new variables. The job of the first new variable, f, is to generate the whole body, except for the first symbol, b in this case. That is, we replace this a production by a goes to bf. Now f needs to derive CDE, that's the rest of the body. But that's too long, so we use g to help. G derives only DE, that's this production. Using the production G goes to DE, and the production for F becomes F goes to CG. Thus, we've replaced A goes to BCDE by the three productions that meet the C and F requirement. A goes to BF, F goes to CG, and G goes to DE. These three productions can simulate the effect of the original production, although they take 3 steps to do so. Thus, making this change surely allows the new grammar to generate anything the old one did. But the new grammar doesn't generate anything the old one didn't, so the languages are the same. The reason is that once we choose to replace A by BF, we are forced to replace F by CG and then G by DE because these two variables have only one production. Thus, using A goes to BF in the new grammar is tantamount to using A goes to BCDE in the old. We thus have an argument why the transformations from clean grammars to C and F grammars do not change the language. You can do formal inductions on the length of derivations in these grammars, but I hope these less formal arguments are convincing. Today we're going to see an automaton that is the equivalent in power to the context-free grammar. The equivalence is analogous to the equivalence between regular expressions in automata, epsilon NFAs in particular. The automaton is called a pushdown automaton, or PDA, a term that was in use long before there were personal digital assistants. After describing the mechanics of the PDA, we'll talk about 2 different but equivalent ways that PDAs can define a language. We'll also mention the deterministic PDA, since the standard model of the PDA is the non-deterministic version, with epsilon transitions allowed. One of the key points to remember is that PDAs define all and only the context-free languages. But unlike finite automata, the non-deterministic version is strictly more powerful than the deterministic version, and only the non-deterministic version defines the class of context-free languages. However, the deterministic version is quite important in compiling, since parsers for programming languages usually behave like a deterministic PDA. Most programming languages are designed to be recognized by a deterministic PDA. For example, we mentioned previously the class of LL of 1 grammars, and such a grammar can be converted easily to a deterministic PDA. We'll get to a formal definition of a PDA shortly, but to start, think of the PDA as an epsilon NFA with an additional stack on which you can store symbols. Like any stack, you can only see the top symbol. The next move of the PDA is a function of 3 things. The move can depend on the state it is in, just like a finite automaton. The move also depends on the next input symbol, or the PDA may make a move on epsilon, that is, without regard to the next input symbol. This behavior is exactly like that of the epsilon NFA. But the thing that makes the PDA different from the finite automaton is that it has a stack of symbols chosen from a finite alphabet, and it can use the top symbol to help decide on the next move to make. Here is the image of a PDA we should keep in mind. At the center is the state. Like the state of the finite automaton, it controls what happens. There is some input which is waiting to be processed by the PDA. The PDA can only see the next input symbol and can use the symbol to help decide the next move. It also has the option to make the move on epsilon without consulting the input. And it has a stack of symbols. It can see only the top symbol and use that to help choose the next move. Moves of the PDA can involve a change of state, like the finite automaton, but it can also push or pop the stack. In any situation, that is, in some state with some next input symbol and some top of stack, the PDA has a finite number of choices of next move. Since it is non-deterministic, it is perfectly acceptable for there to be more than one choice. A move choice consists of a change in state, which could, of course, be to the same state it is in, a manipulation of the stack. At each move, the top stack symbol is replaced by a string of stack symbols. If the string is empty, it has the effect of popping the stack. If the string is of length 1, then the top stack symbol can be changed, or not, since the replacing symbol can be the same as the original. If the replacing string has length k greater than 1, we can see the move as a change of the top stack symbol followed by k minus 1 pushes of symbols. Now we'll give the formal notation and usual symbols for the components of a PDA. There is a finite set of states for which we tend to use Q, just as for finite automata. There is a finite input alphabet for which we'll continue to use sigma. There's a finite stack alphabet, the symbols that can appear on the stack. For this alphabet we use gamma. There's a transition function delta to be described shortly. There is a start state, typically Q0 as for finite automata. There's a start symbol. This symbol is a member of the stack alphabet, and initially the stack contains only this symbol. And there is a set F of final states, again analogous to the finite automata. There are conventions for PDAs that are analogous to the conventions we made for automata and grammars previously. We continue to use lowercase letters at the beginning of the alphabet for input symbols. However, for PDAs, it is sometimes convenient to allow these letters to stand for epsilon as well as the symbols of the input alphabet. Capital letters at the end of the alphabet are stack symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Greek letters at the beginning of the Greek alphabet are strings of stack symbols. We always write stack strings so the top of stack is at the left end. The transition function for a PDA has 3 arguments. The third argument is the symbol at the top of the stack. First comes a state, as for finite automata. Second, an input symbol or epsilon, as for the epsilon NFA's transition function. And last, a stack symbol. Delta for state Q, input A, which can be epsilon, and stack symbol Z, is a set of 0 or more actions. Each action consists of a next state P and a string alpha of stack symbols, possibly empty, with which to replace the top symbol Z. To summarize, when delta of Q, A, and Z contains P alpha, then one choice of move for the PDA when it is in state Q sees A at the front of the remaining input and has Z on top of stack is to go to state P, remove A from the front of the input. Of course, if A is epsilon, then the remaining input doesn't change. And replace Z by alpha on top of the stack. Note that although the PDA may have choices, several different P alpha pairs, it has to pick one pair and then do both things associated with that pair. It can't pick a next state from one pair and a stack string from another. Let's design a PDA for our favorite context-free language, the set of strings with the form 0 to the n, 1 to the n. Okay. We need 3 states. Q will be the start state. It represents the condition that we've so far seen only zeros on the input. P is the state we go to when we see the first 1. We use the state to remember not to accept a string if we ever see any more zeros. And F will be the final state. It's there only so we can accept when the number of 1s matches the number of zeros. We also need 2 stack symbols. Z0 is the start symbol. It has an important job. It marks the bottom of the stack. As we read zeros on the input, we will push 1 X onto the stack for each 0 we read. As 1s come in, we pop 1 X for each 1. So when the bottom marker, Z0, again becomes the top stack symbol, we know we have seen exactly as many 1s as there were zeros, so we accept. Here's the transition function of our PDA. Initially, Z0 is at the top of the stack. When we see the first 0, we push an X onto the stack. Notice that the replacement string is XZ0. That's that. That string replaces Z0, but the net effect is that the Z0 remains and X is pushed onto the top. Remember that stack strings are written with the top at the left. We remain in state Q as long as zeros appear on the input. After the first 0, each additional 0 causes the x on top of the stack to be replaced by 2 x's. Thus, the number of x's on the stack always equals the number of zeros read from the input. When a 1 appears at the front of the input, if x is on top of the stack, then we go to state P and pop the top x. Notice that there has to be an x on top of the stack, so if the first input is 1, when we still have z0 on top of the stack, we have no move at all and can never accept. As long as more 1s appear on the input, we stay in state P and pop an x from the input. Thus, after seeing n zeros followed by m 1s, the number of x's remaining on the stack will be n minus m. And thus, after seeing n zeros followed by exactly n 1s, there are no more x's on the stack, and the top symbol becomes z0 again. The last move of this PDA says that if we are in state P with z0 on top of the stack, then without using any input, we go to state F. The z0 remains on the stack, although that is not important. Here's a moving picture of the PDA we designed with 0, 0, 0, 1, 1, 1 waiting on the input. Initially, it is in state Q with just z0 on the stack. That's the initial configuration. For the first move, we consume the first 0 from the input and replace z0 by xz0 on the stack. Notice the x is on top of the z0. It's at the top of the stack. We consume another 0 and replace the top x by 2 x's. And the same thing happens again. Now the first 1 is consumed from the input. We transition to state P and pop the top x. Staying in state P, we consume another 1 and pop another x. Same thing. Now all the input is gone, but we have z0 on top of the stack, so with epsilon input we can go to state F and accept. We're done, and we accepted the input string that was consumed, 0, 0, 0, 1, 1, 1. To talk more formally about the behavior of a PDA, we need the notion of an instantaneous description, or ID. The ID tells us the current state Q, the remaining input W, and the stack contents alpha. Again, remember that the top of the stack will be the leftmost symbol of alpha. There is an analogy between derivations for a grammar and sequences of IDs for a PDA. The IDs are analogous to the sentential forms of the grammar. In place of the double arrow, we use the turnstile symbol, that's this, to express the idea that one ID I can become another ID J by one move of the PDA. That is, suppose the first ID has state Q and input AW, where A is either the first symbol or epsilon, whatever is used for the next move, and it has stack X alpha, where X is the top symbol and alpha is then everything below that. Suppose the delta of QAX contains P beta. Okay. Then a possible next ID has state P, that's this. Okay. W is remaining on the input because A got consumed. Again, A may be a symbol or epsilon, doesn't matter. And with beta alpha on the stack, where the X here got replaced by the beta. We also have a goes to star relation for IDs defined analogously to the way we defined arrow star for sentential forms. That is, the basis representing 0 moves says that any ID goes to star itself. And for the induction, if I goes to J by some number of moves, possibly 0, and J goes to K by one move, then I goes to K by some number of moves. Here's the sequence of IDs that we get from our previous example. The input is 0, 0, 0, 1, 1, 1, so the initial ID has state Q, that input, and stack Z0. Here it is. The first move consumes a 0 from the input and pushes x onto the stack. So this 0 got consumed, that's what's left, and of course the z0 is now on the stack. The second and third moves do the same. And you can see additional x's being pushed onto the stack. Okay. Next, because the next input is 1, the state becomes p and the 1 is removed from the input. Also an x is popped, okay, and that explains that ID. And 2 more moves pop the remaining x's. It's that and that. And then in the final ID, the state p has become f, and we accept. We can summarize the sequence by saying that the initial ID, this, goes to star the final ID, that. We can also say that any of these IDs goes to star itself and also to any of the IDs that follow in the sequence we just showed you. In order to understand better the idea of acceptance of an input by a PDA, we have to ask ourselves, what would happen if there were an extra 1 on the input? We'll take that up on the next slide. Okay. The sequence of IDs is the same, except that an extra 1 tags along at the end of each input string. The last move, where the state changes from P to F, is still legal because a PDA can use epsilon input even if there is input remaining. State F has no transitions, so the sequence cannot be extended and the last 1 can never be consumed. We conclude that 0, 0, 0 followed by 4 1s is not accepted because the input was not completely consumed even though we entered a final state in the middle of the process of consuming the input. Okay. The normal way to define the language of a PDA is by final state. That is, L of P, the language of a PDA P, is the set of strings W such that when P is started in its start state, with W on the input and the start symbol on the stack, that's this ID, there is a sequence of moves of P that leads to an ID with a final state, there we are, with W completely consumed, it's that, and anything on the stack, I don't care. However, there is another way to define the language of a PDA, and this approach turns out to be rather useful, especially when we show how to convert PDAs to grammars and vice versa. We can talk about the set of strings that make the PDA empty its stack. This language is conventionally called NFP for a PDAP. The N stands for null stack, although we're not really going to use that term. Formally, this language is the set of strings W such that started in the usual ID with input W, that's of course this, P eventually reaches an ID in which it has consumed all of W and its stack is empty. Okay. We don't care about the state Q. It can be final or non-final, doesn't matter. Thus, every PDA defines 2 different languages in 2 different ways. However, the classes of languages defined by all the PDAs in these 2 ways are the same, and in fact are the context-free languages, as we shall see later. That is, if we have a PDA P that defines a language L by final state, then there's another different PDA P prime that defines the same language L, but does so by empty stack. P prime will presumably define a different language by final state, but that doesn't matter. The point is that every language defined by final state by some PDA is also defined by empty stack by some PDA. And conversely, if a language L is defined by some PDA P by empty stack, then L is also defined by some PDA P double prime by final state. Here's a rough idea of how we convert a PDA P accepting L by final state to P prime accepting L by empty stack. Basically, P prime will simulate P. That is, it does what P does with a few exceptions. If P prime finds that P is accepted by entering a final state, P prime empties its stack. Since P and P prime are in general non-deterministic, P prime can also guess that P will read more input. P prime will then not empty its stack in that sequence of moves, but rather will continue simulating P. But since P prime accepts whenever it empties its stack, and P might do that on inputs it doesn't want to accept, P prime needs a bottom of stack marker to prevent it from accidentally emptying its stack during the simulation of P. Thus, we'll give P prime all the states, symbols, and moves of P in order to do the simulation of P, plus a few other bells and whistles which we'll explain next. First, P prime has a new stack symbol x0. This is the start symbol of P prime, and it also has the job of guarding the stack bottom against accidental emptying. That is, if P empties its stack, P prime will find x0 on top of its stack and realize that P can make no move from this ID. Although being non-deterministic, it may have other ways to proceed. P prime thus does not empty its own stack. P has a new start state S and an erase state E. P prime has several additional transitions. This rule says that in its initial ID, it has only one choice. It must change to the start state of P and push Z0, P's start symbol, on top of its own start symbol x0, which remains to guard the stack. P prime is now ready and able to simulate P. Until P accepts, all the moves of P prime are the same as the moves of P, with the guard x0 sitting at the bottom of the stack unseen. And if P prime enters any final state F of P, then P prime has the option of entering the erase state E. It pops the current top of stack symbol, which might be x0 by the way. In that case, delta of F, epsilon, and x0 was previously undefined by P. Moreover, in the erase state E, P prime has only the choice to keep popping the stack and staying in state E. Eventually, P prime empties its stack and accepts. Now let's explain the construction in the opposite direction. That is, P accepts some language by empty stack, and we must design P double prime to accept the same language but by final state. P double prime also simulates P with a few bells and whistles. First, P double prime needs a bottom marker to detect that P has emptied its stack. If P double prime sees this marker at the top of the stack after its initial move, then it knows that P has emptied its stack, and so P double prime must accept by entering its own final state. P double prime has all the states, symbols, and transitions of P. In addition, P prime has a new start symbol x0 that also guards the stack bottom, just like it does for P prime. P double prime has a new start state S and a new final state F. From the initial ID, P double prime goes to the start state of P and pushes the start symbol of P onto its own stack. It is thus ready to simulate P. Once in the states of P, if P double prime ever sees the guard x0 at the top of the stack, it knows P is accepted. P double prime therefore goes to its own final state without reading any more input, and therefore accepts by final state the input that P accepted by empty stack. And a final word about the deterministic PDA. In order that there never be a choice of move, we certainly want the PDA to have at most one choice of move for any state Q, input symbol A, including epsilon, and stack symbol X. But we also have to rule out the possibility that there is a choice between using a real input symbol and making a move on epsilon. To be precise, for no Q in X can both delta of QAX and delta of Q epsilon X be non-empty. Such a PDA can have only one sequence of IDs, starting from the initial ID with a given input string. We generally assume acceptance is by final state, since if you accept by emptying your stack, you cannot ever process any more input if you're deterministic. While we shall not expand on the matter, the class of languages accepted by deterministic PDAs contains all the regular languages, obvious since it can simulate a deterministic finite automaton by just ignoring its stack, but it does not include all the context-free languages. The goal of this lecture is to show you that Pushdown automata define exactly the context-free languages, so let's get to it. Besides the comfort of knowing that two seemingly unrelated concepts are really the same, the grammar PDA equivalence will let us jump between the two notations when we talk about properties of context-free languages. The ability to jump between different representations, regular expressions and deterministic finite automata, was important when we addressed properties of regular languages. And we shall find the ability essential for context-free languages as well. We also find it easier sometimes to describe a PDA for a language rather than a grammar. For example, you might find it hard to invent a grammar for balanced parentheses, but a PDA is easy to think of. Just push left parens onto the stack and pop the stack once every time you see a right parenthesis. If the bottom of stack marker is exposed, then the parentheses were balanced, and you never pop the bottom marker because that would mean you have more right parens than left. Let's start with a language L that has a context-free grammar G. We'll convert grammar G to a PDA P that accepts L by empty stack, and if you want a PDA that accepts L by final state, we know how to convert to one of those. P will have only one state Q, that's all we need. Naturally, Q is the start state. There are no final states because we are accepting by empty stack. The input symbols of P are the terminals of G. The stack symbols of P are all the terms and variables of G. And the start symbol of P is the start symbol of G. Our intent is that P will step through a leftmost derivation of input W from the start symbol S. The secret is that each left sentential form is represented in a subtle way. It is whatever input P has so far consumed, followed by whatever is on P's stack. When P reaches an empty stack, then the left sentential form it represents is whatever input it has consumed, followed by nothing, that is, by the empty stack. That means P has found a leftmost derivation of the input string it has read, so acceptance of the string is justified. If no sequence of choices of the non-deterministic P leads to empty stack after consuming W from the input, then W is not a terminal string derived by the grammar, and P rightly does not accept W. There are two kinds of rules in the transition function of P, depending on whether a terminal or variable of G is at the top of P's stack. The type 1 rules handle the case where A is the terminal on top of P's stack. There better be an A as the next input symbol, or P has guessed wrongly about the leftmost derivation of the input as it actually exists. In effect, we cancel the A on the stack against the A on the input. The left sentential form represented does not change. We have now consumed one more input symbol A from the input, so that becomes part of the left sentential form. But the A that was at the stack top is removed, so it no longer participates in the left sentential form. The type 2 rules handle a variable, say A, on the top of the stack. We need to expand that variable by the body of one of its productions and thus move to the next left sentential form. Of course, we're only guessing. We have to allow any of A's productions to be used. If A goes to alpha is one of these productions, then a choice for P using epsilon input and with A on top of the stack is to replace A by alpha. We're going to prove that P accepts exactly what G generates. Formally, we will show something more general. It seems we always have to show something more general than what we really want. Here we show that if P consumes W from its input, starting with only S on its stack, and winds up with stack alpha, that is, this ID becomes that ID, okay, then in G there is a leftmost derivation of the string W alpha. Incidentally, notice that as we describe the moves of P, we allow any string X to follow W on the input. Since no part of X was consumed, X cannot have any effect on the moves P made reaching the ID shown, So if the statement is true for one x, it is true for any other. That is, x does not matter. We start with the only if part. That is, if P makes the transition shown, then S derives W alpha in G. The basis is 0 steps. Then W is obviously epsilon, since nothing can have been consumed from the input. And alpha is S, since the stack doesn't change. We need to show that S derives W alpha in a leftmost derivation. But W alpha is just S, and surely S derives itself. Now let's do the induction. We'll consider the result of n steps of P. That is, this ID has become that ID. And we'll assume the inductive hypothesis for sequences of n-1 steps. We must consider type 1 and type 2 moves as the last step separately. First, consider the case where the last of the n moves is a type 1 move, where an A at the top of the stack is cancelled against an A on the input. Then the W consumed by the n move sequence must be of the form YA. That's this. And before the last move, the Y was consumed. That is, leaving just AX. Further, just before the last step, the stack of P is A alpha. By the inductive hypothesis applied to the first n-1 moves, we can conclude that there is a leftmost derivation from S of YA alpha. That's this, and it corresponds to the fact that there is an n-1 step derivation of that ID. But YA is W, so we already know that there is a leftmost derivation of W alpha. That is the needed conclusion for the full sequence of n steps. Now let's look at the case of a type 2 rule, where there is a variable A on the top of the stack after the n-1st move. After n-1 moves, P has consumed W from the input and has A beta on its stack. That's that. This, of course, is the ID after n-1 moves. At the nth move, no input is consumed, but A is replaced by gamma, one of its production bodies. Okay. That is, we assume A goes to gamma is a production. Okay. Notice that alpha is gamma beta here. That is, this stack string is really alpha. Okay. Again, we apply the inductive hypothesis to the first n-1 steps. We thus know that there is leftmost derivation from S of WA beta. Since A is clearly the leftmost variable, and A goes to gamma as a production, there is also a leftmost derivation of W gamma beta. That's that. And of course, gamma beta is alpha, so that is really a derivation of W alpha, as we wanted to prove. We also should prove the converse, but we won't. That is, we need to show that if there's a leftmost derivation of W alpha, that is this, then P can consume W from its input with any unseen X following, and turn stack S into stack alpha. The proof is an induction on the number of steps of the derivation, but that's as far as we will take it. Assuming we complete the proof of the converse, we have the statement we set out to prove. P can consume W from its input with any X following, and turn stack S into stack alpha, if and only if G has a leftmost derivation of W alpha. Now we can restrict the statement to what we really care about, the case where X is empty, that is, P has consumed all its input, and alpha is also empty, that is, P has emptied its stack and accepted. We conclude that P consumes W while emptying its stack if and only if there is a leftmost derivation of W in G. That is, W is in N of P if and only if W is in L of G. For our next trick, we'll show how to convert PDAs to grammars. Assume language L is accepted by PDA P by empty stack. If it were accepted by a final state, we already know how to construct a new PDA that accepts L by empty stack, so we're entitled to assume acceptances by empty stack. We'll construct G, a grammar for L, and the idea is to give G variables, which we'll denote by pxq with brackets around them, like this. The job of this variable is to generate all and only the strings W, such that while reading W from the input, P goes from state P to state Q and appears to pop X from the input. While doing so, P can grow the stack well above where X was, but it can never go below where X was, and at the end the stack is shorter by 1 than it was when it started. That is, the net effect is that X has been popped. Here's a picture showing the height of the stack while X is effectively popped while reading W. Note that X might be replaced at the first move or later by another symbol Y. It could even be replaced many times, but the position of the stack that originally held X is never popped until the last move, right at the end here. As we mentioned, for every pair of states P and Q and stack symbol X, there is a variable that we represent by the composite symbol pxq. Although this expression consists of 5 characters, you must think of it as a single symbol in the set of variables of G. Also, as we hinted, the job of pxq is to generate all strings W that have the effect of taking PDA P in state P with only X on the stack to the ID where the state is Q, the input has been consumed, and X was popped. That's that. Notice that since the initial ID shows nothing below X on the stack, we know that X can't be popped until the last step, since PDA P cannot make any moves when its stack is empty. And there is one more variable of G, the start symbol X. There may be many productions for variable pxq. For each move of the PDA from state P with X as the top of the stack, we produce one or more productions. There are several cases, and they get increasingly more complex depending on how long the stack string is that replaces X at the first move. The easiest case is that of a rule that says in state P with input A, which could be epsilon or a real symbol, we pop X. That's that. Okay. There, X is replaced by 0 symbols. Then there is a production pxq goes to A. The reason this is correct is that reading only A is one way to have the net effect of popping X while going from state P to state Q. The next simplest case is when a move replaces X by a string of length 1, say Y. Suppose that move also changes the state to R. Then there is a production pxq goes to A RYQ. That is, one way to pop X while going from state P to state Q is to read input A, going to state R and replacing the X by Y at the top of the stack. Then some number of inputs, say W, has the net effect of popping the Y while going from state R to Q. As a consequence, the net effect of reading A followed by W is to take state P to state Q while popping the original X. Here's a picture of the case where X is replaced by a single symbol Y. How the Y gets popped we don't know, but when it does, the effect is that the symbol A followed by whatever W popped the Y has the effect of popping X while going from state P to state Q. Now it's getting a little more complicated. Suppose there is a move that replaces X by 2 symbols, Y and Z, while going to state R and reading A from the input. That is, the new stack YZ replacing X. In order for X to be erased, there must be some input string U that has the net effect of erasing Y, and U must take the PDA from state R to some state S, which unfortunately we don't know. As a result, we're going to have one production for each possible state S. But after reaching state S, we must have some additional input V that takes the PDA from state S to state Q while popping the Z from the stack. The net effect is that A followed by U and then V pops X from the stack while going from state P to Q. Okay. Here's a picture of that action. Initially you see X got replaced by Y and Z on the stack. Then U had the net effect of replacing Y, of popping Y, exposing the Z. Now we're in state S. And then V has the net effect of popping the Z and winding up in state Q. So we generate many productions for this case, where on input A, state P becomes R and X gets replaced by the stack, on the stack by Y and Z. For every state S, there's a production with head PXQ, and then the A that causes the first move. Remember, A could be empty. And then RYS to effectively pop the Y, winding up in this state S that we really don't know. So that's why there's one production for each S. And then SZQ to effectively pop the Z. We finally wind up in state Q, which is the state that we wanted to wind up because that's the state that appears in the head. As a result of this production, you can see that PXQ can derive any string AUV provided that RYS derives the U and SZQ derives the V. In the general case, where on input A in state P, X is replaced by a string of 3 or more stack symbols, Y1 through YK, and the state becomes R. We need a family of productions in which there are k-1 unknown states, S1 through Sk-1. Right. The productions all have this form. PXQ can be replaced by an A, which again may be epsilon, followed by variables R, Y1, S1, S1, Y2, S2, and so on, with the last of the variables being Sk-1, Yk, and finally the state Q from the head that we want to wind up in. With productions constructed in this manner, we can prove that P accepts W by empty stack. That is, the ID Q0 W Z0 goes to P epsilon epsilon if and only if the variable Q0 Z0P derives W. We're not going to give the proof. It is 2 easy inductions, one for each direction. The only problem is that we don't know state P. But remember, G has another variable S, and that is the start symbol. So we add production S goes to Q0 Z0P for every state P. And now we have a grammar that generates exactly the strings that the PDAP accepts. There is a pumping lemma for context-free languages analogous to the pumping lemma for regular languages. The goal of this lecture is to state and prove this lemma, which is naturally more complicated than the pumping lemma for regular languages, and then use it to show certain languages are not context-free. Let's review the pumping lemma for regular languages. It said that any sufficiently long string W in a regular language has some short, non-empty piece near the beginning that we could pump. That is, we could repeat it as many times as we liked, including 0 times, and the resulting string would also be in the language. We found the string to pump by looking for the first state to repeat as a finite automaton process that's input W. The pumping lemma for context-free languages says that we can find 2 pieces in any long string Z and pump them in tandem. That is, we can repeat each of them I times for any I equal to or greater than 0, and the result will be in the same language. We'll also see that these 2 strings are close together in Z, and one can be empty, but not both. Here's the statement of the pumping lemma for context-free languages. We can see it as the same sort of game with an adversary that we talked about in connection with regular languages. For every context-free language L, that is, you get to pick L, presumably the one you want to show isn't really context-free, there is an integer n. This is something the adversary gets to pick, but once it's picked, it's fixed for the rest of the game. Such that for every string z in L of length at least n, and here you get to pick the z to focus on, you can break z into 5 pieces, u, v, w, x, y, such that 3 things are true. The adversary gets to pick how z is broken, but subject to 2 constraints we'll see in just a moment. And incidentally, v and x are the substrings that get pumped. The first constraint is that the middle 3 components, v, w, and x, are short, no longer than the length of n put together. Remember that v and x will get pumped, so that says not only are they short, but they appear within a bounded distance from each other within z. The second condition that the adversary has to respect is that v and x cannot both be empty, although one can. And if all the above is satisfied and L really is context-free, then for all integers I equal to or greater than 0, u, v to the I, w, x to the I, y is also an L. We win the game and prove L is not context-free by allowing the adversary his choices of n and the breakup of z subject to the constraints 1 and 2, and then picking an I such that u, v to the I, w, x to the I, y is not an L. The proof of the pumping lemma for context-free languages starts with a Chomsky normal form grammar for L. Technically it is for L minus epsilon, but the empty string will never meet the condition of being of length at least n, so its presence or absence doesn't matter. This CNF grammar has m variables for some m, so we're going to let n be 2 to the m. And now let's consider any string z in L of length at least n. That's 2 to the m again. We're going to prove first that any parse tree in a CNF grammar for a string z of length at least n equals 2 to the m must have a path of length m plus 2 or more from the root to a leaf. We'll actually prove the contrapositive. That is, suppose there is a parse tree z with no path longer than m plus 1. Such a path has m nodes labeled by variables at the top, or the beginning, and one node labeled by a terminal at the end. That is, here is a typical path. It will have variables here, here, and here, and then a terminal there. Okay. If we forget about the terminals at the leaves, a parse tree in a CNF grammar is a binary tree. Thus, at each level, the number of nodes can at most double. Thus, there is only one node at the top level, the root. There can be only 2 nodes at the next level, 4 at the third, and 8 at the fourth, and so on. In general, there'll be at most 2 to the power m minus 1 at the nth level. But this tree has at most m levels with variables, and then along each path of variables, the last variable has one child with a terminal as its label. The largest number of leaves occur if all the paths in the tree have exactly m variables. If some paths terminate before level m, there will be fewer leaves. Thus, there are at most 2 to the m minus 1 nodes that are labeled by variables and have a single child with a terminal label, and thus there are at most 2 to the m minus 1 leaves. Finally, we therefore can conclude that the length of the yield is at most 2 to the m minus power m minus 1. Now 2 to the power m minus 1 is n over 2. Since z is of length n, it cannot be the yield of any tree that has paths limited to length m plus 1 or less. Therefore, we conclude that somewhere in the parse tree for z is a path of length at least m plus 2. Now we're ready to prove the pumping lemma. We just proved that z's parse tree has a path of length at least m plus 2. Only the last node in any path can be labeled by a terminal, so there are at least m plus 1 nodes with variables along this path. Let's focus on one of the longest paths in the parse tree for z. Surely there are at least m plus 1 variables along this longest path. Remember that m is the number of variables of the grammar, so along this path there are 2 nodes labeled by the same variable call it A. In fact, to make sure we pump short pieces, let's look only at the bottommost n+1 variables along this path, which could be much longer than n+1, and we know that two of them must be the same. On the next slide, we'll see what the parse tree must look like. Here's a picture of the parse tree for Z. We've shown the path we've focused on and the lowest repeating variables along that path. The purple tree is rooted at the lower A, and the yellow tree, with the purple tree within it, is rooted at the upper A. Let W be the yield of the purple tree. V and X are the portions of the yield of the yellow tree that precede and follow W, respectively. And let U and Y be the portions of Z that precede V and follow X, respectively. Let's look at the yellow. Since the path shown is as long as any other, and that path has at most n+1 variables, we know by the lemma 1 that we just proved that the yield of the yellow plus purple is no longer than 2 to the power m, or n. That is, the length of VWX is no more than n. But V and X both can't be empty. Why? That's a useful property of Chomsky normal form grammars. Since the two A's shown in the tree are different nodes, the upper A must have a child to the left or right of the path shown. That's a consequence of the fact that we eliminated unit production, so all bodies that have variables have at least two of them. Moreover, once we have a variable not on the path, there are no epsilon productions, so we must generate from this variable at least one terminal. That is all we need to conclude that either V or X or both have length at least 1. Now we can take advantage of the fact that we have two A's along the path. We can get rid of V and X by pumping 0 times. That is, we know the purple tree can substitute for the yellow because both trees have the same variable A at the root. If the original on the left satisfies the conditions of a parse tree, that is, every interior node is the head of a production whose body is the labels of its children, then the same will be true of the smaller parse tree on the right. We conclude that UWY is also in the language. Or we could pump twice, that is, replace the purple tree by the yellow, which has the purple within it, and you get a parse tree whose yield is UVVWXXY. And in the previous tree representing pumping twice, we could again replace the purple tree by the yellow and get a bigger tree whose yield is U, 3 V's, W, 3 X's, and then Y. In the same manner, we can get parse trees for all strings with the form U, V to the I, W, X to the I, Y for any integer I equal to or greater than 0. These strings are therefore all in the language L. That proves the pumping lemma for context-free languages. Let's look at an example of how the pumping lemma can be used to show a language not to be context-free. This language, which involves matching the counts of 2 blocks of zeros, is context-free. A grammar or PDA for it is easy to construct. The ideas are very much like what we saw for the language 0 to the n, 1 to the n. But give the language 3 blocks of zeros, all of which must be the same length, and we're suddenly outside what context-free grammars can do. We can prove that using the pumping lemma for context-free languages. So we'll pick this language L, and the adversary now gets to pick n. We don't know n, but we do know it is fixed for the rest of the game. We get to pick z, so let's pick 0 to the n, 1, 0 to the n, 1, 0 to the n. That is, each block of zeros is of length equal to whatever n the adversary picked. Now the adversary gets to break our z up into z equals UVWXY, but he must choose these substrings such that VWX together are no longer than n, and V and X cannot both be picked to be the empty string. There are two cases depending upon whether the adversary picks V and X to have zeros or not. In the first case, suppose there are no zeros among V and X. Then since they cannot both be empty, there must be at least one 1 among them. But then, if we pump 0 times to get the string UWY, we know that there is at most one 1 in this string. The pumping lemma claims it is in the language L, but it can't be because all strings in L have exactly 2 1s. In the second and last case, v and x have at least one zero among them. VWX has length at most n, so these three substrings cannot extend from the first block of zeros to the last because n plus 2 positions separate those blocks. So again consider UWI, which if L is context-free must be in L. Removing v and x must leave at least one of the three blocks of n zeros intact, so it still has n zeros. But v and x have at least one zero, so in UWY, at least one of the blocks of zeros has fewer than n zeros. We conclude that in this case too, UWY cannot be in L, and thus L cannot be context-free. To finish off our discussion of context-free languages, let's look at the properties of this class of languages. Remember, there are two kinds of properties we find useful. One is decision properties, where we tell something about a language or languages in the class, such as whether the language represented by a grammar or PDA is empty. And the other is closure properties, where we prove that some operation, say union, applied to languages in the class, results in another language in the class. First, let's remember that when we talk about a decision property or a closure property for a language class, we're talking about algorithms that take a representation for a language in the class and produces an answer. For the regular languages, we use regular expressions and deterministic finite automata as the representations. Here, for context-free languages, we use the context-free grammar or the pushdown automaton as the representation, whichever makes life easier. And when we use the PDA, we can let acceptance be by final state or empty stack, again, whichever makes life easiest. Here are some questions about context-free languages for which algorithms exist. Given a representation for a context-free language, L, and a string W, we can determine whether or not W is in L. We can tell whether a representation for a context-free language, L, generates the empty language. And we can also tell whether this language L is finite or infinite. Unfortunately, many of the things we can decide about regular languages, we cannot decide for context-free languages. For example, we were able to tell whether two regular languages, say represented by DFAs, were the same. We can't tell whether two context-free grammars or two PDAs define the same language. Another thing we cannot tell is whether two context-free languages are disjoint. We say sets are disjoint if their intersection is empty, that is, they have no members in common. We didn't address the question of disjointness for regular languages, but you can tell whether two regular languages are disjoint. We showed regular languages are closed under intersection using the product automaton trick. We also showed that you can tell whether the language of an automaton is empty. These two ideas together give you an algorithm to test whether two regular languages are disjoint. At this point, we have no way to prove that no algorithm for a task exists. That is the job of the theory of Turing machines and decidability, and that will be the next big topic that we address. Now, the emptiness test for context-free languages has already been given in essence. We showed how to eliminate useless symbols, those that participate in no derivation of a terminal string. Take any context-free grammar and see whether or not the start symbol is useless. If so, the language of the grammar is empty, and if not, then not. The membership test for DFAs was really simple. We just simulate the DFA on the string. We can also test whether a terminal string W is generated by a grammar G, but the test is remarkably hard by comparison. We'll assume G is a grammar in Chomsky normal form. If not, we know how to convert the given grammar to CNF, so let's do that as the first step. There's a small matter that when we convert to CNF, we lose the ability to generate the empty string. But if W, the string we want to test, is epsilon, then there is another approach entirely. Apply the algorithm we learned for finding the nullable symbols, those that derive epsilon. See if the start symbol is one of these, and that lets us test membership of the empty string in the language of a context-free grammar. We're going to give an algorithm called CYK. The initials stand for the three people who independently invented the idea: John Koch, Dan Younger, and Tadao Kasami. This algorithm is a great example of a dynamic programming algorithm and worth seeing for that reason alone. The running time of the algorithm is of the order of n cubed, where n is the length of the input string w. Incidentally, there is another algorithm due to J early that also runs in time order n cubed, but on an unambiguous grammar, Early's algorithm is faster. It's order n squared. However, the CYK algorithm is much simpler, and as I said, worth studying because it is a model for so many useful dynamic programming algorithms. So that is the one we're going to learn. Here's how the CYK algorithm works. Start with an input string of length n. Let a sub I be the symbol in the ith position. We're going to construct a triangular array with short sides each of length n. Each entry in the array is a set of variables of the grammar. The set x sub ij, which will be in position ij, and I is equal to or less than j, is intended to be the set of variables a that derive the substring of the input, starting at position I and ending at position j. That is this. We'll use an induction to fill the table. The induction is on the length of the string derived, which is j minus I plus 1. So we start by computing the entries x sub I, which is the set of variables that derive the string consisting of the one position ai. From these we can find the I plus 1s, each of which is the set of variables that derive the string ai followed by ai plus 1. Then we move to the I plus 2s, which are the sets of variables that derive the strings of length 3, ai plus 1, ai plus 2, and so on. Finally, after we have computed the one set x1n, which represents the entire input, we can ask ourselves whether s is in that set. If so, then s derives a1 through n, and the string w is in the language, and otherwise not. For the basis, we know that the only way to derive a string of length 1 in a CNF grammar is to use a production whose body is a single terminal. So for each I, we can set xii to the set of variables a, such that a goes to ai is a production. For the induction, where j is strictly greater than I, we can compute xij from x's representing two substrings of ai through aj. The first is the substring from ai to ak for some k less than j, and the second is ak plus 1 through aj. Both these strings are of length less than j minus I plus 1, so we have already computed the sets x sub ik and x sub k plus 1j. In order for a variable a to derive ai through aj, there must be some production, say a goes to bc, where b derives ai to ak, and c derives the rest. That is, for each k between I and j minus 1, we look for some b in xik and some c in xk plus 1j, such that bc is the body of an a production. If for any k, b, and c we find such a production, we add a to xij. We're going to do an example of the CYK algorithm. Here's the CNF grammar we'll use, and the input string w will be ABABA. It is of length 5, so we're going to compute sets of variables xij for I less than or equal to j, and I equal to greater than 1, and j less than or equal to 5. That's a triangular array. For the basis, let's see which variables have a production whose body is a. These variables are capital A, has this production, and capital C, which has that production. Thus, if W has the symbol little a in position I, then XII will be AC. We see A in positions 1, 3, and 5 of W, so that explains X11, X33, and X55. For terminal B, we see body B in productions for B and C. That's here and here. Thus, if I is a position of W that holds B, XII will be BC. That explains positions 2 and positions 4. Now we need to compute the 4 entries in the row above. These are the sets of variables that derive substrings of length 2. Here's one example, x12, which is the set of variables that derive the string in the first positions of W, that is, AB. When j is I plus 1, k can only be I. That is, the only way to derive a string of length 2 in a CNF grammar is to use a production where one variable is replaced by 2, and each of these variables derives one terminal. So the reason S is in x12 is that A is in x11, B is in x22, and S goes to AB is a production. And the reason B is in x12 is that A is in x11, C is in x22, and B goes to AC is a production. Notice that C can't be in x12 because C derives only strings of length 1. However, A can derive long strings and yet is not in x12. The reason is that the only production A has with body of 2 variables is A goes to BC. That's this. In order for A to be in x12, we would need to find B in x11 and C in x22. The latter holds, but B is not in x11. Here are the other 3 sets for the row corresponding to the substrings of length 2. We'll leave it to you to verify that those are correct. Now let's start computing x13. A string of length 3 can be broken in 2 different ways, either a string of length 1 followed by a string of length 2, or vice versa. In the first case, k equals 1, and we must combine x11 with x23. x11 has A and C, while x23 has only A. The only bodies we can form from these are AA and CA. But no variable has a production with either of these as the body. Thus k equals 1 gives us nothing. We must also consider k equals 2, where we combine x12 with x33. Now there are 4 possible bodies, B or S followed by A or C. Of these, only BC is a body of a production of our grammar, and its head is A. Thus, x13 turns out to be just the set containing A. Here are the other 2 x's for substrings of length 3. There is a pattern to computing these corresponding to the choices of k that we may make for each. We start at the bottom of the column. For example, for x24, that would be x22. And we start going down the diagonal to the right. For x24, that would be x34. So we're going to pair x22 with x34. We then pair them to see what production bodies we can form, and then we move up the column, here in this case to x23, and down the diagonal, in this case, to x44, and we pair these 2 guys to again see what variables we can form from that one followed by that one. Here's how we compute x14. Starting at the bottom of the column, that is x11, and the top of its diagonal, that is x24. We pair these to see if we can form any production bodies. In this case, we can combine A from x11 and B from x24 to put S, the head of the production with body AB, into x14. Now we move up the column to x12 and down the diagonal to x34, but pairing B or S with B or S doesn't give us any right sides. So we proceed up the column to x13 and down the diagonal to x44, and we pair A with B or C. AC is a body, and it justifies our putting B into x14. Here are the last 2 entries in the triangular table. x25 turns out to be the set containing A. We'll let you check that one out. And x15 is also A. We get A from x14, which has B, and x55, which has C. BC is a body, and A is its head. Since S is not an x15, we conclude that ABABA is not in the language of the given grammar. We also claim that there is an algorithm to tell whether a context-free language is finite or infinite. We won't give the algorithm in detail, but it is essentially the same as the time-consuming algorithm we gave for regular languages. We use the pumping lemma constant n, and as for regular languages, we can show that if a context-free language contains any string of length between n and 2n minus 1, then that string can be pumped and the language is infinite. Otherwise, the language is finite. We're now going to enter the area of closure properties. And for many of the same operations under which the class of regular languages are closed, the context-free languages are also closed. These include the regular expression operations themselves, union, concatenation, and closure, and also reversal, homomorphism, and inverse homomorphism. But unlike the class of regular languages, the class of context-free languages is not closed under intersection or difference. Here's a proof that the union of two context-free languages is a context-free language. Let L and M be the context-free languages, and let them have grammars G and H respectively. We need to rename variables of one of these grammars, so no variable is used in both the G and H. The names of the variables don't matter, so we can always do this. The reason it is so important is that we're going to throw the productions from G and H into one pile, and if they had variables in common, we could accidentally use a production from G on a variable from H or vice versa. Note that we do not change the terminals of the grammars. It's okay if they have terminals in common. In fact, we expect that they will have terminals in common. Suppose S1 and S2 are the start symbols of the two grammars after renaming the variables. And we'll build the grammar for L union M by combining all the symbols of the two grammars G and H. That is, the new set of terminals is the union of the terminals of G and H, and the new set of variables is the union of the variables in G and H, plus a new symbol S that is not a symbol of either grammar and will be the start symbol of the new grammar. The new set of productions is the union of the productions of G and H, plus two new productions, S goes to S1 and S goes to S2. All the derivations of the new grammar start with S. And in the first step, this S is replaced by either S1 or S2. If S is replaced by S1, then the entire derivation must be a derivation of G, because we cannot then get any variables of H into our derivation. Similarly, if the first step gives us S2, then the entire derivation is a derivation of H. Thus, the terminal strings derivable from S are exactly those in L if we start with S goes to S1. Union those in M if we start with S goes to S2. That is, the new grammar's language is L union M. The argument that the class of context-free languages is closed under concatenation starts the same way, with grammars G and H for the languages L and M. These grammars are assumed to have no variables in common and to have the start symbols S1 and S2 respectively. Again, we combine the two grammars as we did for union. The only difference is in the productions we use for the new start symbol S. Here there's only one production, S goes to S1 followed by S2. That way all strings derived from S will be a string of L followed by a string of M. That is, the new grammar will generate L concatenated with M. For Kleene star, let's start with the grammar G for the language L. Let this grammar have a start symbol S1. Form a new grammar by adding to G a new start symbol S and the productions S goes to S1S or the empty string. Then a rightmost derivation from S begins by generating 0 or more S1s, that is, it uses this production as many times as it likes, followed by S goes to epsilon. From each of these S1s we can generate exactly the strings in L, so the new grammar generates L star. Reversal is another operation for which it is easy to show closure using grammars. If we have a grammar G for the language L, we form a grammar for L reversed by reversing the bodies of all the productions of G. For example, here is a grammar for the language 0 to the n, 1 to the n. If we reverse the bodies, we get this grammar. It is easy to see that this grammar generates all strings of one or more ones followed by the same number of zeros. That language is the reverse of the language we started with. We're not going to give a proof that this construction works. It is a simple induction on the lengths of derivations in the two grammars. To prove closure of the context-free languages under homomorphism, let's start with a grammar G for a language L and let H be the homomorphism on the terminal symbols of G. Then H of L has a grammar that we can construct by replacing each terminal A in the body of any production of G by the string H of A. So for example, here G is our customary grammar for 0 to the n, 1 to the n. And here's our usual example of a homomorphism. Then H applied to the language of G has a grammar in which the two occurrences of 0 in the productions of G are replaced by AB, and the two occurrences of 1 are replaced by the empty string. Notice that the resulting language is all strings of one or more ABs. It is in fact a regular language, although in general we can only be sure that it will be a context-free language. Next, we take up the fact that context-free languages are closed under inverse homomorphism. While we seem to have done pretty well using a grammar as the representation for context-free languages so far, here we really need the PDA representation. Start with a PDA P that accepts the language L by final state. We'll construct another PDA P prime that accepts H inverse of L, where H is some homomorphism. The big idea is that P prime will simulate P, but P prime needs to apply H to every input symbol it sees, and since H of A may be a long string, P prime has trouble simulating P in one move, and often it cannot do so. So P prime will take it one step at a time. It has a state with two components. The first is the state of P, which is important in the simulation. But the second is a buffer that holds a suffix of what you get by applying H to some one symbol. This buffer allows P prime to use the symbols of H of A one symbol at a time to cause moves of P. Here's a rough sketch of what P prime looks like. As mentioned, its state has two components, the state of P and the buffer. We show input 0, 0, 1, 1 as an example only. Now P prime can read its first input symbol, 0, and apply H to it. The buffer, which was initially empty, now has the string H of 0. It may be a long string, but its length is finite, so there is only a finite number of states P prime can be in. Now to simulate P, P prime takes the first symbol of H of 0 and simulates P using that as the next input symbol. The simulation could take many moves, as there can be transitions on epsilon input as well as one transition on the symbol itself. However, the symbol is removed from the front of the buffer, so the next time P needs a real input symbol, it gets the second symbol of H of 0. The simulation proceeds in this manner until all symbols of H of 0 are consumed from the buffer. At that point, P prime can apply H to its next input and refill the buffer. To be more precise, the states of P prime are pairs QW, where Q is a state of P, and W is a suffix of H of A for some symbol A. Note that given P and H, there are only a finite number of values of W, and of course P has a finite number of states Q, so P prime also has a finite number of states as is required for any PDA. The stack symbols of P prime are those of P. Moreover, as we shall see, the stack behavior of P prime mimics that of P. And the start state of P prime is Q0 epsilon, that is the start state of P paired with an empty buffer. The input symbols of P prime are those symbols A for which H of A is defined, and the final states of P prime are the final states of P paired with an empty buffer. Now we'll show how P prime simulates P by giving the transition function delta prime for P prime. The first type of transition allows P prime to read an input symbol A, which must not be epsilon, apply H to it, and store it in the buffer. The buffer of P prime must be empty for this to happen, although since P might be able to make moves with epsilon input, P prime is not forced to refill the buffer just because it is empty. It can also make moves without consuming its own input. Formally, delta prime of Q epsilon A and X, this, has one choice. It can remove the A from its input. Again, remember A is not empty. Place H of A in the buffer and leave its stack and state unchanged. Note that H of A might be empty, in which case the buffer remains empty, but it is also possible that the buffer now contains one or more of P's input symbols. P prime also has the option to ignore its own input and simulate P as if P's input were whatever it is in the buffer. Formally, suppose that delta of Q, B, and X contains P alpha. Here B may be epsilon or it may be an input symbol of P. And then for any buffer string of the form BW that is a suffix of H of A for some A, delta prime of Q in the buffer BW with no input, this epsilon input, and X on the top of the stack will contain PW alpha. That is, B is consumed from the front of the buffer, the state of P changes according to the given choice of P's move, and the stack of P prime also changes in accordance with that given move. In order to prove that P prime does what we want it to do, that is, accept H inverse of the language of PDAP, we need to do two inductive proofs, one in each direction, of the statement that characterizes the way in which P prime simulates P. We're not going to give the proofs here. The precise statement of P prime simulates P is given in the middle of the slide. It says that P prime goes from its initial ID with input X, that's this, to some ID with state Q of P, buffer contents X, W consumed from the input, and alpha on its stack, and that's this, if and only if, well, first of all, P goes from its initial ID with input Y, that, to an ID that has state Q, input Y consumed, and alpha on its stack, that's that. And second, H of W is Y, that's what P consumed, followed by X, which is the thing that P prime still has left in its buffer. Once we have that, we can restrict it to this case where X is empty and Q is a final state. It then says that P prime accepts W if and only if P accepts H of W. That is, the language of P prime is H inverse of the language of P. We have not yet addressed intersection. Remember that the regular languages are closed under intersection, and we proved it by running DFAs for the two languages in parallel. But we can't run two PDAs in parallel and still have a PDA. The reason is that the parallel execution of two PDAs requires two separate independent stacks, and a PDA is only allowed to have one stack. That's only an argument that the obvious first try at proving context-free languages are closed under intersection won't work, but the situation is worse. We can see particular context-free languages whose intersection is not a context-free language, so no construction could possibly work. We said that this language, L1, the set of strings with some number of zeros followed by the same number of ones and the same number of twos, is not a context-free language. The pumping lemma gives us an easy proof of that fact. We're not going to do it here, but it's very much like the example of the pumping lemma proof that we did give. But consider L2, the set of strings in 0 star, 1 star, 2 star, that is, strings of zeros followed by some number of ones followed by some number of twos, such that the number of zeros and ones are the same with any number of twos. This language is context-free, and here is a little grammar for it. The job of variable A is to generate zeros followed by an equal number of ones. We've seen this mechanism several times before, and B generates just any number of twos, at least one of them. Now let L3 be the set of strings in 0 star, 1 star, 2 star with equal numbers of 1s and 2s and with any number of zeros. This language is also context-free, and the grammar for L3 uses the same ideas as the grammar we just showed for L2. But L1 is the intersection of context-free languages L2 and L3. We can also show that the difference of two context-free languages is not necessarily context-free. In fact, we can prove something surprising. Intersection can be expressed in terms of difference alone. Therefore, if any class of languages is closed under difference, it is also closed under intersection. The argument is that the intersection of any two languages, L and M, regardless of whether they're regular, context-free, or not context-free, is the difference between L and L minus M. That is, suppose X is in L intersect M. Okay, then X is surely not in L minus M, because it's in both L and M. And therefore, X is in L and not in L minus M. Therefore, it is in this expression on the right side. That proves containment in one direction. For the other direction, suppose X is in L minus M. That's this guy here. Then X is in L, and it's not in L minus M. But if X is in L but not in L minus M, it must be that X is also in M. Thus, X is in L intersect M. That proves containment in the other direction, that is, X here implies X there, and that proves the equivalence of these two expressions. Now, suppose the class of context-free languages were closed under difference, and L and M are context-free languages. Then L minus M would be context-free, and so would this guy, L minus M. But we just proved that this expression is the same as L intersect M. Thus, context-free languages would be closed under intersection, but we know they're not, so we know they could not be closed under difference either. We know that the intersection of two context-free languages may not be a context-free language. However, if we intersect a context-free language and a regular language, then we always get a context-free language. The idea is to run a DFA in parallel with a PDA. Since the DFA has no stack, we do not face the problem of trying to simulate two stacks with one that we face if we try to run two PDAs in parallel. Here's the picture of a PDA and a DFA running in parallel. We can combine the states of the two automata to make one state for a new PDA. It manipulates the stack of the original PDA and feeds inputs to both the original PDA and the DFA. It accepts if both the PDA and the DFA accept. To give the construction of the new PDA, let the DFA have a transition function delta A, and the original PDA will have a transition function delta P. States of the new PDA will be pairs. The first component, Q, is a state of the DFA, and the second component, P, is a state of the PDA. Suppose the original PDA has a choice of move from state P and stack symbol X, where A is consumed from the input. That's this. A could be a real symbol or epsilon. The result of the move is that the PDA state becomes R, and X on the stack is replaced by alpha. That's the move. Then the new PDA, whose transition function we call simply delta, given a state with P as the second component, input A, and stack symbol X, that's this, has a choice of move where the new state has second component R. The first component is what you get by having the DFA make a transition from state Q with input A. That's delta A of Q and A. Note that A could be epsilon here, in which case delta A of QA is just Q, or it could be a real symbol in which delta A of QA is something else. Finally, this choice of move replaces X by alpha on the stack, just as the original PDA did. The final states of the new PDA are the pairs QP, such that Q and P are final states of their respective automata. And the initial state of the new PDA is the pair consisting of the initial states of both automata. We need to prove a pair of inductions on the number of moves made by each PDA. These inductions say that the new PDA started in its initial state with input W, this, consumes the input and enters an ID with state QP, and stack alpha, having consumed the input. And that happens if and only if the original PDA goes from its initial ID with input W to the ID with the same state P and alpha on the stack. And of course the DFA goes from its initial state on input W to the state Q. We'll skip the details as the proofs are not too hard. We're now changing the subject matter considerably. Until now, I've been talking about simple models such as finite automata or context-free grammars that let us model mechanisms like communication protocols or processes like the parsing of programming languages. Today we begin to study the other side of automata theory, the part that lets us show certain tasks are impossible, or in some cases possible but intractable. That is, they can be solved but only by very slow algorithms. It might not be obvious, but just because we can state a problem doesn't mean there is any algorithm at all that can solve it. For example, can you devise an algorithm to tell whether the complement of a context-free language is empty? That is, does a grammar generate all strings over its terminal alphabet? It turns out you can't, and we're going to learn the theory that lets us prove facts of this kind. We begin with a central theme of the study, of what can be solved by computer algorithms. The idea that all data can be represented by integers. The idea of countable sets, those whose members can be assigned integers 1, 2, 3, and so on, is essential here. We're going to meet the Turing machine, which is in some sense the ultimate automaton. It is a formal computing model that can compute anything we can do with a computer or with any other realistic model that we might think of as computing. Turing machines define the class of recursively enumerable languages, which is thus the largest class of languages about which we can compute anything. There's another smaller class called the recursive languages that can be thought of as modeling algorithms, computer programs that answer a particular question and then finish. I realize the concepts are vague at this point, but we'll get to it all in good time. If you took a modern course on programming, you are undoubtedly introduced to the importance of data types or classes. But when you look under the hood, how these types are represented inside the computer, you see that there is only one type, strings of bits. We could base our whole theory on strings of bits, but it is more convenient to convert binary strings to integers. We can almost see how to do that, since integers can be represented in binary notation, but there's a small glitch we'll get to. And to make the idea that all the world is integers even more pervasive, remember that the programs that computers execute are also, under the hood, just strings of zeros and ones, and therefore can be regarded as integers. That lets us talk about the 100th program and things like that. As we shall see, the fact that programs and data are at heart the same thing is what lets us build a powerful theory about what is not computable. As a simple example of a type that is really integers, let's look at character strings. Strings of ASCII characters can be thought of as binary strings, 8 bits to a character. Or if you use Unicode, you need 16 bits per character, but the idea is the same. Strings in any alphabet can be represented by binary strings. And binary strings are really integers. Thus it makes sense to talk about the ith string for any I. However, we have to be careful how we do the conversion from binary strings to integers. Because binary strings can have leading zeros, there is not a unique representation of an integer as a binary string. More to the point, if you do the obvious conversion, then strings like the ones shown all seem to be the integers 5. But we can't call 2 or more different strings by the same integer. However, there is a correspondence between binary strings and integers that is one-to-one and almost as simple. Put a 1 in front of any binary string and then treat it as an integer. This way, no two strings can correspond to the same integer. For example, if we're given string 101, then put a 1 in front of it and treat 1101 as a binary integer, and you'll get 13, by the way. If you put a 1 in front of 0101, then this integer is 21, and so on. For a wilder example, consider images as a data type. There are many representations of images. Let's talk about GIF. A GIF file is an ASCII string, so convert ASCII to binary, and then the binary string to an integer in the way we just discussed. And bingo, you have a notion of the ith image. Here's another wild example, proofs. A proof can be viewed as a sequence of expressions or assertions in mathematical form, each of which is either given or follows from previous statements in the sequence by certain logical rules. We can encode mathematical expressions in Unicode. It has pretty much any symbol you would use in mathematics. But we can convert any expression to a binary string and thus to an integer. There is again a small glitch. A proof is a sequence of expressions, not a single expression, so we need to fix on a way to separate a sequence of expressions. We also need to indicate whether an expression is given or follows from previous expressions. We thus need to introduce two new symbols into our strings. One is a comma to separate expressions. We can't just use the Unicode comma because the expressions themselves may use this symbol. The other is a marker that says, this is a given expression. The following technique is useful not only here, but in general as a way to introduce new symbols with any meaning into binary strings while still keeping the strings binary. First, given a binary string, expand it by inserting a 0 in front of every bit of the string. For example, 101 becomes 01, that's the first one, 00, that's the 0 in the middle, and then 01. Now, as a consequence of this change, strings have no consecutive ones. Use strings of 2 or more ones as the new symbols. For example, we'll use 111 to mark a given expression and 11 as the marker for the end of an expression. Here's an example of what a proof as a binary string could look like. The initial 111 can only mean that the expression to follow is a given expression. Here is the expression itself. It was originally 101, but we expanded it with a 0 in front of each symbol. Of course, 101 is too short to really be an expression, since even one Unicode character takes 16 bits, but let's not worry about that. This 11 marks the end of the first expression. Notice that this 1 cannot be part of a special marker, since all expressions without the special markers have even length, and this 1 is the 6th symbol in the expression. Here's another given marker. And another expression. This one was 0011 with zeros embedded. And another expression ender, and so on. As we said, programs in a language like C or Java are also a data type and can be represented by integers as if they were data. First, represent the program as an ASCII string or in some other alphabet like Unicode if the language requires it. Then convert the character string to a binary string and then to an integer. Now we can talk about the ith program. And this should worry you. There really aren't more programs than there are integers. While that number is infinite, you may be aware that there are different orders of infinity, and the integers are the smallest one. For example, there are more real numbers than there are integers, so there are more real numbers than there are programs. That immediately tells you that some real numbers cannot be computed by programs. We'll get to more concrete explanation of what the dearth of programs really means shortly. We have an intuitive notion of when a set is finite or infinite. A set is finite if there is a particular integer that is the count of the number of members of the set. The term for the count of the number of members is cardinality. For example, a set containing A, B, and C is a finite set, and its cardinality is 3. The formal definition of a finite set is one for which it is impossible to find a one-to-one correspondence between the members of the set and a proper subset of that set. Well, actually, the formal definition of an infinite set is one for which there is a one-to-one correspondence between its members and a proper subset. Then the finite sets are formally the sets that are not infinite. For an example, the positive integers are an infinite set. We can let the proper subset be the even integers, and the one-to-one correspondence matches 1 with 2, 2 with 4, 3 with 6, and so on. Every positive integer I is matched with a unique even integer 2i. A countable set has a one-to-one correspondence with the positive integers. For example, the set of all integers, positive or negative, is countable. A correspondence maps 0 to 1, minus I to plus 2i for all I equal to or greater than 1, and plus I to 2i plus 1 for all I equal to or greater than 1. As a consequence, the positive and negative integers get interleaved in the ordering as 0, minus 1, 1, minus 2, 2, and so on. The binary strings are also countable. We saw how to assign a unique positive integer to each binary string by putting a 1 in front and treating the result as a binary integer. Likewise, the Java programs can be put in one-to-one correspondence with binary strings and then with integers. Many of these integers represent flawed Java programs, things that don't compile, but that is not important. The important thing is that every working Java program has a unique integer. A rather surprising point is that pairs of integers can be put in one-to-one correspondence with the integers themselves. A simple way to see this is to explain an ordering of the pairs as first pair, second pair, and so on. The ordering we want is first by sum, and then for pairs with the same sum by first component. Thus, 1, 1 comes first. It is the only pair with a sum of 2. There are 2 pairs with a sum of 3, these guys, and we put 2, 1 ahead of 1, 2 because it has the higher first component. Then come 3 pairs with sum 4, these 3, again ordered by the first component. You can, in fact, figure out a function f of ij such that the pair ij is the f of ijth in that order. But the important point is that some such function exists, and therefore it makes sense to talk about the ith pair of integers. We call the one-to-one correspondence between a countable set and the positive integers an enumeration of the set. Thus, strings, programs, proofs, and pairs of integers, for example, have enumerations. Now, let's look at the set of all languages over some fixed alphabet, say 0, 1. Could this set be countable? The answer is no, and we can prove it. Suppose it were possible to enumerate the languages so every language over 0, 1 was the ith language for some I. We already know how to enumerate binary strings, so we can talk about the ith binary string. Now, I'm going to define a language L. L is the language containing those binary strings W, such that W is the ith binary string. That must be true for some I, and W is not in the ith language. L is surely a language over alphabet 0, 1. Since we are assuming that the languages over 0, 1 are enumerable, that means that for some j, L is the jth language. So let x be the jth string. Surely some string is the jth in the enumeration of binary strings. Now we can ask, is x in L? It turns out that if it is, then it isn't, and vice versa. To see why, remember the definition of L. L contains W if and only if W is not in the language that corresponds to the same integer I that W corresponds to as a string. So let's focus on the case where W is x, the jth string. In that case, the value of I is j because we know x is the jth string. Further, we know that L is the jth language, so both L, the language being defined, and the, quote, ith language mentioned in the definition of L are all the same, and they are LJ. Thus, when we read the definition of L as it applies to X, it says that X is in L, which is L sub J, if and only if X is not in L, again, which is L sub J. We have a contradiction. X is neither in L nor not in L. That's an impossible situation, and we conclude that our assumptions are wrong. The only unproved assumption we made was that we could enumerate the languages over 0, 1, so that is false. We can't enumerate such languages. As a result, we see that there are more languages than programs, since the programs can be enumerated. A particularly bad consequence of this fact is that there are languages for which no program can tell whether or not a given string is in the language. On the bright side, none of these strange languages are context-free, or therefore not regular, since the CYK algorithm gives us a membership testing program for any context-free language. The process of coming up with the language L that can't be in any enumeration is called diagonalization. The reason should be apparent from this picture. Imagine an infinite matrix in which the rows correspond to languages and the columns to binary strings. A 1 in the entry for row I and column J means that the jth string is in the ith language. 0 means it is not. If we could enumerate languages, then we could create such a table. Look at the entries along the diagonal and complement each one. That is, replace 0 by 1 and vice versa. Here's what it looks like. The complemented diagonal, rotated 45 degrees, looks like a language. It tells which strings are its members. Here, strings 1 and 2 are not in the language, the third and fourth are, and so on. But this language cannot be any row because it disagrees with each row in at least one position. In particular, it disagrees with the ith row in the ith position. We're now ready to look at the theory of Turing machines. One important purpose of this theory is to prove certain particular languages to have no membership algorithm. The first step is to prove certain languages about Turing machines themselves not to have membership algorithms. We're then going to introduce the important notion of a reduction from one problem to another. These are proofs of the form: if there is an algorithm for problem P, then there is an algorithm for problem Q. We'll draw this as Q is reduced to P. If we already know that there's no algorithm for Q, then how could there be an algorithm for P? Because if there were an algorithm for P, then this reduction would give us an algorithm for Q. Okay. By use of reductions, we don't have to resort to diagonalization or another trick to prove that P has no algorithm. Here is the picture of a Turing machine we should keep in mind. There is a state which, like all other automata, can only be in one of a finite number of states. There is a tape, this, infinite in both directions and partitioned into squares, each of which can hold a symbol of a finite tape alphabet. There is a tape head that always points to one of the tape squares. The Turing machine makes moves just like the finite automaton or pushdown automaton. For the Turing machine, the move is determined by the state and by the tape symbol under the tape head. In one move, the Turing machine can change its state, write a new tape symbol over the old one in the square its head is scanning, and move the head one square left or right. We might ask why we introduced the Turing machine rather than representing computation by C programs. While you could develop a theory around programs without using Turing machines, it would be much harder. The thing that we'll come to appreciate about Turing machines is that they are so simple in their operation compared to programs in a programming language or even real computers. That wouldn't matter if Turing machines could not mimic real computers, but they can, as we shall argue. And in fact, one could argue that because Turing machines have infinite storage capacity on their tape, they are even more powerful than computers, since computers always have a finite amount of storage, however large that may be. But the difference is not essential, since in principle, We could always buy more storage for a computer. One could counter-argue that the universe is finite, so where are you going to get the atoms from which to build all those disks? But even if you accept that the universe is finite, the limitation doesn't seem to be affecting what we can compute in practice, so we're never going to argue that a computer is weaker than a Turing machine in a meaningful way. So here's the formalism we'll use for Turing machines. There's a finite set of states, and we'll follow our tradition of using Q for this set. There's a finite input alphabet for which we use the traditional sigma. There's a finite tape alphabet, gamma, which always includes the input alphabet. The transition function is, as always, delta, and we'll talk about how that works next. There's a start state Q0, a member of the set of states Q. Again, this is as before. There's a blank symbol, which we usually represent by capital B. This symbol is in the tape alphabet, but is never an input symbol. And there's a set of final states, F as usual. And there are several conventions about letters we shall use. They are consistent with our earlier conventions for finite and pushdown automata. Lowercase letters at the beginning of the alphabet are still symbols of the input alphabet. Now, capital letters at the end of the alphabet are tape symbols, which might or might not be input symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Again, that's as usual. And Greek letters at the beginning of the alphabet are strings of tape symbols, which again may include some input symbols. Now let's see the transition function delta for a Turing machine. The Turing machine is deterministic, and moreover, it does not have to have a move in any situation. Delta takes two arguments, the state and the symbol scanned by the tape head. Delta of QZ, for state Q and tape symbol Z, can be undefined, in which case the Turing machine can make no more moves scanning a Z in state Q, and the Turing machine is said to halt. But if delta of Q and Z is defined, then it is a triple PYD, where P is the new state, Y is the symbol that replaces Z in the square being scanned on the tape head, and D is the direction for the tape head to move. This direction is either L for left or R for right, and the move is by one square. Here's an example of a Turing machine. Its input symbols are 0 and 1. The Turing machine scans right on its input looking for a 1. If it finds a 1, it changes it to 0 and goes to a final state F and halts. However, if it sees the blank symbol before seeing a 1, it changes the blank to 1 and moves one square left, repeating the process just described. There are two states for our Turing machine, Q and F. Q is the start state and F is the final state. As we mentioned, the input alphabet is 0, 1. The tape symbols are only 0, 1 and the blank B. One move of the Turing machine is given here. It says that in state Q, scanning a 0, in state Q scanning 0, it stays in state Q, leaves the 0 on the square it was scanning, and it moves right. Another rule says that if it is in state Q and sees a 1, it goes to final state F, replaces the 1 by a 0, and moves right. It doesn't matter which way the head moves in this situation since it has accepted its input, but it always has to move left or right, so we'll say right. The last move of the Turing machine is this. It says that in state Q, while scanning a blank, it replaces the blank by 1 and moves left, staying in state Q. Here's the beginning of a moving picture of this Turing machine. The three moves are shown in the upper right, with the move that is applicable in a given situation shown in red. Here, the Turing machine has just started. It is in its start state, and the tape head is at the left end of the input, which is 0, 0 in this case. That is, here's the input. The rule in red says that in state Q, scanning 0, it moves right and leaves the state and symbol unchanged. So we'll see that on the next slide. Here it's done that, and it is in the same situation, again scanning a 0, so it again moves right. Now it sees a blank on its tape, so another rule is applicable. This rule says that stay in state Q and replace the blank by 1 and move left. So it's made those changes, and the first rule is applicable again. The Turing machine is going to move right while leaving the state and symbol unchanged. Here the second rule applies. In state Q, it is scanning a 1, so it goes to the final state F, replaces the 1 by 0, and moves right. Here we see the effect of the last move. The Turing machine has no move for when it is in state F scanning a blank, so it halts. It has also accepted since F is a final state. Moving pictures of a Turing machine can get a bit cumbersome, so we're going to develop an instantaneous description, or ID notation, for Turing machines similar to what we use for pushdown automata. But in a sense, the Turing machine IDs are even simpler because the input and tape contents are combined into one string. Moreover, we represent the state and the head position by embedding the state to the left of the symbol being scanned. We'll always assume that state symbols are chosen so they do not conflict with tape symbols, and thus we can always tell which symbol is the state. As we suggested in our little example, the Turing machine gets its input on the tape. The input, which is always a string of input symbols, is placed on the tape surrounded by an infinity of blanks to the left and to the right. The Turing machine begins in its start state with the head at the leftmost input symbol. If the input string happens to be epsilon, then the Turing machine's tape is entirely blanks and the head is scanning one of them. An ID is a string of the form alpha, q, beta. Here, alpha beta is the contents of the tape between the leftmost and rightmost non-blank symbols. That is, the tape consists of an infinity of blanks, alpha, beta, and then another infinity of blanks. We should observe that after any finite number of moves, the Turing machine has only visited a finite number of tape squares, so there can only be a finite number of non-blanks. Thus, we always have a finite representation for the tape, even though it is infinite in extent. The state is Q, and it is placed immediately to the left of the symbol the head is now scanning. Remember, we assumed state symbols are chosen, so none of them are tape symbols. Therefore, we can always identify Q. As a special case, Q can be at the right end of beta. If so, it means that the symbol being scanned is a blank. This can only occur if the Turing machine has just moved to the right and there are only blanks to the right. We use the turnstile notation, that is this, to represent one move, and we use the turnstile star, this, to represent any number of moves, including 0 moves. These are exactly as for PDAs. Here's an example which corresponds to the earlier Turing machine example, but now using the ID notation. We start off in the start state with the state to the left of the input. At the first move, the Turing machine moves right, here, and then right again. Now it is scanning a blank, and its action was to replace the blank by a 1 and move left. Notice that the state is now 2 symbols to the left of the end, and it's scanning what used to be the rightmost 0, that is this guy. It again moves right, and when it sees the 1, it enters state F and again moves right, changing that 1 to a 0. Now we'll discuss the turnstile relation formally. We have to discuss what happens on rightward moves separately from what happens on leftward moves. So suppose there is a right move where in state Q, scanning a Z, the Turing machine goes to state P, writes Y, and moves right. Then in any ID with QZ as a substring, which means that the Turing machine is in state Q and the Z is being scanned, we can replace QZ by YP. That has the effect of moving the head right, as well as making the state and symbol changes called for. There's a special case when Z is blank. Then it is additionally possible that from an ID with Q at the right end, that is this, which means that a blank is being scanned, for the next ID to replace the Q by YP. That is, the blank which we didn't see in alpha Q has been replaced by Y, that's here, and the state Q became P, P of course moving to the right of the Y that it just wrote. Now consider a left move, where again we are in state Q scanning Z. The new state will be P, and the symbol Y will be written over the Z. If there's any symbol X to the left of the state in the current ID, such as this, then in the next ID, the Z is replaced by Y, and the XQ is replaced by PX. That means that X is being scanned in the next ID. And of course, we have gone to state P from state Q. But we also have to take care of the case where the ID has nothing to the left of the state, which means that there is an infinity of blanks to the left of the present head position. Then we reflect the move by replacing the Z by Y, that's that, and introducing a blank to be the symbol immediately to the right of the state. It's okay if the ID represents a blank explicitly, and this is one of several situations where we have to do so. However, it is important to note that the length of the ID can only grow by 1 at each move, so it remains finite after any finite number of moves. There are actually two ways to define the language of a Turing machine. Final state is one of these ways, of course. Formally, L of M for a Turing machine M is the set of strings of input symbols W, such that started in the initial ID, that's Q0 W, with W on the tape, M gets to some ID with a final state. The other way to define a language is by halting. We define H of M to be the set of input strings W such that started in the initial ID again. M gets to some I for which no move is possible. The two methods of defining languages define the same class of languages, as we can show by simple Turing machine constructions that are not too different from how we show that PDAs accepting by final state and by empty stack have the same language defining power. Given a Turing machine M, we're going to modify M into a new Turing machine M prime. The language M prime accepts by final state, M prime will accept by halting. We can easily make the final states of M be halting states by removing the rule for delta of Q and X whenever Q is a final state. But we have to protect against the possibility that M halts without accepting, because that M prime would then accidentally accept. So for M prime, we introduce a new state S whose job is to make sure M prime never halts. Once M prime is in state S, on any tape symbol X, M prime stays in state S, leaves the X as it is, and moves right. Thus, M prime will always have a next move in state S. Eventually, it will get to the infinity of blanks to the right on the tape and look at them one at a time. And to make sure M prime doesn't halt accidentally, whenever delta of Q and X is undefined for M, and Q is not a final state, we'll have M prime enter the state S. The construction in the other direction is also pretty easy. Now we assume M accepts some language L by halting, and we want to modify it to become M double prime, which accepts L by final state. We introduce a new state F, which is the final state of M double prime. F has no move, so in fact M double prime will also halt when it accepts, but it doesn't matter. Once a Turing machine enters a final state, if acceptance is by final state, then nothing it does in the future will negate the fact that the input was accepted. If M halts in any situation, that is, delta of Q and X is undefined, then define it and make the next state be F. We now have a proof that the class of languages accepted by Turing machines using final state is the same as the class of languages accepted by Turing machines using halting. The name for this class of languages is the recursively enumerable languages. You might rightly wonder where this name came from. It actually predates Alan Turing's paper describing Turing machines, and it refers to an earlier notion of anything we can compute. I'm not going to say more about that. But there's another important class of languages related to Turing machines. These are called the recursive languages. These, we shall see, are a proper subset of the recursively enumerable languages. An algorithm, formally, is a Turing machine accepting by final state that halts on any input regardless of whether that input is accepted. This notion of an algorithm is consistent with the informal notions you may have learned. However, it is limited to acceptance or rejection of input. That is, all algorithms in this sense render a yes-no decision, but do not compute an output. We can extend the notion of what a Turing machine does to allow it to produce output and then halt, in which case we have exactly the same notion of algorithm that is taught in freshman computing. A language that is accepted by final state by some algorithm is called a recursive language. This term, too, comes from the history of attempts to answer the question, what can we compute, prior to Turing's insights. For example, every context-free language is a recursive language. You can implement the CYK algorithm for any context-free language on a Turing machine. That Turing machine will halt once it has computed the triangle of sets of variables and checked whether the start symbol of the grammar is in the final set. But the recursive languages go way beyond the context-free. In fact, it is very hard to come up with a language that is not recursive, except by using tricks like the diagonalization we discussed earlier. Now we're going to explore the Turing machine in some depth. We start off with what I like to think of as programming tricks for Turing machines. It's not that anyone is really going to program a Turing machine, but we need to argue about what a Turing machine could do if we really needed to have it do it. That is how we argue about the capabilities of Turing machines. For example, we argue that it can simulate a real computer. Then we delve into the matter of Turing machines with less capability, but the same ability to define exactly the recursively enumerable languages. And we argue that some natural extensions of the Turing machine idea, for example, make them non-deterministic, do not add power. They still accept only the recursively enumerable languages. The conclusion I want to draw from these restrictions and extensions is that the class of recursively enumerable languages is really an important class with many definitions, and that it really does represent what can be computed by any realistic notion of what computation means. And finally, we'll look at some of the closure properties of recursive and recursively enumerable languages. The first programming trick is thinking of the tape as if it had multiple tracks. This idea enables us to describe Turing machines that do things like leave markers on their tape so they can find their way back to an important place. We get k tracks if we think of each tape symbol as a vector with k components, each component chosen from some finite alphabet. We can think of the ith component of each tape symbol as forming the ith track. Input symbols will have the blank symbol in all components but one, which then becomes the track on which the input is placed. Here's how we can visualize a Turing machine with 3 tracks. This symbol is viewed as the vector xyz, but it is really just one tape symbol. Let's suppose the input is written on track 1. Then the input symbol 0 must be thought of as the vector 0 blank blank. And the blank symbol is thought of as the vector blank blank blank. A good use of the idea of tracks is to use one track for data and another track for marks. In the marking track, almost all the tape squares have a blank value, but one or more have special symbols, the marks, that indicate a place on the tape that the Turing machine needs to find later. Here's an example. The bottom track holds the data and the top track is the marking track. This symbol xy represents a marked y. And these symbols are unmarked w and z respectively. A similar trick is to think of the state as a vector, with each component from some finite alphabet. The first component is used to control operation, what we normally think of as the state. But other components are used as a cache to hold values the Turing machine needs to remember. Typically these values are bits or tape symbols, but they can be anything as long as they are chosen from a finite alphabet. Here's an example that will illustrate the 3 tricks we talked about. The Turing machine is not really useful. All it does is copy its input over and over again, moving right on the tape. Here are the values that will appear in the control component of the state, along with the intuition about what they're supposed to be doing. In control state Q, we mark the current position, store the current input symbol in the cache component of the state, and move right. From Q, we also enter the control state P. In state P, we run to the right looking for a blank. When we find it, we deposit the symbol that we've stored in the cache on the data track, and then we move left. From state P, we also enter control state R, in which we run left looking for the mark that was left by state Q. When we find it, we remove the mark, enter state Q, and repeat the process with another symbol. A state is a vector of the form little x, capital Y. Here little x is Q, P, or R, one of the control states, and Y is the cache component. Its values are 0, 1, or B. Incidentally, we shall see that the only state P uses 0 or 1 in the cache. The other two states just have the blank in the cache. Thus, there are really only 4 states. Tape symbols will be vectors UV. The first component represents the marking track, so U is either X, the mark, or a B, which is no mark. The second component is the data track, so V can be either 0, 1, or B. We regard BB as the blank symbol, B0 as input symbol 0, and B1 as input symbol 1. We'll now describe the transition function of this Turing machine. But before we do, let's understand that A and B can each have the value 0 or 1, but in a rule, all occurrences of one of these letters has the same value. Thus, this is a pair of rules, one for each value of A. It says that if the control state is Q, copy whatever symbol A is on the data track into the cache. That is, this guy winds up here in the cache. The position under the head is marked X, as we see here. And the head moves right, and the control state becomes P. There are 2 families of rules for control state P. If the current tape symbol does not have a blank in the data track, then stay in the same state, leave the tape symbol as it is, and move right. Note that A and little b can represent either 0 or 1 independently, so there are really 4 rules represented here. When the blank symbol BB is reached, place the symbol A that is in the cache in the data track of the square currently reached. That is, the guy in the cache winds up in the data track. Go to control state R and move to the left. And here are the rules for control state R. In state R, as long as we do not see the mark in the first track, we simply move left with no change in the state or the tape symbol. When we find the square that has the mark, we do 3 things. We remove the mark, we go to control state Q, and we move to the right. We'll be at the position just to the right of where the mark was. We're back in state Q, so the whole cycle will repeat again with whichever input 0 or 1 is in the next square. Here's a motion picture. We are in control state Q with an empty or blank cache, and we're at the left end of the input 0, 1. We're going to pick up the 0 for the cache and mark the current square, going to control state P and moving right. We did all that. Now we failed to see a blank in the data track, so we'll just move right again. Now we see the blank, so we deposit the 0 in the cache and go to state R and move left. Bingo! We haven't found the mark, so we'll move left again. Now here's the mark. We remove the mark, go to control state Q, and move right. And here we are in a situation similar to that in which we started. We'll pick up the 1, mark the square we're at, and move right in state P. Here we go off on another cycle. It never ends. We keep writing 0, 1, 0, 1, 0, 1, so on the data track. We're now going to start exploring restrictions of the original Turing machine model that are powerful enough to simulate the original model, and therefore also define exactly the recursively enumerable languages. Our first restriction is a minor one compared with some of the amazingly strong restrictions we're going to mention later. But this restriction is that we can assume the tape is infinite to the right of the input only. Tape squares to the left of where the input is placed do not exist and may not be used. The Turing machine halts if it tries to move left into a non-existent square, but we shall see that in the construction that simulates a two-way infinite tape by a one-way infinite tape, that it is also possible to design a Turing machine so it never makes that mistake and never falls off the tape. Suppose we have an ordinary Turing machine with a two-way infinite tape. We want to simulate it with a one-way infinite tape. So let's call the initial position of the head square 0. Positions to the left are -1, -2, and so on, heading left, while positions to the right are +1, +2, and so on. The new Turing machine will have 2 tracks on its tape and never move left from position 0. The top track holds the positions 0, 1, 2, and so on of the original Turing machine. And in the bottom track, paired with position 0, is a special marker, a star. It is the presence of this marker that warns the new Turing machine never to go left from that point. Also on the bottom track are all the negative positions of the original Turing machine with position -I paired with position I. That is, the bottom track holds the tape to the left of position 0, but backward. Here's a picture of the new Turing machine. Its state holds the state of the original Turing machine plus a bit, U or L, that tells it whether to look at the upper or lower track to simulate a move of the original. When that bit is U, the new Turing machine moves its head in the same direction as the original, but if the bit is L, then it moves in the direction opposite to that of the original. At the first move, the marker star will be placed on the lower track. However, there is no need to modify the input symbols, since the negative positions of the original Turing machine initially hold blank, and we can treat each of the input symbols and the blank of the new Turing machine as if they had a second component that is blank. There are several other restrictions that are discussed in the text, but we're not going to cover here. It might be surprising, but if you give a pushdown automaton, even a deterministic pushdown automaton, a second stack, then it can simulate a Turing machine. The idea is that one stack holds whatever is to the left of the head, including the head position itself, with the top of the stack at the right end of the string. The second stack holds what is to the right of the head position, with the top of the stack at the left end. The 2-stack PDA can figure out a move of the Turing machine. If the head moves left, then a symbol is popped off the first stack and pushed onto the second. If the head moves right, then the top symbol is moved from the second stack to the first. Moreover, an even stronger restriction on the 2-stack PDA can be made in addition to determinism. The 2 stacks can each be a counter, that is, a stack that has only 2 stack symbols. And one of these symbols, the bottom marker, can only appear as the bottom symbol. Thus the stacks each act like counters. You can add one or subtract one, but you can only tell when the count is 0. You can't tell one large count from another. This comment speaks for itself. The guy who discovered this construction that lets 2 counters simulate a Turing machine was Patrick Fisher. He was one of the really early computer science professors and apparently attracted the attention of the Unabomber. Pat was sent an exploding package which was opened by his secretary, who was injured in the blast but fortunately survived. Now we're going to look at several extensions to the basic Turing machine that we've described. These extensions have some use when we talk about closure properties of the recursively enumerable languages, but mainly they are considered to convince you that the basic Turing machine is good enough. It captures all of what we might think of as computing by any means. That is, our goal is to simulate each of the extensions with the basic model, and thus to show that the extensions define only the recursively enumerable languages. Our first extension will allow any finite number of tapes. Then we add non-determinism. The last extension is really a demonstration of how a Turing machine can simulate a name-value store. That is, a storage system that lets us associate any value with any name. Recently, very large-scale name-value stores have become a significant factor in the big data world, with systems like Google's Bigtable. However, our purpose here is more mundane. A name-value store is the hardest part of a computer to simulate. In essence, the memory hierarchy of a computer can be thought of as a place where we store values and locations, whether the locations are memory addresses, cache addresses, or block numbers on a disk. If we can show how a Turing machine simulates a general name-value store, then we should have a good idea of how the Turing machine can simulate a real computer. A multi-tape Turing machine has k tapes for some fixed k. There is one head for each tape, and each head is positioned at one square of its own tape. To determine a move of the multi-tape Turing machine, we have to look at the tape symbol under each head as well as the state. And the action of the multi-tape Turing machine consists of a new state, a new symbol for each tape square that is scanned, and a direction for each of the heads. The heads move independently, and some heads may choose to stay where they are rather than move at a step. To simulate k-tapes, we'll use a Turing machine with a single tape, but we'll regard this tape as having two k tracks. K of the tracks are used to simulate each of the k tapes, while the other k tracks are used to mark the head position of each of the tapes. That is, these tracks are blank except for a single X in one of the squares. Here's a picture of a one-tape Turing machine simulating a two-tape Turing machine. There are 4 tracks. 2 of these tracks hold the contents of the 2 tapes, while the other 2 tracks hold only a single X each, marking the positions of the 2 tape heads. That is, the 2-tape Turing machine has the head of its first tape scanning this C, and the head of its second tape is scanning this W. I hope it is clear that the ordinary Turing machine can, to simulate one move of the 2-tape Turing machine, visit each of the X marks, store the symbols that the 2-tape Turing machine sees in cache components of its own state, and finally figure out the move of the 2-tape machine would make. The 1-tape machine then visits each of the positions with the X's again, changes symbols as the 2-tape machine would, and moves the X's to reflect the head moves of the 2-tape machine. The 1-tape machine needs to be careful to remember in a component of its own state how many X's are to its left, so it can always find them all on its own tape. But if we design the 1-tape machine to do that correctly, then it is possible for it to simulate the 2-tape machine, although it will obviously take many of its own moves to do so. Now let's look at the non-deterministic version of a Turing machine. We'll talk only about 1-tape non-deterministic machines, but the addition of several tapes along with non-determinism doesn't add power either. The basic idea is that the Turing machine is allowed to have more than one choice of move for any state tape symbol pair. Once a choice is made, then the next state, new symbol, and head direction are determined. That is, you may have several choices in the non-deterministic Turing machine, but you can't pick a state from one, a symbol from another, and a direction from the third. As for the non-deterministic finite automata and pushdown automata, the non-deterministic Turing machine is said to accept if any sequence of choices leads to an ID with an accepting state. The basic trick is to use the tape of the deterministic machine to represent a queue of IDs of the non-deterministic machine. The deterministic machine will make a systematic search of all the IDs the non-deterministic machine can reach. If it finds one with a final state, then the deterministic machine accepts. But if it never finds one, the simulation may go on forever, but the deterministic machine will never accept. Incidentally, we should start to become aware of a surprising behavior of Turing machines. Sometimes they run forever without accepting or halting. Moreover, we can't tell whether the Turing machine is going to do that or whether it will eventually halt, either accepting or not. That is, you can't tell whether a Turing machine is an algorithm. Anyway, back to our description of how the deterministic Turing machine simulates the non-deterministic. The deterministic machine needs a separate track in addition to the track that holds the IDs of the non-deterministic machine. One purpose of this track is to mark the ID that is currently at the head of the queue of IDs. And we need another mark whose job is to allow the deterministic machine to make a copy of the ID at the queue head, one symbol at a time, while it changes this ID to reflect one of the choices of moves of the non-deterministic machine. Here's a picture of what the tape of the deterministic machine looks like. On the data track, there is a sequence of IDs separated by a special symbol, £, which we assume is not a symbol that can appear in the IDs themselves. The mark X is at the £, just before the ID that is at the head of the queue. The IDs to the left of this point will never be useful again since they have already been processed, but it is more trouble to erase them from the tape than it is to just leave them there. The mark Y indicates the last position of the front ID that has been copied, with one choice of move of the non-deterministic machine. The deterministic machine will run back and forth between the Y and the first blank it sees to its right, storing the symbol under the Y in its state and depositing it at the first blank. When it returns to the Y, it moves the Y one position right until it has copied the entire ID. However, making the changes that reflect one move. The process is just a little more complex than the simple Turing machine we gave as our example of the use of multiple tracks, which ran back and forth copying its input. Here's how the deterministic machine processes the front ID on the queue. First, the deterministic machine looks for the state within the front ID. By storing the state and the symbol to its right in its own state, it now knows all the choices of moves for the non-deterministic machine. Suppose there are m choices of move. Then the deterministic machine will create m new IDs at the rear of the queue, that is, to the right of the portion of its tape currently holding IDs. The deterministic machine decides on an order for the m choices and creates an ID reflecting each choice one at a time. After creating all m, it finds the x marker and moves it to the pound sign to the right, thus moving to the next ID in the queue. However, as an exception, if the deterministic machine ever creates a new ID with an accepting state, then it accepts and halts its operation. I described the workings of the deterministic machine fairly informally, but I hope you are convinced that the deterministic machine really could be programmed to do what I suggested. That is, you could write down a delta transition function that did all the things I talked about. However, there is an additional concern that must be addressed. Can we be sure that if any sequence of choices by the non-deterministic machine leads to a final state, then the deterministic machine will eventually follow each ID in the sequence and thus will also accept? To prove that, we first observe that there is an upper bound, say k, on the number of choices of move that the non-deterministic machine has in any situation. Thus, there are at most k IDs reachable after one move, k squared reachable after 2 moves, k cubed after 3 moves, and so on. Suppose the final state is reached after n moves for some n. Then the number of IDs the deterministic machine might have to look at is at most this, which is the sum of the first n powers of k, before it sees the ID with the final state. The exact formula is not important. The point is that k is finite and n is finite, so the number of IDs examined is finite. To see this point, notice that all the IDs reachable after one move are put on the queue before any ID that is reachable by 2 moves, and all the IDs reachable by 2 moves are placed there before we get to any ID that takes 3 moves to reach, and so on. That is, the queue is organized shortest distance first. To summarize, if the non-deterministic machine accepts, it does so in n moves for some finite n. Therefore, the deterministic machine will eventually construct the accepting ID of the non-deterministic machine, even though it may take a number of its own moves that is exponential in n. However, if no sequence of non-deterministic choices leads to acceptance, then the deterministic machine does not accept. Thus, the two machines define the same language. All the constructions we just showed will turn out to be quite useful in the future. We're going to have to do several important constructions involving Turing machines. When we do that, we'll assume the Turing machine that is input is as simple as possible. In particular, we'll assume it is a deterministic machine with one tape, infinite only to the right. However, when we do the simulation, we're free to use a Turing machine that is as powerful as we need. In particular, we can allow it to be non-deterministic and to have as many tapes as we need. But first, let's take up how we simulate name value stores by a Turing machine. The Turing machine will have several tapes that we'll describe later, but one of the tapes is used to hold the sequence of name value pairs. As suggested here, the format we use is to separate pairs by pound signs and to separate the name from the value by a star. We assume neither pound nor star are symbols that can appear in any name or value. A second track of this tape will be used to mark the left end of the sequence. This mark never moves, it's just there so we can find the beginning of the sequence and scan it looking for a particular name. A second tape will be used to hold the name that we want to look up. To look up the value associated with a name, use the marker to find the left end of the store. Compare each name with the name on the second tape. If we find a match, then the associated value is between the star and the next pound sign. However, one operation we need to be able to perform on a name value store is insertion. This operation is like what happens when we store into a computer's memory. When we insert name value pair NV, if there was no value previously associated with name N, then V will now be associated with N. However, if there was an old value associated with name N, then that value is replaced by V. Regardless of which case applies, the first thing we need to do is to look up the name N using the second tape to hold N as we just discussed. If we scan the entire store and we never find N, then append N star V pound sign to the right end of the store. That is a true insertion rather than a rewriting of a value. But if we find some NV prime in the store, we have to replace V prime by V. If V is shorter than V prime, then you can leave blanks to fill out the value. But the hard case is when V is longer than V prime. Here we have to shift the entire portion of the store that follows far enough to the right to make room for V. Here's how we'll do it. We use a third tape and we copy the entire portion of the first tape that is added to the right of V prime. But make sure to mark the position on the first tape that holds the star to the left of the V prime. Remember, this tape has a second track for marks. Now, write V on the first tape where V prime was. It's okay to overwrite any squares to the right of where V prime was. Then we restore the first tape by copying from the third tape everything that was copied there. The net effect is that the portion of the first tape that held data to the right of V prime has been moved right as many squares as was necessary to fit V in place of V prime. Here's a picture of the sequence of moves. First, we copy everything to the right of V prime onto tape 3. Then we overwrite V on tape 1, covering anything we have to. And then we copy tape 3 onto tape 1, positioning it to the right of whatever space V has taken. Okay, now we're going to see something of the closure properties for both the recursively enumerable languages, that is those that are defined by Turing machines that may run forever if they don't accept, and the recursive languages, those defined by Turing machines that will eventually halt without accepting if they choose not to accept the input. Each of these languages is closed under the regular expression operations union, concatenation, and star. They're also closed under reversal, intersection, and inverse homomorphism. The recursive languages, but not the recursively enumerable languages, are closed under difference and therefore complementation. The recursively enumerable languages, but not the recursive languages, are closed under homomorphisms. Let's first look at closure under union. Let L1 and L2 be languages accepted by final state by Turing machines M1 and M2 respectively. To make things simple, we're going to assume that M1 and M2 are one-tape machines with a semi-infinite tape. For the language L1 union L2, we construct a Turing machine M with two tapes. The first thing M does is to copy its input from the first tape to the second. Then M uses one tape to simulate M1 and the other tape to simulate M2. M accepts if either accepts. To show that the recursive languages are closed under union, observe that both M1 and M2 will eventually halt whether or not they accept. M will accept if either does, but if neither accepts, then M will eventually halt without accepting, so M is also an algorithm. For closure of the recursively enumerable languages under union, we don't know that M or M2 may run forever if they do not accept. If either accepts, then M will surely accept. However, if neither accepts, then M may run forever. But that is okay, since we only want to prove that L1 union L2 is recursively enumerable in this case, not necessarily recursive. We're going to use picture proofs for Turing machines quite a bit. Here's how we represent an algorithm. a Turing machine that always halts. It's just a box with two output signals, accept and reject. We should understand that reject just means that the machine halts without accepting. We know that an algorithm will eventually make one of these signals, and of course not both. Then the design of M can be expressed by this diagram. It gets its input W from the outside, and it feeds it to M1 and M2, which it then simulates. M produces the accept signal if either M1 or M2 accepts. If neither produces accept, then they eventually both produce reject, and M produces the reject signal when they both do. Thus M will make one of these signals, but not both, and of course it makes the right signal to accept the union of the languages. And here's how we represent a Turing machine that is not necessarily an algorithm. It makes an accept signal if it accepts, but we cannot expect it to make a reject signal. It may just keep making moves, but never accept. This diagram is the design of M for the case where M1 and M2 are general Turing machines. Again, M feeds both the input W. If either raises the accept signal, then M does too. We have no idea what M does if neither accepts, but it doesn't matter. M has the form needed to show that the union of the languages of M1 and M2 is a recursively enumerable language. Here's a picture proof of the fact that recursive languages are closed under intersection. M1 and M2 are algorithms. We design M to feed its input to the simulated M1 and M2, and M accepts if both accept, and M rejects if either rejects. And here's a picture proof for the intersection of recursively enumerable languages. Again, M feeds its input to M1 and M2, and it accepts if both accept. Now, difference and complement give us very different stories for the two classes of languages, recursive and recursively enumerable. If you want to accept the difference of the languages of algorithms M1 and M2, simulate them both until they halt. Accept if M1 accepts and M2 rejects, and otherwise reject. The picture is much like what we saw for union and intersection of recursive languages, only the logic combining the signals is different. An important consequence is that the complement with respect to some alphabet sigma of a recursive language is recursive. Surely sigma star, the set of all strings over sigma, is recursive. So the difference of sigma star and a recursive language is the complement of that language. Unfortunately, this approach does not work for the recursively enumerable languages. They are in fact not closed under difference or complementation. We'll see a particular recursively enumerable language whose complement is not recursively enumerable soon. But just to see why the construction for recursive languages doesn't work, remember that M2 may never halt. So if M1 accepts, we may never know that the input is in the difference. Now let's show that the recursively enumerable languages are closed under concatenation. Let L1 and L2 be defined by Turing machines M1 and M2. Assume M1 and M2 have one semi-infinite tape each. And for concatenation, we're going to construct M, a two-tape non-deterministic Turing machine. Given input W, M guesses a prefix X of W, that is in L1. Then let Y be the remainder of W, which then must be in L2, if that is, if W is to be in the concatenation of the languages L1 and L2. M moves Y to its second tape. M simulates M1 on input X and M2 on Y. If both accept, then M accepts. Since it is non-deterministic, it will guess every possible way to break W into two pieces. So it always accepts W if W is in L1 concatenated with L2. Next, we claim the recursive languages are also closed under concatenation. We can't use the non-deterministic trick, or at least it's rather hard to do so. However, M will systematically try each possible breakpoint for W into X, Y. Run M1 on X and M2 on Y. M1 and M2 always halt on each X and Y. If for any breakpoint both accept their pieces, then M accepts. But if all breakpoints lead to rejection by one or both of M1 and M2, then M eventually runs out of things to try and rejects. For closure under star, the same ideas work as for concatenation. Suppose M1 is a Turing machine for some language L, and we want a Turing machine for L star. For the recursively enumerable languages, guess how many pieces to break input W into, and guess where the points of separation are, except if M1 accepts each piece. For the recursive languages, don't guess, but enumerate the breaks systematically. Since M1 is guaranteed to halt anytime it is given a piece of the input W to examine, we'll eventually get through testing each of the possible ways to break the input. Reversal is easy for both classes of languages. First, reverse the input and then simulate the Turing machine for language L on the reversed input. We'll not say anything more about this simple idea. Inverse homomorphism is also quite simple. Suppose L is a language, either recursive or recursively enumerable. Let M be a Turing machine for L and let H be a homomorphism. We'll design a Turing machine for H inverse of L. We'll start by applying H to the given input W. Simulate M on H of W. Accept W if H of W is an L. If L is recursively enumerable, then we've got a Turing machine which may not always halt for H inverse of L. But if L is recursive, then we know M will always halt, and thus so will the machine we just designed. Last, let's show that the recursively enumerable languages are closed on their homomorphism. So suppose L has a Turing machine M1. We'll construct a non-deterministic Turing machine M for H of L. Given input W, M guesses a string X and checks that H of X is W. If so, M simulates M1 on input X. If M1 accepts X, then M accepts W. Thus, M accepts H inverse of L. This construction won't work for the recursive languages. The reason is that if H maps some symbols to epsilon, then the string X that M1 accepts may be arbitrarily long, and M may have to simulate an infinite number of possible X's. It can never be sure that there is no X in L for which H of X equals W. Now we are ready to show some particular problems not to have algorithms. The central ideas for this lecture are, first, that Turing machines can be enumerated, so we can talk about the ith Turing machine. That lets us diagonalize over Turing machines the way we diagonalized over languages, showing a particular language that cannot be the language of any Turing machine. Then we establish the principle that a problem is really a language, and we show specific problems not to have Turing machines. To enumerate Turing machines, we're going to develop a specific representation of Turing machines as binary strings. It is sufficient to provide a code for Turing machines whose input alphabet is 0 or 1, although we could encode others if we wanted to. The reason it is sufficient to assume only 0 and 1 are inputs is that Turing machine codes themselves will be binary strings. So we can focus on Turing machines with input alphabet 0, 1 as inputs to other Turing machines with the same input alphabet. The first thing we need to do is to assign integer codes to the components of a Turing machine. We give integers 1, 2, 3, and so on to the states. We'll assume that Q1 is always the start state, and we'll also assume that Q2 is always the one final state of the Turing machine. Notice that once a Turing machine enters a final state, nothing further matters, so we can always merge all final states into one. Thus, we can restrict our attention to Turing machines with a single final state and know that we can still define any recursively enumerable language. The other states will be numbered 3, 4, and so on. The tape symbols are also numbered starting at 1. We'll assume x1 is always the input symbol 0, and x2 is always the input symbol 1. x3 will always be the blank, and any other tape symbols are numbered 4 and above. There are two directions, but we need to number them. D1 is left, and D2 is right. Consider a rule expressed using the integer numbering of the components. That is, the state is Qi, and scanning symbol Xj. We'll suppose the Turing machine goes to state Qk, right symbol XL, and moves in direction d sub m. Represent this rule by blocks of I, j, k, l, and m zeros separated by single ones. Notice that all the integers are positive, so the representation for a rule never has consecutive ones. We then represent an entire Turing machine by all its rules concatenated and separated by pairs of ones. Once we have Turing machines represented by binary strings, we can convert these strings to unique integers using the trick we explained a while ago. Put a 1 in front of a binary string and treat the result as a binary integer. Thus, we can talk about the ith Turing machine. And of course, we earlier learned we could talk about the ith binary string. A small matter is that some binary strings represent flawed Turing machines. For example, it might have a pair of double ones with other than 4 single ones between them. That would not represent 5 blocks of zeros and therefore would not represent any move of a Turing machine. However, let's assume any binary string that is flawed represents a Turing machine that accepts the empty language. Likewise, if I is the integer we get from such a string, then the ith Turing machine accepts the empty language. So here is a table relating Turing machines to the strings they accept. The value in row I and column j is 1 if the ith Turing machine accepts the jth string, and 0 if it does not. Notice that if the ith Turing machine is one of the flawed ones, then its rows is all zeros. Any matrix of zeros and ones with rows and columns corresponding to all the integers can be diagonalized over. That is, we can construct an infinite sequence of zeros and ones, call it D, such that the ith bit of D is the complement of the bit in position II along the diagonal. We can argue that D is not a row of the matrix and therefore does not represent the language accepted by any Turing machine. Okay. D can't be row J because it disagrees with the jth row in their jth entries. Thus, D cannot be a row, and therefore the language it describes, the language that contains the ith string if and only if the ith bit of D is 1, is not the language of any Turing machine. Notice that this language can be described as the set that contains the ith string if and only if the ith Turing machine does not accept the ith string. Let's give a name to this language, L sub D, or the diagonalization language. Again, L sub D is the set of binary strings W, such that W is the ith string for some I, and the ith Turing machine does not accept W. We just argued that L sub D is not a recursively enumerable language. That is, it has no Turing machine. We earlier proved that since there are more languages than integers, and since there are no more Turing machines than integers, we already know that there were languages with no Turing machine. But now we're much better off. We have a particular language, L sub D, and a description for this language, such that L sub D is one of the languages without a Turing machine. Note, however, that L sub D is a delicate language. We know what it is, but we can't, for example, always tell whether a given binary string W is in L sub D. To do so, we can figure out the I such that W is the ith string. That's the easy part. Then we can write down the code for the ith Turing machine. In fact, that code is W. If W is the code for a flawed Turing machine, we know it doesn't accept W. But some W's give good codes for Turing machines, and in fact every Turing machine with input alphabet 0 and 1 has at least one code W. We can't always figure out whether a Turing machine is going to accept or to run forever without accepting, so for at least some W's we can never learn whether or not that W is in L sub D. Let us introduce the formal concept of a problem. Informally, a problem is a yes-no question about an infinite number of possible instances of the problem. Here's an example of a problem that is actually quite famous, and we'll see why soon. The instances of the Hamilton cycle problem are undirected graphs. There are an infinite number of graphs, of course. The answer to the question implied by the Hamilton cycle problem is yes, if there is a Hamilton cycle in the graph that is a cycle that passes through each node exactly once. For example, here's a graph that happens to have a Hamilton cycle. It's also got some other edges here and there. But The important thing is it does have the Hamilton cycle in which every node appears once. So formally, a problem is simply a language over some alphabet sigma. Each string in sigma star can be viewed as an instance of the problem once we decide on an encoding for instances as strings. We'll see a number of examples of these encodings, but we already saw one when we encoded Turing machines as binary strings. It should not be hard for you to devise an encoding for graphs in a similar spirit. Then the language associated with the problem is the set of strings that code instances for which the answer is yes. Typically, as we did for Turing machines, our coding allows certain strings that are flawed. They don't really represent an instance. We'll always assume that flawed encodings represent instances for which the answer is no. For example, as a problem, the language LD can be stated, does this Turing machine not accept its own code? When we talk about problems, we use the term decidable. It means that there is an algorithm to answer its question. That is, a Turing machine that accepts the encoded instances of the problem for which the answer is yes, and also halts without accepting the other instances. So a decidable problem is really the same thing as a recursive language, if we think of the language as encoding a problem. The opposite of decidable is undecidable. So here's what we know about languages so far. In the center we see the recursive languages, or as problems, the decidable problems. Then there is a superset of the recursive language called the recursively enumerable languages. These, recall, are the languages accepted by Turing machines with no guarantee that they will halt on inputs they never accept. And then there is outer space, the uncountably many languages that are not recursively enumerable. They have no Turing machine at all. So far we have one example of a language, L sub D, that lives in this region. Remember that the undecidable problems are all those in either the second ring, the recursively enumerable but not recursive languages, or in outer space, that is, everything that is not yellow in this diagram. And a big question we need to answer, are there any languages in the second ring, those that are recursively enumerable but not recursive? And remember, the real goal of our plan is to show some real problems that are undecidable. The fact that L sub D is undecidable, and in fact super undecidable because it is not even recursively enumerable, is interesting, but it doesn't by itself tell us anything about the real world. So here are some examples of real problems that are undecidable. Will a program ever reach a particular line of code? Is a given context-free grammar ambiguous? Are two given grammars equivalent in the sense that they generate the same language? But still staying within the world of Turing machines rather than the real world, but a necessary way station on our trek to the real world, is to show a particular language to be recursively enumerable but not recursive. This is the language we call L sub U, the universal Turing machine language. In more detail, the universal Turing machine takes as input a binary string consisting of the code for some Turing machine M and some input W for M. The universal Turing machine accepts the coded M and W if and only if M accepts W. The idea of the universal Turing machine should not seem strange if you've ever contemplated a Java virtual machine. The JVM takes a coded Java program and an input for that program and executes the program on the input. In fact, the JVM is more general in capability than a Turing machine, which can only make a single accept output. The JVM can cause whatever output the program calls for it to be made. So let's see how to build a universal Turing machine. First of all, inputs to the universal Turing machine are of the form a code for machine M, 3 ones, and then the binary string W. Since a valid code for M can never have 3 consecutive ones, it is never ambiguous what part of the input to the universal Turing machine is M and what part is W. The universal Turing machine accepts its input if and only if that input has a valid code for some Turing machine M, and that Turing machine accepts W. So, for example, the universal machine never accepts a string that doesn't have 3 consecutive ones. We'll design the universal Turing machine as a multi-tape machine. The first tape will hold the input, and we never change that. The second tape is used to represent the current tape of M during the simulation of M with input W. We'll discuss this representation shortly. The third tape of the universal machine simply represents the state of M. The first thing that the universal machine needs to do is to examine its input, and particularly that portion that represents M. It has to check that between consecutive double ones there are always 5 blocks of zeros, and it also has to check that a block of 3 ones appears somewhere on its input, and regards this as the end of the rules for M. Finally, since M is assumed deterministic, the universal machine needs to check that there are never 2 rules that agree on the first 2 components. All this checking will require running back and forth on the input quite a bit. It can be facilitated by copying blocks of zeros onto one of the other tapes and comparing these with the rest of the representation for M. If any flaws are found with this code for M, or the 111 is not found, then M is regarded as a Turing machine that accepts nothing, so the universal Turing machine immediately halts and rejects its input. Assuming the code for M is valid, the universal Turing machine next examines the code for M to determine how many squares of its own tape it needs to represent one symbol of M's tape. That is, we discover the longest block of zeros representing a tape symbol, and add 1 to that for a marker between symbols of M's tape. Thus, if, say, x7 is the highest numbered symbol, then we'll use 8 squares to represent one symbol of M. Symbol xi will be represented by I zeros and 7 minus I blanks, followed by a marker #. For example, here's how we'd represent x5. 5 zeros, 2 blanks, and then the #. Now initialize tape 2 to represent the input W. Remember, zeros are x1 and ones are x2. The blanks on the second tape of the universal machine all represent x3, the blank of M, but we won't initialize those squares until we need to. Finally, we initialize tape 3 to hold the start state. That state is always Q1, so it is represented by a single 0. Now we're ready to simulate M. We have the current state on tape 3 and the tape of M represented on tape 2. We scan the moves of M on tape 1 until we find a move that matches both the state and this tape symbol. If we can't find one, then apparently M halts without accepting W, so the universal machine does so as well. But if we find a match, we'll find right after that on tape 1 the new state, which we install on tape 3, replacing the old state. We also find a new tape symbol with which to replace the old tape symbol under the head on tape 2. And we also move the tape head 1 simulated square of M's tape, left or right, whichever the move says. And most important, if M enters an accepting state, then the universal machine stops simulating and accepts its own input, which, remember, is the pair machine M plus input string W. We claim that the language L sub u is recursively enumerable but not recursive. We just showed that there is a Turing machine for the language L sub u, so surely LU is recursively enumerable. But suppose L sub u were recursive. That means there is a Turing machine that always halts and whose language is L sub u. If that were the case, then L sub d, the diagonalization language, would also be recursive. We're going to explain why on the next slide. But we already know that L sub d isn't recursively enumerable, let alone recursive. So let's assume that L sub u is recursive. We construct an algorithm for L sub d as follows. We're given an input W. Let's suppose W is the ith string. The first thing to do is to check whether or not W is a valid code for a Turing machine. For example, that it doesn't have 3 consecutive ones. If the code is not a valid string, then the ith Turing machine defines the empty language. That means W, the ith string, is not in the language of the ith Turing machine. Therefore, W is in L sub d. Now, suppose W is a valid code for a Turing machine. Then simulate the hypothetical algorithm for L sub u on the input W111W. That bit string represents the ith Turing machine processing the input that is the ith string. Eventually, this algorithm will halt and tell us whether or not the ith machine accepts the ith string. If the algorithm says yes, the ith machine accepts the ith string, then we say no, because that means W is not an L sub D. However, if the hypothetical algorithm says no, then we accept W, because W is an L sub D. We proved that there is no algorithm or any kind of Turing machine for L sub D. Therefore, we must blame our assumption. The only thing we assumed without proof was that there is an algorithm for L sub U. That means there really is no algorithm for L sub U. Put these facts together and we conclude that L sub U is really recursively enumerable but not recursive. So here is our improved version of the universe of languages. We still have the decidable problems, or equivalently recursive languages, in the center. Outside, there are two kinds of undecidable problems. The second ring is the languages that are recursively enumerable but not recursive. We now have a concrete example of such a problem, L sub U, the universal Turing machine language. And beyond that is the not recursively enumerable languages, of which we have one concrete example, L sub D. Now we're going to see more undecidable problems. We begin with Rice's theorem, which tells us that almost every question we can ask about the recursively enumerable languages is undecidable. And we then introduce a problem called post-correspondence problem, which we also show is undecidable. Post problem does not appear to have anything to do with Turing machines, so the fact that we can show it as undecidable is a valuable step on our road toward showing real problems undecidable. However, post problem is still just a game, but we can use post problem to show some real problems, for example, questions about grammars, to be undecidable. We'll first see Rice's theorem. That theorem involves what are called properties of languages. Formally, a property of languages is any set of languages, the languages that we say have this property. For example, the property of being infinite is the set of infinite languages. The property of being empty is the set containing only the empty language. While properties like being infinite apply to any language, even not recursively enumerable ones, we need to represent languages, and the Turing machine is the most powerful tool we have for representing languages. So we'll talk about properties of recursively enumerable languages only. So we'll consider a property to be a problem about Turing machines. Given a code for a Turing machine, does it define a language with that property? So for any property P, we can define a language L sub P, the set of binary strings that represent a Turing machine whose language has the property P. So for example, L sub infinite is the set of codes of Turing machines that define an infinite language. There are two properties we call trivial for reasons that will be obvious. For these two properties P, L sub P is decidable. One of these trivial properties is the always false property that contains no recursively enumerable languages. We can think of this property as is not a recursively enumerable language. This property is actually true of some languages, but those are outside the recursively enumerable class, obviously, and we're talking about properties only as applied to the recursively enumerable languages. How do we decide this property? Given an input W, we ignore it and say no. Notice that even if W represents an invalid Turing machine code, we have agreed to take all those strings as representing a Turing machine that accepts the empty language. But the empty language is a recursively enumerable language, so we are correct in saying that W's Turing machine does not have this property. The second trivial property is the always true property. We could express the property as is a recursively enumerable language. The algorithm for this property is to ignore the input and say yes. And Rice's theorem says, for every property P except the two trivial ones, L sub P is undecidable. An important part of the proof of Rice's theorem, which we'll be working on for a while, is the idea of a reduction. There are actually several different notions of reduction. We'll come back to that point later. But the simplest one, and the one we need for Rice's theorem, is an algorithm that takes an input string W for one language, or problem L, and converts it to another string X that is an input to another language or problem L prime, with the property that X is in L prime if and only if W is in L. The value of having such a reduction is that it tells us L is no harder than L prime, at least as far as decidability is concerned. If I know L prime is recursively enumerable, then I also have a Turing machine program for L. If I know L prime is recursive, then I also have an algorithm for L. In either case, the solution for L is to take the input W, convert it to X, see what the Turing machine for L prime does, and take its output to be that answer for W. The thing that turns a string W into X is called a transducer. So far we've only talked about a Turing machine whose only output is the yes or no that is implied by accepting or halting without accepting, respectively. But we can get other kinds of output from a multi-tape Turing machine if we designate one of its tapes to be the output tape and regard what is written there when the machine halts as its output. We could, for example, imagine such a transducer that takes W on its input tape and writes X on its output tape and then halts. So if we reduce language L to L prime using such a transducer, and L prime is decidable, that is, there is an algorithm to test membership in L prime, then there is also an algorithm for L. That is, we start by applying the transducer to input W and producing output X. We apply the algorithm for L prime to input X and decide whether or not X is an L prime. Either way, the algorithm renders a decision, either yes or no. And these two steps form an algorithm for L. The whole thing takes input W and tells us whether or not W is in L. We sometimes see a reduction used to discover an algorithm for L, but the more important use of the idea is in the contrapositive. If we already know that there is no algorithm for L, then there cannot be any algorithm for L prime. That's how we're going to use reductions. We'll take one problem that we may not be interested in, but that we know is undecidable, and reduce it to another problem that we are really interested in, but whose status we don't yet know, and then we will conclude that the second problem is also undecidable. Moreover, when we get to intractability, or the theory of NP completeness, we'll be using reductions that are fast to argue that a problem like L prime can't be solved faster than the problem L. There are more powerful forms of reduction that let us reach the same conclusion. That is, if there is an algorithm for L prime, then there is an algorithm for L. We actually saw one example of a more complex reduction where we started by assuming that there was an algorithm for L sub u, the universal language, and showed how we could then construct an algorithm for LD which we know does not exist. However, the hypothetical algorithm we constructed for L sub d involved more than just turning one string into another. We first had to check whether the input W was a well-formed code for a Turing machine, and if not, we answered the question directly. Moreover, after doing a transduction where we turned input W into W111W, we had to complement the answer that we got from the hypothetical algorithm for L sub u. That is, we turned a yes answer into no, and vice versa. In the simple version of reduction, we are not allowed to modify answers in this way. We have to take whatever answer we get. We'll revisit this issue of more general kinds of reductions when we talk about NP completeness. There, the simple reduction is called a Karp reduction, and more general kinds of reductions are called Cook reductions. Steve Cook and Richard Karp, by the way, were the people who made the earliest contributions to NP completeness theory. We're now ready to prove Rice's theorem. The idea is that we can reduce L sub u to L sub p for any non-trivial property p. Then, since we know L sub u is undecidable, it follows that L sub p is undecidable. Here's how we reduce LU to LP. The input to LU is a Turing machine M and an input W for M. The output will be the code for a Turing machine M prime. That is at least the right form, since LP is a set of Turing machine codes, those for which the language of the machine has property P. Of course, for the transduction from M and W to M prime to work, we must arrange that M prime has property P if and only if M accepts W. That is, M prime is an L sub P if and only if M and W is an L sub U. We'll design M prime to be a two-tape machine. On the first tape, M prime simulates another particular Turing machine which we'll call M sub L on its own input, say X. On the second tape, M prime simulates M on W. It is important to understand that M prime has only its own input X, which the transducer does not deal with, or C. The transducer knows about M sub L. It is built into the design of the transducer. The transducer gets to see the code for M and the string W, that is on its own input. Thus, the transducer can build both the moves of M and the input W into the transition function of the machine M prime, that is its own output. None of M sub L, or W is input to M prime. We're going to assume that the empty language does not have property P. If that is not the case, then consider the complement of P, say Q. Surely the empty language then has property Q, but if we could prove that Q were undecidable, then P also must be undecidable. That is, if LP were a recursive language, then so would be LQ, since the class of recursive languages is closed under complementation. So let L be any language with property P. We know L exists because P is not trivial. Also, let M sub L be the Turing machine that accepts L. Here's how M prime behaves. To begin, M prime writes W on its second tape. It can do that because the transducer, seeing W, generates a sequence of states that write W one bit at a time. M prime, from its start state, enters each of these states in turn. Then M prime moves the tape head for tape 2 to the left end, goes to the start state of M, and simulates W on input W. Again, M prime can do that because the transducer sees both M and W and makes the transition function of M part of the transition function of M prime. Suppose during the simulation of M on W, M enters an accepting state. Then M prime goes to the start state of M sub L and simulates M sub L on the input X to M prime, which has been just sitting there on tape 1 being ignored so far. Where does M prime get the transition function for M sub L? M sub L is a particular Turing machine, one that accepts a language L with property P. Thus, the transducer itself can be designed so that it writes the transitions of M sub L out as part of the transition function of M prime. If M sub L accepts the input X, then M prime enters an accepting state. If M sub L never accepts X, neither does M prime. Thus, if M prime ever gets to the stage where it simulates M sub L, then M prime accepts the same language as M sub L does, that is L. But if M does not accept W, then M prime never gets to the stages where it simulates M sub L, and therefore M prime accepts nothing. Here's a picture to help us remember what M prime does. It first simulates M on input W. So far, M prime's own input X is ignored. But if M accepts W, then M prime simulates M sub L on its own input X. And M prime accepts X if and only if X is in L. So to summarize what we know about M prime, first, suppose M accepts W. Then M prime simulates M sub L on X and accepts X if and only if X is in L. That is, if M accepts W, then the language of M prime is L. We know L has property P, so M prime is in LP. Now look at the opposite case where M does not accept W. Then M prime never even starts the simulation of ML, and therefore M prime cannot accept its input X. That is, in this case, the language of M prime is the empty language. We know the empty language does not have property P. Thus, if M does not accept W, M prime is not in the language LP. We conclude that the algorithm we described for converting M and W to M prime is a reduction of L sub U to LP, and therefore that LP is undecidable. That is Rice's theorem. This is a picture that reviews the argument for why the existence of the reduction from LU to LP proves LP is undecidable. We have a real reduction algorithm. I hope you are convinced that you could program this algorithm if you were paid enough. We then contradict the hypothesis that LP has an algorithm by supposing that algorithm existed. then you could put together the reduction plus the hypothetical algorithm to build an algorithm for LU. Since we already proved that there is no such thing, we have to look at what of this story hasn't been proved. The finger points at the hypothetical algorithm for LP. Since we didn't prove it exists, we just assumed it did. Thus, the assumption must be responsible for the false conclusion, and we can conclude instead that there is no algorithm for property P. Thanks to Rice's theorem, we suddenly have an infinite collection of undecidable problems about the languages defined by Turing machines. Here is just a tiny sample of the questions that are undecidable about Turing machines M. Is M's language regular? Or is it context-free? Does this language include at least one string that is a palindrome, that is, a string that is the same as its reversal? Is the language empty, that is, does M accept any string at all? Does the language contain at least 1,000 strings? But Rice's theorem also applies to programs, since you can write a program to simulate a Turing machine. That tells us any non-trivial question about what a program does will also be undecidable. I want to emphasize about what a program does. There are lots of questions about what a program looks like that are decidable. For example, I can tell whether a program uses more than 20 variable names, but that's not a question about what the program does. An example of a question about what a program does is, does the program eventually halt on any input? That is undecidable. Or, does the program correctly sort its input? That's undecidable. Or, does this line of code ever get executed? That's undecidable. We're now going to take up post-correspondence problem, affectionately known as PCP. PCP is the first example of a problem that is undecidable yet doesn't involve Turing machines or programs, which are really the same thing. As we said, PCP is not really important by itself since it's just a made-up problem, but it leads us to proofs that many other problems are undecidable. These problems are unrelated to Turing machines but are related to matters like context-free languages that were not developed for the purpose of exposing undecidable problems. That is, we studied grammars for their use in matters like describing the structure of programming languages. We had no intent to describe problems that turned out to be undecidable. It just turned out that there were undecidable problems lurking in the theory of context-free grammars. An instance of PCP is a list of corresponding strings. That is, a list of pairs of strings over some particular alphabet sigma. The instance has some number of pairs, say n. The first pair is W1x1, the second is W2x2, and so on. None of these strings can be the empty string. The property of the list that makes the answer to this instance of PCP be yes is that when we take the first component from each pair on the list, that is, WI1 is actually the first component of the pair that we indexed as I sub 1. I can't draw on the slide two levels of subscripts. Then the second WI2 is that W from this list that has in the I that is from the I-tooth pair on that list, and so on. Then we get the same string if we take the W's from the pairs as if we took the second components or the X's from the pairs. Okay. Such a list of integers is called a solution to the instance of PCP. Here's a simple example instance of PCP. The alphabet will be 0 and 1. And there are two pairs. The first pair is 0 and 0, 1. The second pair is 1, 0, 0 and 0, 0, 1. Okay. Every time a list of integers has 1, it refers to this pair, and every time it has a 2, it refers to that pair. Okay. In this case, it turns out there is no solution to this instance of PCP. The analysis of this simple instance is not so easy. The easy part is that no solution can start with the second pair. Why? The reason is that if we choose 2 as the first integer in the so-called solution list, then the first string made from the W's that are first components will begin with this 1. But the second string, the one made from the corresponding x's that are the second components, begins with this 0. I don't care how you continue, a string that begins with 1 can never equal a string that begins with 0. However, it is possible that the solution list begins with index 1 because for pair 1 the two strings are not inconsistent, that is, one is a prefix of the other. So let's see if we can build a solution starting with the first pair. Since the two strings are not equal, we have to add another pair. We can't choose pair 1 because the first string would then begin 0, 0, and the second string would begin 0, 1. That could never lead to a solution. So the second index in the solution must be 2. Now both strings begin with 0, 1, 0, 0, and the second string has an additional 1. We're back where we were at the previous choice. We can't pick 1 as the third index, but we can pick 2, and we get a match up to a point, with the second string again having an additional 1. If you think about it, we can never make the two strings be the same, because to do so we'd eventually have to use a pair whose second string was shorter than the first. But there is no such pair in this instance. We conclude that this instance has answer no. On the other hand, let's change the instance a little by adding a third pair, 1, 1, 0, and 1, 0. Now the list of indexes 1, 3 is a solution. From the first strings of the pairs, we get 0 followed by 1, 1, 0, which is 0, 1, 1, 0. That is, 0, 1, 1, 0 is a 0 followed by a 1, 1, 0. From the corresponding second strings, we get 0, 1, that's this, followed by 1, 0, that's that, and that also is 0, 1, 1, 0. In fact, there is an infinity of solutions for this instance. Any string of indexes in the language of regular expression 1 to star 3. That is, after the 1 we can use pair 2 any number of times, including 0 obviously, and finally use the pair 3. So here's the plan for proving PCP is undecidable. We're going to start by introducing a modified version of the problem called MPCP, or the modified post-correspondence problem. The modification is that a solution to MPCP must begin with the first pair, but otherwise the modified and original PCP problems are the same. We'll show how to reduce L sub u, the universal Turing machine language, to MPCP, and then we'll show how to reduce MPCP to P sub p. In fact, this part is easier, so we'll do it first. Just to get the distinction between PCP and MPCP clearer, observe that if we treat the list of 3 pairs from our previous example of PCP as an instance of MPCP, then the answer is yes. The reason is that there is a sequence of indexes beginning with 1, say 1, 3, that produces equal strings from the first and second components of the pairs. But we can reorder the pairs, say by putting 1, 1, 0 and 1, 0 first. As an instance of PCP, order of pairs doesn't matter. There is still a solution. But as an instance of MPCP, there is now no solution. Any solution would have to begin with index 1, but then the first of the two strings would begin 1, 1, 0, and the second would begin 1, 0. So no matter how we extend these strings, they disagree in their second positions, and so they are not equal. Before we can talk about reductions, we need to express PCP and MPCP as languages. The instances of these problems can have any alphabet. So it is not immediately obvious how to express the set of all PCP instances that have a solution. Again, the problem is that there is no finite alphabet for this set, and languages just need a finite alphabet. So we need to code symbols in a finite alphabet. We'll represent the ith symbol of an alphabet by the symbol A followed by I in binary. Thus we only need 3 symbols to represent any number of symbols. The order of symbols of the alphabet is not important. For example, if we have an instance over alphabet A through Z, we could represent A by A1, B by A10, and so on. But we could also represent Z by A1 and y by a1, 0, and so on, it should be clear that the particular symbols used for the alphabet of a PCP instance does not affect the outcome. And the only other symbols we need to represent instances is the comma and left and right parentheses. Thus, the alphabet for the language of PCP instances will have an alphabet of 6 symbols, the A, 0, 1, comma, left paren, and right paren. Now that we have a finite alphabet for coding instances, we can define 2 languages. L sub PCP, the language of coded instances of PCP that have a solution, and L sub MPCP is the same for the modified problem. Now we can do the reduction of MPCP to PCP. We'll describe the transformation only, but you should be able to visualize the process being performed by a Turing machine transducer. Our input is an instance of MPCP. The output instance of PCP will use the same alphabet as the input instance, plus 2 new symbols, the star and the $sign. Of course, all symbols, the new ones and the symbols in the input instance of MPCP, will be coded using A, zeros, and ones as we just described. For each pair WX in the input instance, there is a pair in the output instance based on W and X. For every first string W of the pair, we add star after every symbol. So, for example, 0, 1 becomes 0 star, 1 star. And for X, the second string of the pair, we instead add a star before every character. So, for example, 1, 1 becomes star 1, star 1. The output instance also has a new pair unrelated to any input pair. This pair is $sign paired with star $sign. And the output also has a second pair based on the first input pair. This pair has stars placed after the symbols of the first string and before the symbols of the second string, just like in rules 1 and 2 on the slide. But the first string also has a star at the beginning. So, for example, the pair 0, 1 paired with 0 would become star 0 star 1 star paired with star 0. Here's an example. On the left is the instance of MPCP that is input to the transducer. On the right are those pairs with the added stars. Notice that for each pair, the stars come after the symbols on the first string and before the symbols on the second string. And we always add this pair, which will serve to make the strings of the PCP instance match when there is a solution to the MPCP instance. Its job is to add the missing star to the second string. And this pair also comes from the first pair. It is just like the first pair of the PCP instance, except for the star at the beginning of the first string. Notice that this is the only pair in the entire PCP instance where both strings start with the same symbol. For example, this pair has 0 as the first symbol of the first string and star as the first symbol of the second string. Okay. All these pairs have second strings that begin with star and a first string that begins with 0 or 1. Suppose the MPCP instance has a solution, a sequence of indexes that yield string W when we use the first strings in the pairs and the same string W when we use the second strings. Then we can get a solution to the constructed PCP instance. In this case, the solution string will be W padded with stars before each symbol of W and also at the end followed by the $sign. For example, if W is 101, then the PCP instance's solution is star 1, star 0, star 1, star $sign. To get the PCP solution, we use the same sequence of indexes as in the solution to the MPCP instance with 2 exceptions. First, we use the index of the special pair as the first index. Recall this pair was constructed from the first pair of the MPCP instance with the extra star. And we also add to the solution of the PCP instance the index of the ender pair star, dollar, and dollar to the end of the list of indexes. Thus, a solution to the input MPCP instance means that the output PCP instance also has a solution. But the other direction also holds. If the PCP instance has a solution, we can modify it to get a solution for the input MPCP instance. The first index in the PCP solution must be the special pair because that's the only pair of the PCP instance where both strings start with the same symbol. To change this index to 1, the index of the first pair of the MPCP index. Leave all the other indexes unchanged, but remove from the PCP solution the last index, which must be the index of the ender pair. Why? That's the only pair where both strings end with the same symbol. Thus we've shown that the answer to the questions, does the input MPCP instance have a solution, and does the output PCP instance have a solution, are the same. That means we have a valid reduction from MPCP to PCP. If we can prove MPCP is undecidable, which we'll do next, then we have a proof that PCP is also undecidable. So our next task is to show how to reduce L sub u to MPCP. Given an instance M and W of L sub u, we'll convert this to an instance of MPCP whose only possible solutions yield strings that represent the sequence of IDs that M enters when its input is W. More precisely, suppose this sequence is a sequence of IDs that M enters, starting with the initial ID with input W. Then any solution to the constructed MPCP instance will yield a pair of strings that begin with the sequence of IDs separated by pound signs. However, until M enters an accepting state, when we look at the two strings of the partial solution, one formed from the first strings of the indexed pairs and the second from the second strings of the indexed pairs, the second string will always be a full ID ahead of the first string. Only if M accepts will we be able to choose pairs that make the first string grow faster than the second and eventually make the two strings become identical. We're going to assume, as we can, that the Turing machine M from the input to L sub u has a semi-infinite tape and never moves left from the initial head position. That is, given the actual binary string representing M, we can modify the represented machine to mark its left end of tape, as we did when we described the construction of a Turing machine with a semi-infinite tape from one that had a two-infinite tape. Then we can perform the reduction on the new Turing machine that we know does the same as M rather than on M itself. However, in what follows, we will continue to refer to the input machine as M. The MPCP instance we construct will have an alphabet that consists of all the states and tape symbols of M, or rather the modified M, plus the special marker pound sign. We assume that the symbols used for states and tape symbols are disjoint, so we can tell one from another in the ID. Here's the beginning of the construction of the MPCP instance from M and W. The first pair has a first string that is just a pound sign, but a second string that is the entire first ID with input W, surrounded by pound signs. Note that the transducer gets the CW on its input so it can generate this pair. We'll add the pair pound sign, pound sign. It lets us add markers to the end of one ID in the first string at the same time we add it to the following ID in the second string. Add pair XX for every tape symbol X. This pair lets us add an X to the ID we're forming in the first string at the same time we add an X to the next ID, which is being formed on the second string. Of course, in order to make sure that the strings match, it must be the case that an X appears as the first unmatched symbol of the second string. Recall, the second string is one ID ahead, so these pairs, in effect, let us copy the tape of one ID to the next ID, but prevents us from making changes that are not justified by a move of M. Here's a picture of copying IDs. Suppose we have just reached a point in the sequence of indexes when the second string has a complete ID more than the first string, but otherwise the strings match. We can add to the solution we're constructing the pair AA. That has the effect of putting the first symbol of the new ID at the end of the first string and also extending the second string by the same symbol. That's what we want, since there's no way this A could change in the next ID. We can also then add the index of the pair BB to the solution, extending the new ID one symbol further. This might or might not be the right thing to do. The problem is that if the move of M in state Q with symbol C is to move left, then the second symbol of the new ID is the new state, and B will be the third symbol. But just because we can choose the pair BB doesn't mean we have to. If M is going to move left, there will be another choice of next index that simulates the move correctly, and the sequence where BB is chosen instead will fail to yield a solution to the MPCP instance we're constructing. Now we need to add the pairs that reflect the moves of M. For every state Q in tape symbol X, if the move of M is to the right, say PYR, we have a pair in which Q to the left of X, that's this, can be replaced by a P to the right of Y. That correctly reflects the change in ID that occurs at the rightward move. And if the move is to the left, then we have a family of pairs, one for each symbol Z that could appear to the left of the state. Note that we arranged that M can never move left from its initial position, so there is no possibility that the state is at the left end of the ID if M moves left. So if the leftward move has state Q and symbol X replaced by state P and symbol Y, then for every Z there is a pair that puts P to the left of the Z and replaces the X by the Y. One other possibility is that in the current ID, the state is at the right end of the ID, scanning a blank we've never visited before. If so, the state will actually be to the left of the pound sign. Okay, and the pairs are almost the same, but when constructing the second string, we should imagine an extra blank in front of the pound sign. The blank is replaced by the new symbol Y, of course. Following a previous example, suppose that in state Q, scanning C, M does indeed move right, going to state P and writing E in place of C. Had M moved left in that situation, the sequence of pair choices would be dead in the water, unable to continue. However, in that case, we could have chosen not to use the pair BB, but instead use a pair that incorporated the left move and handled the B properly. In this case, we have a pair with QC as the first string, so we can match that string on the bottom. It also extends the bottom string with EP, reflecting a move of M. Once the move has been handled, we can just match symbol against symbol. Here the pair DD is used. And once we are at the end of the ID, we use the pair of pound signs to separate the IDs, and we're now ready to continue the sequence of pair choices to copy the new ID, which is ABEPD, and make it changed by another move. But we need some more pairs in the MPCP instance so that in case M accepts, we can find a solution. Note that if M never accepts, then only the rules given so far can ever be used, and these can never lead to a solution because the second string is always one ID longer than the first. However, if M enters a final state F, then it is possible for the F to, we'll say, eat the neighboring symbols of an ID. We no longer have real IDs of M, but it doesn't matter. We've simulated M enough to know that M accepts W, and our only concern then is to make sure that there's a solution to the MPC instance based on M and W. Thus, we add to the instance of MPCP pairs XFYF, FYF, and XFF for all tape symbols X and Y. Using these pairs, together with pairs of the form XX to copy parts of IDs as we have done, we eventually get to an ID that is only the state of F. Of course, that isn't an actual ID of M, but it doesn't matter anymore. And one more pair, F pound pound, paired with the pound sign, will end the two strings being formed, making them the same and yielding a solution to the MPCP instance. So here's an example where M has entered the final state F, and a sequence of choices, either copying a symbol or allowing f to eat the adjacent symbol or symbols eventually leads to identical strings. So here's what it looks like. Well, we'll just have to copy that a, but now the f can in effect eat the b and c adjacent to it. We have to copy the d, we have to copy the e, we have to copy the pound sign. Now the f can eat the a and the d, but we have to copy the e, we have to copy the pound sign. Now f doesn't have anything that it can eat to its left, but it still will eat the e. And finally, copy the pound sign, and now f pound pound paired with pound makes everything evened up, and we have our solution. Now we know that PCP is undecidable because we successfully reduced L sub u to its own language, M sub PCP. And we're going to reduce PCP to the problem, is a context-free grammar ambiguous? Then, for the first time, we'll have an undecidable problem that arose naturally. That is, not because we were looking for undecidable problems. Before we can talk about any problem involving grammars, we need to find a code for grammars using a finite alphabet, just as we did for PCP. So to start the encoding of grammars, let's represent the ith terminal by symbol A followed by I in binary. That may look like we're thus forgetting what the actual terminal symbols are, but since we're interested in ambiguity, we can rename the terminals any way we like as long as we don't name two terminals the same, and the ambiguity or unambiguity of the grammar will not change. Then we'll represent the ith variable by capital A followed by I in binary. We will assume that A1 is always the start symbol. The right arrow between the head and body of a production will be represented by itself. Likewise, the comma separating productions and the symbol epsilon will represent themselves. For example, this grammar is represented by this string right here. The bar connecting alternative bodies for S has been expanded so that there are two separate productions. This represents S goes to 0S1, and this much represents S goes to capital A. Finally, this represents capital A goes to little c. Suppose we have a PCP instance with k pairs, and let the ith pair be wi xi. We need k index symbols to represent the numbers of the pairs, and we'll use A1 through AK, which we may choose to be symbols that do not appear in the PCP instance itself. Notice that we're going to talk about reducing an uncoded instance of PCP, so it can have any alphabet, to an uncoded grammar, which also can have any symbols. However, the process we describe really takes place with all the symbols coded in the manners we have described. It is easier to follow the construction in the uncoded form, so that's what we'll do. The list language for the first half of each pair, the strings W1 through WK, has a context-free grammar with productions A goes to WI, capital A, little ai. It also has the same sort of production, that, but with A omitted from the body. The latter kind of productions, these, are used to end the derivations. All the strings in this language are some sequence of the WIs with repetitions allowed and in any order, with the corresponding index symbols following, but in reverse. For example, here's a derivation. Okay, A could derive in one step, let's say W1, A, little a1. And then in one more step, we could use, let's say, the terminal production for W2. So we get W1, W2, and then A2, A1. Notice that the sequence of A's is the reverse of the sequence of W's. And we can do the same thing with the second string from each pair. We'll use variable B and Xi's in place of Wi's, but the idea is the same. The language of strings generated from A and B each consist of a concatenation of strings, either from the WIs if it's A or the XIs if it's B, and these are the first or second components of the pairs. They're followed by the reverse of the sequence of indexes of the pairs from which these strings came. Here's an example of a PCP instance over alphabet AB. We'll use 1, 2, and 3 as the index symbols. So the grammar with start symbol A is this. For example, the second pair, whose first string is BAA, gives rise to these two productions. Here's BAA with the variable A in the middle, and then 2, which is the index. And then there's another production that's the same but without the capital A. And here's the grammar for the second strings in the pairs with start symbol B. As an example, if we choose the three pairs in order 1, 2, 3, then there's a derivation from A that looks like this. So A, use the first choice, that's this production. Then we'll use the second choice, which is this production, and that gives us A, B, A, capital A, the 2 and the 1. And then we'll use the third pair, but we want to end it, so we'll use that production, and that gives us A, B, A, B, A, sorry, B, B, A. That's that. And then 3, 2, 1. We're now ready to show how to reduce PCP to the ambiguity problem. Given the PCP instance, construct the two list languages with variable A for the first strings of the pairs and B for the second strings of the pairs. Then add the productions S goes to A and S goes to B. Of course, S is the start symbol of the grammar. Okay. We'll show the resulting grammar is ambiguous if and only if there's a solution to this instance of PCP. But first, let's look at an example that should actually expose how the proof in general works. Okay. Here's the grammar constructed from the PCP instance that we saw earlier. It is the sets of A productions and B productions we saw plus the two productions for S. Okay, notice there is a solution 1, 3. That is, the first pair was AAB, and the third pair was BBA with BA. When we take the first strings of each pair, we get ABBA, that's this, followed by that. And when we take the second strings of each pair, AB and BA, we also get ABBA. And this common string followed by the index string in reverse, which is that, will have two leftmost derivations, one starting with A and the other starting with B. Here is the derivation starting with A, and here's the derivation starting with B. So here's the proof this construction is a correct reduction from PCP to ambiguity. First, suppose the PCP instance has a solution, say represented by the sequence of index symbols A1 through AK. Note there can be repeats in this sequence. Then W1 through WK is the same string as X1 through XK. That's what it means for this index sequence to be a solution. Then there are two leftmost derivations of the string that is W1 through WK, or equivalently it's X1 through XK, that is followed by AK down to A1. One starts with S goes to A, and the other starts with S goes to B. For the converse, we're going to show that if there are two leftmost derivations of a string of terminals, then one must begin S goes to A, the other must begin S goes to B. Suppose there are two leftmost derivations that begin with S goes to A. Then we can look at the sequence of index symbols in the resulting terminal string in reverse and learn exactly the sequence of productions used. Except for the last production used, each would be the unique A production that generates the index symbol and has an A in the body. And the final production would be the one with the last, that is leftmost index symbol, and no A in the body. The same idea works for derivations that start with S goes to B. There can be only one with a given sequence of index symbols. Here's an example. If the derivation starts with S goes to A and produces a terminal string with index sequence 2321, then here's what the derivation of parse tree has to look like. Okay. First of all, we start with A. The first production used must generate the 1 at the right end, and we need to keep the A, so this is the only choice. So we've generated W1 off to the left of the A. The next index symbol from the right end is a 2, so we have to use this production. Again, we still need to keep that A there because we have more index symbols to go. Then the third from the left index symbol is 3, so this is the production we have to use. And then the last index symbol is 2, that is the leftmost index symbol is 2. So we're going to get rid of that A and use this production. That's the only way we could generate a string with 2321 at the end and no other index symbols. We can prove many things about context-free grammars to be undecidable as well, but to do so we need to show that the complement of a list language is also context-free. Remember that the complement of a context-free language need not be context-free, but fortunately these are. For the proof, we find it easy to construct a pushdown automaton, in fact a deterministic pushdown automaton, for the complement. The PDA we construct will start with a bottom marker on its stack. At first, some symbols from the PCP instance, not indexed symbols, will appear. The PDA simply pushes them onto the stack. After the first index symbol arrives, start checking that the proper strings appear on the stack. That is, if we see an index symbol AI, then check that the proper WI appears on the stack with the right end of WI at the top. The PDA pops all the symbols of WI if so. Note that we're assuming this is the complement of the list language based on the first components. If it is for the second components, we'll check that XI appears on the top of the stack, again with the right end at the top. What we seem to be doing is accepting the list language itself rather than the complement, but I didn't tell you when the PDA accepts. In fact, it accepts every input, with only the exception of when it has found a string in the list language. That is, if the input so far was some sequence of PCP symbols followed by some sequence of index symbols, and these sequences are not empty, and the bottom of stack marker is now exposed, then the PDA does not accept this string. It will accept any other string that follows, which cannot then also be a solution to the PCP instance. Now we can use the complement language. Let LA and LB be the list languages for the first and second components of an instance of PCP. And let LA complement and LB complement be their complements. Now all 4 of these languages are context-free languages. Let's consider the union of the complement languages. This is also a context-free language by the fact that context-free languages are closed under union. I claim that this union equals sigma star, where sigma is the alphabet consisting of all the symbols used by the languages involved, if and only if there is no solution to the PCP instance. Suppose there were a solution, say represented by the index symbols A1 through AN. Then this string is not in the complement of LA, and the equal string, this, is not in the complement of B. Thus, if there is a solution, there is a string missing from the union. Conversely, suppose string Y AN down to A1, let's say this, is missing from the union. That means Y is the string you get by using indexes A1 through AN and taking the first strings from the index pairs. And it's also the string you get by doing the same with the second pairs. That means A1 through AN is a solution to the PCP instance. We have now reduced PCP to the question, is a given context-free language equal to all strings over its terminal alphabet? Thus, this problem is undecidable. Here's another undecidable question about context-free languages. Is the language also a regular language? We do exactly the same reduction from PCP, And one direction is easy. If there's no solution, then we just showed that the union of the complement languages is sigma star, and that's surely a regular language. But we also need to show the converse, that if L, the union of the complement languages, is something other than sigma star, then it's not a regular language. Suppose we have a solution to the PCP instance, and in particular, let X be the index symbols in reverse. That gives you the solution, and let W be the string you get by using the first string from each of the indexed pairs in order, or obviously equivalently the second string from the same pairs. Now, let H be the homomorphism defined by H of 0 is W and H of 1 is X. Remember, L is the union of the complements, the strings that are not solutions to the given instance of PCP. We claim that 0 to the n, 1 to the n, is not an L for any n, because if we repeat a solution to a PCP instance any number of times, we also get solutions to that instance. However, H of y is an L for any other y. That is, H of y is not a solution. This point requires a little thought. First, if y isn't zeros followed by ones, then H of y isn't of the right form to be a solution to PCP. That is, it will not consist of PCP instance symbols followed by index symbols. But if y consists of n ones preceded by a different number of zeros, then it can't possibly represent a solution. H applied to the n ones gives a particular sequence of index symbols. But we know the PCP instance symbols that this sequence of index symbols corresponds to is H applied to n zeros. Therefore, it couldn't also be H applied to a different number of zeros. So if L, the union of complements, were regular, then H inverse of L would also be regular, because regular languages are closed under inverse homomorphism. And the complement of H inverse of L would be regular because regular languages are closed under complementation. But this language we just argued is the set of 0 to the n, 1 to the n, such that n is at least 1, a language we know very well not to be regular. We now take up the last major topic of this course. The subject is intractable problems. These problems are decidable, but colloquially they are said to be problems that take at least exponential time as a function of their input size. The reality is a bit different, but they are problems for which there is an overwhelming amount of empirical evidence that these problems take exponential time, although no solid proof of that belief. If a problem does take time that is exponential in its input size, then that means it can in practice only be solved for small instances. Suppose to be concrete that the time it takes to solve an instance of size n is 2 to the n. Then doubling the speed of machines makes essentially no difference in how large an instance you can solve. It adds 1 to the size n that you can solve in a fixed amount of time. Using 1,000 machines instead of 1 has the effect of adding 10 to the size n. And using 1,000,000 machines, each 1,000 times faster than today's machines, adds 30 to n. You never get to really big sizes of problem instances that you can solve. As a result, it is generally accepted that in order for a solution to a problem to be considered usable in practice, it has to run in less than exponential time, and in particular in polynomial time for some large polynomial. While an algorithm that runs in some large polynomial time, like n to the 1,000th power, is no more practical than one that runs in time 2 to the n, we find in practice that if a problem has a polynomial algorithm at all, then it has an algorithm that runs in some low-degree polynomial like n squared or n cubed at the most. In this lecture, we introduce several important preliminary concepts. We introduce the idea of a Turing machine that is time-bounded. It can only run for a time that is a known function of its input size before it has to stop and tell us whether it accepts or rejects. We introduce the class P of problems or languages, it's the same thing of course, that can be solved by a Turing machine that runs in polynomial time as a function of its input size. We also meet the class NP, which is problems that can be solved by a Turing machine that is non-deterministic, but has a polynomial time bound along each branch. Finally, we'll learn about polynomial time reductions, which are reductions where the transducer runs in time that is polynomial in its input size. These are used to show one problem intractable by reducing a known intractable problem to it. We say a Turing machine is T of n time-bounded, where T of n is some function of n, like n squared or 2 to the n. If given an input of length n, the machine always halts in at most T of n steps. Okay. We allow the Turing machine to have several tapes. In some circumstances, we allow the Turing machine to be non-deterministic, although in that case we will specify that it is a T of n time-bounded non-deterministic Turing machine. Also in that case, we mean that any sequence of moves of the non-deterministic machine is no longer than T of n. In practice, a deterministic multi-tape Turing machine is close to the idea of an algorithm that runs in time proportional to T of n, or big O of T of n. That is, while some algorithms take longer on a Turing machine, even multi-tape, than on a real computer, these are rare. Moreover, when there is a difference, the difference tends to be small. A Turing machine M is said to be polynomial time-bounded if it is time-bounded by any polynomial. It could be linear, quadratic, cubic, or n to the 1000th power, as long as it is some polynomial. The languages that are accepted by polynomial time-bounded Turing machines form the class P. Now, P is defined formally in terms of Turing machines, but it could just as well have been stated as polynomial time on a real computer. The reason, which we address on the next slide, is that if an algorithm runs in some polynomial time on a computer, then it will run in polynomial time on a multi-tape Turing machine, or even a one-tape Turing machine, although the degree of the polynomial may be higher in some cases. That is, we saw a way to simulate a name-value store by a computer. That is the part of a real computer that takes the most time when simulated by a Turing machine. But if a computer runs for on the order of T of n steps, then it can't store or retrieve more than T of n items in its memory. A Turing machine can simulate one lookup or insert into a name-value store in a number of steps that is proportional to the length of the tape that holds the store. But that length is proportional at most to the number of steps the computer has taken, which is T of n, and thus the Turing machine takes at most T squared of n of its own steps. If T of n is a polynomial, then so is T squared of n. The exponent grows, of course. A cubic algorithm on a computer might take time proportional to n to the 6th on a Turing machine, but it's no worse than that. And since we're trying to divide the world of problems into those that have polynomial algorithms and those that don't, we can think Turing machine or computer, whichever is more convenient. As you might expect, when simulating a program, it's best to simulate a Turing machine. But when devising an algorithm, it's best to think about a computer program. Here are two examples of problems or languages, which is the same thing, in the class P. For each context-free grammar G, there is an algorithm, the CYK algorithm, that takes an input string W and tells whether W is in the language. The running time of this algorithm is O of n cubed. The second problem I want to talk about is finding a path in a graph. Here we're given a directed graph that is a list of its nodes and arcs. We are also given one node as the source node X and another as the sink node Y. The answer is yes if there is a path in the graph from the source to the sink. Graphs must be coded in a finite alphabet, which should not be hard to see. Represent the ith node by n followed by I in binary, and represent an arc by a pair of nodes, the tail and the head of the arc. Use two special symbols to indicate the source and sink nodes. Note that if there are m nodes, it takes order log m space to represent one node, so n, the input length, is actually somewhat greater than the number of nodes and arcs, but the difference is unimportant since we are only worrying about polynomial versus not polynomial. Depth first search answers this question in time that is linear in the number of nodes and arcs. On a Turing machine, you might need order n squared steps, since for one step of the depth first search, you have to locate on the input the arcs with a given node as the tail. That could require that you run all along the tape just to simulate one computer step, but n squared is still a polynomial, so as far as membership in P is concerned, n squared is just fine. And just to make sure, when we talk about polynomial time, we include every running time that is less than some polynomial. That is, the definition of P only requires that the language be accepted by some Turing machine whose running time is bounded above by some polynomial. For example, there are many algorithms that run in times like order n log n, but that's less than n squared, so the problems solved by algorithms like this are surely in P. Before proceeding, I want to examine in detail a problem that seems to be in P but really isn't, and I want you to understand why. This is really important in understanding what the class P really means. The problem called knapsack is this. We're given a list of n positive integers. The answer to this instance of knapsack is yes, if and only if we can partition the integers into two groups whose sums are equal. For example, if the integers are 1, 2, 3, and 4, then I can partition them into 1 and 4 in one group, and 2 and 3 in the other group, and the sums in each group will be equal. Incidentally, the problem is called knapsack because of the view that the integers are weights of items, and two hikers want to divide the items between their two knapsacks so each carries equal weight. At first glance, we can solve the knapsack problem by a polynomial time dynamic programming algorithm. That is, we maintain a table of all the differences in sums we can achieve by partitioning the first j-1 integers. When we incorporate the jth integer, we take each possible difference and both add and subtract the jth integer, thus getting two new possible differences. After looking at all integers, we see if 0 is a possible difference. To be more precise, for the basis we consider none of the integers. Then the table has true for 0 difference and false for all the other differences. For the induction, suppose we have a table for the first j-1 integers. We build a new table to reflect the partitions of the first j integers. Initially, each entry in the new table is false. But suppose the jth integer is I sub j. For each difference m that was true in the old table, set the entries for m plus I sub j and also m minus I sub j to be true in the new table. Let's compute the running time of this algorithm as a function of the sum of the integers. Let's say that sum is s. We need order s space to construct a table for one value of j, since the differences must be in the range minus s to plus s. And it only takes order s time to construct each table from the previous one using a real computer. Maybe it's order s squared on a Turing machine because we have to move the head a long distance to write each entry. But again, when designing algorithms and worrying only about whether something is polynomial time or not, a real computer is the right model to think about because the programming details are generally easier. Okay. Note that n is equal to or less than s since the integers are each positive. That is, the sum of the integers is at least equal to the number of integers on the list. Thus, we can build a table that corresponds to the set of all the integers in order s squared time, s for each of n different tables. We then look in this table and see if 0 is true. If so, the answer to the knapsack instance is yes, and otherwise it is no. However, that conclusion is actually deceptive. Although it is true that we just described an algorithm that runs in time no more than the square of the sum of the integers, and that algorithm really does solve the knapsack problem, it doesn't tell us that the knapsack problem is in P, and in fact it is almost surely not in P, as we shall see later. The reason this algorithm doesn't show knapsack to be in P is that membership in P requires that the algorithm runs in time polynomial in the input size. But we can't just define input size to be the sum of the integers in the input. The input size is always the number of cells it takes to write the input on a Turing machine tape. For the knapsack problem, this input length is not necessarily polynomial in the sum of the integers, as we shall see on the next slide. The longest input length occurs if we have n integers, each of whose values is about 2 to the n. If we write the integers in binary, the input to the Turing machine is order n squared in length. But a table then requires about n 2 to the n entries and at least that much space to write down. That is, the sum of all n integers can be around n times 2 to the n. We can't construct one table in time less than its length, so the total time of the algorithm is on the order of n squared times 2 to the n. But the input size is n squared, and n squared 2 to the n is not a polynomial function of the input length. By the way, we usually like to have n be the actual input size for the Turing machine. So if we substitute n for n squared, we can say the inputs of size n leads to an algorithm that takes time proportional to n times 2 to the square root of n. That is still not a polynomial. Thus, the dynamic programming algorithm we described, while it is really a good algorithm when the integers are of limited size, does not show the knapsack problem to be in the class P. There is another problem which we can call pseudo-knapsack. The question is the same, but the integers are represented in unary, not binary. That is, integer I is represented by I1s followed by some marker symbol to separate integers. This problem is in P, and the dynamic programming algorithm proves that. But it is not the classical knapsack problem where integers are represented in binary, the sort of rational way to represent large integers. The second important class of languages for our story is NP, the non-deterministic polynomial class. NP is defined in terms of non-deterministic Turing machines. The running time of a non-deterministic Turing machine is the maximum number of moves it takes along any branch. That is, by making any sequence of choices. If there is a polynomial bound on that time, then the non-deterministic machine is said to be polynomial time bounded. And the language or problem it accepts is said to be in the class NP. For example, the standard version of knapsack, where integers are represented in binary, is an NP. The non-deterministic polynomial time algorithm that solves this is fairly simple. First, it uses its non-determinism to guess a partition of the integers into two subsets. This can be done in time that is linear in the input length using 2 extra tapes for the 2 subsets. Then sum the subsets and compare. Say yes if this partition yields 2 equal sums. And this part can surely be done in time that is quadratic of the input size and can be done in linear time if you're clever and use a few extra tapes. Thus, standard knapsack is an NP. Note that this fact doesn't suggest a deterministic polynomial time algorithm, since it may take exponential time to simulate the non-determinism of the Turing machine. Are P and NP really the same class of languages? That is, can any problem that is solved by a non-deterministic Turing machine in polynomial time also be solved by some deterministic Turing machine in polynomial time, even if the degree of the polynomial was higher? This question was posed by Steve Cook in 1970. At first, it didn't seem all that hard or unlikely. After all, non-deterministic finite automata can be simulated by deterministic finite automata, even though the number of states might grow. And deterministic Turing machines can simulate non-deterministic ones. But the problem has proven to be very, very difficult, and mathematicians who once sneered at the question and assumed it was easy because computer scientists had thought it up, now recognize it as one of the most important mathematical questions, perhaps the most important unsolved question. However, there are thousands of problems that are in NP, but for which no algorithm in P has been found. And unfortunately, neither is there a proof that these problems are not in P. What we do have is a linkage of the large class of problems called NP-complete problems, which we discuss on the next slide. What we do know, then, is that either all these problems are in P or none of them are. So they mutually enforce the notion that none of them are, since many have been worked on for decades and no polynomial time algorithms for any of them have been found. So we're going to address the question of whether P equals NP by identifying complete problems for NP. Say a problem in NP is NP complete if the following is true about the problem. If the problem is in P, then P equals NP. That is, every problem in NP is also in P. It turns out that almost every problem that is known to be in NP but is not known to be in P is NP complete. There is only one well-known exception, graph isomorphism. Given two graphs, is there a one-to-one matching of nodes between the two graphs that makes the graphs identical? This problem is known to be in NP. Just guess the matching of the nodes in the two graphs and check that the right edges exist. But there is no polynomial time algorithm known, and neither is there a proof that graph isomorphism is NP complete. But graph isomorphism is an exception to what appears to be an almost general rule. If it is an NP and it isn't known to be in P, then it is NP complete. While the definition of NP completeness merely states that there has to be some way of proving P equals NP from the assumption that the problem is in P, there is a standard way of making such proofs, and it appears to be sufficient for all the NP complete problems that we know about. This method involves reductions of the type we talked about for Turing machines in general, but with the condition that the transducer run in polynomial time as a function of its input size. Intuitively, a complete problem for a class embodies, in some sense, every problem in the class. For example, post-correspondence problem embodies every Turing machine, even though it is hard to see PCP as involving computation. It seems to be about concatenating strings in constrained ways. So it might surprise you to know that each NP-complete problem, such as knapsack, embodies all non-deterministic polynomial time computation, even though the knapsack problem seems to be about anything but computation. So in order to show problem L to be NP-complete, we have to show that every problem in NP is somehow embedded in L. We need a transformation from every problem in NP to L, and this transformation has to be sufficiently fast that if we had a deterministic polynomial time algorithm for L, then we could use it to build a deterministic polynomial time algorithm for each problem in NP. We're going to define a polynomial time transducer. Notice that people frequently shorten polynomial time to polytime, and we'll start doing that too. So a polytime transducer is a deterministic Turing machine that takes an input of length n, runs for some polynomial number of steps p of n, and produces an output on an output tape. It is important to observe that although we do not restrict the output length, since the Turing machine only runs for p of n steps, it could not write more than p of n symbols. Thus, the length of the output of a polynomial time transducer is always polynomial in the length of its input. Here's a picture of a polytime transducer. It can have any fixed number of tapes. One is the input tape and one is the output tape. We argued on the last slide that the output length must be polynomial in the length of the input, but the real constraint on the polytime transducer is on how long it runs. It is not acceptable to have it run for time that is exponential in its input length, even if the output is short. Consider two languages or problems, say L and M. We say L is polytime reducible to M if there is a polytime transducer T that takes an input W that is an instance of L, produces an output X that is an instance of M, and the answer to L on W is the same as the answer to M on X. That is, W is in L if and only if X is in M. Here is a picture to help us remember what a polytime reduction does. On the left is the set of strings over the alphabet of L, divided into those that are in L and those that are not in L. On the right is the set of strings over the alphabet of M, also divided between M and its complement. In the middle is the polytime transducer T. Every string in L is transformed by T into a string that is in M. There can be strings in M that are not the target of any string in L. And every string not in L, but over the alphabet of L, is transformed by T into a string that is over the alphabet of M, but is not in M. Again, there can be strings in the complement of M that are not the target of any string in the complement of L. Formally, we say a problem or language M is NP complete if, first of all, it is an NP, and for every language L in NP, there is a polytime reduction from L to M. An important consequence of the fact that M is NP complete is that if M has a polytime algorithm, then so does every language L in NP. That is, the classes of languages P and NP are the same, or P equals NP. Notice that earlier we suggested that the definition of NP completeness was simply that the language had this property. Steve Cook's original definition of NP completeness was exactly that, and it is often referred to as Cook completeness. Cook concentrated on showing one particular problem, the question of whether an expression of propositional logic was satisfiable, that is, made true by some assignment of truth values to the propositional variables. But shortly after Cook wrote his original paper on NP completeness, Dick Karp wrote another paper that showed many of the classical problems that had been puzzling mathematicians, sometimes for centuries, were NP-complete. Karp used only polytime reductions from the problem Cook had proved NP-complete. Since then, it is generally accepted that the preferred definition of NP-completeness is the one we gave here, the existence of polytime reductions. To make the distinction, this notion of NP-completeness is often called Karp-completeness. So here's the plan for proving certain problems to be NP-complete. Here's all of NP. SAT, the satisfiability problem for propositional logic that we just discussed, is one problem in NP. Cook's theorem is that every problem in NP reduces in polytime to the SAT problem, so SAT is the first known NP-complete problem. Cook also proved a restricted form of SAT called 3-SAT to be NP-complete by reducing SAT to 3-SAT. We'll learn what the 3-SAT restriction is shortly, but in brief it is SAT restricted to expressions that are the AND of clauses with 3 literals per term. A literal is a variable or a negated variable, and a clause is the OR of literals. Then from 3-SAT we do polytime reductions to many other problems, either directly or indirectly. Each problem we can reach from SAT by a chain of polytime reductions is thus proved NP-complete. But before we embark on this quest, let's make sure that polynomial time reductions work in the sense that they let us draw the desired conclusion about all of NP reducing to the target problem. So suppose M has a polytime algorithm, say running time Q of n for some polynomial Q. Let there be a polytime transducer T from some problem L to M. And let the time taken by T be P of n for some polynomial P. The output of T, given an input of length n, is at most of length P of n. So when we run the algorithm for M on this input of length P of n, the algorithm takes time Q of P of n. Note that a polynomial of a polynomial is a polynomial. The degrees of the polynomial are multiplied, but it's still a polynomial. We claim there's a polytime algorithm for L. Given an input W of length n for L, apply the transducer T to W. The result is an output X of length at most P of n, and more importantly, T takes time only P of n to produce this output. Apply to X the algorithm to tell whether it is an M. As we observed on the previous slide, this part takes time Q of P of n. Then return as the answer for W whatever the M algorithm says about X. The total time of this algorithm is P of n plus Q of P of n, which is polynomial if P and Q are. It is a correct algorithm because the fact that T is a polytime transducer from L to M says that the answers to input W and output X are the same. In this lecture, we're going to prove one problem, satisfiability for Boolean expressions, to be NP-complete by showing how to reduce the language of any non-deterministic polytime Turing machine to satisfiability. We will then cover 2 of its restricted versions called CSAT and 3-SAT respectively. We'll learn shortly what those mean. Our first step is to learn about Boolean expressions, or what is the same, expressions of propositional logic. These expressions consist of constants, variables, and the operators and, or, and not. There are only 2 constants, true and false, which we'll usually represent by 1 equals true and 0 equals false. The variables can only take on these 2 values as well. The operators and, or, and not have the usual logical meaning. When we write these expressions, we'll use concatenation, that is, no operator symbol for and. So xy really means x and y. We'll use plus for or, so x plus y means x or y, and we'll use the minus sign for not, so minus x really means not x. Here is an example of a Boolean expression. X or y is true when at least one of x and y is true, and not x or not y is true when at least one of x and y is false. So the whole expression is true when at least one is true and at least one is false. Since there are only 2 variables, that means exactly one is true and exactly one is false. As for any kind of expression, remember to use parentheses to alter the order in which operators are applied. the order of precedence is not first or highest, then and then or. Thus, the parentheses in the example expression are needed to make sure that the ors are applied before the ands. A truth assignment is an assignment of 0 or 1, that is false or true, to each of the variables of a Boolean expression. In general, the key question about Boolean expressions is which truth assignments give them the value true. But for our NP-complete problem, we need only this very simple question: given a Boolean expression, does there exist at least one truth assignment for which the value of the expression is true? So this expression is satisfiable. There are, in fact, two satisfying assignments, those that make one of x and y true and the other false. But this expression, x and not x, is not satisfiable. There are only two truth assignments. X can be assigned true or it can be assigned false. If x is true, then not x is false. That is, the and of expressions, one of which is true and the other is false, has value false. Similarly, if we assign x false, then x is false while not x is true, and the and of these is again false. We must see the SAT problem as a language, just like all the other problems we've discussed. First, the instances of the SAT problem are all the Boolean expressions. Since expressions can have any number of variables, we must code expressions in a finite alphabet. The parentheses, the plus and minus, can represent themselves, but we need to have a scheme for representing variables. We'll represent the ith variable by the symbol x followed by I in binary. So here is an example of an expression coded this way. We've assumed that x is the first variable, so it is represented by an x followed by 1. That appears here and also there. Y is the second variable, so it is represented by x and 2 in binary. That's x, 1, 0. What we call the variables doesn't matter as far as satisfiability is concerned, so we could have called y the first and x the second. Generally, the easier part of proving a problem NP-complete is proving it is an NP. Generally, you just guess a solution and then in polynomial time you check it. And the SAT problem is no exception. Okay. Well, we need to describe a non-deterministic Turing machine that can take a coded Boolean expression as input and tell if it is satisfiable. And of course, the non-deterministic machine must be polynomial time-bounded. In this case, order n squared time suffices. The power of non-determinism lets us guess a truth assignment. We'll use a second tape to write down the guess of a truth value for each variable. Then, in the expression itself, replace each variable by its guessed truth value. We can now evaluate the expression bottom up. The non-deterministic machine accepts if the value of the expression with this assignment is true. Notice the power of non-determinism here. The number of assignments could be exponential in n, the length of the expression, but the non-deterministic machine works on all the expressions sort of in parallel, thus appearing to finish in time that is polynomial in the input size, because we only count the time taken for processing one single assignment. Also, notice that non-determinism is more than parallelism. Given any fixed number of processors, say 1,000, we could divide the time needed to evaluate the effect of each truth assignment into 1,000 groups and evaluate them in parallel. But if there are 2 to the n assignments, it would still take each processor time 2 to the n divided by 1,000, which is still exponential in n. We're now going to give the proof of Cook's theorem that the SAT problem is NP-complete. Since we don't have any NP-complete problems yet, we can't do a reduction from some one other problem to SAT. Rather, we have to show how to reduce any problem in NP to SAT in polynomial time. We do these reductions by assuming nothing about the problem L that is an NP, except that it has some non-deterministic polynomial time-bounded Turing machine that accepts L. To make the reduction from these Turing machines to SAT easier, we're going to make some restrictions on the Turing machine, but only restrictions we can assume without losing any of the problems in NP. That is, every problem in NP has one of these machines, which we'll describe on the next slide. The restrictions we make are the following. First, that the non-deterministic machine has only one tape, and that the head never moves left of its initial position. We'll assume the states are never also tape symbols, so we can tell which symbol in an ID is the state. Point 3 clearly loses us nothing, since we can always change the names of the states without changing what the machine does. And we've already seen the constructions many tapes to one and two-way infinite tape to one way. Each of these constructions can square the number of steps the Turing machine makes, but that's okay. The square of a polynomial is still a polynomial. This slide has a collection of random but important comments about what we assume about the non-deterministic polytime Turing machine M, in addition to the restrictions we assumed on the previous slide. First, let P of n be the particular polynomial upper bound on the running time of M. We'll be simulating M on an input W, which is of length n. This next assumption is really about how we define the next ID relation. We're going to assume that if M accepts W, then there is a sequence of exactly P of n moves from the initial ID with the final state in the last ID, and perhaps other IDs as well. We're going to assume that if M is in an accepting state, then the identical ID represents one legal move. So if M enters an accepting state early on, then the sequence of IDs leading to acceptance can be extended to length P of n by repeating the first ID that has an accepting state. There is no harm in doing this. M is already accepted, so entering an accepting state more than once will not change anything. And this is an observation rather than an assumption. Remember that the head cannot move more than P of n squares in P of n moves. So we're going to represent each ID by a sequence of exactly P of n plus 1 positions, the first P of n tape squares, and the state. Initially, most of these are blank, but it's okay for some of these P of n plus 1 positions to hold a blank beyond where the head has reached so far, even if this blank is not technically part of the ID. We have to design a polytime transducer that can turn the input W into a Boolean expression that is satisfiable if and only if M accepts W. The transducer is designed knowing M but not W. The first thing the transducer does, seeing W, is to determine its length n. The expression that is output from the transducer will involve P of n plus 1 all squared, what we call variables. But these variables are not the propositional variables of Boolean logic. Rather, they are collections of propositional variables that together represent the symbol in a particular position of a particular ID. That is, the variable we'll call xij represents the jth position of the ith ID. Thus, I and j are each in the range 0 through P of n inclusive. Think of the variables arranged in an array. The rows represent successive IDs, and the columns represent positions in those IDs. We'll start with the initial ID, with the start state, input W, and the rest of the positions blank. We'll design the expression to be satisfiable if and only if M accepts W. We'll see that the expression constrains the values of the variables so that the only way the expression can be satisfiable is if each ID represents a move from the previous ID, or the previous ID has an accepting state and the next ID is the same. And the expression also requires that the state in the final ID, I sub Pn, is an accepting state. Thus, from M, which it knows, and W, which it sees, the transducer constructs an expression. Any satisfying truth assignment for this expression will give the x's the proper values that form an ID sequence of M with input W, leading to acceptance. Now remember, the x's are not Boolean variables. They represent states and tape symbols of M. However, each variable can take on only a fixed number of values, the sum of the number of tape symbols and the states of the known Turing machine M. Thus, we can represent each xij by this number of propositional variables, exactly one of which can be true. That is, for each state or tape symbol A, let y sub ija, that's this, be a propositional variable, and we want y sub ija to be true if and only if x sub ij equals a. As we describe the construction of the Boolean expression, we must make sure that we take time that is only a polynomial in n. There are many components from which the final expression is built, but they fall into two classes. Some depend on w and therefore depend on n. These components are and must be of size that is a polynomial in n. And more importantly, we can write them easily so that the time taken to write them on the output is polynomial in n. The second kind is those that depend only on m. These take a constant time as far as input size is concerned. That is, m may have lots and lots of states and lots of tape symbols, but these quantities are independent of n, so as far as we're concerned, they're all just constants. And to make our lives a bit simpler, don't forget that if an expression has a set of arguments whose size is fixed independent of n, then no matter how large the number is, it is a constant as far as n is concerned. So the time to write any such component is a polynomial in n. In fact, it's a 0th degree polynomial. Now let's start to describe the output of the transducer. The output is an expression, and we want it to be satisfiable if and only if m accepts w. The whole expression is the AND of 4 sub-expressions, each of which enforces one of 4 conditions. First is the sub-expression we'll call unique. It enforces the rule that there is only one symbol in each position of each ID. That is, the value of xij is unique. The second sub-expression is starts right. It forces the initial ID to be the start state followed by w. The next is moves right. This really should be moves correctly, but that's too many syllables. This expression enforces the condition that each ID follows the previous ID by one move of m. And as that convenient exception, if the previous ID has an accepting state, then the next ID may be the previous ID. Finally comes the expression finishes right. This condition says that somewhere in all that stuff is an accepting state. For unique, we use the AND over all IDs I, positions j, and states or tape symbols y and z of the expression, not y sub ij capital Y, or not yij capital Z. This little expression is satisfied as long as at most one of the two Boolean variables, yij cap y and yij cap z, is true. Put another way, if xij were to have two different symbols, say cap y and cap z, then one of these little expressions would be false. But unique is the AND of all these expressions, and the entire expression is the AND of unique and the other expressions. Thus, the entire expression cannot be satisfied by any truth assignment that makes any pair of variables yij and yij z both be true. Now let's formulate starts right. This expression requires the first ID to be the one m starts in with input w. Let w, whose length is n, consist of symbols a1 through an. We want x00, the first position of the first ID, to be the symbol that is the start state of m. That's used conventionally q0. And we want the next n variables to represent w. That is, x0i must be ai for all I up to n. And all the other positions of the first ID are blank. That is, x0i is blank for I between n plus 1 and p of n. But there's a propositional variable for that. Each of the conditions that makes up starts right is of the form some one of the x variables is a particular symbol. But that's what the propositional variables yija do. So we can write starts right as the AND of y sub 0, 0, q0 and y 0, 1, a1, the first symbol of w, and y 0, 2, a2, and so on. And after, let's say, y0 n a n, then you got to have y0 n plus 1 comma blank, and so on. So finish is right is easy. M accepts if and only if the last ID has an accepting state, because once M enters an accepting state, it appears to stay in that state until the ID numbered P of n. So take the OR of the Boolean variables y sub P of n, j, and q, where q is an accepting state and j is anything from 0 through P of n. Now let's see how long it takes to write down the 3 of the 4 expressions we have described. Remember, we have yet to describe the hard one, moves right. Unique is actually the most time consuming. It requires that we write down big O of p squared of n symbols. The p squared comes from the fact that we range over all I and j between 0 and P of n. The constant factor comes from the fact that for each I and j there are a large but finite number of pairs of states and their tape symbols, each of which needs a little expression. The number of pairs may be large, but it is independent of n, so it is a constant. And that expression involves 2 parentheses, 3 logical operators, and 2 propositional variables, only a constant number of things. But let me remind you again that the real issue is not how long the expression is, but how long it takes to write it. But the expression is simple, and it is simple to write the expression by looping on I and j, thus taking time proportional to its length. Starts right is the and of P of n propositional variables, and again the pattern is simple, so we can write this expression in order P of n time. The same holds for finishes right. There are P of n propositional variables, and we need to output those variables connected by ORs. Oops, I lied. The running times are a little larger than I said. Not enough larger to take us out of the polynomial class, but larger by a factor of log n. That is, I cannot really output a propositional variable like y sub ija in one step, or even a constant time. The reason is that we have to use a finite alphabet to represent order p squared of n propositional variables. We agreed to represent a variable by the symbol x followed by an integer in binary, like this. To represent order p squared of n variables requires integers whose length is order log n. But this is no big deal. A factor of order log n is less than a factor of n, so all it can do is raise the degree of a polynomial by 1, not even that much. So in what follows, we're going to ignore factors of log n and just assume we can write down a propositional variable in constant time and space. We're now going to start working on moves right. A lot of this expression simply says that xij equals xi minus 1j. That is, a symbol in the ith ID is the same as the symbol in the same position of the previous ID. That will be true whenever the symbol in that position is not the state, and neither are the positions to the left and right in the previous ID the state. Since a state can only move one position, we know nothing changes 2 or more symbols away from the state. So we're going to construct one sub-expression for each I and j, saying that either xij equals xi minus 1j, or the state is lurking about. The idea that the state is lurking is the OR of those propositional variables y sub I minus 1 k a, where k is within 1 of I and a is a state symbol of m. Now we need to translate the equality of xij and xi minus 1j into propositional variables, but we just need the OR of yija and yi minus 1ja, that's this, for all symbols a. The reason that works is that we already have unique to enforce the condition that for only one symbol a can yija or yi minus 1ja be true. The expressions we constructed for each ID I and position j will be part of moves right. Each says colloquially that the tape symbol can't change if the state isn't nearby. They will be ANDed together with expressions that enforce the correctness of the moves of m for the case when the state is nearby. To write the expression for moves right, we need to consider both the case on the left, where a position holds a tape symbol, and so do its neighbors to the left and right, and the hard case on the right, where the state is nearby. In the easy case, there is no doubt that the symbol in position j of the ith ID is the same as the jth symbol of the I minus first ID. We already covered this case in the previous slide with the expressions that say if the state is not nearby, then the symbol doesn't change. But in the hard case, there are three positions, the positions that hold the state in the I minus first ID and its neighbors, that can be affected by the move. Moreover, since we're simulating a non-deterministic Turing machine, there may be a choice of move, and we need to coordinate the three positions in the ith ID to make sure that all three reflect the changes of a single choice of move. For the hard case, the pieces of the moves right expression must do two things. It has to pick one of the possible moves of M, that is, a state of Q, a tape symbol A, and a direction, that is, the choice of one of the triples in delta of Q and A. And then, for that move, it must enforce the condition that when the jth position of the ID I minus 1 holds the state Q, and the j plus first position of the I minus first ID holds a symbol A, then in the ith ID, the positions j minus 1 through j plus 1 reflect that move. Note that either the j minus first or the j plus first position is unchanged, so the expression also has to enforce the condition that this position is unchanged from the previous ID. That is, suppose delta of QA contains, perhaps with other choices, a leftward move going to state P and writing B over the A. That would be that. Then, for any IDI position J and tape symbol C, that is, this is ID I minus 1, that's I. This is position j minus 1, that's j, and that's j plus 1. Okay. Then, one possibility for the 6 variables represented by this rectangle, that is this, is the combination that is reflected here. That is, P has moved, the state has become P has moved to the left. The C is unchanged, but its actual position is different. And the A has been replaced by a B. Similarly, if the move is to the right, that is something like that, then the 6 values are the ones we must enforce for the variables in this rectangle. And those, well, the C doesn't change at all. The state Q becomes P and it moves to the right. So it's here. And then the A got replaced by B and the B appears over here. Now we can assemble the parts of moves right that enforce the moves. We already gave the formulas that say if the state is none of x I minus 1 j minus 1 through x I minus 1 j plus 1, then xij equals xi minus 1j. That is, you can't change a symbol if the state is not nearby. Now we have to include expressions that constrain the 6 variable x's that are near the state in the I minus first ID. For each possible move, write an expression for each position j and each ID I that expresses the constraints on the 6 relevant x's for that move. There is one more type of move of M that isn't really a move. We need to allow no change in ID if M is an accepting state. For each accepting state of M, there's a fake move in which nothing changes. For each I and j, take the OR over all moves of M of the expression you just wrote for I and j. Now, for each I and j, you have an expression that says the 6 relevant x's reflect some move of M. Take the AND of these expressions over all I and j. Also include in the AND all the expressions from earlier that say symbols don't change if the state is not near. Okay, there's a small glitch in all this material. We assumed position j was not 0 or p of n, the leftmost and rightmost positions that are represented by the IDs. If j is one of these, there are only 4 x's involved, and we need to modify so that the missing symbols are assumed blank. The same fix-up is needed for the rules that say the symbol doesn't change if the state is not nearby. If the symbol in question is at one of the n positions 0 or n, then there is no possibility that the state is outside this range, and we can omit that requirement. Now consider how long it takes to write down the moves right expression. Moves right consists of the AND of 2 p squared of n expressions, 2 for each ID I and position j. One of the two is the expression that says the symbol doesn't change if the head is not nearby. The other says that if the head is nearby, then the 6 relevant symbols are related in such a way that they reflect one move of m. Each of these expressions can depend on the number of states, symbols, and moves of m, but none of this depends on n. That is, as far as the length of the input w is concerned, each expression is of constant size. We claim that each of the order p squared of n expressions is easy to write down in time proportional to their length by a transducer that knows the moves of m. So the transducer can output moves right in time that is polynomial in the length of its input w. As always, there is another factor log n because we must write the Boolean expression in a fixed alphabet, but factors of log n cannot take us out of the polynomial class. So, to sum up the proof of Cook's theorem, it takes time less than order p cubed of n for the transducer to output the Boolean expression that is the AND of the 4 key components: unique, starts right, finishes right, and moves right. We claim that this transduction really is a polytime reduction of the language of m to the language SAT. First, if m accepts w, then there is some ID sequence that leads to acceptance. Imagine the p of n plus 1 by p of n plus 1 matrix of the xij's. The accepting sequence of IDs lets us fill out this table correctly, giving the value to xij that reflects the sequence. The expression we constructed will be satisfied when we assign to the propositional variables yija the truth values implied by this choice of xij's. So if m accepts w, then the expression is satisfiable. Conversely, if we have a satisfying assignment for the expressions, we can get unique values for the xij's from the propositional variables. The unique expression assures that the xij's can be given unique values. And starts, finishes, and move right assure us that the xij's form an accepting computation of m with input w. That is enough to show that every polytime non-deterministic Turing machine's language is polytime reducible to SAT. We now have one problem, SAT, that we know to be NP-complete. We're going to reduce it to other problems in order to show them NP-complete as well. But it is easier to polytime reduce a special case of SAT called 3SAT to other problems. So our first step is to show that SAT is NP-complete even if the Boolean expression is in a very special form. The first restriction that we place on expressions is that they be in CNF, that is, conjunctive normal form. These expressions are the AND of clauses, and a clause is the OR of literals, and a literal is either a propositional variable or its negation. So our next step will be to show to be NP-complete the problem CSAT, which is whether a Boolean expression in conjunctive normal form is satisfiable. Here's an example of a CNF expression. The first clause, this, is x or not y or z. That is, x, not y, and z are each literals. The second clause is just this, not x. That's okay. A clause can be the OR of only one literal. The third is the OR of 4 literals, which are not w, not x, y, and z. Okay, we're not going to reduce SAT to CSAT. Rather, we'll examine Cook's proof and see where it needed to be fixed up to make the output expression be in conjunctive normal form. That way, we will have a direct reduction of every problem in NP to CSAT. Okay. Everything but moves right is already in CNF. You can review the constructions, but when you do, you'll find that unique is the AND of clauses. So is starts right. In fact, each clause has only one literal, which is in fact an unnegated variable. and finishes right is the OR of unnegated variables and therefore is a single clause. Now let's look at moves right. It is the AND of an expression for each I and j, where I is an ID number and j a position in that ID. Recall this expression says that either the head is not near position j and the symbol in position j of ID I is the same as the symbol in the same position of the previous ID, or the head is at position j in the ID I-1, and the three symbols of ID I around position j reflect one move of the polytime Turing machine M. Here's the subtle thing. As complicated as these expressions are, they depend only on M and not on the input length n. As a result, we can write the expression for a given I and j in conjunctive normal form. It is possible to convert any Boolean expression to conjunctive normal form. I'll show you the trick on the next slide. This conversion does, in the worst case, exponentiate the length of the expression, but it doesn't matter in this application because the only expressions to which we need to apply the conversion are expressions whose size is independent of the input length n. Thus, the time taken to convert to CNF for each expression is just some constant, independent of n. Here's how we'll convert a given Boolean expression to CNF. We'll consider each truth assignment that makes the expression false. Note that if there are k variables in the given expression, there could be 2 to the k such truth assignments, and the resulting expression will take that much time to write down. But again, we're only exponentiating a constant, and the result is still independent of the input size n. For each such truth assignment, we construct one clause. If variable x is assigned true in this truth assignment, then the clause has literal not x, and if x is assigned false, then the clause has literal x. That way, the only time the clause, which is the OR of all of these literals, is false, is if this is the exact truth assignment. The resulting CNF expression is the AND of the clauses for each truth assignment that makes the original expression false. Thus, the CNF expression is made false exactly for those truth assignments that make the original expression false, and therefore it is of course true exactly when the original is true. For example, consider the expression not x or y and z. This expression is made false by 3 truth assignments, those in which x is true and at least one of y and z is false. Let's convert the first truth assignment, where x and y are true and z is false. Here is the resulting clause. Since x and y are assigned true, the clause has not x and not y. Since z is assigned false, the clause has z without negation. Notice that the only way to make this clause false is to make each literal false, which means giving each variable its value from the truth assignment that generated the clause. The other 2 truth assignments generate the next 2 clauses, this and this, and the entire CNF expression is the AND of the 3 clauses. It is therefore made false exactly when the variables are given one of the 3 truth assignments. A Boolean expression is said to be in k conjunctive normal form, or KCNF, if it is the AND of clauses, each of which contains exactly k literals. The problem KSAT is whether a KCNF expression is satisfiable. For example, the expression we derived on the previous slide, which we show here, is in 3CNF. Notice it is the AND of clauses, and each clause has exactly 3 literals. We're going to prove that the problem 3SAT is NP complete. The easy part, as is often the case, is that 3SAT is an NP. We already saw that the general problem SAT is an NP. Just guess a truth assignment and check that it makes the expression true. Since 3SAT is a special case of SAT, the same non-deterministic algorithm works for 3SAT. We're going to prove the NP completeness of 3SAT by polytime reducing CSAT to 3SAT. We might suppose that the way to do that was to find a polynomial time algorithm to convert every CNF expression into a logically equivalent 3CNF expression. But not only can you not do that in polynomial time, you can't do it at all. That is, there are Boolean expressions that simply have no 3CNF expression. I'm not going to prove that formally, but an example is the expression with 4 variables that is true if and only if an odd number of the variables are true. that is, exactly one or exactly three of the four variables are true. Fortunately, the reduction does not have to preserve equivalence of the input and output expressions. Since we are dealing only with whether expressions are satisfiable, all we need to preserve as we transform the input expression to the output expression is that either both are satisfiable or neither is. Thus, we're going to give a polytime reduction that does not preserve equivalence. In fact, it doesn't even preserve the set of propositional variables. Rather, it introduces new variables into clauses that have more than three literals in order to split them up into many clauses of three literals each. So, consider a clause with k literals, x1 through xk. Remember, these are literals, not variables, so any of the xi's could be not followed by a propositional variables. We need k minus 3 new variables, which we'll call y1 through yk minus 3. These y's appear in no other clause, and they're really variables, not literals. Also notice that if k is equal to or less than 3, then no new variables are introduced. We're going to replace the clause x1 through xk by k minus 2 clauses. The first consists of the first two literals, x1 and x2, and the first new variable unnegated, that's y1. The second, which is this, has only one of the original literals, x3, and two variables. The previous variable, y1, is negated, while the next variable, y2, is not negated. That pattern repeats. Each new clause has one of the original literals, say that, a negated previous y, and an unnegated next y. Then finally, the last of the new clauses has the last two of the original literals, and only the previous y negated. We need to show that when we make this change, the new expression is satisfiable if and only if the original expression was. For the first direction, we'll show that if there is a satisfying truth assignment for the original expression, then we can extend this truth assignment to also provide truth values for the y's that will make the and of all new clauses true. So suppose that there is a satisfying truth assignment for the original expression. Then this assignment makes at least one of the literals, the x's, true. Say it makes xi true. Then we can assign y sub j the truth value true for j less than I minus 1, and assign y sub j the value false for y equal to or greater than I minus 1. For this truth assignment, the clause with xi, that is this one, is made true by xi. All the previous clauses, those there, can be made true by their unnegated y's, and all the later clauses, all of these, are made true by their negated y's. Conversely, suppose that there is a truth assignment that makes all the new clauses true but makes none of the literal x's true. Assuming that no x's are true, the fact that the first clause is true, that is this, says that y sub 1 must be true in this hypothetical truth assignment. And then the second clause says that since x sub 3 is false, and not y sub 1 is already known to be false because we had to make y1 true, that means that y2 must be true. We can reason the same way to show that all the y's are true. But then the last clause, this, which has only false x's and a negated y, must be false. We have shown that when we convert one long clause of the input to a sequence of clauses with three literals per clause, the satisfiability or non-satisfiability of the expression is preserved. We can repeat this argument for every long clause, thus converting the original expression to an expression with at most three literals per clause, and that is satisfiable if and only if the original is. Technically, we are not done, because the original expression could also have clauses that are too short. For a clause with only one literal x, we introduce two new variables, y1 and y2, and replace one clause by the four clauses shown. Notice that the y's appear in all four combinations. So if x is false, one of these four clauses will be false, no matter what truth values we assign to the two y's. For example, if y1 is true and y2 is false, then this clause will be false whenever x is false. But conversely, if x is true, then all four clauses are true regardless of the truth values of y. And don't forget that these introduced y's are new. They appear in no other clauses, just like the y's we introduced to split apart the long clauses. And the final case is a clause with two literals, say w and x. For this clause, we introduce one new variable y and replace w plus x by two clauses, one with a non-negated y, the other with a negated y. The same argument as for the clause of a single literal applies here. If a truth assignment makes both w and x false, then one of the two new clauses will be false. But if the truth assignment makes at least one of w and x true, then both new clauses can be made true. Okay. The conversion of the clauses from the input CNF expression to clauses in 3CNF takes only linear time and the length of the input sequence. That is, we run through each long clause, generating new variables and new three literal clauses as we go, taking time that is proportional to the length of the original clause. The constant of proportionality may be large, but the algorithm is still linear. Well, we have to be careful, as always, to remember that there is a finite alphabet involved. That means when we create new variables, the y's, it may take log n time to write down their numbers, so the algorithm really could take order n log n time to generate the output expression. But as always, we'll ignore factors of log n. They cannot take us out of the polynomial class. We thus have a polytime reduction from the problem CSAT to the problem 3SAT. And since CSAT was shown NP-complete by the modified construction in Cook's theorem that produced the CNF expression, it follows that 3SAT is also NP-complete. Now it's time for the payload of the theory of NP-completeness. We're going to see some perfectly ordinary problems, not apparently related to computation in any way, that are also NP-complete. Of course, we can cover only a tiny fraction of the problems that are known to be NP-complete. But the methods, ways of designing reductions, are the things to take away from this discussion. If you encounter a problem in your work and can't come up with an efficient solution, there is a good chance that you can devise a reduction that proves it NP-complete. That proof guides your thinking. You need to consider, for example, whether you need to solve the problem in all its generality, or whether a simpler special case would give you what you need. You need to consider efficient algorithms that offer an approximation to what you really want. Without the assurance that the problem is NP-complete, you are less likely to want to attempt, or to justify to your boss, taking one of these simplifying steps. But before moving on to reductions that show the problem's node cover and knapsack to be NP-complete, we introduce one more nuance into the theory. NP-hard problems are those that would be NP-complete if only they were in NP, but that are probably or certainly harder than anything in NP. We talk about the tautology problem, which is an example of such a problem, even though it is very closely related to the problem SAT. We are ready to reduce 3SAT to a number of other problems, thus showing each of them NP-complete. These reductions can be directly from 3SAT or from another problem that we previously proved NP-complete. Remember, the key issue is that each reduction must be in polynomial time. However, in most cases, the construction is computationally simple, so as long as the output is of length polynomial in the input, it will be easy to argue that the running time of the transducer is polynomial. Of course, if a problem is NP-complete, it must be in NP. Usually this part of the proof is quite simple, since a non-deterministic polytime Turing machine can use its non-determinism to guess a solution in linear time and then check that it has guessed the solution using some polynomial amount of time. However, there are some interesting cases where we can only show a problem to be NP-hard, meaning that if it is in P, then P equals NP, but the problem itself may or may not be in NP. A curious example of an NP-hard problem is the tautology problem. A Boolean expression is a tautology if it is true for every truth assignment. For example, this expression is a tautology. Every truth assignment makes x either true or false. So one of the first two terms, that is this or that, will have to be true, and therefore the whole expression is true. We don't even need the term y and z. If you look at Cook's original paper on NP completeness, he was really trying to argue that tautologies required exponential time to recognize. Because tautologies are the theorems of logic, that's what logicians care about, not satisfiable expressions. Cook was able to reduce all of NP to satisfiability, but that is enough to show that if there were a polytime algorithm for tautologies, then P equals NP. We'll address this point in a few slides. In fact, there is good reason to believe the tautology problem is not an NP. On the other hand, as complement, the non-tautologies, including those inputs that don't make sense as Boolean expressions, is an NP. We use the non-determinism to get a truth assignment and evaluate the expression in polynomial time for this truth assignment. If the value is false, then the non-deterministic machine accepts its input. On the other hand, if the non-deterministic machine accepts whenever it finds the value to be true, it accepts the satisfiable expressions, not the tautologies. The class of languages called co-NP is those languages whose complement is an NP. For example, we just argued that the tautology problem is in co-NP because the non-tautologies are in NP. Okay, now P is closed under complementation. We didn't prove this exactly, but it is easy to show because if I have a deterministic Turing machine that halts within P of n steps for some polynomial P of n, we can modify it to accept the complement language. Just have the new machine simulate the original. It halts without accepting if the original machine accepts, and it goes to a new accepting state if the original halts. Since the complement of every language in P is also in P, it is surely an NP. That proves the class P is a subset of co-NP as well as of NP. Another important connection is that if P does equal NP, then P also equals co-NP, and therefore NP and co-NP are equal. However, it is possible, but unlikely, that NP and co-NP are the same, but that they are bigger than P. We can prove the tautology problem to be NP hard. For the proof, suppose there is a polytime algorithm for the tautology problem. Then given a Boolean expression E, convert it to not E, which takes only linear time since all we have to do is add not and a pair of parentheses. Now notice that E is satisfiable if and only if not E is not a tautology. So use the hypothetical algorithm for the tautology problem to tell whether or not E is a tautology in polynomial time. Then just complement the answer. That is, say E is in SAT whenever the answer you got is that not E is not a tautology, and say E is not satisfiable whenever not E is found to be a tautology. That would be a polytime algorithm for SAT, which would show P equals NP. That is all we need for proof that tautology is NP hard. Now let's meet a real problem from operations research that CARP proved to be NP complete. A node cover for a graph is a set of nodes of that graph such that every edge has at least one of its two nodes in the set. We need to express the problem of finding the smallest possible node cover as a yes-no problem. We do so by asking whether, given a graph G and an integer k, does G have a node cover of size k or less? This is the formal problem or language called node cover. Notice that if we had a polytime algorithm for the minimization problem, that is, given a graph, find a node cover of smallest size, then we could prove that the formal problem node cover was in P. Just use the hypothetical polytime algorithm to find a smallest node cover, count the number of nodes in the cover, and see if it is at most k. That means that once we prove the formal node cover problem, or the yes-no version of the problem, to be NP complete, we also know there is no polytime algorithm for the minimization version unless P equals NP. Here's an example of a graph. One of the interesting things about NP-complete problems, and node cover is one such, is that even small instances of the problem seem hard. So how small a node cover can we find for this graph? Do you see the answer yet? Well, we'll work it out. We have to pick either C or D for our node cover, or else the edge CD isn't covered. We may as well pick C because C covers every edge that D covers, and more. We also have to pick either A or E, else the edge AE is not covered. But picking C and either A or E does not cover the edge BF, so we need at least 3 nodes in the cover. But here's one example that works. B, C, and E together cover all the edges. Thus, given this graph and the budget k equals 3, the answer is yes. The same answer applies if the instance of node cover in this graph is this graph with a higher budget. However, if we are given this graph with a budget 2 or less, the answer is no. We're now going to prove node cover to be NP complete. Okay, we'll give a polytime reduction from 3sat. Given an instance of 3sat, we construct a graph. There is a node for each literal of each clause, so the number of nodes is 3 times the number of clauses. It helps to imagine the nodes arranged in a rectangle, where the columns correspond to the clauses. Each column has 3 nodes, 1 for each of its clauses. There are vertical edges connecting each pair of nodes in a column, and thus there are 3 vertical edges per column. There are also horizontal edges that connect nodes in different columns. 2 nodes are connected if they represent literals with the same variable, and exactly one of those literals has that variable negated. And finally, the budget k is twice the number of clauses, which is also exactly 2/3 of the nodes. So here's an example of an instance of 3sat with 4 clauses. We'll construct a graph that has a node cover of 8 nodes, if and only if this expression is satisfiable. So here's the column for the first clause. The literals of the first clause are x, y, and z with no negations. So those are the labels of the 3 nodes in this column. And similarly, we construct a column for each of the other clauses. It is convenient that all 4 clauses have the same 3 variables in order, either negated or not. So this graph is going to turn out to be easier to understand than might be the case otherwise. Now we add the horizontal edges. For example, in the top row, where all of the x's are, each node labeled x is connected to each node labeled not x. Again, because all of the x nodes line up and the horizontal edges are truly horizontal. In more complex examples, they would not be, although they always go between columns. Similarly, we see connections in the second row between nodes y and nodes not y, and in the third row are the edges between z and not z. And the final part of the output is the budget k. Since there are 4 clauses, the budget is k equals twice that, or 8. The first thing to observe about the constructed graph is that a node cover must have at least 2 of the 3 nodes in every column. If it has only 1 node in a column, then the vertical edge between the 2 unselected nodes will not be covered. And if the node cover has 0 nodes from a column, then all 3 edges in that column will be uncovered. But the budget is exactly twice the number of clauses. So if all 3 nodes in one column were in the node cover, then some other column would be shortchanged. It could get only 1 node and we would not have a node cover. The conclusion is that there can be no node cover with fewer than k nodes, and if there is a node cover of exactly k nodes, then these k nodes must be exactly 2 from each column. We're going to show that there is a tight relationship between the node covers and the truth assignments, and this connection goes through the nodes that are not selected for the node cover. That is, a satisfying assignment for the 3sat instance will yield a node cover if we omit from the node cover one of the nodes from each column that is made true by the assignment. And conversely, a node cover with 2 nodes per column will give us a satisfying assignment by making all the literals whose nodes are uncovered to be true. We'll prove all this in a minute, but first an example. For example, here's the 3sat instance we saw earlier, and here's the graph with budget 8 that we constructed. Here's a truth assignment. It happens to be a satisfying assignment, so we can pick a node from each column that is made true by the assignment. Here's one such choice. There are others. For example, in the first column we could have picked y instead of x. I claim that if we take the other 2 nodes from each column, we get a node cover. Surely all the vertical edges are covered since we have 2 nodes in each column. But what about the horizontal edges? Suppose we have a horizontal edge, say with x at one end and not x at the other. and neither end is in the node cover. That means both were selected as the literal that made their clause true. But how could that be? They can't both be true in any one truth assignment, so they can't simultaneously make their clauses true. We need to show that what we described is a polytime reduction from 3-sat to node cover. It is easy to see the transducer takes polynomial time. It works clause by clause, generating no more nodes than there are literals. The vertical edges can be generated at the same time, and they number only 3 per clause. The horizontal edges can be generated easily if we list all the nodes labeled by each literal. After seeing all the clauses, we can generate horizontal edges. For each variable x, we look at the list of nodes for literals x and not x. We generate edges for all pairs, one from each list. The total number of edges generated is no more than quadratic in the length of the input, and the edges can be generated in constant time each. We also need to show the reduction is correct, of course. That is, if we construct graph G and budget K from the 3-sat expression E, then G has a node cover of size K or less if and only if E is satisfiable. For one direction, suppose E is satisfiable and let A be a satisfying truth assignment. The argument that G has a node cover of size K is really just the argument we gave for our example earlier. That is, we begin to construct the node cover by selecting for each clause of E one of the literals that truth assignment A makes true. We know there is one because A is a satisfying assignment, and the only way to make a 3-sat expression true is to make each clause true. Then the node cover consists of the 2 unselected nodes from each column. Notice that some of these nodes may also have their literal made true by assignment A, but it doesn't matter. The important thing is that the unselected nodes all correspond to true literals. This selection of nodes has exactly k nodes, since k is twice the number of clauses. So if we can prove it is a node cover, then we have shown that G has a node cover of size at most k, in this case exactly k. We claim the nodes we selected include at least one end of each edge, so indeed we have selected a node cover. First, consider the vertical edges. We selected 2 nodes from each column. There are only 3 nodes per column, so only one is unselected. Thus, any edge in that column has at least one selected end. And how about the horizontal edges? Okay, each horizontal edge has ends corresponding to literals x and not x for some propositional variable x. The truth assignment A has to make either x or not x false. Whichever is false could not have been selected as the literal that makes its clause true. Therefore, it is surely selected for the node cover. That means every horizontal edge is covered, and the k-selected nodes do indeed form a node cover. The converse also follows the outline of the proof we gave in our example. So, suppose G has a node cover with k or fewer nodes. Since all the vertical edges must be covered, there must be at least 2 selected nodes in each column, because one selected node can cover only 2 of the 3 edges. We claim that from the nodes not selected for the node cover, we can figure out a satisfying assignment for E. If there is an unselected node corresponding to literal x, then make propositional variable x true in the truth assignment. If there is an unselected node corresponding to literal not x, then make x false. We'll see why this works on the next slide. Well, what could go wrong? We might have made a truth assignment that makes some variable x be both true and false. That is, nodes corresponding to both literals x and not x might have been outside the node cover. But that can't happen because there is a horizontal edge between these 2 nodes, and therefore at least one is in the node cover. Thus, we do have a consistent satisfying assignment, and the expression E is in 3-sat whenever G has a node cover of size up to k. Now let's revisit our old friend the knapsack problem. We're going to prove knapsack is NP-complete, but it is easier first to reduce 3-sat to a variant of knapsack, which we'll call knapsack with target. That is, given a list of integers L and an integer target k, is there a subset of L that sums to exactly k? Once we've shown knapsack with target NP-complete, we'll reduce it to the real knapsack problem, which is given a list of integers L. Can we divide L into 2 parts whose sums are the same? We have to show knapsack with target is an NP, but that, as usual, is an easy argument. just use the non-determinism to guess a subset of L, then compute the sum of the integers in the guessed subset, and accept if that sum is exactly k. We're going to reduce 3sat to knapsack with targets, so suppose we have an expression E in 3C and F and a target k. Let E have C clauses and V propositional variables. We're going to think of the integers in the list L we construct as written in base 32. We can write them in binary, so we need 5 characters per digit, but the factor of 5 is of no importance if we are only worried about performing the transduction from 3sat instances to knapsack instances in polynomial time. The length of each integer will be C plus V, so each integer could be as long as the entire expression E. There will be 3C plus 2V integers. That means the length of the output could be on the order of the square of the length of the input. But that's okay, it's still a polytime transduction as long as we can generate the integers in time proportional to their length, which we can. Here's a picture of some of the base 32 integers we will use, those for the literals. Notice that each digit will be either 0 or 1, but the base is still 32. We need a base that large to avoid carries from place to place when we add integers. The high order V positions represent the variables. We'll have one integer for each literal xi or not xi, and thus there will be 2V such integers. The integer has a 1 in the ith position from the left end of the first V positions if it corresponds to a literal based on propositional variable xi, that is, it's either xi or not xi. The C low order positions correspond to the clauses. The integer for a literal will have a 1 in the position for each clause that it makes true, and all other positions in this integer hold zeros. There will also be 3 integers for each clause. The integers for the ith clause have, respectively, the base 32 digits 5, 6, and 7 in the ith position from the left end. All other positions are 0. So here's a tiny example. There are 2 clauses and 3 variables in this expression, so C equals 2 and V equals 3. Let's number the 3 variables x, y, and z by 1, 2, and 3 respectively, and number the clauses 1 and 2 in the order in which they appear. Let's see the base 32 integers constructed for this example. Okay. First, consider the literal x. There are 3 variables, so the first 3 positions correspond to the variables. X is the first, so its position is at the left end of the first 3 positions. That's here. Thus we see a 1 there and 0 in the first 2 positions. The last 2 positions correspond to the 2 clauses. When x is true, both clauses are made true, so we have 1s in each of the last 2 positions. Now consider a literal not x. The first 3 positions are the same as for literal x, but not x doesn't make either clause true, so the last 2 positions are both 0. That is, these. Here are the integers for y and not y. Among the first 3 positions, they both have their 1s in the middle, as they should. Y makes the first clause but not the second true, so it has a 1 in the low order position, and that's the one that corresponds to the clause 1, and it has 0 in the second from last position. These digits are switched for the literal not y, because not y makes the second clause true but not the first. And here are the integers for z. In the 3 high order positions, they each have 1 in the highest position, as that. Like y, z makes the first but not the second clause true, so the 2 low order positions look like the previous 2 integers. That is, these are like those. Now let's look at the integers for the clauses. For clause 1, we have integers with 5, 6, and 7 in the low order position, and for clause 2, we have the same digits in the second lowest position. We'll pick the target as shown. Note that k in base 32 is v1s followed by c8s. Thus it is easy to write down in time proportional to the length of the input to the transducer. We claim that when we add a subset of the 2v plus 3c integers, there cannot be any carries from one place to the next higher place. We'll see why on the next slide. In the high order positions, only two integers have a 1 in any position, so there can be no carries there. For the low order positions corresponding to the clauses, each position has integers with 5, 6, and 7 there. Even if all three are in the selected set, that's only 18, not enough. But what other integers could contribute to a low order position? Only the three integers for literals that appear in the clause that corresponds to that position. But these three integers only have 1 in that position, so the maximum sum in any position is 21. So there are no carries. But we could have made the base 22 instead of 32, but 32 is easier to convert to binary, so we went with 32. The important consequence of no carries is that the target can only be met by making each position in the sum match the corresponding position of the target. We'll see how this connects satisfying truth assignments to knapsack solutions in the next slide. First, consider the high order positions, the positions for the variables. If the sum of a set of integers matches the target, then the sum must be 1 in that position. That means either x or not x is true for each propositional variable, but not both. That in turn means that the selected integers correspond to a truth assignment. Now let's look at the low order positions for the clauses. The target has 8 in that position. We can't have 2 or 3 of the integers that have 5, 6, or 7 in that position. The sum would be too great. The only way we're going to have integers that sum to 8 in position for a clause is if between 1 and 3 of the integers corresponding to the literals of that clause are chosen, and we can use one of the integers 5, 6, or 7 to make up the difference and reach exactly 8. Now we need to prove the construction we just gave works. First, I hope you see how to construct a single integer for the output in time proportional to the n, which is both the length of the input expression e, and to within a constant factor, the length of the integer itself. Since the number of integers is proportional to the number of clauses plus the number of variables, and there can't be more than n variables in an expression of length n, it is also true that the number of integers in the output is at most proportional to n. Thus, the output can be constructed in time on the order of n squared, and the transduction is polynomial time. We need to show it as a correct reduction. As always, there will be two parts. First, we'll show that if e is satisfiable, then there is a subset of integers summing to exactly k. That is, the output instance of the knapsack with target problem has a solution. Then we'll show the converse, that if there is a solution to the output instance, then the input expression is satisfiable. For the first direction, assume e is satisfiable and let a be a truth assignment that makes e true. For a subset of integers, we'll start with the integers that correspond to the literals that a makes true. That gives us the necessary 1 in the position for each of the variables, that is the high order positions. The integers we selected so far make each clause true, so their sum in the positions corresponding to the clauses, that is the low end positions, will each sum to 1, 2, or 3. So for each clause, add to the set of integers we're choosing the integer that has 5, 6, or 7 in that position, whatever is needed to make the sum be 8 in that position. Now we have a set that sums to 1 in each of the high order positions, that is the positions for the variables, and to 8 for each of the low order positions, that is the positions for the clauses. That sum is exactly the target, so there is a solution to the output knapsack instance. Now we must show the converse. Assume the output instance has a solution, a subset of its integers whose sum is the target. First, look at the high order positions, those corresponding to the variables. The subset of selected integers matches the target, so it has 1 in each of these positions. The only way that could happen is if we select exactly one of the two integers for the variable corresponding to that position. If x is that variable, that means we picked either the integer for x or the integer for not x, but not both. That means we have a truth value for each variable x. If we pick the integer for x itself, then make x true, and if we pick the integer for not x, make x false. Either way, the literal for the integer we picked is true in this truth assignment, which we'll refer to as a in what follows. Now, look at the position for one of the clauses. We discussed earlier that with only 5, 6, and 7 available for a given position, we have to pick exactly one of them if we are to reach 8 in that position. But we can only reach 8 if the selected integers for the variables have among them something between 1 and 3 ones in that position. That means the truth assignment A must make each clause true, and therefore A is a satisfying assignment. We have now proved that when an output instance has a solution, the input instance is satisfiable. That was the second of the two needed directions, so now we know the transduction is correct. The output has a solution if and only if the input is satisfiable. We're now going to prove the original knapsack problem is NP-complete. We'll refer to it as partition knapsack, but it is exactly what we earlier called just knapsack. That is, given a list of integers, can we partition them into two disjoint sets with equal sums? We'll show partition knapsack to be NP-complete by reducing knapsack with target to it. Remember, we already saw that partition knapsack is an NP, but if you forgot, just guess the partition and sum the two sets. Here's the essence of the reduction from knapsack with target to partition knapsack. Suppose we're given an instance of knapsack with target, say the list L and target K. The first thing we need to do is compute the sum S of all the integers. That takes time proportional to the input length n. Now we can make our output, which is an instance of partition knapsack. This output is a copy of the list L followed by 2 or more integers. One of those integers is 2k, that is twice the target, and the other is S, the sum of all the integers on list L. Here's an example of a knapsack with target instance, the list L consisting of the integers 3, 4, 5, and 6, and a target of 7. The resulting instance of partition knapsack has the same integers, then 2k, which is 14 in this case, and finally the sum S of 3 plus 4 plus 5 plus 6, which is 18. This instance of knapsack with target has a solution. We can select the integers 3 and 4 from L. Their sum is the target 7. The output instance of partition knapsack also has a solution. Take the integers in the solution to the input instance, that is 3 and 4, and include the last integer, the sum of all the integers on list L. Notice that both the selected integers, 3, 4, and 18, and the unselected integers, 5, 6, and 14, sum to 25, which means we have a solution to partition knapsack. That turns out not to be a coincidence. Including the integer that is the sum of L always turns a solution to the input instance into a solution to the output instance. We'll see that when we prove the correctness of this polytime reduction. So here's the proof of correctness. First, observe that the sum of the integers in the output instance of partition knapsack is 2 times S plus K. That is, the integers on list L sum to S, and there's another integer S in the output list, so that makes 2S. And then there is an integer 2k in the output list, which makes 2s plus 2k. Therefore, if we are to partition the output list into 2 parts, each part must sum to s plus k. First, suppose the input instance of knapsack with target has a solution. That means there is a subset of L that sums to k. In the output instance, we can pick this subset of L plus the integer s to sum to s plus k. Of course, what remains will also sum to s plus k, so we have a solution to the output instance. And conversely, suppose there is a solution to the output instance. We claim that the two integers s and 2k cannot be in the same partition because their sum is s plus 2k, and that's more than half the sum of all the integers in the output instance, which recall is 2s plus 2k. Now, if the output instance of partition knapsack has a solution, then the subset of L that is in the same partition as the integer s must sum to s plus k. That's half the total. That means the subset of L sums to exactly k. Now look at the input instance of knapsack with target. We just showed that there is a subset of L that sums to k, so this subset is a solution to the input instance. That completes the proof that the input instance has a solution if and only if the output instance has a solution. We therefore have a valid polytime reduction from knapsack with target to partition knapsack and we now know the partition knapsack problem is also NP complete. Good afternoon. Spring has hit California. You can see that I am wearing one of my Hawaiian shirts, unlike the button-downs that I recorded the lectures in. So everything's feeling good. And in this video, I'd like to discuss a few questions that have arisen in the discussion forum and that I think may represent common misconceptions. First, I want to remind everyone to be aware of the types of things that we discuss: strings versus characters, and so on. Then I want to point out a subtle difference between an automaton accepting a string and accepting a language. And finally, there are a few interesting edge effects that we need to understand. You may have heard of the Zen koan, "What is the sound of one hand clapping?" I don't know, but here we face a harder problem. Under the sound of no hands clapping, I want to remind people what it means, for example, to compute the sum of 0 integers. We're familiar with types or classes from work with most any modern programming language. The things we talk about in an automata theory also have types, and confusing one type for another is just as dangerous here as it is in programming. Two distinctions I want to emphasize today are, first, between characters and strings, and then between sets and the members of those sets. A string is a sequence of 0 or more characters. In most programming languages, double quotes are placed around a string, and single quotes around a character. The distinction is most important when the string is of length 1, because then it looks just like a character if you don't do something like double quote it to indicate its type. Most importantly, epsilon is the way we represent the empty string. In most languages, the way to represent the empty string is by double quotes with nothing in between them, like this. And I think most confusion occurred when people noticed that in an epsilon NFA, some arcs are labeled by the string epsilon, while others are labeled by input characters or input symbols. Previously, DFAs and ordinary NFAs had all arcs labeled by characters, but epsilon is not a character, and yet we appeared to use it where you expected an input symbol, that is, a character, to appear. But there is no real problem, since a character can be coerced to be a string of length 1. It's in fact very natural in programming languages. For example, in Java, an easy way to convert characters to strings is to write the empty string concatenated with that character. Since characters are coerced to strings, the character, say 0, is converted to the string 0 and concatenated with the empty string, which leaves just the original character but converted to a string of length 1. So for an epsilon NFA, just think of the characters labeling the arcs as strings of length 1. Then you can concatenate the epsilons and characters along any path and get a string naturally. As with any kind of automaton, the sequence of labels along any path is of type string. Here's a pretty picture of a path in an epsilon NFA. It doesn't matter whether the states are distinct or if some repeat along the path. You just concatenate the labels. Epsilon, the string 0, the string 1, the string epsilon again, string 0. The concatenation of these 5 strings, then, is the string 0, 1, 0. Now let's move on to sets and elements. Elements come in many different types, for example, integers, strings, characters, and so on. Sets can have elements as members, so for example, a language in the world of automata theory is a set of elements of type string. That is, the type of a language is set of strings. And remember that epsilon is a string, while the empty set is a set. There is a notion of membership that relates a set to the members of that set. A set can have members. The element types, like string, do not have members. Technically, the members of a set can be sets themselves, but we're not going to talk about such sets much. Occasionally, we mention the power set of a set S, whose members are each of the subsets of the set S, and thus are sets themselves. But in most cases, you can assume that sets have members that are elements and not sets. The empty set is a set, but it has no members. All other sets do have one or more members. And elements do not have members either. For example, epsilon has no members. But the reason epsilon has no members is because it is of a type for which having members makes no sense. We must not confuse the empty string with the empty set. They each have no members, but for very different reasons, and their types are not the same. Let's see how the set-element distinction applies to states of a non-deterministic finite automaton. First, states of any automaton are elements, not sets. The subset construction seems to create a DFA whose states are sets of the states of the NFA. But really, what we are doing is computing sets of NFA states and giving each one a name. This name is the name of a DFA state, and each DFA state corresponds to a set of NFA states, but the DFA state is an element with an associated value, and the value is the set of NFA states. We can even use the set of NFA states as the name of the DFA state, but we should then understand the notation for the set. Like the set containing P and Q, that is this, is a string that is the name of a DFA state. Here's another point that has caused some confusion. Automata accept strings, the labels of the paths that lead from the start state to an accepting state. But we also said that an automaton accepts a language. This language is the set of strings that the automaton accepts. If we say automaton A accepts language L, then we mean that L consists of all and only the strings that A accepts. Thus, while the typical automaton accepts an infinite number of different strings, it accepts exactly one language, the set of strings that it accepts. Let's remember that the phrase automaton A accepts language L means that L is the one language of A. A accepts all the strings in L, and A does not accept any other strings. The extreme case of the confusion would be an automaton like the one shown, which accepts every string, but only accepts one language, the one we refer to as 0, 1 star. That's this. That is, it's the language of all strings of zeros and ones. If you don't see the difference between accepting strings and accepting a language, you would erroneously conclude that this automaton accepts every language whatsoever, such as the set of 0 to the n, 1 to the n, such that n is equal to greater than 1. It doesn't. It accepts this language, set of all strings of zeros and ones. I now want to talk about a point of confusion that comes up in several places. What happens when you try to apply an operation to zero things? For example, we know what it means to sum 2 integers or 10 integers, but what if we are asked to sum 0 integers? Or if I have a string of zeros and ones, it makes sense to ask whether the string has an even or odd number of zeros. But what if the string is empty? So, for example, 4 plus 7 plus 3 equals 14, no problem. If I just want to sum 4 plus 7, I'll cross out the 3, again no problem, that's 11. If I just want to sum the 4, no 7 there, fine, that sum is 4. Now, if I take the 4 away, what's left? What is its sum? I claim that in general we should take the operation applied to nothing to be the identity for that operation. For sum, the identity is 0. That is, 0 plus anything is that other thing. This is a well-accepted convention. I can't prove to you that the sum of zero things must be the identity zero, but neither have I seen a reasonable justification for any other convention, and if you have one, it would be a great topic for the discussion forum of the class. And it is natural and intuitive, as we can see, if we write the obvious code to sum the n elements of an array. Here's what the code looks like. You initialize the sum to 0, there, and then go through the array in a loop, and you go through n times. You'll get the correct sum for any n equal to or greater than 1, but what happens if n happens to be 0? If that's the case, you never execute the loop, you just jump right around it, and the sum is left at 0. And initializing the sum to anything but 0 makes no sense and would not give the correct result for n equals or greater than 1 unless you did serious contortions to the code. Here are some other examples where the identity for the operator is the only thing that makes sense. The OR of zero propositional variables is false because false is the identity for OR. That is, false OR x equals x. Similarly, the AND of no propositions is true because true AND x equals x. The product of no integers or reals is 1 because 1 times x equals x. And if we concatenate 0 strings, we should get the empty string, since epsilon concatenated with any string x is x. As an example of why the convention for strings makes sense, look at an automaton where the start state is also an accepting state. This automaton has more to it, I just didn't draw it. There is a path from A to A that goes through no arcs. It is of length 0. In general, the string that labels a path is the concatenation of all the strings that come from the input symbols along that path. Again, remember that the characters labeling the arcs are converted to strings for concatenation. But in this case, the path has no arcs, so its label must be the concatenation of 0 strings, that is, the empty string. That's great, because it means that the empty string is accepted by this automaton. And since the automaton starts out in an accepting state before it reads any input, that makes sense. Next, let's look at the question of whether 0 is odd or even. Curiously, this question causes a great deal of disagreement. For example, I remember one day in 1973 when we had gas rationing. You could only fill up on a day whose number was even if the digits on your license plate formed an even number, and ditto for odds. But what if your license plate had no digits, a vanity plate like lover? Okay. Since legislatures are not mathematicians, different states had different policies, some treating a plate like this as odd and others as even. But we know that 0 is even because it leaves remainder of 0 when divided by 2. That is, 0 is 2 times an integer, namely 0 in this case, plus a remainder of 0. And anything that leaves that is of the form 2 times any integer plus 0 is even. Now the empty string has 0 of every character, and 0 is even. So if we ask a question like, does the empty string contain an even number of some character like 0, the answer is yes. And if we ask whether it has an odd number of zeros, the answer is no. Okay, and here's a bonus answer. Okay, few people actually use automaton and automata correctly. Let's learn to be pedants and use them right. Okay, automaton is a singular noun and it's plural, and a regular plural because of its Greek origin is automata. 1 automaton, 2 automata. But it gets worse. Okay, everybody says automata theory, never the singular form automaton theory. But other theories use a singular form of the noun that describes what they are about. For example, physicists talk about string theory or quantum theory, never strings theory or quantums theory, well, that should be quanta theory anyway, since quantum is another irregular plural. And don't ask me why. Anyway, see you in class.
Hello everyone, I am Chen Guangzhu, the teaching assistant for this course. Today, I will host the second problem session. We will discuss several topics which cause confusion in some students, and this will include cleaning star and paths in the DFA. Then we will show the solution for the first challenge problem. Let's begin with cleaning star. Cleaning star is an operation on regular expressions. For example, we can have 1 star, where 1 is a regular expression of length 1. However, there is a common misconception that 1 star is an infinite long string of 1s. This is not the case. In fact, 1 star is still a regular expression, whose language, L1 star, is the set of strings of 0 or more 1s. Although this set is infinite, each element in it has finite length. This is similar to the set of integers, where the set is infinite, but each element it contains is finite. Now we come into the topic of infiniteness. As we know, infinite objects are important in mathematics, like the set of integers or a line that contains an infinite number of points. Yet, in a computational model, a computer can never get an infinite input, unless you can represent it in finite form. For example, we can represent a regular language with a regular expression, which has finite length. We can also store 3 numbers as parameters for a line. In such cases, we extract important information that can represent the whole set. This concept is a bit like sufficient statistics, in case you have heard of it. Now we will take a minute to discuss a fallacy we found in the forum. In the thread, it talks about a DFA that accepts all strings of 0s and 1s except those whose last character is 1. Then a student asks, what about the string 1? Basically, sometimes we fall into the fallacy that you cannot have a last character unless you have other characters. This is not true. In fact, if we resort to strict mathematics, we would define that for n greater than or equal to 1, the last character of any string a1, a2 through an is just an, period. Thus, coming back to the question, the string 1 is not accepted by this DFA, because the last character is 1. Another thing worth mentioning is that the empty string, epsilon, has no last character. Thus, the statement its last character is 1 is false, so epsilon is accepted by the DFA. We will now start to discuss the conversion from a DFA into a regular expression. Firstly, let's have a review. In the conversion, we introduce the notion of k-path induction, where Rijk is the regular expression for the set of labels of k-paths from state I to state j. This means that, starting from I, if the DFA receives any string from Rijk, it will go to state j and will not pass any node with label greater than k. And Rijk describes all such strings. In the lecture, we gave a way of computing Rijk, which is either via not going through state k or going through k 1 or more times. This gives us a formula. Rijk is Rij k minus 1 or Rik k minus 1, Rkk k minus 1 star, and Rkj k minus 1. Now let's take a closer look. In the illustration, we can see that RIK, k-1, corresponds to the part from I to the first encounter of k. Then all parts between k can be described by RKK, k-1. As we do not know how many times the path will go through k, we use RKK, k-1 star. In the end, we have RKJ, k-1, which corresponds to the label of path from the last encounter of k to j. Here, we point out that the labels of the path from the first encounter of k to the last can also be represented by RKKK. Because it is just a path from k to k, going through nodes with labels not greater than k. And in edge cases, both RKK, k-1 star, and RKKK contain epsilon, the empty string. In spite of the equivalence, we pick RKK, k-1 star, because this will give us a formula where quantities with a higher superscript will always only depend on quantities with lower superscript, which makes the implementation and understanding much easier. Lastly, we will show our solution to the first challenge problem. The problem says that L is a language with alphabet 0, 1, and 2. L contains no strings that have 3 consecutive zeros, 3 consecutive 1s, or 3 consecutive 2s. For example, the string 11000220 is not in L because it contains 3 consecutive zeros. The task is to prove that L is regular and then give a DFA for L. Firstly, we can prove that the complement of L has a regular expression, which is in this form. We have 3 consecutive zeros, or 1s, or 2s, with any number of zeros, 1s, and 2s before and after. This regular expression exactly defines all strings that do contain 3 consecutive zeros, or 1s, or 2s. Additionally, we have the nice property that regular languages are closed under complement. So it follows that L, the complement of the language of this regular expression, is regular. To construct a DFA for L, it turns out that we can directly do it without the trick of union or complement. We define the state to represent the run of the same symbol that appears at the end of the string. Specifically, we will have start state S, which we enter only initially, when the input string so far is epsilon. Then we have state A0, A00, A1, A11, A2, and A22, and a dead state D. The intent is that if the current string read in contains any 3 consecutive zeros or 1s or 2s, the DFA will fall into D and stay there. Otherwise, say the string has ending 012011, the DFA should go to state A11 because it denotes that the string has 2 1s at the end. Here is the final transition table for the DFA of L. Note that whenever we already have 2 zeros, which is described by A00, an additional 0 will kick the DFA into the dead state D. But character 1 or 2 will shift the state to A1 or A2, as now the longest run of symbols at the end is a single 1 or a single 2.
Today I'm going to make a few comments that I hope you will find interesting. I'll start with one of the challenge problems because I think the construction is interesting, but unlike the hint I gave, This construction uses a non-deterministic automaton. I'm then going to address a question that came up in one of the early discussion threads, but that really wasn't appropriate until now. It concerns whether there are things that can do what a Turing machine cannot do. And finally, there have been several threads doubting one or another form of proof that I have used in class. These doubts are much more reasonable than some might imagine, and so I'm going to try to sort out what needs to be assumed and what needs to be proved. I'm also going to touch on what it really means to offer a proof and have that proof believed, and I definitely don't mean the instructor is always right. Recall that half of language L is the set of first halves of the strings in L. So if L is there's two strings, say 0, 1, 1, 0 and 0, 1, 0, then half of L is just the set containing 0, 1. The reason is that for this string, 0, 1, 1, 0, the first half is the 0, 1, and for the other string, 0, 1, 0, it's of odd length, so it has no first half. We want to prove that if L is regular, then so is half of L. And we're going to start with a DFA called A for L. And we're going to construct an epsilon NFA called B, whose language is half of L. So here's how we're going to construct B from A. First, the states of B are pairs of states of A, plus an additional state S0, which is the start state of B. B starts out in S0, makes one epsilon transition, and from then on never returns to S0. And after that, B will always be in a state that is a pair, PQ, of A states, and furthermore, it will make no more epsilon transitions. Here's what we intend to be true whenever B can be in state PQ, after reading the input W. Now remember, B is non-deterministic, so it can be in many such states at once. But first of all, the first state of the pair, P, is the state that A enters after reading input W. So although B can be in several different states after reading W, they all have the same first component, and B simulates A using the first component of A's state. The second component, Q, is a state such that A can go from that state Q to an accepting state of A while reading some input X whose length is the same as that of W. B will be in all states PQ such that Q satisfies the condition I just set. It can get to a final state of A and some input whose length is the same as that of the input that B has read so far. Notice that B doesn't know how long an input string it has read. Finite automata can't count. But we'll work out the transitions of B so that what we want to be true about the second component will indeed be true. The accepting states of B are those pairs that have the same state in both components. The reason this choice makes sense is that if B is in a state, say QQ, then B has read some input W that takes the DFA A from its start state to state Q, and there's also some input X of the same length as W that takes A from the state Q to an accepting state. Thus, if B is in state QQ after reading W, that means there is some WX in L where W and X are of the same length. That in turn means that W is in half of L. Now let's design the transitions of B. From its initial state S0, B goes on epsilon to all pairs of A's states where the first state is the start state of A and the second is one of the accepting states of A. As we shall see, B never returns to S0. And this first move guarantees that the empty string is handled correctly. B accepts the empty string if and only if Q0, the start state of A, is accepting. But that means A accepts epsilon and half of epsilon is epsilon. Thus B accepts epsilon if and only if epsilon is in half of L. Now we need to design the transitions of B so that after the initial epsilon move, it is only in the states we said it should be in, given the interpretation we put on a pair of A's states PQ. So the transition from state PQ of B on an input symbol A will be to those pairs of states RS that satisfy two conditions. First, as we wanted, the first component of B's state just tracks A's state. That is, R is where DFA A goes on input A when it is in state P. The second condition concerns the second component. There must be some input symbol B such that A goes from S to Q on input B. Notice the transition is from the new second component to the old second component, so the new second component has a path to acceptance that is one longer than before. Thus, if X takes A to state P, then XA takes A to state R. That's this. We could prove by simple induction on the length of W that the first component of B's state after reading W is always the state A would be in after reading W, but we won't do the proof. We can also prove by induction on the length of the input that the second component of B's state can be all and only the states of A that reach an accepting state by following a path whose length is exactly the same as the length of the input B has read so far. As I said, we're not going to do the inductive proof that this construction works, but I'll set it up for you. Okay. The inductive hypothesis, which we prove by induction on the length of input W, is that B goes on input W from one of its states Q0F, where Q0 is the start state of A and F is one of A's accepting states, to all those states PQ, such that A goes from Q0 to P on input W, and A also goes from Q to F on some input X of length equal to that of W. Once we have the inductive proof, we have only to observe how B makes epsilon transitions from its own start state to each of the states Q0F, and that B's accepting states are the ones with the same state of A for both components. Here's a little example. I'm not going to go over every transition of B on the right, but I invite you to pause the video and study it if you like. First, A is this two-state DFA on the left in orange, and B is the epsilon NFA in purple on the right. From the initial state S0 of B, there is only one epsilon transition since A has only one accepting state P. This epsilon transition goes to the state QP because Q is the start state of A and P is an accepting state. Notice that because A has only one accepting state, we could have dropped state S0 and simply made QP be the start state of B. Now let's consider where QP goes on input 0. Since A goes from Q to P on input 0, that says the first component of the new state must be P. But we also have to look at the second state of QP, namely P, and ask from what states of A are there transitions to P on any input symbol. We see there are transitions to P from both P, which is this, and from Q. It's that. Thus, QP goes to PP and to PQ on input 0. That's these two transitions here. Next, let's see where PQ goes on input 0. First, we consult A, and we see that on input 0, A takes P to P. That's this. So the first component of the new state must be P. Then we ask from what states of A are there transitions to Q. Here we see the only transition to Q in A is this one from P. As a result, the second component can only be P in the new state. Thus, the only transition of B from state PQ on input 0 is to PP. We'll leave the rest of the transitions to you, but notice that the two accepting states of B are PP and QQ, those with identical states in the two components. Now that we know about Turing machines, we can address a question that I recall from one of the first posts on the forum. The questioner was evidently impressed by something called aspect systems. I think I remember reading about them a generation ago. They were supposed to be the next big thing after object-oriented programming. I guess they weren't, but it doesn't matter what they are, because presumably they are some software system, which means they are ultimately executed on a computer. And as we saw, a Turing machine can simulate a computer, we really only dived into the matter of how the storage units of a computer are simulated, but the rest is easy, the arithmetic units, the control logic, and such. The bottom line, no programming system can do what a Turing machine cannot. Real programming systems can do things much faster because the Turing machine is designed to be the simplest possible device that computes, but it's only a matter of speed and not of capability. But another attack on the use of the Turing machine as the definition of what can be done by a computer comes from an entirely different direction. There are those who think we'll eventually be able to build computers that use quantum physics to do things that appear impossible in the world of Newtonian mechanics. In particular, these hypothetical devices behave something like non-deterministic automata, always appearing to guess right. One of the most interesting conclusions is Shor's algorithm for factoring numbers in polynomial time on a hypothetical quantum computer, which is something we doubt can be done on a conventional computer. There have been some interesting experiments in which particles are somehow linked by their spins and carried far apart. A change in one manifests itself as a change in the other, allowing communication over vast distances without any perceptible link. That means, for example, you could not eavesdrop on the communication, so it is more secure than conventional Newtonian communication. I really don't believe there will ever be practical quantum computers. The problem is that a physical device that is needed to represent a single bit in a quantum computer, called a qubit, is huge. I've heard it has to be roughly the size of a refrigerator in order to isolate it from other qubits adequately. But even if we can make really tiny qubits, we are still faced with the fact that a non-deterministic Turing machine is no more powerful than a deterministic one. You should have seen that video explaining why by now. To be fair, proponents of quantum computing claim that while they may not be able to solve anything that a conventional computer cannot, they can do certain things faster. The one big example they point to is Shor's algorithm for factoring numbers. It looks to me like this case is the exception rather than the rule, and the advantages of a quantum computer, if we could ever build one of useful capacity, is small. There are a number of questions about the mysteries of proofs and the logical rules one can use, and a number of these questions arose in a thread about why I claim that one stack, as in a pushdown automaton, could not simulate two such stacks. I didn't prove that point, and in fact it is more than a little vague. What does it mean for one stack to simulate two stacks? If you make a reasonable attempt to combine the action of two stacks into one, you will find you're okay as long as the two stacks push and pop at the same time. Then you can keep in one stack symbols that represent pairs of symbols, one from each of the stacks you're simulating. But two stacks need not push and pop at the same time, and when one pushes while the other pops, you get stuck. There is no sensible thing to do that will represent both moves. Well, if the difference between the lengths of the two stacks is 2, or any constant, then you can remember the top symbols of the longer stack in the state, and only keep the shorter stack and the bottom portion of the longer stack on the single stack you're trying to use. But that's not good enough, because as time goes on, there may be no limit on the difference between the lengths of the two stacks you're trying to simulate. But the failure to prove something is no proof that it can't be done. So the first thing I need to do is to give a precise definition of what would be considered a successful simulation of two stacks by one. I propose that as a minimum, if I had such a construction, I would be able to use it to design one PDA P that could simulate two others, P1 and P2, and in particular to accept if and only if both accepted. That is, I would have a PDA construction that showed CFLs were closed under intersection. But we already know that CFLs are not closed under intersection. So let's assume that a construction to build P from P1 and P2, as on the previous slide, exists. Then in particular, I could apply the construction to PDAs that accept the two context-free languages that we showed in the lecture have a non-context-free intersection. That is, let P1's language be the set of strings of zeros followed by ones followed by twos, such that the numbers of zeros and ones are the same. Let P2's language be the same, except that the constraint is that the numbers of ones and twos are the same. Let P be a PDA accepting the intersection of these languages. The language of P is the set of zeros followed by an equal number of ones followed by an equal number of twos. Since we assumed we can construct P from P1 and P2, P exists, and therefore its language is context-free, as we know are all languages accepted by PDAs. But we know this language is not context-free. We have reached a false conclusion, so we know that our assumptions are wrong. We have made only one assumption, that P can be constructed from P1 and P2. Since we drew a false conclusion from our assumption, that assumption must be false. That is, we have proved that there is no way to simulate two stacks by one in a manner that is sufficient for us to figure out whether the PDAs using these two stacks both accept a given input. We might be able to simulate them in some weaker sense, but that sense would have to be very weak indeed, and I would not want to think of it as a true simulation, since I couldn't tell from the one stack what both of the, quote, simulated stacks were doing. This proof used a number of logical tools that are sound, but which we might be tempted to question. First, we use proof by contradiction. That is, if we assume some statement S and we use correct logic and true statements to derive something false, then the statement S itself is false. Here S was, you can simulate two stacks with one, in the formal sense of being able to compute the intersection. This is a generally accepted form of logical reasoning, and I don't want to suggest that we should doubt it. Proof by contradiction appears to work in the real world. However, it doesn't really follow from any more basic principles. You need to take it, or something equivalent to it, as an axiom of logic. If you try to prove that proof by contradiction works, you will have to start with something like, well, assume the rule doesn't hold. That is, you need to assume proof by contradiction works in order to prove that it works. An amusing sidelight is that proof by induction, another staple of this course, is also something that needs to be assumed. If you try to prove that proof by induction works, you wind up either using a proof by induction or, what is equivalent, a proof by least counterexample. That is, you say that if you can prove the basis and induction step of some statement, say S of I, and yet S is not true for all I, then consider the least I for which it is false. S of I can't be the basis because you proved that. And if I is not the basis, then you know it is true for I minus 1, and you proved the inductive steps. That is, you know S of I minus 1 is true, and you prove the inductive step, which implies in particular that S of I minus 1 implies a S of I. So again, S of I could not be false. But the idea of least counterexample is equivalent to proof by induction. And it is an assumption. There does not have to be a least counterexample. For example, consider the statement about real numbers is not greater than 0. There is no least counterexample because if x is a counterexample, that is, x is greater than 0, then x over 2 is a smaller counterexample. It is smaller than x, but also greater than 0. Of course, we never suppose that induction works for real numbers. It doesn't. It only works for things like integers, trees, and other discrete things that can be ordered like integers. For these domains, inductive proofs appear to reflect how the world works, so we're okay assuming inductive proofs are valid in those domains. But there's a more worrisome point than the fact that we have to accept some axioms of logic. When I derived something false, I immediately pointed my finger at the assumption you can simulate two stacks with one. This reasoning is important. We use it heavily, especially when we justify the idea of reductions from one problem to another. Definitely, I never proved that assumption about two stacks, so it might be the cause of a false conclusion. But could there be any other assumptions that I used without proof? And could one of those be the cause of the false conclusion instead? I don't think so. I believe everything I used was either proved or I could prove it if challenged, but I could be wrong, couldn't I? No proof is complete and undisputable unless it is written in a very, very formal system. But interesting proofs, such as my claim about two stacks being better than one, are just too complicated to be written that way. In practice, mathematical proofs are accepted by a community using a social process. That is, interested people look at the proof, and if they doubt one or another point, they can challenge it and drill down into the details of why the point is true. Either they will be convinced or the person who claimed it was true will withdraw the claim. That's how mathematics arrives at the truth. I'm going to conclude with a discussion of something that has nothing to do with automata theory per se, but rather applies our understanding of what makes a proof believable to the question of whether we can prove programs correct. There was a paper written on the subject about 40 years ago by 3 computer scientists of serious note. Alan Perlis was the first winner of the Turing Award. Rich DeMilo later became Chief Technical Officer at Hewlett-Packard and was also Dean of Computer Science at Georgia Tech. Dick Lipton was the guy who replaced me when I left Princeton in 1979. He also has a number of important ideas to his credit, including the one I want to talk about now. The paper started by making the points I just made, that you can only believe a proof if good mathematicians have looked at it critically and attempted to challenge any questionable points in the reasoning. In fact, the title of the paper is Social Processes and Proofs of Theorems and Programs. They then went on to draw a significant conclusion. Proofs of correctness of a program need to be subjected to the same scrutiny, or they can't be believed. But proofs of program correctness are boring, and no one is going to participate in the social process needed. Thus, they argued, it was not realistic to suppose that programs of any significance would ever be proved correct. Interestingly, that reasoning is pretty much held up. 40 years later, we still write code, hope it works, fix it if it doesn't, and do not suppose that we can prove it correct formally. There are a few exceptions. First, there has been much more progress than the 3 authors might have expected in automated theorem proving. Computers don't get bored, so to the extent that we could get them to do the checking, we can avoid the social process problem. A second, oddly, is that if you pay people enough, they will do the checking even if they do get bored. So there have been a few instances where a lot of money and time was spent doing a proof of correctness for a non-trivial piece of software. With that thought, I'll leave you folks to finish up the study of Turing machines, and then we'll go on in week 6 to the matter of NP completeness and intractable problems. In this final set of comments on questions received, I'm going to address some subtleties regarding decidability and NP completeness. My first point is that single instances of a problem, that is, one input to a Turing machine, will always be decidable. But that decidability is technical, and it's useless if the underlying problem is really a hard one. And I was pleased to see that people are thinking how they could form a startup based on their solution to P equals NP. Here in Silicon Valley, we like to see people thinking that way. It's not just about intellectual challenges. It's about making the world a better place and getting rich while doing it. The first question from the forum concerns a doubt about my comment regarding Rice's theorem, that as a consequence of that theorem, it is impossible to tell whether a program does something specific, like a sort. Let's suppose we have a program that is alleged to sort an input list of integers. The questioner suggested that we can feed the program a list of integers, run it, and see whether the output is sorted. We could even feed the same program any finite number of lists, like 1,000,000 lists, in turn. It is true that if the program fails to sort any of the finite number of input lists, then you know it is not a sorting program. However, just because it sorts 1,000,000 inputs correctly doesn't mean it will sort the 1,001st correctly. I can give you several examples of bugs that only showed up in 1 out of 1,000,000 or more cases. The most famous is probably the Pentium multiplier bug, with a much tinier than 1 in 1,000,000 odds of it showing up on any given multiplication. But people were getting errors due to the hardware rather than the program. The point is that testing is a good idea. It does uncover most bugs, but that's still not an algorithm for deciding whether a program does what it is claimed to do under all circumstances. And in fact, there is no such algorithm. Rice's theorem proves that. It is worth remembering that problems, or their languages, are questions about an infinite number of instances. The answer to all, or all but one of those instances, may be no, but a solution to the problem still has to deal correctly with all possible instances. Single instances of a problem are always decidable, although we can't necessarily tell what the answer is. That is, suppose we have a problem represented by language L, and we ask if W, a single instance, is in L. There are two Turing machines, one of which answers yes, that is, it accepts any input, and the other of which answers no, that is, it rejects all inputs. One of these Turing machines answers the question, is W in L? Unless L is recursive, I can't figure out which of the two Turing machines answers the question. But I am absolutely certain that one does, and therefore the question, is W in L, is decidable. It has a Turing machine that always halts and gives the correct answer. Of course, this observation is useless, since we can't really solve anything with it that we couldn't already solve because the language L was recursive. The second question I would like to address is almost the same question, but regarding intractability rather than undecidability. The questioner hypothesized that they could invent an algorithm that runs in polynomial time and appears to solve some NP-complete problem, let's say SAT to be concrete. That is, they tested it on 1,000,000 expressions and it gave the correct answer in all cases. They then asked whether they could sell the solution to a company. The objective would be that the company would be able to solve problems quickly that no one else would be able to solve in less than exponential time, and thus could charge for the service. That's not quite the right approach. The right thing to do would be to start a company of your own, implement the solution, and sell the service. Once you have a business going, your company would be much more valuable than an unimplemented and untested idea. So you could sell the company for much more than you could sell the idea. You may, for example, have heard how Sergey Brin and Larry Page offered to sell the key ideas behind Google to Yahoo for $1 million, but Yahoo wasn't interested in developing the idea. Now Google is worth 10 times what Yahoo is worth. The second issue was whether you could keep the algorithm secret and still convince people that you had a solution to an NP-complete problem, and therefore to all NP-complete problems. That's not impossible, and we'll talk about it on the next slide. There's a fairly ancient theory called zero-knowledge proofs due to Goldwasser, Macaulay, and Rakoff. Their techniques were motivated by exactly this conundrum. If you had solved P equals NP in the positive, and you wanted to prove to people that you had a solution without revealing your algorithm, could you do it? In the previous problem session, we argued that proofs of theorems require a social process where you reveal your proof to interested mathematicians, and they can examine and argue about anything that seems doubtful. Well, the methodology behind zero-knowledge proofs is also a social process, but of a very different kind. A verifier gives you many instances of the problem you want to solve, and you produce a solution to each but do not reveal them. You are then asked a question about each solution and must answer them all correctly to be believed. There is considerably more to the concept, however. Wikipedia has a good explanation of how a zero-knowledge proof works if you had a solution to the NP-complete problem called Hamilton's cycle. That is, whether a graph has a cycle that contains all the nodes exactly once. We just talked about being able to solve single instances of undecidable problems. The same idea applies to intractable problems as well. That is, suppose we have an NP-complete problem or language L, and we want to know in polynomial time whether a given instance W is an L. Since everything is now decidable, we can even run the non-deterministic polytime Turing machine and see whether W is an L. It will take us exponential time, but eventually we finish. And now we can design our polynomial time Turing machine to take input W and accept or reject whichever our exponential time analysis told us correct. This Turing machine can do anything it likes on inputs other than W. But as was the case for undecidable problems, this approach doesn't really help us. We can pre-compute the solution to any finite number of instances and use them in a polytime Turing machine, but that is not the same as solving the problem. Our, quote, solution is still useless for any instances whose solution we did not pre-compute. But let us return to the original question. Suppose someone came up with a polynomial time algorithm that they thought might solve SAT, but they couldn't prove it. Could they test it on, say, 1,000,000 expressions and check that it worked well on all 1,000,000? If so, wouldn't that be good evidence that the algorithm worked for any expression? Well, we have to be a little careful how the test expressions are selected. See, the easy case is if there were a satisfying assignment, that is, the answer is yes. In this case, we could expect the algorithm to provide at least one example of a satisfying assignment, which we could check easily and quickly. The hard case is when your algorithm says, no, there is no solution. There is no way known to verify that no is the right answer without checking the exponential number of possible truth assignments. That's not feasible for 1,000,000 test cases or even one large test case. But perhaps we could handle this case if we knew that any expression that had a satisfying assignment had many such assignments. If that were the case, a randomized test would work. Pick a reasonable number of assignments and evaluate the expression on each. If any of them are satisfying, then your algorithm is wrong. But if none are satisfying, then you could conclude with high probability that your algorithm gave the correct no answer. Unfortunately, there are lots of expressions that have exactly one satisfying assignment. For example, consider what happens if you apply the construction in Cook's theorem to a deterministic Turing machine. There will be only one truth assignment, the one that reflects the unique computation of that Turing machine. I have enjoyed greatly the experience of using modern technology to present this material on the basics of automata theory to a worldwide class. Thanks to all of you who stuck with the difficult and challenging material. I hope it will have some good effect on your future careers, even if you aren't the one to prove that P equals NP. And I hope everyone who has come this far will do well on the final exam. As mentioned on the class announcements, the exam will be available for the 3-hour period of your choice during the week starting 11th of June. Certificates of accomplishment will be emailed to all whose total marks on the class are at least 50%, with the final accounting for half the marks and the homeworks accounting to the other half. Goodbye and good luck.